creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. On today's program, we're going to be looking at the evolution of computer hardware, from mainframes to minis to micros. We'll see some examples of the oldest mainframe computers, and we'll take a look at one of the newest microcomputers, the HP 150 from Hewlett-Packard. Gary, are we at the end of the line in the evolution of computer hardware, or are there major new phases of this evolutionary process still to come?
Well, fortunately, we're obviously not at the end of the line. We're at some point in time in the evolution of using, let's say, microprocessors as general-purpose computers, and they're just getting smaller, faster, less power, and most importantly, they're less expensive than they ever have been. I guess the logical conclusion is they get so small that you lose them like you do your keys. But as far as evolutionary trends, there are a lot of new things happening with microprocessors, use of microprocessors as controllers for, let's say, intelligent devices such as a wheelchair that finds its way around under microprocessor control. So I think there's a lot of exciting things that are going to happen that will be off the mainstream of using computers as general-purpose computers as well.
Okay, to start our look at the evolution of microcomputers and mainframes and minis, we went to Boston to visit the Computer Museum.
Established in 1979, the Computer Museum houses the most extensive collection of early computers in the world. Its galleries feature some of the earliest known calculators, like the Pascaline, invented by the French mathematician Blaise Pascal in 1642. The Pascaline stored numbers on 10 little rotating dials. Moving one dial up to 10, moved the next dial one notch, and so on. It was the first consistently reliable example of a computing machine. In the late 1800s, Herman Hollerith devised a card punch calculator to speed the tabulation of the 1890 census. The cards were hand-punched, but electrically read, a concept that showed up much later in the earliest IBM machines and is still used occasionally today. The forerunners of modern computers didn't appear until the late 1930s and 1940s. The Whirlwind, of which only a few parts remain, was a massive machine, covering 3,000 square feet and weighing over 3 tons. The heat given off by its 18,000 tubes required constant monitoring, and in spite of its great mass, the Whirlwind's processing capacity was about the same as a present-day 16-bit microprocessor. It was not until the invention of the transistor in 1947 that a new era of smaller, more efficient computers became a reality.
This is the TX0, the world's first general-purpose computer using transistors. And it still works. We'll see a demonstration coming up next.
The TX0 was an experiment in transistorization, the first solid-state general-purpose computer. Its transistors were encased in little removable tubes so that they could be easily checked. Designed and built at the Massachusetts Institute of Technology in 1956, the machine used a modest 5,000 watts of power. Punch tape served as an input device, rewound by hand after each use. Although the machine was transistorized, it was and still is very sensitive to heat and will only run if the temperature stays below 80 degrees. The TX0 was equipped with some very modern peripherals, a video screen and a light pen, a half-inch tape drive, and it even featured a video game program involving a mouse with a memory, threading its way through a maze to reach a piece of cheese.
TX0 was built at Lincoln Laboratory, and the notion was to test two ideas. One was transistorized circuitry, and the second thing that it was designed to do was to test a very large memory. And it did that very well. And then it was used. Then it was moved to MIT for real use. But its role really was a circuit tester and a memory tester.
Displayed in the Computer Museum's lobby are some of the biggest solid-state machines ever made, supercomputers. The IBM Stretch, Control Data 6600, and the ELIAC 4 represented the most powerful class of computers of their time.
Well, the ELIAC began with some ideas in the early 60s for doing a lot of computing in parallel. And the idea behind ELIAC is to have a number of processing elements, in this case 64 processing elements, each with a small amount of memory, and then to have a single instruction that executes, that operates on all of that data in parallel, so that in fact you get speed by this massive parallelism. ELIAC's main effect was as byproducts to they stimulated the use of semiconductor memory. It also stimulated the idea to make faster machines, and the fact that fast machines were really important in a whole bunch of applications.
The development of integrated circuits paved the way for faster, smaller, more powerful machines, and the mini-computers of the 1960s. But what was considered small in those days bears little resemblance to what we call personal today.
Some people consider this Link computer to be the first truly personal computer. It has a keyboard, it has a CRT, it even has mass storage devices. But this part was only the terminal. This, in fact, was the computer. And in the days of this computer, this was considered portable because it was on wheels.
Mini-computers were a major breakthrough, equaled only by the appearance of microcomputers in the next decade. Progress in very large-scale integration of circuits promises even further size reductions and increased processing capacity. But the future holds more than just a change in the relationship between power, size, and speed.
Well, I think the next sets of challenges that we have right now are going to be integrating video and television and voice into machines, and I think that those are beginning to happen to a reasonable degree, and maybe I can't predict whether the video disc will come in or not, or whether that kind of how important that technology is going to be. But I think just the notion of storing pictures and operating on those pictures, that's kind of the next frontier.
Herb Lechner has joined us. Herb is Vice President for Information Systems and Administration at SRI International. Herb's got quite a background in computing. It goes back several years. I understand you programmed the ENIAC at one time.
Yeah, that's right, Gary.
So our title is Mainframes to Minis to Micros. Could you give us some idea, just for general information, what these different kinds of computer systems are all about?
I'm not sure, Gary, that there is a precise definition, because yesterday's mainframe is today's micro from a performance point of view. But I think that we normally think of the mainframe as being the faster, high-end computer system that we find in scientific research. And we certainly think of the micro as being a personal computer which does one application at a time for one person. And somehow or the other, the minis get kind of compressed in between.
In talking about these three different types, Herb, will three different kinds of computers continue? I mean, is there a reason to continue to have mainframes and minis and micros, or do you see like micros taking over with the kind of job that minis did in the past?
I think we'll continue to see the spread both in the high end and in the low end of the computer line. There's a constant demand for faster and faster machines. The Japanese fifth generation objectives is a clear evidence of that. While at the same time, now that we have broadened and matured the computer field to encompass the home and the office and the individual, I'm sure we'll see a push to the downside also.
In fact, if you take a look at just some of the recent developments, I guess, in microprocessors, there's quite an emphasis on data communications to mainframes, getting at information services, and this seems to be some sort of a coupling of the mainframe use with microcomputers. So there's some synergism there for sure.
That's right. Some people have commented that the advent of the microcomputer is merely a spreading of the components of the mainframe system over a larger area.
Speaking of synergism, Gary, I'd be interested, maybe both of you could talk to this, because CPM is one key factor in what I'm about to ask you. Was there a synergism between operating languages, operating systems, or software in general, and the evolution of hardware?
Well, I think definitely the software has played a key role in the evolution of hardware. And in the markets that these various classes of machines service, I think we see that very clearly. In the mainframe area, the more powerful computers with many more peripheral devices and disks and tapes will service multiple users at the same time, and the software has to be massive and somewhat complex to support that. Whereas in the small side, we're seeing a trend towards simpler software, easier to use software that services the needs of an individual.
Well, I think also at least in small computer evolution, it's been an evolution that's been paralleled. It's paralleled the large computer systems and mini computer systems to a large extent. And I think that nowadays there's some breaking away from that. Mainframe world is many times batch or time-sharing oriented, and now with small computer systems we're looking at more of an emphasis on, say, real-time control, more the kinds of things you'd find in an industrial control environment or even in a home. So there is some, I think, differences there. There are some differences that are starting to show up.
Yes. Yes,
Herb, not trying to date you, but you were with IBM in the 50s, I mean, the early days of this stuff. I'd just be curious, did you guys envision at that time that in the early 80s computers would be where they are right now and that we'd have made this kind of progress, this kind of evolution?
Well, I certainly didn't. And I can recall in the days of the 702, we wondered if we would ever sell 30 such systems in the entire United States market. So clearly we did not have our sights set on the proliferation of computing we've seen today.
Well, it's interesting. Just the other day I saw a small computer system. I can't say exactly what kind it was, but it was running PL1, and it was the kind that you can put in your briefcase. So there definitely has been some change in the characteristics of computers.
Yeah, it's a walk down nostalgia lane to see the museum and think back to the days when we had an installation team of 17 people sent out to install a computer over a year that my kids handle in their spare time.
Okay, speaking of the newest thing, in just a moment we're going to take a look at one of the newest examples of a microcomputer, the HP 150. It's a computer where your fingers can do the talking. Okay, joining us now is Cyril Yansounis. Cyril is the general manager of the personal computer group at Hewlett-Packard. And Cyril, we mentioned that the HP 150 is a good example of one of the newest microcomputers in the field. Maybe you could run a demonstration program for us and particularly point out the new technology aspects of it.
Yes, I'd like to do that very much. I think when we set up to design the HP 150, we had in mind the professional user, but the user who is sophisticated in the use of information, but not sophisticated at all in the direct use of a computer tool. So we really focused on developing a technology and a total approach for a very intuitive use of a personal computer. And what we have embedded in the HP 150, the most visible part is what we call touchscreen capability. The fact that you can interact directly with the personal computer without accessing the keyboard by basically using what is the most intuitive tool that you have, basically using your finger to point and select objects or select things on the screen.
Could you show us with what you have up there?
I would like to show you what we have on the screen there. What we have on the screen there is what I call an electronic Rolodex. We all are very familiar with the Rolodex on our desk. It's a set of cards, and you can turn wheels back and forth until you see the right name, as an example, appears in front of you. We can do exactly the same thing here. I have an electronic Rolodex. It appears very much like a Rolodex on the screen, and I can move it up. I can move it down just by pointing on the wheel on the screen. I can go and select a name. Let's suppose that now I have the set of names and I want to select a name there. I have Stewart, Cheifet name there. I can just select that card and the Rolodex opens there, and I get all the information that I have embedded in the product on Stewart Cheifet. I have his address, his phone number, and so on. As a matter of fact, if what I want to do next is call him, I just indicate that I want to dial the phone, and if I had a modem attached to the product here through a phone, I would automatically dial the phone. So let's go back to the Rolodex, and you can see then I can really roll it up, and I can roll it down, and I can do quite a few things. can recall, again, just by pointing the application. I can recall the specific program, what I could have selected, again, just by pointing to the screen, another application.
Touchscreen is not really new as a technology. It's kind of a new application of this in this computer. Is that right?
That's absolutely true. Touchscreen is not new to and it's not a new technology. It has been used on terminals mostly as, again, a pointing and a selection device. What we have done there is really embedding very well the touchscreen capability of the product with the software, with the application, and really trying to see everywhere we could replace keyboard access by basically pointing directly to the screen.
Cyril, do you see a shift from using a keyboard to using this touchscreen display? For example, we have lots and lots of applications that are written for small computer systems, and how are you going to get all those programs to move over to a touchscreen?
Okay, I think that the way we have designed the product, in fact, is by allowing very simply current and existing application to basically use a touchscreen capability. The product itself has built the ability to recognize if you are putting your finger and really selecting either a specific place where you want to put your finger on, or an area where you have your finger in that specific area. So you don't really have to burden the application itself by all that. It's really basically replacing the movement of cursor. Okay, but again, instead of having to move the cursor with the keyboard or with any other device, you can really point to it directly with your finger.
One of the criticisms, though, has been that holding your finger up there in your arm would be kind of tiring. In fact, I heard somebody say that there was an attachment they thought was going to come out for the HP 150, which is a little armrest, and holds your arm up there while you're touching it. Is there a problem with that, or is that just a rumor?
All the studies that we have made, and we have very extensively tested the product, obviously, before we put it on the market, show that this is really not a true problem. You don't really spend a lot of time with your hands up there and pointing to the screen. I have myself a pretty good feeling that the ideal user interface, as a matter of fact, doesn't really exist. It's really going to come out of the combination and a lot of experimentation of a lot of the user interface that today exist, like touchscreen, like ability to move a cursor through a mouse or a tablet, probably one day also using voice. And I think it's going to be a combination of all those different user interfaces applied to very optimally to some specific type of application. I think there are going to be a good matching of the kind of user interface with the kind of application. So I think it's going to be a combination of all those user interfaces which are really going to make another step forward in user friendliness.
I see two things looking at that machine that seem new in technology. So you've got microfloppies on there rather than the traditional 5 1/4 inch. And I was wondering if you could comment on that. Also, there's a printer sitting in the monitor, which is something I haven't seen before.
That's right. I'd like to, maybe I'll start by the printer and then we'll go to the microfloppy. Let me give you a good example of the nicety of really having a printer built in. As you can see, as a matter of fact, it doesn't even appear. It's really building the product there. It's user installable. It takes a minute or two from any user to basically receive his printer and put it and install it in the product. Let's take a good example. Let's suppose, in fact, I really want to go back and reselect this card. It's, again, your card, Stewart. It has information. I'd like to have a hard copy of that information. I'll just go and say print card. And my printer is really going to start printing that card. And in a couple of seconds, we'll be able to tear it out there and give it to you. The microfloppy, it's an area where we also believe there that we are kind of pushing the technology. We're using, as a matter of fact, a 3.5 inch technology, and I think that I have one in my pocket here. It is a kind of semi-rigid microfloppies. It's, as you said, different than the 5 1/4, but has today basically the same density, the same capacity as a bigger 5 1/4 disk. As time goes on, as a matter of fact, we think over the next several months, we'll see significant improvement in the capacity of those products, doubling and even quadrupling the capacity of those microfloppies, probably even getting to the range of 1 megabyte that you can basically carry with you. This is really the ideal, we think, personal mass storage media. We have also seen tremendous reliability improvement using those kind of products, and one can really see why. The semi-rigidity, the fact that it has an auto shutter, so in some sense you never have outside contact with the media itself.
Herb, we've seen an example that Cyril's been showing us here of one of the newer versions of a microcomputer. Where would things be going after that? We talked with Gary at the very beginning of the show about what's the next step. It will be in the direction that Cyril mentioned of more user friendliness, as we tend to say. What's the next stage in this evolution of hardware?
Well, I think that there are a couple of trends that we see evolving. Clearly, making the computer easier to use and making more software available that is easier to use is one of the trends. Another trend seems to be, especially in the business environment, networking the computers together. Because given your own computer and being able to do many things on that computer, it seems like this almost commands the next step as being, now let us interchange data between computer users, and we see the local area networks and networking becoming a factor.
I would agree with you on some of those points. I think that most of the networking, though, is going to be more in data communications over telephone lines, that is, linking the office with a home and things of that sort. We have a tremendous network throughout the whole world that is based on telephone system, and I think we're going to just see a lot more evolution in that direction. LANs have had a lot of problems in just setting up the networks, and they're very expensive. So, but I agree with you.
I agree 100% with that. I think that, in fact, we do have this network system, which is our telephone systems. I also think there is another reason, in my opinion, we're going to see this very good matching between telephone networks and computers and personal computers, is the integration of voice kind of capability as a user interface within personal computers. And in that case, it makes even more sense then to be able to share basically the same media to transport your information. It's data information, it's text, it's also your voice.
Okay, gentlemen, we're out of time. Cyril Yansuni of Hewlett-Packard and Herb Lechner of SRI, thanks very much for being with us. On behalf of Gary Kildall, I'm Stewart Cheifet, hoping you'll join us again next week for another edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. On today's program, we're going to be talking about integrated software, the new breed of business programs which all work together. And when we mention integrated software, you probably think of Apple's Lisa. Well, in just a few minutes, we're going to be talking to the man behind the Lisa project, John Couch. But first, Gary, there really was integrated software before Lisa, wasn't there?
Well, we're actually talking about two different interrelated topics. One of them is integrated applications, and the other is the use of a visual interface. Integrated applications generally is a term that's applied to business applications that work together, such as a word processing system, a spreadsheet, a graphics drawing package. And they're integrated when they use common data formats and common command formats. The second topic is really the visual interface. The visual interface really uses a new technology of high-resolution graphics to make that program-to-user interface a little more enhanced and animated and a little more fun to deal with. So the Lisa and also the Vision that we'll be seeing today are really descendants of the Xerox Star, which was really then in turn a descendant of the work that was done by Alan Kay in Smalltalk at Xerox PARC.
Okay, before we meet John Couch and Lisa, let's take a background look at the principle of integrating work functions.
Integrating the various branches of an organization to work in unison has never been simple. If each task or department is isolated, making them work together requires clear and accessible channels of communication. At the very least, they all need a common language to clearly assign jobs, coordinate tasks, and make changes as quickly and as directly as possible. In this regard, computer software has a long way to go. Until very recently, the kind of software programs available to businesses, for example, performed single, separated functions, like word processing or graphics. With integrated software, several functions can be combined into one package, available at the same terminal, using the same language. A common database allows an operator to perform several tasks simultaneously, and to switch quickly from one task to another by splitting up the screen or creating windows that overlap. Integrated software has its routine commercial applications, business records, office management, spreadsheets, the corporate bureaucracy. But the concept of integrating programs and program directions is part of a long-range goal critical to the development of more manageable computers, making the machine easier to use. Integrated software is a step in that direction, using a low level of artificial intelligence to manipulate diverse programs like tools. Paradoxically, the simpler a program is for the user, the more complex it must be for the machine. And to some experts, today's small computers are still too immature to use integrated software effectively.
Joining us now is John Couch, the creator of Lisa, formerly with Apple, and now off doing quite a few things on his own. Welcome to Computer Chronicles, John. Gary?
Well, John, I mentioned earlier in the opening segment that the Lisa machine seems to be related to Smalltalk and the Xerox Star. I remember it's been over 10 years ago I went to Xerox PARC and saw a high-resolution display like this. Can you give us some idea what that genealogy is? How did we end up with a Lisa?
Well, it really goes back to 1978 when I joined Apple Computer and went to work with Steve Jobs in a group called New Products. Our job was very simply to define the new products or the personal computer of the 1980s. And we attempted at that particular time to address some of the concerns that we had in terms of the growth of the personal computer industry via the Apple II. One of them certainly was that we felt the machines were too difficult to use. It required a person to learn a new language, a command language, in order to use the machine, and there was very little integration amongst the applications. It was very difficult to take data from one application into another application, and those systems that were integrated what I call at the file level, where you could write information to a file and read that file into another application, but then again you were forced to go through the command interpreter, through the command language, to learn how to use that system. We saw the Xerox work, a lot of us during grad school, like yourself, and came to the conclusion that we could build a personal computer, taking advantage of the new technology in terms of the bitmap display, replace the command interpreter entirely with a graphics language. In other words, emulating the way people work in an office rather than asking them to change the way they do things, and use that same user interface to provide the integration in terms of moving data from one application to another.
Now, the real breakthrough here was in the price, wasn't it? The Xerox Star is a very expensive machine, and the Lisa is relatively inexpensive, but it still is criticized for being high-priced.
Right. It's really interesting because if you look at the Star, yes, it was high-priced, and I think the real benefit of the Star was the alternate user interface, the displacing of the command interpreter. There was really very little integration as we define integration in terms of moving data from one application to another on the original Star. There was no spreadsheet. There was fundamentally integration between graphics and text, and that's where the integration stopped. Our goal was to build a software architecture such that And what I mean by architecture is it's like a home. It's what the house looks like to the outside person. Is it a French country or is it English Tudor? And how it's built in terms of the data structure. Our goal was to define a software architecture that would define the path for data movement and at the same time using a graphics user interface such that integration was a very cornerstone of that architecture. In other words, you could take data not only from word processing, business graphics, but from spreadsheets, as well as accounting packages, and any other piece of software that were to be written on the Lisa system, you would be able to cut and paste that data.
John, what kind of user did you have in mind when you designed something like Lisa?
To tell you the truth, we had ourselves in mind. One of the things about Apple Computer is there's this desire to build products that we ourselves wanted. And, you know, originally Steve Jobs and Steve Wozniak wanted a personal computer. They couldn't afford to go out and buy one, so they built one themselves, a la the Apple II. In looking at the Xerox Star, we wanted a computer that was integrated, that was easier to use. So we set a goal for a learning time of less than a half hour. We felt that that was the limitation in terms of really penetrating the personal computer marketplace, that although we've sold over a million Apple IIs, that there are still 32.5 million people out there in the office today that could benefit from a tool like a personal computer. And the single limiting factor was they were difficult to use. We asked them to learn something new. They didn't have the time to do that, and they couldn't integrate the typical functions that they did in their daily job. So our first goal was to build a product that we ourselves wanted. If you remember, I think Apple did away with typewriters back in 1979 and sort of built our company on top of personal computer technology. We grew from 7 million to 1 billion with at least one personal computer on everybody's desk and at least one at home, and in some cases 2 or 3 in an environment.
I want to go back just for a minute to, you mentioned there was a half-hour learning time for the Lisa. It's also been criticized that a half-hour learning time is done through all the graphics that is kind of cutesy oriented, the lid that opens up in the trash can, things like that, and that this tends to get tiresome. Is that tiresome and actually get in the way when someone learns the Lisa well? Is that criticism really true, or?
I don't see that, and I haven't seen that. I think that some of the things that I've seen. I've used the system myself since I've been outside of Apple since June. I've put a complete financial plan, which now stands about 2 inches thick, and so I've used the system myself extensively, and I've definitely learned a lot about where I would like to see integrated software go, and where I think the software industry in general is going, and the limitations of the Lisa architecture. But I don't see that at all. I think that the garbage can was just something that we chose as an alternative to saying delete your files. You simply pick up a document and throw it into the garbage can. Everyone knows how to throw paper away.
Does integration of software, as you put it together in Lisa, depend on any technological breakthrough? Did you have to solve any particular problem to get to this level of integration?
I think so. I think if you look at software, at least my view of software had been, in particular like programming languages, you tended to deal with arithmetic operators, add, subtract, multiply, and divide. And the data types tended to be very fixed. Integer numbers or real numbers, and therefore you did add, subtract on 2 integer numbers. There's a very well-defined calculus for the result of adding 2 integer numbers together or multiplying 2 integer numbers. When we took a look at the data structures for the Lisa system, they weren't simply just numeric numbers or floating point numbers. They tended to be textual strings, say the things you deal with word processing, data structures that represented high-resolution graphics, data structures that potentially could represent voice. So they were very unique data structures. And the operations on those data structures, which would be tree structures or linked lists, something of this nature, were not just add, subtract, and multiply. They were very complex mapping function in order to map a data structure that represents, say, a pie chart into a word processor that didn't understand pie charts at all. And
John, we only have a couple of minutes, unfortunately, to demonstrate this, so I kind of want to rush you along into it. Maybe you can show us with the Lisa here an example of how you'd move from one software program to another.
What I have on the screen is a number of windows, and I think that's certainly one of becoming the buzzwords of 1983, integration and Windows. But we have the mouse, and we have the what we call pull-down menus, and these are the traditional menus, except we don't take the real estate on the screen. And then we have a number of windows, in this particular case, applications, and you can have as many on the screen as you'd like. we basically point to something, select it. You can tell the selected object because it's blackened here. And if I wanted to move to some other place on the screen, it would simply be a matter of pointing to that, pushing the button, and control is now transferred from that particular application to this application. So I can go back. And I can move these windows around on the screen like I can move any of the objects on the screen. I can size them to be any particular size or shape. I can scroll with them in them and do whatever. This particular application that I happen to bring with me, I own a computer store called Computer Kingdom. It happens to be the sales for 1982, and I can enlarge this a little bit, and you can see that I have sales, the month, the hardware sales, software sales, and some training sales. And the object was simply to point to the data. Our goal was to point to things. And so I simply point to the data, like for the sales from January through December for both hardware and software. I go up to the verbs. We consider this to be the noun and the pull-down menus to be verbs. And I will make a copy of that particular data. And now I can move the window aside and look for some graph paper. Simply point to the graph paper, selecting the mouse button. And now the application that does graphing will be loaded into the system, and I can simply say, well, I would like that data to be plotted X and Y. So I just simply move down, and I simply say paste, and the data is then pasted there. And as you can see, that the data the number of digits was actually longer than fit in that particular area. So I simply move the column along the side. Move the column head to the right, like you would do.
So a little graph appear there.
And then there's a graph, and if I want to see the graph, I can see the graph. And if I'm not interested in my data, I can move it. I can move that over, and
Okay,
you
John,
see a pie chart.
I have to interrupt. I know you said it took you 3 years to figure this out, and I gave you 3 minutes to explain it.
It's okay.
However, coming up in just a minute, we're going to take a look at Vision, another version of integrated software, and that'll be next. Joining us now is Bill Coleman. He's group manager at VisiCorp, involved in the development of Vision, which is VisiCorp's version of integrated software, I take it, Bill. And maybe you can give us a demonstration of Vision.
Yes, we call Vision the Applications Manager. It's an all-software system in which applications can be installed and the integration is provided. With Vision, you manipulate it with a mouse. There's a global command line. Commands are always available to actually maneuver and utilize the windows, all communications between the windows. I'll give you a demonstration of manipulating the window. You make a selection just by selecting with the mouse. Prompted to select the window you want to open. These happen to be closed windows I've previously opened for this demonstration. I'll open the services window. You notice while something is going on, you'll get an hourglass. Now we've opened a window. This window happens to be all the services available to the user in Vision. I'll manipulate this window just to show you how they can be manipulated. This is open. We can utilize the full screen. There's a lot of times when you're entering text or using your spreadsheet, you're going to want to use the full screen. You can frame it to any size or location just by selecting it, determining the location and size you want it to be. It'll be recomputed and put into a window of that size. All windows have basically three usable components. There's the contents area in which the application actually operates. There's the menu area in which the menu operates as you point to something that's selectable in the universe. And there's something called an option sheet, which you can configure this option, or in this case the services window, Vision itself, to operate the way you'd like to. You may have heard the beeping that's been going on. I'll scroll this up. There's an option down here I can change so I don't have to listen to the beep in my office. Now it'll just flash. If I do something right once, if I do something wrong 3 times. When I'm done with that, I can quit it. Another capability of Vision, as in a lot of integrated applications, is help's always available. Just select help, point at something you want help on, say I don't know what the start command is. It'll open up another window in the center of the screen, unfortunately, over this one, which will describe specifics about that. You can find out more or less information going through. We'll get rid of that window. And I'll open up a graphics window, which has a graphics program running, and I'll open up a spreadsheet window. These are 2 applications I've previously installed in the system. I've opened the window. They have applications running. There are things you can do. you can do all of the normal spreadsheeting and graphics functions, but when using these windows, you now can transfer data from one to another. I'll transfer some data. Basically, select transfer, select the window in which you want to transfer from. You select the actual data you want to transfer. Say I want to transfer a column of numbers here. And that's the data I'll transfer. It'll highlight now. And I'll transfer it to this application.
Okay,
now,
Bill, I have to interrupt because we want to get to talking a little bit about this.
Okay.
We're talking about integrated software. Maybe, John, you can talk about this. Lotus 123 is a program we hear a lot about now as an example of that. How would Lotus be different from, for example, the Lisa you showed us or Vision?
Okay, I think it's very simple. Lotus is one application. Basically what they've done is they've implemented spreadsheeting, graphics, and some database intrinsics within one application. It's bounded by that particular application, and its data structures therefore know about the three different types of data. There is no integration beyond that, say, to an accounting package or any other piece of software anyone may write. I think with Lisa, and if I'm right, with Vision, these are systems themselves. They are architectures themselves, and they provide a interface to other applications so that you can install additional applications into the environment and therefore cut and paste information from them to other ones.
This brings up a good question, Don. Do you consider Vision and Lisa, are they both really closed systems in the sense that you provide the applications, or do you define how those interfaces are actually set up so that a company X can come in there and write an application that runs, say, under Lisa and uses all those facilities you've already defined?
Yeah,
or the same thing for Vision?
Well, they're both open systems. We are both in the marketplace providing a toolkit that allows applications developers to write their applications. And as John mentioned, both of these systems provide a lot more than just the services underneath. They provide the tools and the structures such that a developer can utilize the facilities of the system so that the interface and the usage of the mouse and the usage of menus and all of the facilities are provided and that they're consistent. A user won't have to relearn from one application to another.
That's also true for Lisa.
Yes, I think when Lisa was introduced, it was introduced with 7 applications, a terminal application as well in terms of taking data off a central database and then moving it into the word processor. And there is a toolkit, and that toolkit is available, and it allows a user to say write an accounting package or a legal package, and rather than having to attempt to embed word processing into a legal package, they can use the word processing or one or a number of word processing packages that have been written for Lisa and get the integration through the architecture rather than, trying to build it into an application. The question is how big can an application get before it runs into the boundary conditions of the hardware?
An alternate scheme, I guess, is one that Desk, or the Quarterdeck people have come up with called Desk, D-E-S-Q. And their idea is basically to put a layer of software over the top of existing applications, such as the word processors that already exist. Do you think that this is sort of a patchwork approach right now, or is it going to go away, or is that an approach that's really going to be successful in the long term?
You want to answer that one?
Well, I think it has its place. It's not a level of integration. What it does is it provides a way that you can view portals to current existing applications. Therefore, there's little or no integration for the user's point of view in the way they would use the programs. And there's very, very little capability to transfer data. Both Vision and Lisa have a lot of knowledge of the data structure, so they can transfer a lot more than just the little data you see on the screen.
Yeah, what they do basically, though, in Desk, though, is they do transfer through cut and paste by creating command lines, basically.
Right, and basically it's an integration at the file level, and they put a command interpreter over there that sort of hides that a little bit from the user. So it's sort of a compromise.
We only have a couple of minutes left, and I know we want to get into a little bit about what's happening next, John. Where do you see integration of software going?
Okay, I think, based on the experience that I had with Lisa and being involved in the software business for 15 years, that there's an area that I call programming by example, and that is rather than transferring the data through a conduit, through a pipe like we do in Lisa and some of the other systems, the systems reside on a database management system so that the data is always present. This allows you to do two things. One, it allows us to go towards what I would refer to as intelligent applications, applications that know who the executive staff is or who the Western regional salespeople are because they reside on the database itself rather than having to transfer that information. And secondly, the area of programming by example, where once you have defined a path, for instance, to say, I call the Dow Jones database, and I cut the information from Dow Jones into a spreadsheet, and then I put it into a report. Once you've defined that path, you can then can that path so that it is now an application. You created that application by programming by example.
John, Bill, Gary, we're all out of time, I'm afraid. Thank you very much for joining us this week, and we look forward to seeing you again next time on another edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Gary, what I have here is a ROM chip in this cartridge, and I'm going to take this ROM chip and stick it inside this machine and load it in there and press a couple of buttons, and if everything works according to plan, this is an example of computer music, and computer music is our subject today. This little RAM pack, which I have over here, has 15 songs on it. Matter of fact, there's a ROM Chip of the Month Club now where you can buy your popular songs on a chip instead of on a cassette tape or on a record. This is a simple example, but how does a computer make music? How is it doing this?
Well, as you're aware, Stewart, this is a very special device. It's not a general-purpose computer. But most of the home computers that are available now, like the Commodore 64 or the IBM Personal Computer, have special hardware for sound generation or tone generation. And what you do is you write a program in BASIC or Logo or one of those languages, if you like, and then you can produce tones, series of tones, and a certain frequency and duration. And I understand there are also some software packages coming about that are like word processing packages, only as for music processing or score processing. And it's going to be interesting today, I think, because we'll have some real experts that will tell us all about it.
Indeed we will. We'll be meeting Will Harvey, the author of Music Instruction Set. We'll see a demonstration of the Alpha Centauri music system. And there are two major centers for computer music in the country, one here in Northern California at Stanford. We'll be meeting the director of the Stanford Center later on in the program. First, let's go across the country to Cambridge, Massachusetts, and a visit to MIT's Experimental Music Studio.
The use of computers in musical composing is not a new idea, but recent advances are giving composers a new degree of power over their medium, the ability to create and manipulate sound waves of their own design. Systems like MIT's Music 100 can dissect a note into its sound wave components, The composer can then make adjustments to each aspect of the note's physical characteristics independently and instantly. Specially developed music languages translate the sound processing as specified by the composer. From this input, a digital data stream is computed. Finally, the digital form is translated into a signal for amplification, pre-recorded, and played back over audio tape during the performance. A computer that can reassemble the building blocks of a sound wave opens up a new spectrum to the composer and the musician, a range of sounds beyond the natural limits of mechanical instruments and the human voice. In a sense, the music program can compose not only the score, but the instrument as well. The next step in computer-composer interaction is real-time production synthesis, a live interactive performance between computer and instrument. To achieve this kind of instantaneous but programmed manipulation requires very high-speed computers capable of several 100 million calculations per second.
Okay, joining us now is Will Harvey. Will created Music Instruction Set, a hot piece of software being offered by Electronic Arts right now. And John Chowning. John is director of Stanford's Center for Computer Research in Music and Acoustics. Did I get that right?
Right. Karma, we call it.
Karma. Gary.
You know, I was just going to mention, I think with that Casio tone, I finally found an instrument that I can play.
I think we have some more here.
Right. John, I think it'd be worthwhile just to talk for a minute about the state of computer-generated music. Where are we at today?
Well, it's, I guess, nearly 20 years old since Bell Labs engineers and scientists first conceived the idea. And what's happened in the recent years is evident in things like personal computers, and that is large-scale integration. And what that means specifically as far as computer music is concerned is that we're getting more and more power in smaller and smaller units, which means that what was once in the lab now can be put in concert hall or into smaller environments.
Some purists, John, and maybe Will, you could talk from your end on this too, think that computers and music is somehow wrong, and somehow depersonalizing composition and creativity. What role really does the computer play in computer music, John?
Well, a computer, of course, being based upon programming languages, is really an access, I think, to a mode of thought or a body of thought that really represents, I guess, tens of thousands of man-years of thought about thought. And I think that's the significant difference between computers and music and electronic musical instruments of the preceding years. That is, as soon as a computer language is involved, one has access to a degree of power and generality, which was certainly not the case in ordinary electronic musical instruments. I mean, look what Will's done here with a personal computer and a programming language and a considerable amount of imagination. So it really doesn't depersonalize music, I think, but rather maybe humanizes computers, I guess I would.
Do you think it helps with the composition process of this composing music to be
Of
able
course.
to have that interactive
Sure.
nature?
I think a programming language is such an enormously rich resource that it must, at any level, enhance the compositional process.
Will, you guys are different ends a bit. John is working at Stanford with a big mini and a complex operation, and you're selling a $40 software. From your end, how do you see computers and music meshing? I mean, how did you get involved in this combination?
I think computers are a way that people can be introduced to music. And with this program, what we tried to do is allow a person who doesn't know anything about music and who might be intimidated even by it to go out and to fool around with music already created or to create his own and be able to do everything just with a joystick.
Maybe you can show us a little bit about how a music instruction set works.
Okay. Well, basically, you're moving around with the joystick a little hand, and that hand represents your hand. So in order to create music, what you do is you move your hand around and you pick up notes and you set them on the staff, which you see there. After you get the notes set up on the staff, you can move to one of these little pictures here, and the pictures do things. For instance, if you want to play the music, you go to the little piano, which is there. Or if you want to go to the home position, which is at the beginning of the song. You go to Little Home and press the button. I've got a piece here that is included with the product, and so I'll move the hand down to the piano and press the button. It'll play through the piece. Then going to the home, we can go back to the beginning of the song.
The notes going across the staff or showing us the music that the computer's playing at the time.
Right. Basically, it's tying together what it sounds like and what is on the screen. So it's like having sheet music in front of you that scrolls right past your desk. Whereas with the sheet music, you can pick up your pencil and eraser and erase notes and change them or move them around, or even pull out the scissors and cut and paste in different areas. With this, you can move your hand around, pick up a note, move it somewhere else, and drop it. If you want to sharpen a note, you just pick up...
And what you did is press the button to hear what the note on that particular place sounds like.
Right. Actually, I dropped the note, which actually changed the music that's in there right now. So if I played this, it wouldn't sound very pretty. It also tells me what that note sounds like. So if I were composing music, for instance, or just wanted to know where it was, I could tune my ear.
Certainly makes learning about music a lot more fun.
A lot of fun. You can start out, instead of having to learn to play an instrument, you have to learn to use a joystick, which isn't all that difficult. But you can start out by taking Mozart or Bach and then fooling around with it and changing notes and seeing what it sounds like.
What's your experience with people that are first playing around with this? Do they like to learn about music because of this interaction?
The first thing whenever they see a new computer program is to be overly cautious. So they'll move around the hand and be very careful not to move a note too far, this or that. But it doesn't take too long, maybe 5 or 10 minutes, before they realize, hey, this is fun. I'm not going to kill myself if I do something wrong.
Will, you said this program is for people who don't know too much about music, but yet you said you've got to take a note and place it on the staff, and a person who doesn't know much about music doesn't really know how to do that, does he?
Well, as far as moving a note around, the instruction manual tells you what the staff is and some of the basic music notations. You are required to be able to move around notes, move around the hand, pick up and drop notes, but you don't have to know if this is an A or a B or a C sharp or what. For instance, I can point to this position here. I'm pointing to that note, and I could say, well, what am I pointing to right now? And press P. And it plays the note. It says I'm on D. And it also says down here, you're sitting on note D. So it correlates the position on the staff of a note, the sound of the note, and the letter name of the note, which is a novel idea.
Mm-hmm. John, briefly, how would that compare with the kinds of things you're doing at Stanford?
Well, let's see. We assume, for example, in our environment that these abstract symbols notation have already been learned. I mean, our activity is really centered around musicians who have studied for some considerable time, and engineers and psychoacousticians, for example. And our interest in notation is maybe at a slightly different level, having to do rather with music manuscripting, and perhaps later we can talk a bit about that. But I find this very interesting because it's as Will has pointed out, it's a very accessible medium, and through which one can learn a rather abstract and difficult sort of language, if you will. I mean, music notation. I think that's good.
Okay. In just a moment, we're going to take a look at a reasonably sophisticated device which you can plug into your computer, the Alpha Centauri system, and that's coming up next. With us now is Ellen Lapham. Ellen is president and co-founder of Centauri Corporation, the people who make the Alpha Centauri computer music system. Gary?
Ellen, what you have here seems to be somewhat different from Will's previous demonstration. How does what you're doing differ from the music instruction set?
Well, we're both in the music business, and we're both, in fact, using computers to do things that are musical. The key concept behind Centauri and what we do with music, simply music, is turn it into a musical instrument, a live musical instrument that you can play, you can listen to, you can transform sounds with, you can design sound, you can compose, and you can even learn keyboard. So what I actually can show you today is a program we call Simply Music. What I'm looking at on the screen here is a list of albums. Just as I have a 45 RPM record on my player, or 33, so I have a diskette. It goes into my disk drive. And now when I do a directory or catalog, I can see the list of songs I have previously recorded or someone else recorded loaded in. Why don't we listen to Yezu? Now, I played that piece in a couple of weeks ago, or someone else did, or perhaps you played it in yesterday. If you're learning to play keyboard, though, listening to music is not just what you need to do. You also need to see what's going on. So we're using the power of the computer now to give you a keyboard instrument that you can play and listen to, give you a video screen that shows you the music you're playing, and if you don't know how to read music, I will help you even further. I can load in a display of the keyboard itself so that when I play back Yezu, I can see the parts that were played. Now that's a fairly complex piece. If I were learning to play music, if I'd never approached a musical instrument before or a computer music system, I might choose a more easy to learn song. For instance, Merrily. Now this is a pretty simple song, but it gets the point across that you too can learn to play keyboard with this fairly fancy technology just by
That sounds like segue music, Ellen, and I'm going to take advantage of that music to turn to John for a second. And John, one thing, of course, you're dealing with a computer so large we couldn't bring it here in the studio at your Stanford location. One thing you're involved in is music notation. I think you have an example of that in front of you. Show us what that is.
It's an extension of the same idea, and I guess demonstrates what one can do with an enormous amount of effort and over a large number of years. This is a program that was developed by Leland Smith, also on the music faculty, who over a 10-year period has refined the music manuscripting program, which allows one to use a standard printer plotter to output music in large scale, and it's photo-reduced to become publishable quality. Well, the advantages are that his program automatically does part extraction, finds page turns, and of course eliminates all the problems of error making in music publishing. So it's a contribution of considerable importance, I think, in the music industry. The same basic ideas, but reaching a very high degree of refinement.
John, okay, you've brought with you an audio tape from your system at Stanford. We're going to play that tape right now, and if you can put on the headset so that you can hear it as we play it, and tell us what's going on in this audio tape.
Okay, this is an example of high-quality vocal synthesis using frequency modulation synthesis. It took me about 6 months to find the little cues to naturalness that seem to be so very often lacking in most electronic music synthesis. Now, having worked out this algorithm, we can play the next example and hear an extension of nature into a slightly unreal domain. For example, I've modeled now the human voice, but of a very, very large man. So it's deeper than any real human being could sing, as if he had a 6-foot chest, I guess, and a 3-foot neck. So the vocal resonances are greatly amplified because we have this independent control over the dimensions of sound in its abstract form. Now, one of the most important things about synthesis, and which will accrue to devices such as this and the things that little synthesis algorithm that Will was using, has to do with using the technology in such a way that we have a very clear sense of what's natural sounding. The next example demonstrates first just a pure tone, which we'll hear, which is the pitch of what will become a sung vocal tone. Then in a few seconds we add all the harmonics or information that would be present in a real sung tone, but it only becomes natural at the moment we introduce the vibrato and this kind of wiggling in the pitch space, which is common to all natural sounds virtually. Once more, pure tone. Now harmonics, but not natural. And now it sounds natural, sounds vocal-like. So we can, by doing a vast amount of research and analysis in psychoacoustics and signal processing, we can extend to this miniaturization which we see a kind of quality of sound which I think will be a very great improvement.
Okay, John, we're going to move from Stanford now and go back across the country to Cambridge and MIT's Experimental Music Studio for a brief performance of a duet for piano and computer.
John, is the work that we're seeing in computer-generated music, is that still mostly in the laboratory, or is it being used in production now?
Well, I think with the large-scale integration, we're seeing many of the techniques that have been developed in programs, et cetera, over the years in the context of a lab, finding application now in industry. There are, music synthesis algorithms that can be implemented in large-scale integrated circuits. We'll certainly more and more find use in devices of this sort, and organs and synthesizers and who knows what else.
Ellen, you mentioned earlier the concept of your floppy disk as a kind of record album with titles on it. We saw at the beginning of the program this kind of ROM cartridge. Do you see a kind of new form of music publishing in which you could buy floppy disks for a computer playback system?
Absolutely. In fact, my floppy disk is my personal diskette. I can self-publish, which means that now I'm a composer and a publisher all rolled up into one. That is, I have my Centauri. I generate my own music, I save it on diskette, and I can send it off to friends across the country or around the world. So now every musician and every student becomes a publisher, and that means also that the teachers become publishers of their own musical material, and the professional composers can also publish for the audience of people who have the same instrument. So absolutely, yes, it is a new form of publishing, but a very personal one.
Very quickly, we have about a half a minute left. Do you find a resistance among professional musicians and composers, or they really love to get into this?
Well, I mean, at Stanford, virtually every composer who comes to study there not only learns about computer music, but becomes a rather exceptionally good programmer. So I think there's very little resistance, especially in the young generation. After all, people the age of is at will, the young man. Well, I mean, he's already beat the hurdle, you see. He already understands a great deal about programming because these things are in the environment, and that's good.
Okay, John Chowning of Stanford and Ellen Lapham of Centauri, thanks so much for being here, and thank you for joining us. We'll see you next week again on the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. makers of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Gary and I are playing with Flight Simulator here on our IBM PC. This is a good example of how you can use a computer to simulate a real-world situation. That's the subject of today's Computer Chronicles, computer simulations. And later on we'll be looking at more sophisticated computer simulations, flight simulations, and also the use of computer simulations in architecture and urban design. Gary, it seems to me in a way, let's shut him up there. Everything a computer does is really a simulation. What specifically do we mean now when we talk about computer simulations and environments?
Well, today's discussion is going to be mostly about generating scenes, generating an environment that is simulates a situation that someone wants to experience. And you use a lot of graphics and a lot of computing power usually to do that. The idea is basically that in many cases it's a whole lot cheaper, less expensive to generate the environment and test it and work with it than it would be to do the real thing. For example, it's a lot less expensive to run a simulation of a 747 landing with its gear up than it would be to do the real thing. So this is going to be the kind of discussion we'll talk about, generating the real-world situations with a computer system.
Okay, to start out, we're going to take a look at some examples of computer simulations that are in use right now.
Bayonet 1-6, shot. Over. Shot out. Impact.
This is a flight simulator used by the military to train helicopter pilots in air-to-ground combat. Deceptively simple in its visual effects, the simulator requires a complex combination of movement and real-time response to be realistic. Although in appearance computer-generated imagery resembles certain video games, there is an important difference. Computer simulations use random factors to imitate the randomness of reality. In a sense, every computer program is a simulation, the mathematical equivalent of some sequence of events. But in their most modern forms, simulations become more and more realistic. Just as film animation achieved a remarkable level of detail in the 40s and 50s, the computer's video image is beginning to overcome its inherent flatness and is approaching a true three-dimensional appearance. By combining three-dimensionality with infinitely changing perspectives, computer imagery achieves the ultimate effect of realistic movement. In this architectural model, buildings can be viewed from almost any perspective, at ground level, from above, even through the window of a future building across the street. In this case, the computer's ability to plot and see through a building's layers has all but eliminated the need for hand-drawn blueprints. From battle games to battlegrounds, a simulation can make fantasy possible and reality fantastic. But like other technological achievements, simulated imagery is a tool that can be used to build or a tool that can be used to destroy.
Okay, joining us now is Frank Lewandowski. Frank is senior scientist at SingerLink, and SingerLink is involved in some very sophisticated flight simulations and military applications of some of these flight simulations. Frank, welcome to the Computer Chronicles.
Thank you.
Stewart, yeah, this is a very interesting subject. This happens to be my second great love is aviation.
After computers.
After computers, of course. Computers pay for the bills. But this, I think, is the second generation of a program that was done, if I'm correct, by Bruce Artwick, SubLogic. I saw it on the Apple II, and it looks like it's improved quite a bit since then. Can you give us, Frank and I, a demonstration?
Yeah, Frank, you might be interested in seeing this kind of personal computer version of a simulation. Then maybe you can compare the kinds of things you do at SingerLink with this. What we have right now is the basic menu of the parameters we can use to set up the simulation. We can locate the aircraft at any particular set of coordinates. Right now it's positioned at an airport outside Chicago. We can program it to take off from any one of 20 different airports in the United States. It's not quite the way it should be, but it will be good enough. You can set up the time here, the weather conditions, what season you want it to be in. The computer will simulate the daylight and nighttime, the weather factors appropriate to that time of season, cloud layers. You can even set in a reliability factor of the hardware. This says that the plane is going at 100% reliability, meaning that nothing's ever going to break down. I could set it at 0 reliability and some of the pieces would not work. Okay, we'll go into the simulation here, and as you can see, this is the view outside the front of the airplane, and we're sitting on the runway right now at this airport outside Chicago. You can see the sky, the ground. That's Lake Michigan out there. There's the control tower. Here's our cockpit, the instrument panel of a Cessna, which is this simulation is based on. The normal instrumentation, ground speed indicator, attitude indicator, altimeter, we have our turn coordinator, heading indicator, vertical speed, tachometer, navigation gear, fuel gauges, oil pressure, gear down, lights on, and so on. We'll try to take off now. It just doesn't always work. I've just revved up the throttle. And right, sorry. Well, you're the pilot, I'm not. And as you can see, this is the view outside as we try to take off here. We'll give a little elevator action here. We can look out the rear window and see us leaving the airport. Doesn't look like we're going to make it up here. See if there's any elevator. I think we're going to take off, actually. You can take a radar view of what's going on right now. Let's see, did we make it? Yes, we're up in the air. Terrific, we're climbing. You can take a look from a radar view and see the airplane and zoom out or zoom in from that perspective. We can go back to the view out the front of the airplane. Again, look out at the back of the airplane. We can see the airport receding there. Look out the right window. Look out the left window. We can look down and visually confirm that our landing gear is still down there.
It's a wheel sticking out.
That's right. And we can try to get into a turn here, and you'll see the horizon move around. That's pretty much what it does. I'll just go into a stall here and crash so we can get going here.
Stewart, this is a, you can tell when we're looking at it, it's rather a choppy scene. And Frank, would you have any comments about this? This is obviously not a real-time picture that we're observing here.
No, what we're doing here, of course, is that you're updating a scene which is made up of probably 20 or 30 lines, and you're updating it 2 to 3 times a second. Well, the thing is that in aircraft simulation, if we were to do the actual scene out of the windscreen of an aircraft, we need a much more sophisticated scene than that. A pilot just wouldn't accept this kind of a scene for military training. And so we usually have to go to something in the order of 8,000 edges for every television frame time and have to compute a new scene each time at each television frame time, as opposed to here where we're doing 2 or 3 a second.
So the computer power that you have behind the scene generation that you're working with is considerably more than an IBM PC then.
Well, I think there is probably, what, 1 IC in this or so?
One chip, one
microprocessor chip. Well, we have something in the order of 40,000 chips in one of the visual simulators that we build. So the difference is quite substantial.
What are the applications, Frank, of the kinds of simulations you would do at SingerLink?
Well, obviously aircraft for the airlines, that kind of simulation, but that usually is limited to takeoff and landing. And that isn't a particularly difficult thing to train. The more difficult ones are the military ones, where you're actually trying to train someone either at air-to-ground combat or air-to-air combat or one of those kinds of activities. The problem there, of course, is the fact that you aren't training somebody just for the mechanics of the flight. You have in there all of the other elements, which are the opponent, the other combatants in the scene. It's an entire environment. The entire scene has to be simulated as well. So that's what we're in the business of doing.
Maybe we could take a look. I think we have some videotape of some of the simulations that you have done, Frank, and if we could roll those now, and you could kind of give us a play-by-play of what we're looking at.
Well, this one here is the scene. It's a real-time scene now. What you're saying is that when this was done, it was computed on a television frame by television frame basis. Obviously, now we're playing it back from a pre-recorded flight. But in actuality, this is a scene which is computed. And what we're going to see now is the A-864, which is going to fire a missile. It did. We're going to now go back and track the missile to some extent, and we're going to see that what we did is we hit that tank that we had laser designated just a few minutes before.
Now, these pictures, Frank, I just want to make it clear. It looks like an artist could have done these. These are not painted. These are computer generated.
Yes, and they are generated every 30th of a second.
Okay, so normally, again, you're not playing back a video disc or a videotape here. You're generating these pictures in real time.
That's right. What we're going to see here in a moment is we have already fired the missile, and we're going to laser designate the tank, and now we've hit the tank. This is the present state of the art right now in computer generation.
Okay. So you have a database that represents the terrain And then
Right.
you are able to then take other different perspectives on that terrain depending upon where you're...
What you do is everything in the entire world, whether it be a mountain or a tree or our military targets as these, every one of these is coded into an X, a Y, and a Z coordinate. So what you do is from some point in space, you must then record the values of all of those vertices for everything else in the world. And then what you do is you have this orthographic database. You then, from the particular point in space where the eye is, either whether it's my point or whether it's any of my opponents, the point is that we compute the scene based upon those input coordinates.
And that's what takes all the computing power then, is to
Absolutely.
compute each one of these little points.
Mm-hmm. Do we have another example, I think, of...
Well, what we have an example of is that at the present time, I showed this as being the present state of the art, but what we have done is we've emulated now where we're going. The next few years, we're going to be developing the texture as you see it here on the ground. We're going to be developing the trees, the trees which are show foliage, and as you can see, the sky, the clouds, and all of the other elements. In fact, well, you couldn't quite see it, but as the helicopter got closer, you could actually see the pilot and the weapon system operator in the cockpit of the H-64. Now we're coming down into a village. Notice the texture on all of the buildings. Notice the tank. It's been destroyed. It's got a big hole, and obviously the gun is down.
Frank, how long is this going to be before this sort of scene generation is actually going to take place?
Well, all of these elements are being done right now. At the next thing, in about a year or so, we'll have the texture on all of those hills, as you see. And it'll be a few years past that when we have the trees and some of the other elements of that scene. But that is where the industry is going.
And when is this going to? When are we going to find these in the arcade? Or in the arcades?
Some of the arcade people are getting awfully close at times. Some of those new scenes are coming from video disc, and what they're doing is they're actually mixing video scenes and computer-generated scenes. Whereas on all of these, none of this is video. This is all generated frame by frame in a computer.
Mm-hmm. Okay, there are other uses of computer simulations, obviously, besides flying, and one of those is in architecture. Suppose, for example, you wanted to build a new skyscraper in the middle of a city. What would the consequences of that building be? Well, we're going to take a look at computer simulations in architecture in just a moment. Okay, joining us now is Steve Harrison, who heads up the computer division of Skidmore, Owings & Merrill. That's an engineering and architecture firm in San Francisco. Welcome to the Computer Chronicles, Steve. Steve, tell us, how does an architect use computer simulations?
We use it in quite a number of ways. We use it in architecture, engineering. We use it in perspective drawing. We use it to study shadows on an urban environment. We use it to study the effect of earthquakes on large steel frame buildings. We do energy simulations, watching the performance of a building over a year as the sun travels in different paths over the sky.
And Frank, how would the kind of simulation that Steve is talking about differ from what you do?
Well, the thing is that they do not have the same constraints that we do in an aircraft simulator, and that theirs is not real time. We have to compute the scene dependent upon every motion that the pilot takes. If he moves the throttles or he moves the stick, the scene that we generate out the windscreen of the aircraft has to reflect what he's done, and it must do it immediately.
Now, when you said, Steve, you do earthquake simulations, that's not in real time?
No, it's not. We take a tape that was made of the actual forces in an earthquake, and then we play that against the frame that we have designed. An earthquake analysis will probably run for 4 or 5 hours on a computer, whereas the actual earthquake runs for a few seconds. And we're only looking at the most serious part of an earthquake.
I think we have some videotapes here that will show some of the drawings that they're making, right?
Yeah, if we can take a look, and Steve, maybe you can give us a little explanation as to what we're seeing.
Here we're going to do some perspective studies of the City Hall of San Francisco. The building was built much before our firm was in existence. It's a wire frame representation, as though made with coat hanger wire, but in a second we're going to fill in the building with a grayscale. The building is kind of a gray color, so this is a pretty good representation of it. You'll notice that there is not much surface detail on it, but for the purposes of massing studies, this is quite adequate. As you can see now, we're building up the dome as a series of faceted elements.
What, just to give an idea of just the computing power required to generate these pictures, what kind of a system do you have behind this?
The SOM software runs on VAX computers, and the terminal is a Tektronix 4113 color raster terminal. This is a VAX 780, although the software will work just as well on the smaller VAX 730 or 750.
You say SOM software, so I think your firm designs the software that does this.
We've developed our own proprietary system. The software you see here is called Draft, which is used for perspective drawing, 3D drawing, 2D drawing. We do our own software.
Okay, I think we have a second demonstration up now, Steve, and tell us what this is.
This is going to be Davies Symphony Hall in San Francisco, which our firm designed. On the lower left, you see a plan view of it. On the upper left, you see an elevation of it. And on the upper right is a perspective view. In a minute, we're going to zoom in a little closer on this perspective, zooming in specifically to look at the window detail, which is the sort of thing that architects are very concerned with. As you can see, the window coming up just about now. There we go. The information in the lower right are the commands to run the program. These are the same kind of commands that a person doing working drawings, that is, drawings that would be used to build the building, would also use. Again, we're getting in even closer to the window detail here.
Are these the kinds of systems that are being used throughout the industry or the architectural industry these days? Or is this something that's really very special to your company?
We feel it's very special to our firm, although there are a number of other firms that do have systems that begin to approach this. We try to keep, obviously, one step ahead. There are a number of non-proprietary systems that can be purchased that do some aspects of this, but we have what we feel is an integrated system that applies to all the architectural and engineering disciplines in the firm.
Would you use simulations to get involved in things like the environmental impact of a new structure?
Absolutely. In fact, that's one of the major uses of this particular system. The massing studies, especially for studying the mass of a building in a tight urban environment, very concerned especially with something like shadow in San Francisco, where if you have a shady area in the summertime, it can be very cold. That environmental impact reports spend a lot of time dealing with this particular subject in San Francisco.
When you say massing, by the way, what do you mean by a massing study?
Just so, the mass of a building, its volume, the blocks of it in space, those are the sort of issues that architects are concerned about, as well as the surface detail and the way the building goes together.
You spoke about the shadow studies. I believe we have a demonstration of that right now. Maybe you could walk us through this one, Steve.
Right. Now we're going to look at another familiar building in San Francisco, again in plan view. This is the Bank of America World Headquarters. It just popped up in red. And then the green are shadows being cast at 1-hour intervals across California Street in San Francisco. And we're going to zoom in here and look a little more closely and see what everybody already knows, and that is that the plaza on the north side of the building will remain in shadow during most of the day. There we go. The building is in red, and there's the shadow in the morning at 1-hour intervals. And as you can see, the street and the plaza remain in shadow.
Now, Steve, that's a very impressive demonstration, but there must be a considerable cost factor in that kind of simulation. Is studying the shadow of a building that difficult to do in a sort of manual way?
Yes, it is, especially if you're making major changes. The traditional way is to build little models, but in a place like San Francisco where there are a lot of other structures and there's a large interaction between the shadows, that this is probably the easiest way to test a large number of different designs.
One of the things that came up in this last clip was that you showed a plan view of the building. Are you using this, or do people use these kinds of simulations for interior design at all, placement of objects within the rooms?
Oh yes, in fact, the same system is used for interior perspectives as well. Interior perspectives turn out to be a very interesting problem because they have a lot more edges, especially the open office sort of environment, and when you do it in wireframe, it gets to be kind of a jumbled image. And when you do it in a hidden line drawing, you just see this great sea of small lines and planes across the top of the partition systems.
Frank, getting back into your kind of simulations, it's very sophisticated and very realistic, but I assume there are things you still can't do. What else would you like to be able to do in your type of military simulations?
Well, of course, we would like to have a much better texture. We would like one of the biggest problems you have is that those objects which are right in the foreground, you need much of them. You'd like to have textured surfaces. You'd like to have rocks and pebbles. If you're going to learn to drive a tank or maneuver a tank, you want this kind of detail. Well, that's very difficult to do because even in the textured scenes that you saw, that's a geometric type of texture. You'd really like to have much more realistic texture.
When you're talking about realistic texture, do you actually go out and digitize a piece of property? Is that an approach you take sometimes, figuring out where the rocks are? And
oh, yes. Well, for example, when we do an airport, we go out and get all of the civil engineering drawings, all of them, and then we extract the data that we want from those engineering drawings. That means that the grassy strips, any kind of shrubbery that's around it, any tree blocks that are around it, all of the buildings, all of the huts, any radar, whatever is out there, we digitize every bit of it.
Frank, in about 30 seconds, all the time we have, how can you simulate the human factors? Can you simulate the emotional responses of the pilots in these situations, apart from just the graphics of it?
Well, you remember that in addition to the graphics, which you're looking at here out the window display, you're also moving giving him all of the impression of sound. You're giving them all of the impression of the motion of that aircraft. You're giving him buffeting. You're giving him all of those other cues. And all of those put together with the realistic portrayal of the motion of that aircraft, you're giving him everything he ever needs.
Steve, and finally, a couple seconds, what would you like to do to improve your simulations?
We'd like to get one of his systems. But short of that, again, we would like to be able to do the kind of realistic scene that he's talking about. We find that when we go from wireframe to hidden line drawing, they begin to look cartoonish, and so our architects are very concerned about a very realistic scene.
Okay, gentlemen, we're out of time. Frank Lewandowski of Singer Link and Steve Harrison of Skidmore, Owings & Merrill, thanks for joining us, and thank you for being with us on the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Herb Lechner, sort of sitting in for Gary Kildall this week. Not really. Gary's going to be with us, but on the other side of the table today, because our subject is operating systems. And as you may know, Gary Kildall is the creator of CP/M, perhaps the major operating system in use today. Herb, operating systems is kind of a tough subject because as computer users, we all deal with operating systems, but frankly, not very many of us really understand what it is. Give us a brief general introduction to an operating system.
Well, Stuart, I guess operating systems are most exciting when they don't work, and that you don't want to have happen. But on the small machine side, operating systems manage the computer resources, and they save the programmer a tremendous amount of nitty-gritty effort, and they provide a standard operating environment to enable applications to run on different machines and on different configurations. On the large machine side, operating systems become very sophisticated and literally manage the computer resources in such a way that they can achieve their potential.
Okay, before we get to Gary and our other guests, we're going to take you inside a computer to see exactly what the operating system does.
Hello, can I help you?
Yeah, where are we?
Well, you're standing inside an Apple IIe microcomputer.
And who are you?
Well, I'm Bruce Tognazzini. I'm an engineer with Apple Computer, and I'm here to check out and make sure everything is perfect on this computer, because we have a report that in just a few seconds here, one of our owners is going to be turning this computer on.
And what is all this stuff?
Well, these are the parts that make up an Apple computer. That particular chip that you're standing on
is
called a microprocessor, and it's pretty much the heart of the computer, kind of the moderator of the talk show that goes on. And these two chips down here, these are very important ROM chips, which have the built-in basic language and the very kernel of the operating system. And then these 8 chips out here are the RAM chips, and they hold the information that comes in from the disk drive and that the user types and the programs and so forth.
Bruce, we're trying to figure out what an operating system does, and maybe you could help explain it.
Well, sure. An operating system essentially runs the entire computer once it's come in, but right now it hasn't turned on. Although I see the user's about to flick on the switch. It's all right. It's only about 12 volts. The power light goes on, and then the little microprocessor here has the job of checking itself out and then turning control over to this ROM chip. This ROM chip, in turn, has a very small program which goes back to the back of the computer and checks out and sees whether it can find a disk controller card, which of course it can because there's one plugged in here. And on the disk controller card is another ROM, and this ROM now takes control from that one and begins to bring in the disk operating system off the disk drive through this white cable. You probably saw the disk drive while you were on your way in here. And then that comes down and starts filling in these RAM chips here. Fills up about 1/5 to 1/4 of the RAM chips with the disk operating system. It brings in any language and perhaps any program the user wants to do. And after about 15 to 30 seconds, it's all done. The screen gives a message to the user, and then the user can go to work.
Okay, well, I've got to get back to the Computer Chronicles. Thanks a lot.
Certainly. Thank you.
The operating system is a sophisticated computer program that makes the computer easier to use and operate more efficiently. Operating systems are sometimes called systems software or systems programs, as contrasted with application programs, which are the subject of a later lesson. Operating systems provide up to 7 functions, not all of which are present in smaller computer operating systems. One function of all operating systems is to establish the way users interface with the computer. For example, how data are stored on files and how programs are initiated. A second function of operating systems is to permit multiple users to share the same hardware. A third function is to manage data files so that data may be shared among several users or applications. Potential users can be scheduled and unauthorized access prevented. A fourth important function is the handling of all input and output data. Since many applications will run on the computer and share its storage devices, it is necessary to have a common control over how data is stored, accessed, and retrieved. A fifth function is to provide error recovery for the computer system. If an error occurs in the process of reading data from an input device, for example, the system will try to reread the data several times until the error is recovered or bypass procedures initiated. System accounting is a sixth operating system function. This function keeps track of the machine resources so costs can be apportioned among multiple users. How much CPU time is used by each application? How many disk and tape records are written and read by each application, and so forth. The last function provides maintenance accounting. It keeps track of correctable machine errors to aid the maintenance and replacement of failing components. Operating systems available for today's microcomputers are approaching the sophistication of the systems described here and are the subject of the video portion of this program. Gary Kildall shows one of his latest in the next segment. Let's join him now.
Joining us now is Gary Kildall, no stranger to this program, of course. Gary is the creator of CPM, host of Computer Chronicles, and also Chief Executive Officer of Digital Research. And with Gary is Tony Fanning with the Corporate Engineering Department of HP Labs at Hewlett-Packard, and Tony works primarily with MS-DOS. Herb?
Gary, in view of the immense success of CPM 80, could you tell us a little bit about how the idea got started and how it came to be what it is today?
Well, I guess I'm sort of known as an operating system person, but realistically, I started back in the early days of computing and mostly interested in programming languages rather than operating systems. And I was working with Intel Corporation, working on a language called PLM. It was used as in the early days of microprocessors, and it was necessary to have some kind of an operating system to support the language. And that's where the name came from. CPM was a control program for microcomputers, just as PLM was named a programming language for microcomputers. And we were using paper tapes at the time, and we needed to have something else to store programs on besides paper tapes. It was a pretty tedious process. And so floppy disks came around, and CPM was in the software that made those floppy disks usable in a small computer system.
Gary, operating system is a bit of a mystery to a lot of normal computer users who just take advantage of it but never really get to delve inside of it. Could you give us a rough description of what the operating system does inside the computer? Well, basically there are three levels of software, if you want to think of it that way, that you work with in a personal computer. One of them is the level of machine instructions. So it's just if you turn the machine on, you don't put any diskettes in, the machine is capable of understanding some instructions. Those are machine instructions. But you have to put something in there to make the thing operate. The second level is what is called system software, and that lies right above the machine language itself. And the third level is the application software, and that's what you actually go out to the store and buy, is the application software. And then the application software then uses the system software as a foundation. System software then runs the machine using the machine instructions. So in that middle layer of system software, you find a number of things like programming languages, utilities, and operating systems. Now, an operating system then is sort of the traffic cop. It keeps track of file, or how your files are stored, how your display is handled, and the keyboard is handled, and things of that sort. And so it's just the foundation for it's like a record player when you're playing records.
Well, you have the perspective as a developer, Gary. Tony, you're a user of operating systems. What, as a user, do you seek to find in an operating system?
Well, I have an interest, of course, technically in the operating system and how it works, but really when I'm using it, I want the operating system to be transparent to me. I don't want to see it. I just want to use an application, and I know you asked a question earlier about what should one look for? Well, what are you trying to do? If I'm trying to do something like, for example, word processing, I'd like the operating system to just disappear and not bother me.
Now, you work primarily with MS-DOS, Tony. How would that be different from, say, Gary's CPM?
In a lot of ways, it does the same types of things that Gary's CPM does. I think Gary can tell you about some variants of CPM which are very different from what MS-DOS currently does. It's basically the same thing. It allows you to take care of files, take care of transfer of data from one place to another. It takes care of the whole human interface between you, your fingers, a computer, the programs that run in it.
Gary, we've been through several generations now of, say, CPM, and each one adds something. Can you describe for us what gets added each time? How do you improve an operating system each time you come out with a new version?
Well, the real key to any system software is trying to match what you're doing with that software with the computer system, the capability of the computer system that you have. And what happened, I think, early on in the microcomputer days is that a big computer system had 16K of memory. And so the idea is to tailor down an operating system that uses only a very small part of that memory. Now, when you add more memory, faster processors, then you get more functionality that you add to the operating system, as you do more for the operator. And what's happened with, well, these 8-bit systems, for example, are all now 64K. Those are maximum memory size. And even in the 16-bit machines, the average memory size is, let's say, 128, 256, even 512K. We're moving in that direction. And so what happens is the operating system expands, gets more functionality to take advantage of that larger memory area.
One of the early attributes of CP/M and some other operating systems were that they were simple and clean and neat. And now with the computers becoming larger and this growth occurring that you're talking about, are we going to see the sophistication and complexity grow in the operating system?
Well, it certainly is true that it's very easy to add what are called bells and whistles to an operating system, things that really don't add much to the functionality just because there is more memory space. And I think that's the real crucial issue, is how do you add the right kinds of functions. What we see now with 16-bit machines and large memory systems is that we'll see things like concurrency, and we'll be able to demonstrate some of that today. That is, large computer systems have had concurrent operating systems, or multitasking is what it's called in large computer business, for years, and that's the idea of being able to use a computer system to do more than one thing at the same time. But if you look from the small computer, microcomputer days on to today, you see what's happened is that we started with single tasking or single user systems. And so what's happening now is we're coming together, and concurrency, or the idea of doing your printing while you're doing your word processing, for example, is the one that we're finding in that additional functionality that's added.
Gary, you have, I think, concurrent CP/M up here on the IBM PC right now. Maybe you could just run through a little bit and show us what the components of this system is.
Okay, now the idea of a concurrent system and concurrent CP/M is it's what's called a real-time system. That is, it's able to switch between programs in very short time intervals, and, for example, be able to receive data over a modem while you're seeing the directory operation. Now, what I'm going to do here is I'll use the keyboard to switch between what we call virtual screens. That is, you can imagine now that you're looking at 4 different consoles as I switch from console to console. So if we say console 0 is the one that we're looking at right now, and that happens to be shown in the lower left-hand side of the screen. Console 1, you'll see, happens to be a display of memory locations. Console 2 that I switched to happens to be a directory, and console 3 is a brand new free screen. Now I'll start a command here. I'll start the debugger just to get something going. And it's loading off the disk, and it's also giving me the prompt telling me it's ready to go. Now I'm just going to say display all of memory, so we'll have something active going on there. Now while that's going on, I'll switch back, and you can see that we're in a directory operation here. And so I'll just start that one again on this console. And as it's going, I better type it right here. That seems to be the weak point in the system, is the operator. And then as this is going on, I'll go ahead and switch back, and we can see what now we're getting a display of the directory right now, and I'll switch back, and you can see this other program is still actively processing. Okay, that's finished. Switching back again to the original screen. Now this is a very short demonstration of the concept of multitasking or concurrency, but the way it would actually be used, to say in a business, is that you'd have your word processor working on one screen, and then meanwhile you'd switch over to, say, another screen to do spelling checking or receive data over a modem. So the effect is that you get multiple microcomputer systems in front of you on your desk. Now this is the way that operating systems are moving right now. Because of the fact we have, let's say, 0.5 megabyte of memory in the machine, we want to make sure that we use that machine effectively. Because what we're looking at nowadays with computers of this type are really the mainframes coming down to your desk. So we want to make sure we have that capability.
Okay, well, Unix and Xenix may sound like 2 characters out of a Star Trek episode, but in fact they're 2 very elegant operating systems, and we're going to take a look at them in just a moment.
Operating systems for the larger computer systems evolved over time and were primarily used to improve hardware efficiency. Their main job was to keep the CPU and main storage as productive as possible, scheduling as many different users and applications through the hardware system as possible. One way this was accomplished was through multitasking or concurrency. This is the computer's ability to run several applications at once. Most applications, which use a fair amount of I/O, do not use the CPU efficiently. The CPU is frequently idle, waiting for the application program to get data from a slower I/O device. The operating system accomplishes multitasking by allowing an application program to run until it requests I/O. The operating system then suspends CPU processing for that application and starts another application, which continues until it needs I/O. The operating system will initiate as many applications as are needed to keep the CPU busy. When the I/O requests are satisfied, the operating system will reinitiate a suspended application. This is just one example of the types of relatively sophisticated function performed by the operating system. Unix, an operating system originally introduced for mini computers, but which is quickly finding application in micros, is the subject of our next segment. So let's get back to our program.
Joining us now is Gene Yates, who's president of Yates Ventures, a company involved in research primarily involving the Unix operating system. Gene, welcome to the Computer Chronicles.
Thank you.
Tell us a little bit about Unix and what it is, especially compared to CP/M and MS-DOS, the other things we've been talking about.
Well, Unix is another of the standard operating systems that computer users are growing to find more interesting to them because of the variety of application software and different brands of computers that they can choose by going with a standard operating system as the basis of their computer system. And Unix is particularly unique because it runs on microcomputers, mini-computers, and mainframes, from the smallest to the largest systems, from an IBM personal computer to a great big huge Cray supercomputer. Unix is available for all of them. Unix is also very easy to network so that you can connect these different brands and sizes of computers together easily. And if both computers use Unix, you can find yourself sending electronic mail, transferring files, sharing application software programs very rapidly, more so than with many other products. Another major facet of Unix is that it's multi-user. That means that more than one user can access several different programs at the same time with Unix. So one person at a terminal into a computer could use an accounting system, while another person at the same time is doing word processing, while another person is sending electronic mail, each running a different application at the very same time using the same computer, just different terminals.
Gene, as I recall, Unix grew up in Bell Labs and then was for a while licensed only to universities and not-for-profit organizations. Yes. Is it fully commercially supported now?
Well, Unix has a long history, and it was first introduced in its most primitive form in 1969. It wasn't until the Bell system was deregulated, I think we're all aware of the big doings with ATT, that ATT could really sell and support the product. They legally couldn't do much with it because they were precluded from entering the computer industry until deregulated. But the newest version of Unix, called System 5, which is about the 6th version ever released by them in a number of different names, is commercially supported. And although the product still needs to be enhanced and improved for small systems and beginning end users, ATT seems to be making some big strides toward that.
Mm-hmm. Gene, how does Xenix compare to Unix?
Okay. Well, the Unix software from ATT is sold in two forms. It's actually licensed. Source code license is an expensive, very high-cost license that lets you take the software and actually change it or rearrange it or make it different for your specific kind of computer. Computer manufacturers or software companies buy source code licenses, and Microsoft is one of those companies. Microsoft has purchased Unix source code and has fixed it, changed it, enhanced it, whatever, so that it runs on different kinds of microcomputers. It runs on the Tandy System 16, the Apple Lisa, the Fortune Systems 3216. It's rumored they'll be introducing it for the IBM PC XT. So Xenix is just Unix with a few enhancements for personal computers or for microcomputers.
Tony, you have used Unix. I always sort of associated Unix with the PDP mini computer line, and Gene has just told us that it's growing up and down. What has been your experience with Unix, and how long have you used it?
Oh, I guess I've used it about 5 years, which makes me a relative newcomer compared to a lot of the people that have been using it, but makes me an old-timer with respect to the microcomputer users. I still haven't used it, actually, on a microcomputer, which is pretty amazing. As I told you earlier, I do use MS-DOS on a variety of computers. MS-DOS is reputed to be moving in the direction of looking more and more like Unix. You might want to tell us about what that really means. I'm really curious to see what the next release will be like.
Well, it's difficult because so far the most energetic movers and shakers towards microcomputer Unix have been companies not ATT, because ATT hasn't been allowed to. Microsoft and now a few other companies as well are getting into it. We can theorize that ATT will introduce a whole line of computers. They are going to be a computer company that's fairly well established. If they introduce micros, minis, and mainframes all running Unix, we'd have to assume that whether they do it immediately or fairly short term, they should try to offer the commercial features that the user is going to demand. Because right now it costs a lot more for a computer company to hold the hand of a beginning Unix user than it does for MS-DOS or a CPM86 product.
Gary, Tony said MS-DOS is moving in the direction of Unix. Where is CPM in this picture?
Well, I think that the influence from Unix has been a very good one in the microcomputer industry, especially around Unix tools, the C language, the utilities, things of that sort. There's also work that we're doing with Unix ourselves in conjunction with Intel, and we'll see some offerings of that sort. So we believe that it's basically that the Unix systems are, for a variety of people, a certain segment of the market is a very important market. We feel also that in the case of CPM and concurrent CPM that there is more of a commercial orientation to those operating systems. So there's a matrix of these operating systems that kind of complementary in many ways.
I get the feeling that when someone buys CPM, they buy it and they do not touch it. They put it on their computer and hope that it becomes invisible to them, except to do the functions they want. I don't believe there's any two Unix systems alike, at least as I last touched base with it, that seems to be modified, used by systems developers, and tinkered with. Does that represent a difference between the two markets for these systems?
Well, you have to keep in mind that CPM86 and new versions of CPM are enhanced and increasingly functional versions of a microcomputer product. Unix is a mini-computer derived product. It's a big system product, and consequently it has 400-some built-in programs that do everything from typesetting to electronic mail to text processing to calendar to metric to inch conversion functions to extensive programming tools. It's a very big system. But it's very modular. It's like building blocks or alphabet blocks from childhood. You can take these blocks and you can combine them in many different ways. So people who buy Unix typically, for example, my Unix computer sitting on my desk, I've extracted from it about 2/3 of the programs because I don't use them. I'm not doing program development, I'm not doing typesetting, and I just keep the parts that I like. And the nice thing about Unix is that it's sort of a do-it-yourself operating system. You can take all of these utilities that are available and make your own little system together. It does take more studying and expertise to be able to do that than with CPM. It's a harder to understand product.
Folks, we are out of time. Gary Kildall of Digital Research for today, Tony Fanning of HP Labs, and Gene Yates of Yates Ventures. Thanks for joining us, and thank you for joining us for this edition of the Computer Chronicles.
These are very exciting times for creators and users of operating systems, and the future looks very bright. There is a handful of very popular personal computer operating systems. CPM and MS-DOS are two. Now Unix is also becoming available for micros. The popularity of these systems has spread largely through the work of third-party software developers and hardware designers. On the other hand, there are some thriving proprietary systems like Apple-DOS and TRS-DOS, which are well supported. So there has yet to emerge a standard that the entire industry is willing to endorse. As with the entire computer industry, operating systems development is in a constant state of change. As new capabilities are added to a hardware system, such as hard disks, telecommunication ports, and laser disks, operating systems must be revised to accommodate them. As new hardware designs were incorporated in the 16-bit microprocessor, designers had to create new operating systems to take full advantage of the increased processing power. And now, the new 32-bit microprocessors with increased speed and efficiency are challenging the creators of system software. There will be a continuing and expanding competition at the system level as there has been at the hardware and application level. Some of this competition will focus on creating operating systems that provide application program portability. That is, the ability for application programs to run on many types of computers. In our next lesson, we'll discover the world of application development and program utilities. Be sure and read Chapter 8 in your text, and I'll see you then. I'm Herb Lechner.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall, and piled up in front of us is just a small example of the word processing programs which are available. Gary, I'm told that today there are about 150 different word processing programs you can buy, and some word processors, in fact, word processors like the little one I was using here, it doesn't come on a disk at all. It comes built into ROM inside the hardware here. Now, in this particular Radio Shack 100, it has what it calls a text editor. But I'm not sure, how does that differ from a word processor?
Okay. Stewart, a text editor is really a program that's used to prepare programs. When you write a program the very first time, and obviously in most cases is not correct, and you have to go back and make changes to those programs. And to do that in an interactive way, you use a text editor. But a text editor is really not very good for working with documents, paragraphs, cut and paste operations, things that you normally do to prepare a document. So that's what a word processor is for. And word processors, as you mentioned, come in a variety of sizes and styles, and it's tough to make a choice sometimes. We'll be able to talk about some of those things today.
Okay, we're going to be looking at more than just traditional word processing. We'll also be looking at writing processors or writer's aids, software which not only helps you type better, but hopefully helps you write better. But even traditional word processing has changed much of business writing, and one good example is the way word processors are used in the newspaper business.
The modern newspaper office has become a cooperative venture between the printed word and its electronic counterpart. Word processors have eliminated many of the intermediate steps between a writer's notepad and the camera-ready copy. In many instances, a story never sees a page of paper until the final stages of printing. Instead, a column can be electronically transferred from the writer's word processor over phone lines to a terminal in the editorial department. Like a remote cottage industry, the columnist, living 30 miles away from his workplace, types and makes corrections on his own terminal, picks up his telephone, and sends his story through to the city desk. Recently, entire books have been written this way, stored on disks until the final draft, and shipped via modem to the publisher. Word processing means more than just electronic transmission. It also offers different degrees of interaction with the creative process, from correcting spelling errors to stylistic advice. Writers disagree on what effect word processing will have on the quality of our written language. Some writers are concerned that computer assistants may promote dry, bland writing by diluting an individual's style. But others claim that they improve writing ability because they operate at the writer's discretion, providing as much or as little editorial assistance as the user chooses. To what degree these language manipulators will change how we write, as well as where we write, remains to be seen.
With us now is Jim Edlin of Bruce and James Program Publishing, and Jim is the designer of Word Vision, one of the newest word processors on the market. And with us also is Paul Schindler, West Coast editor of Information Systems News and a reviewer of software. Gary?
Well, I think I'll just start this off and talk a little bit about the definitions that we're working with, just to get everybody sort of on the same basis. Word processors are said to be the most popular applications for small computers, and also they're one of the very first applications. What sort of things do you look for as the standard features in a word processor, and what kind of desirable options would you look for?
Well, it's interesting to think about a word processor just in the terms of the name. It's a computer program that allows you to process words, just like older computers were primarily oriented towards processing data. The most important thing is it should be easy to learn and easy to use. I know those are popular buzzwords, but it should allow you to sit down with a blank screen and with a minimum of fuss and muss create a document. And since most of us are not perfect, it should allow you to correct errors easily, to move portions of the document around, and then in a function which is separated in some packages and integrated in others, you should be able to take the words which you've just written casually on the screen and format them in a precise and pleasing way. The number of lines per page, headlines on the page, footnotes, superscripts and subscripts if you're writing a scientific paper. Those are the major features. As with any software program, I'm personally convinced that it's like an automobile. You should never buy it unless you've taken it for a test run. It should be something that you're that familiar with at least.
Mm-hmm. So go to the dealer and try it out and see what.
Try it out. Try several.
Mm-hmm.
Paul, there's a tremendous price range in word processing programs. You've got, say, Jim's Word Vision, $50 to $70 range. You've got WordStar, maybe up to $500. How different can word processors be to cover that tremendous price range?
They tend to differ in function. And one of the things I've learned after 5 years of writing in the computer press is that you can't just deal with price or just deal with performance. I think the most fundamentally important concept I've learned in writing about all of these products, hardware and software, is that you have to think in terms of price performance. And typically, the price reflects the performance. With all due respect to Word Vision, which is a nifty software package, there are things that WordStar can do that Word Vision can't. I'm also told, however, there are things that Word Vision can do that WordStar can't. And it's a matter of deciding what you personally need. I'm a reporter. I need to be able to slap words on the screen. In fact, I own a word processor. It's an unusual one written by a friend of mine that has no page formatting back end. I don't print my stories out on paper. I send them to a computer in New York, so I don't care. But if someone cares, they'd better find a package with sophistication in that area. So the price tends to reflect, as a rule, the level of sophistication of the program.
I think that's changing to some extent now. The price is a very difficult thing to work with right now, because a lot of companies that are really trying to do mass marketing of software, and so the price may be much less because the market is much larger.
On that one, because it's true what you say about price performance, but on the other hand, there's also a time factor in that. The $5 calculator you can buy in the Safeway today will do more than the $500 calculator you could buy 10 years ago. So really you have to consider price levels as they change over time and as they change over the market. Because when a company like IBM puts out 600,000 computers in a single year, and as those numbers keep growing, the numbers which a company like ours can amortize its development and other costs over are growing so substantially that it's possible to offer more and still charge less.
So it's really important to look at the functionality that's provided in the software package as well as the price, for sure.
One of the things, I was at a recent writer's seminar on not being afraid of the computer, and one of the things that someone suggested in terms of hardware, and I think it's equally applicable to software, is don't buy more than you need. You don't need some gigantic 32-bit super microcomputer if all you want to do is simple word processing. If you're never going to do a spreadsheet and you don't need a database, buy a small machine and a simple package. And I think it's exactly the same in software. You can, there are articles appearing constantly which compare all the word processors along an axis of 42 features. Well, if you only need 6 of those, then buy the least expensive package that has the six features you need.
Jim, you've got WordVision tantalizingly sitting on our IBM PC here, and maybe you could tell us a bit about WordVision and how it differs from the word processors which have preceded it.
I would. Before actually twiddling with the keys, I guess I could say a couple of things conceptually about it. One of which is we call it a writing tool rather than a word processor. And our theory there is that this is a tool meant for a person who is working with his or her own words rather than somebody working in a secretarial context with someone else's words. And the premise we've started from is that you have to look and see, are those needs different? And we think they are. And then to respond to those different needs rather than emulate what's been working in every office for 5 or 10 years. The second thing, we come from a perspective of what we would call people literacy. We have heard the various people crying, the world needs more computer literate people, and we've said no. What the world really needs and what we now can have is people literate computers, computers that understand what people do. So you can see, for example, one of the things we've resorted to is familiar symbols and sequences, red, yellow, and green like on a traffic light, which most of the people who will use such a machine instinctively understand in a part of their brain where they don't have to think through things. They understand red and green. So we've used it on the screen, and indeed, although we make it possible for people not to have to do this if they would object to it, we also use it on the keyboard. We have taken IBM being the first machine we've addressed, both, I guess. We've taken their keyboard and said, yes, it's very fine clay, but it could stand a little modeling. And so I've applied some of the labels that we supply, and actually in more recent versions now, we supply slip-over key tops instead of these labels that help people find their way around this keyboard.
Okay, Jim, we have very little time, so maybe you could get to a quick demonstration of WordVision itself.
Sure. From this traffic light screen, if you wanted, say, to work with a file on a disk, first you'd press the green key to get your blank sheet of paper, and then a key that says Files to begin working with files of writing that you may have stored on disk. You get pictures of file folders. You would never have to type in, as say in earlier programs, the name of the file you want. You simply point to it and you press a key that's indicated right on the screen. The folder pops up, and in a moment you'll see the text that was stored in that file appear on the screen. Now if you wanted to rearrange that, say, have it look different on paper, and that's one of the two things that a tool like this helps you do, you'd press a key that says Format, and then the yellow one for page appearance. You would get on the screen an image of the page that you're working with and a list alongside of the various things about it that you can change. For example, making the text width smaller, or moving it around so that the margins are different to adjust it on the page. Very quickly when you're through, as it tells you right on the screen, you press the key with the familiar stop sign. It spends a moment doing its business, and it all comes back, rearranged just the way you said.
Okay, thank you, Jim. We're going to be back in just a moment and take a look at not only a writer's tool, but what are sometimes called writer's aids, not only software that can help you type better, that actually will help you write better. And that'll be coming up next. Okay, joining us now is Warren Kuhl of AT&T Western Electric, the developers of the Writer's Workbench, which we're going to see in just a moment, and Wayne Holder of Oasis, and I believe, Wayne, you have Word Plus and something called Punctuation and Style. Gary, you want to start?
I guess the software we've seen so far really makes your personal computer into a sort of a fancy typewriter, but I understand that the way that you're working with software that really goes beyond that. It's sort of the next stage of analyzing the words and paragraphs that you composed. Can you tell us a little bit about that?
That's correct. Our software is designed to take over where the writing process leaves off. Writing is inherently a creative process that you don't want to interrupt with concerns such as finding spelling errors and looking for redundant phrasing and so forth. So our software takes the files that you've created and runs through a series of punctuation, spelling, and stylistic checks and gives you recommendations where those problems can be fixed.
Could you run a demo for us of
Certainly.
Plus?
I have a simple file in here. What I'll do right now is to just have the spelling checker take over and run against the file. As it operates, it's going to scan the text and then bring up any spelling problems that it finds, which should take it about 15 seconds. Then it will allow me to interactively look at the spelling errors that I have and to summon up suggestions from the built-in dictionary for what the correct spelling should be. Then it will make those corrections automatically in the text. At this point, it's finished checking the file. I now have my first misspelled word there, which is although. If I ask the computer for assistance, or the program for assistance, it will bring up the correct spelling in the upper left. I can hit the correction key, bring the spelling down, and then proceed on to the document in that way. The idea is that you get simultaneous aid and correction so that it takes the tedium out of doing the spelling checking process.
How about punctuation and style? What does that do?
Well, the second step really would be doing writing style analysis, which I'll bring up next. That is, if you were to look at writing style books, you'd have a collection of problems that people typically fall into traps in phrasing. This program is designed to quickly scan the text for those problems. When it finds a problem in the text, it will bring it up and show it to me on the screen. I can then have the choice to mark the problem in the file so I can later go back and edit it. Here it's found utilization, which is sort of a fancy way of saying use. The program is recommending that you scale that down. If I continue on through, it'll find small in size, which is a redundant way of just simply saying small, and so forth. In that fashion, the program would proceed to the text and make different recommendations.
Wayne, do you enumerate all the possibilities that the program actually checks for? In other words, when you're doing a spelling check, do you have a dictionary of words, or are you actually looking for letter combinations that are unlikely? Or in a case like this,
in the spelling checking, we're using an actual dictionary that it compares against. In the phrase checking, we have a list of phrases that we've compiled from different phrase books and other sources that will, in fact, a large part of the work is based upon some of the original work that was done at AT&T for the Writer's Workbench. And for the punctuation checking, we have simply constructed a program that tries to reflect all the nuances of punctuation.
Wayne, is these programs available to run on a floppy, on a micro?
That's the idea. Ours are designed to be practical packages that a person can buy now and use on most of the available word processors and microcomputers that they can buy.
Okay, Wayne, you mentioned this is somewhat derivative of Writer's Workbench, and Warren, that's your area at AT&T. Maybe if you guys could help move the K-Pro out of the way, and we could then get to Warren's demonstration of Writer's Workbench. And I understand, Warren, you're really tied in here to a computer over in Hayward somewhere.
Yes, we are.
And show us what Writer's Workbench does.
Okay, I think it's significant to mention, first of all, the Writer's Workbench is a feature package running on Unix System 5. And at that, we point out here that it's a relatively powerful set of tools that aid a writer in structuring and sharpening their writing talents. And I like to always point out that that's important to the reader also, because I do a lot more reading than writing on my job, and I think that's a good thing to point out. One of the things that we do here, we do many of the things that we just saw Wayne demonstrate. We have the proofreading side, and we have a prose, which is going to do a stylistic analysis of the text that we have out here. I'll be very brief here. It goes over spelling, it goes over punctuation, double words, diction, many of the things you just saw, but it also looks for split infinitives, and that's one of the powerful parts of it. And we'll take a look at that. Let's just briefly jump down into the area that Wayne just left. There are 4 areas that actually do or allow the user to structure or tailor their own environment. The spelling area, there's the word choice, which is very similar to the stylistic points that he just made, and there's a sexist phrase dictionary out there that can be styled locally also. And in fact, here's a case where our text had some sexist phrase in there, manpower, and it itemized that, and then it'll go a little bit further in the next screen and actually make a recommendation that says substitute the words personnel, staff, or workers instead of manpower. Okay, and it goes on to many of the other types of words that Wayne was talking about. For example, which and that, something that we commonly misuse. I know I do a lot, and it'll make recommendations in that area. Now, the more powerful parts of Writer's Workbench software becomes a derivative of the fact that you can go out and assign a part of speech to every word in the text. And by doing that, you can actually find split infinitives. Here it found an adverb splitting the form of the verb to fine, to hopefully fine. And the way it does that is it goes, as I said, and here you have an actual text that we were running on this demo, and you can see where these parts of speech have been assigned here. Here's the verb, the adverb, and the verb. Gives it a lot of powerful things that it can do. Now, in addition to what you see there, that aids in the stylistic analysis portion of this. Let's talk just briefly here. We use a couple different sets of comparative samples, and in here we're using instructional samples. You can put it documentation. Lawyers may put legal type documents out. You can go down to your boss's level, as a matter of fact, and let it go out and compare. Once it's done that, it comes back and makes an evaluation based on the comparison that it just did. For example, here it said that this text, in accordance with a Kincaid readability, was written for 13th grade education level for comprehension. And if you go a little bit further down here, it says for instructional text, it should be written at a 10th grade level so that it's better understood. They go on to then make many recommendations, and I do have, just to show you, there's a fair amount of text that comes back to the writer to enable them to go through and determine how to structure that according to that scale. The important thing to say is it does this based on the mix of simple to complex to compound complex sentences. And here you can see it said 71% of the sentences were complex, 14% were simple. The difference here is 57 and should have been closer to 28 or less than 28. So it goes into a lot of this type of analyzations.
Warren, where is something like this being used right now?
Primarily in the Bell Labs and the AT&T Western Electric locations. It's also been used in the Colorado State University. 2,500 students have gone through that, where they've overwhelmingly reported good results, and now it's being run as part of their composition courses.
It seems like it'd be a tremendous teaching tool just to get some feedback on your writing.
Definitely.
Do you think that that people will become a little more dependent upon this and expect it to be very reliable and sort of say, well, since it passed the Writer's Workbench, I guess it must be must be good material.
I sure do. On top of that, I think it's important to point out that it's important in the other areas of business and professionals where you're going after a style like in journalists, where you want something to come back. You can actually go out here and do things in a passive sense. In other words, in creative writing, that's a little bit different than in the technical type writing. You might want to look for all the passive and the to-be forms of the verb. You can do that. And when you do something of that nature, you can go back and flavor it. For example, instead of saying it was thundering, you can say the thunder or lightning. The lightning flashed across the sky. Something along those lines. And you can get very, very thought-provoking words. And I might point out that...
It'll have to be brief.
Okay. The real important part of the Writer's Workbench is there are 27 different functions that can be run. You've only seen a very few of them here from the standpoint of the stylistic analyzation. The types of things that go out and look for abstract words, things that look for topics, there are very, very powerful things in terms of reporting in this area.
Warren, Wayne, thank you very much. They're fascinating, fascinating applications. And thank you for joining us. Hope we'll see you again next week on the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. On our program today, we're talking about the problems of computer security. And I imagine by now just about everyone has heard of the movie War Games and the kind of computer security problems raised by that scenario. But more typically, problems with computer security do not involve spectacular things like nuclear war, but rather mundane things like stealing money and stealing information. Gary, our guest on this program is Don Parker. He's considered the world's leading expert on computer security, and he says something very interesting in his book on computer crime. He says, data stored in a computer can be safer than data stored by a physical means, like in a locked filing drawer of some sort. Yet here we are doing this program, and there seems to be a sense that the security of computer data is kind of vulnerable.
Mm-hmm. Well, there are techniques that can make data more secure, as long as those techniques are used. Unfortunately, it often takes a clever individual to come along and break the system before those techniques are applied, and we find out how vulnerable these systems are. We're raising a whole new generation of computer-wise people through the personal computer revolution, and there's bound to be a portion of that population that's going to use that knowledge in some kind of malicious way. Today, I guess, computer crime really is a problem because it's a matter of information is power, and when that power is made available through unguarded information, then it's a threat to all of us in the society. Time-sharing services are particularly vulnerable because they're designed to be shared by a number of strangers who make a phone call. And we're going to take a look and just see how easy it is to make that call.
It's pretty easy to get into a computer database. All you really need is a personal computer, something like this, some terminal software. You also need a modem, which connects your telephone to your computer, a telephone, and you need to know the phone number of one of these computers. I'm going to dial up a computer database right now. I happen to know the number of one. It's just a local call. It's not even a toll call. And we'll wait to hear a high-pitched tone, which tells us that the host computer is answered. Okay, the computer has answered, and we're going to now just go into a normal log-on procedure. in which the computer is going to first ask me for my ID number, and I happen to have one, so I'll enter that. And if the host computer now accepts my ID number as a legitimate number, it will proceed to ask me for my password. And at that time, I'm going to have to come up with meeting another test here to get into the computer database. And it's now asking me for my password, which I will type in. You can't see it on the screen because the program is meant to protect the security of my password, so you can't steal it from me. And if the host accepts it as it did, you can see I'm now into this computer database. You see how easy it was for me to get into that computer database. Of course, I was a qualified user. The problem is that even unqualified users can get into these computers. They're called hackers, and they try to get into these computers just for the sake of finding out what's inside. And by using common passwords and even sometimes randomly chosen code numbers, they can get into banks, hospital records, even federal agency computers.
Global thermonuclear war. Fine. All right.
In the film War Games, adolescent hackers gain entry to top-secret defense programs and play nuclear blackmail for real. Although experts claim that the possibility of this happening is essentially zero, federal officials are now planning to strengthen the very tight security measures that already exist. If mischievous amateurs don't seem too threatening, there's also the professional thief, a new kind of spy who's traded in his trench coat and camera for a keyboard and video display. And how to foil this new breed of information thief is a problem faced by a growing number of companies and institutions. Can a computer really be programmed to keep its secrets secret?
Society has a huge investment in computers and an even greater one in software. What's more important than the financial investment is the degree to which we have come to depend upon computers. Without them, databases are empty. Words don't get processed, numbers don't get crunched, and the speed of information handling to which we have grown accustomed slows to a crawl. One might think that the protection of such essential and valuable resources would be routine and substantial. But this is not always the case. Recently, most of our time has been spent improving and expanding our systems, adding to their flexibility, making networks, and basically being more productive. The security aspects have often been overlooked. Additionally, good computer security often runs counter to making computers accessible, friendly, and easy to use. We'll find out more about the need for adequate computer security in the rest of the show. In the next segment, we'll meet one of the leading experts on computer crime. Now let's get back to the program.
Our guest today is Don Parker from Stanford Research Institute. He's a foremost expert in computer crime. He's been working in the area for 30 years now. Don, welcome to Computer Chronicles. It looks like with the widespread use of computers in society today that we have a whole new high-tech criminal. Can you tell us a little bit about the scope of this problem, computer crime?
Yes, unfortunately, we don't have any statistics on this computer crime problem. Therefore, we have to learn from it based on kind of a case-by-case approach. For instance, in just the last 4 years, we have had the largest funds transfer fraud, $10.2 million. We had the largest in bank embezzlement, $21.3 million. We've had the largest securities fraud, $53 million. We've had the largest commodities fraud, $50 million. And the largest inventory fraud, $67 million. This is an indication that the more we are using computers, then the larger the losses potentially are. And we're certainly breaking a lot of crime records the more we use computers.
So you think the escalation is a real problem right now?
Yes, it really is an escalation, because I think that business crime is probably going down in incidence the more we use computers. But at the same time, when the loss does occur, it tends to be larger.
Can you give some idea what characteristics of a computer criminal is? What sort of individual do you find doing this sort of thing?
Well, we've interviewed about 35 of these people so far, at least of the more sophisticated computer criminals. And we find that they tend to be young, but then people in the computer field generally are young anyway. They exhibit the Robin Hood syndrome, or it's a variation of Robin Hood. It's stealing from the rich and keeping it, but it's the idea that they differentiate very strongly in doing harm to people, which is highly immoral to them, and doing harm to organizations that they can easily rationalize. Not only that, they're doing it to a computer, and the computer can't cry or hit back. And so the computer is an ideal target for people who could not possibly come up and stick a gun in your face and steal money from you. That'd be being a criminal. But when you can do it through a terminal or a computer, then it's an entirely different matter. These people do not see themselves as criminals. They see themselves as problem solvers. They have some intense, unshareable problem that they're trying to solve. They are in a position of trust, and they find that violating that trust is the easiest way to solve their problem.
Don, are you talking about amateurs here or kind of career computer criminals?
So far, most of the problem has been from amateur white-collar criminals. However, now we're starting to see an increasing number of what you might call career criminals, people whose livelihood on a continuing basis is dependent on crime. And you might expect that, since for several years now, almost every major prison in the United States has been teaching data processing to the prisoners. So they do have an opportunity to learn the technology. And they're finding that they can't engage in their traditional crime except in this new environment, this electronic environment.
Don, what are some of the techniques that people criminals use to attack a computer system?
Well, we have about 1,100 cases in our research files at SRI now, and based on what we have studied over the past 13 years, there are a number of common techniques that are emerging. The most common one is we refer to as data diddling, or false data entry. It's changing data before it goes into the computer, but relying on the computer to hide the evidence of the false data. We're also dealing with very sophisticated techniques such as Trojan horses, logic bombs, salami attacks, piggybacking, data leakage, super zapping, and so on. These are all of the technical or jargon terms for these techniques.
Could you take one of those and explain? For example, Trojan horse seems to be a fairly explicit term. What would that mean? It seems to imply that there's something built into the program. Is that the case?
That's right. The Trojan horse is one of the most fundamental criminal methods that has been used. And it is the idea of taking a program and building secret instructions into that program. So when the program is executed in a protected domain in a computer system, it not only performs what it is supposed to do, but it also does the additional instructions as well.
I see, and this would be used to maybe put money into someone's account, an employee's account, or something like that.
It could be used then for a whole variety of programmed frauds within a computer system that might use a technique like logic bomb, for example, where you have programmed a branch instruction in a program so that when certain conditions for the fraud to occur are optimal, then the time bomb or the logic bomb goes off and causes the crime to be perpetrated.
There seems to be this seems to be a sort of an inside attack on a computer system when you put in a Trojan horse or a logic bomb or something like that. Now, we've seen an example earlier of war games where it was the system was attacked from the outside by attempting several passwords and systematically gaining entry to the system. Is that something that actually has taken place, where you try to go through a whole sequence of passwords and then you actually find out one that fits and goes into the system?
Yes, there's a whole range of malicious system hacking techniques to gain access from a remote terminal, where the name of the game essentially is to impersonate an authorized user. That is, you have to know the person's ID and password to gain access. There is a scanning technique where you can automatically or sometimes manually simply scan telephone numbers, gain access to a computer, and then scan various possibilities of access codes, passwords, to find or hit on one that then is access to that system.
How about user-friendly systems? help or they hinder in the computer crime?
Well, that's a part of the war that we're raging today. We all want our systems to be friendly. And unfortunately, a system being friendly is almost the opposite of its being secure. And so we're trying to find the balance between a friendly system and a secure system, because the number of people who have this capability to access these systems is growing very rapidly. And so we have an enemy that is increasing in size and in sophistication, and therefore we can no longer allow our systems to be as friendly as they have been.
What about there's I guess we'd call a computerized community bulletin board network that's grown up around the whole technical hobbyist area. You talked about a pirate version of this. Can you tell us a little bit about what one of these pirate bulletin boards would be like and what the purpose is?
Well, as you know, bulletin boards are extremely useful services in the computer field. But unfortunately, there are some of them that are set up, as you say, for malicious purposes, referred to as pirate boards. In fact, in one listing I saw recently, we found 128 of these so-called pirate bulletin boards across the country. They are used for intelligence purposes among malicious system hackers, and they often will broadcast the telephone numbers of computers and any passwords that may be available, and describe various protocols for logging on to other people's computer systems to engage in this unauthorized access to systems.
Excuse me, Gary and Don, in a minute I want to get to looking at some solutions to the kinds of problems you've been raising, Don, and we're going to do that in just a minute.
Most of the discussion revolving around computer security deals with computer crime. There are, however, other accidents and conditions that we need to guard against. First, we must protect our computer operation from natural disasters such as fire, power outage, floods, and the like. Second, systems should be protected from the accidental destruction of data when someone unintentionally gains access, or if an incorrect terminal procedure is executed, or if a programmer accidentally destroys current data while modifying an operational program. We can't always prevent damage, but we can ensure continued operation by storing backup copies of programs and data files. Third, we need to take reasonable precautions to ensure that employees do not abuse their access to computers with excessive personal use. Fourth, we must protect our equipment from unauthorized use by outsiders. Good access control, including personal passwords, systems and log monitoring, separation of responsibilities, and external balancing controls are some of the procedures for guarding against intrusion. In the next segment, we'll hear from one of the foremost experts on computer security. So let's get back to the program.
Don, you've given us a good idea of what some of the problems are related to computer crime, so why don't we take a few minutes and figure out what some of the solutions are. We have joining us also Jim Holmes from Tri-Data Corporation. Jim has a product that helps us secure a dial-up system. So, Jim, could you tell us a little bit about the product?
Certainly, I'd be delighted to. We've come up with one approach to be able to help secure dial-up networks. As you've discussed with Don previously, dial-up networks have the requirement of dialing in and usually entering a logon or a password that the system itself requires. Now, we've gone one step further, and we've taken within a 212 modem type device, an auto dial modem that would reside on the front end of this processor, our timeshare system. You would place our device in, and it has what we call an answer verification capability. We can go through, and I'll give you an example of how we would store one. Let's say your name was Adam. We could put in your name and a password that you would use to access the system. So we enter AA for add and answer verification, and then type in your name, Adam, and put a space in, and then enter your unique password. And we could put in a password of anywhere from 1 to 250 characters. Typically, your passwords that are used on systems are 5 or 6 characters. The longer the password, the tougher it would be for someone to break in. Now, we found often people are trying to use 20 or 30 character passwords if they're really intent on trying to provide security for the dial-in operation. Once we've entered the command here, we could go back and identify exactly who has access to the system from outside through dial-in ports by looking at a directory of answer verification routines. Upon receiving a call to the host computer where the system would be typically connected, we would go through and check for any of these given passwords. The passwords can be contained or control how many characters are received before the call would be disconnected. One of the problems that occurs in a lot of the dial-up systems is when you dial in, the system will repeatedly allow you to enter the password, and it will come back and say error, re-enter password. With our device, after you've re-entered it once or twice, it will automatically disconnect the call, thus preventing someone from gaining access to the system. And that's the way we're controlling the answer portion of the dial-up environment. Now, in addition to that, there's also an originating portion which can be used to help control our secure networks. Many of the companies, the larger companies today and telephone operating companies, are using our device because of the sophistication of being able to remotely configure passwords and log on procedures to their systems. By allowing them this remote configuration to the system, and that's done very simply. Let me give you a demonstration. We would do AD for add a dial directory. We would put in a label. Let's say we're going to call an accounts payable system, and we could put it in ACCT pay space, put in the telephone number of the system we want to call, and then space over and put in a password that would be sent to the system. And the password would just be stored by putting in a sequence of characters. Again, they could be entered from the local keyboard, or the unique portion of our system is that they could be downline loaded from a remote terminal or a remote computer. And by doing this, you could put in, again, from 1 to 250 character password.
Now, do I understand this correctly, is that the basic idea is that you dial into the computer system and then the computer system dials back to you again to verify that you're the actual person that you say you are. Is that correct?
Well, with our device, what we're doing is dialing into the system and entering a password. Once the password has been entered, at that point you then have access to the computer system itself.
Yeah, I think there's another system, Gary. I think the Backus security system, which has a thing called Digilink, in which, in fact, what happens is you have the salami technique. I call it the pizza defense, where the pizza parlor calls you back to make sure you're the guy who ordered the pizza, where the host computer calls the dialer back to make sure that the dialer was, in fact, the proper party requesting the services.
Well, do these kinds of devices, do they really adequately secure data? What is your feeling about that?
These devices add another layer of security and provide a significantly more secure computer system today than we have ever had in the past. However, we have to be aware that no computer system commercially available today is adequately secure relative to the value of the assets, of the information assets stored in them. Therefore, we have to compensate for the technological limitations in systems through operational, physical, procedural methods in order to make an organization secure that is using the computer.
Don, we often look to the Japanese now for what they're doing in computers in general. Are the Japanese doing anything with regard to these security problems that we should be aware of?
Well, the Japanese are a little bit behind in that they haven't experienced the kinds of computer crime that we have here in the United States, but they are just now starting to understand that problem. And, of course, they're trying to address the U.S. market where they don't quite understand the criminal problems that we have in this country. Crime is a very cultural thing, and so it's quite different from one country or culture to another.
Are the laws adequate right now in our country to deal with this very sophisticated form of crime?
Well, the laws are improving a great deal. We have a long ways to go. We have 21 states that now have specific computer crime laws. And we have several bills in Congress that would, if passed, provide specific protection on a federal, nationwide basis.
It seems like there's also a problem with operating systems that become popular nowadays that the source is available to individuals. For example, Unix. that has become widely used in commercial environments. So what effect does that have on people that really can get at the source programs? Have you seen any effect from that at all? We get a large operating systems like the IBM operating systems that have years and years of security work. These more popular operating systems now, what effect does that have?
Well, Jackson's law says that with a big enough hammer you can break anything. And therefore, any of these systems can be broken with a sufficient amount of work or skills, knowledge, and access. So it's security is always a relative situation. And large computer programs are complex to the extent that they're not predictable. And if a program is not predictable, that is, if we don't know what it does under all circumstances, then we have to assume that it is not secure. Therefore, on a long-range research basis, we're aimed at developing the idea of a provably secure system where you could prove how it performs under all conditions and therefore gain some assurance that you have an adequately secure system.
Don, we have just about 1 minute left. I want to ask you we talked about war games earlier in the national defense area. How about economics? I mean, we have the banks now all tied to this massive electronic funds transfer system. What is the potential for a major economic disaster if the wrong guy got into that?
Well, the potential is catastrophic, but the issue has to do with the risks involved. And we believe that security is advancing along with advancing technology and along with the increasing amount of money that is exposed in these large funds transfer systems. So that the risk is relatively low today, but our major problem, however, is to make sure that the security, that the electronic fences built in these systems keeps up with that technology and with the amount of assets that become exposed in these systems.
Real briefly, about 30 seconds left, what about cryptography? Is that a solution?
Cryptography is the most powerful safeguard, I think, that has ever been developed in protection of data through communication lines and also as might be stored in computer media. However, we don't have a problem to solve in that area yet, the eavesdropping problem. However, in the future, it will become the most significant safeguard that we have.
Gentlemen, we're out of time. Don Parker of SRI, thank you very much for joining us. Jim Holmes of TriData, and I hope you'll be back with us again next time for another edition of the Computer Chronicles.
It's very difficult to get a handle on how much computer crime there is. Companies that have been ripped off are often embarrassed and reluctant to report the crime. Prosecution of a company's employees for computer crimes is very rare. It may surprise you to know that only about half our states have computer crime laws, and federal legislation has lagged. So we really don't know how much computer crime there is. But we do know that computers have been involved in a number of well-publicized, multi-million-dollar crimes, and that intrusion into host computers by unauthorized individuals is becoming commonplace. Our best defense is a good offense. First, we should not be psyched out by the computer technology. We can take responsibility for computer security without being a computer expert. And if needed, experts are available. Second, we should make an overall risk assessment of what our computer threats are and determine how much it is worth to protect against these threats. Third, we can take steps to physically protect our hardware and data, as previously mentioned. Fourth, we can use security checklist guidelines to ensure that our procedures are sufficient. Fifth, we can make sure that we address the greatest non-technical exposure, the users, by making our policies clear and by following common sense practices. In our next lesson, we'll cover the fascinating field of artificial intelligence. Be sure and read Chapter 24 in your text, and I'll see you then. I'm Herb Luckner.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and I'm turning the wrong knob here. This is Gary Kildall, and this is Armatron, our noisy little robot here. We're using Armatron to demonstrate some of the basic things that a robot can do, and even though this is a small toy, it really does demonstrate those things. For example, this robot has a shoulder, which can turn along that axis. It can lift by its shoulder or come down. It's got an elbow, which it can bend. It has a wrist, which it can move, and it has a hand, which it can open. And it can actually do something that humans can't do. It can twist its wrist around that particular joint. Now, Gary, this is a small example of a robot. It's certainly not a computer. How do computers and robotics relate?
Well, there are a whole lot of devices that fall in this category of robots, and they go from the simple show robots all the way up to a sophisticated assembly line type of robot. And in a show robot, for example, there's a human operator that somehow is communicating with this device, making it roll around, giving brochures and things of that sort. But as we add more intelligence on board, then that's where the computer comes into play. The computer then controls all the devices, makes some onboard decisions based on its own intelligence.
Well, there's been a science fiction fascination with robots throughout this century, but the fictional robots bear little resemblance to today's real robots.
The image of a robot has taken many different forms since the clockwork musicians and dolls of the 18th century. But during the mechanical age of the early 20th century, the robot became a frightening symbol of the future, threatening to transform the world into an over-mechanized, dehumanized society. In heavy industries, the worker was becoming an accessory to the machine, repeating the same task hundreds or thousands of times in precisely the same way. To those not benefiting directly from the new methods, mechanization of work and life called up bleak images of the future. Fritz Lang's Metropolis depicted the year 2000, a world divided between industrial barons and downtrodden workers, slaves to an underground machine city operating day and night. The drive for efficiency leads the city's master to consult an inventor who has devised the ultimate tool, a mechanical replacement for the imperfect human being. This remarkable film may not have been completely accurate in its predictions, but it anticipated a fictional idea of robots that persisted for decades after it, a human-made, human-like mechanism that behaves like its creator. More often than not, the machine tended to destroy its creator as well, prompting writer Isaac Asimov in 1947 to devise the first 3 laws of robotics. These prescriptions assume either a large degree of intelligence or, interpreted another way, programmed behavior, one of the principal criteria for modern robotic systems. While not usually designed with human characteristics, post-war robots were, from early on, capable of programmed motion. Servo mechanisms or feedback-controlled robots began to appear in the late 1950s. From 1960 on, robots became useful adjuncts to a number of industries, particularly in jobs that were uncomfortable or hazardous to humans, like welding and painting. Repetitive functions as performed by the machine-like humans in Metropolis were being taken over by robots with more human-like capabilities, including sight, touch, and error detection. In some of the latest applications, CAD/CAM systems work directly with a robot arm to transfer the design of a part from the video screen to the finished product.
Joining us now is Dr. David Nitzen, Director of the Robotics Department at SRI International, and Matt Guerreri, who's an executive with Autobotics here in the Silicon Valley. Gary?
David, I guess everybody has the idea that a robot should go around and wash your dishes and clean your house and so forth, but I have a feeling there's a lot more to robotics than that. Can you give us some idea what's going on in the industry?
Well, industry has been using robotics for 15 years already. These are robots that are designed to do dirty jobs in industry. And they're doing them.
What do you mean by a dirty job?
Well, undesired jobs. Jobs that are hard, strenuous, dangerous, harmful, and lethal.
What is an example of something like a dirty job that would be a lethal job, something you've seen going on?
Lethal is not yet in operation. This would be in the future. I mean, by that I mean jobs in hot environment, nuclear power plants and the like. But examples of undesired jobs is handling workpieces in heat environment, hot environment.
What about in assembly language control, not control, but doing assembly processes? I know the Japanese have been very heavily involved in that. What's going on in just the industrial use of robots?
Well, that's the other kind of deadly job, the humanizingly dull jobs that are so common in a lot of our factories, and which Americans have demonstrated a strong dislike for, and it's the reason why a lot of our production is going offshore. And what's being done now, I think, in industry is that we're addressing those kinds of mundane assembly tasks and taking the dehumanizing jobs and giving them to machines to free up human beings for more creative, more challenging kinds of work.
Yeah, but you see, a very important point about assembly is that here the competition is very strong, because to do assembly is a very complex task, especially if it's done in unstructured environments, not when pieces are jigged. If it's done like people. On the other hand, assembly people on assembly line, people working on assembly line, are paid very little. There are a lot of women that work in on assembly line, and they are underpaid. So it's a double slam. On one hand, it's complex. On the other hand, you have to compete with very cheap labor. And the labor becomes even cheaper when it goes to Mexico or it goes to East Asia. So that's where the challenge is. On the other hand, with the undesired jobs like heat treatment or die casting or forging or arc welding, where the cost for the workers is high and it's a very undesired job and it's very easy to do, that's more cost effective.
I guess one of the differentiating factors in robots that are used, say, industrial in applications of that sort, that you can build a very precise robot that, say, would weld within a few millimeters of where it should weld, or you could use, say, vision processing to figure out where the object is and to manipulate it with very coarse mechanical devices.
Yeah, or as David points out, putting the robot into a structured environment, such as an integrated work cell, where the work is presented to the robot in such a way that it doesn't require the extreme accuracy or sensory capability that some of the anthropomorphic machines currently require. Henry Ford revolutionized American industry by bringing the work to the worker on the assembly line. And we see a very similar trend as a necessary part of the evolution of robotics in American industry, where we structure the workplace to suit the robot and make the robot easier to integrate into the overall scheme. And that's really applied robotics. It's a different set of problems than the technologies necessary to anthropomorphize machines, which is the basic research being done in robotics now.
And I would like to make a very important point, I think is an important point, and that is that people worry, about unemployment and so on. I want to make an observation, which I think is important. The number of blue-collar workers that have been displaced or replaced so far by industrial robots is very, very small. And the projection, if we extrapolate from the past for the next 5 to 10 years, is also going to have a very small impact on the labor force. Okay. And my point is that I think the main reason for this is the fact that today's robots are not intelligent. They cannot compete effectively with human workers.
Now, is that changing, though, with the applications, say, artificial intelligence and, say, knowledge-based systems? Are those a factor in what's going on?
Well, I think, as David points out, there's a whole spectrum of applications, from the very simple, which are being handled by the very simple pick-and-place mechanical devices that, for example, the Japanese would call robots and we don't, to the very esoteric applications, which require lots of intelligence, lots of sensory capability. But there's a broad spectrum of applications somewhere in the middle, where if you select the application properly, then in fact the machine can be very cost-effective and very competitive with a minimal amount of intelligence. Ultimately, we will have to go to intelligent machines and distributed intelligence architectures where the robotic elements in a totally automated factory would be in communication through several levels of computer hierarchy.
Matt, you mentioned the Japanese, and the perception is that the Japanese are ahead of us in robotics, and you kind of pointed out a fine line in terms of defining what a robot is. What is your version of what's going on in terms of research in Japan and this country in robots?
I would say that the Japanese are ahead of us in terms of automating their factories. And their way of automating the factories is a very systematic approach of looking at a factory as a unit of production and going in and solving the problem systematically from the bottom end up, looking for the easiest applications that they can resolve, learning in the process, and then moving on to the next most difficult applications. And we see that as a very logical way of introducing automation into our factories. On the other hand, Americans are way ahead, I think, in terms of some of the technologies associated with the anthropomorphic machine. Certainly vision systems, I think we have a lead over the Japanese and perhaps some of the other sensory areas. But it's becoming a world business, and Fanuc Limited, which is one of the leading manufacturers in Japan, has just signed a joint licensing agreement with General Motors. GMF is now going to be, if not already, the leading supplier of automation systems.
Gentlemen, I have to interrupt because we're going to take a short break and then come back and meet two personal robots, Hero from Heathkit and Teachmover from Microbot. That's coming up in just a moment. This is George Oliver, president of George L. Oliver Company, who distributes the Hero 1 robot here in Northern California. And George, maybe you could get Hero to give us a basic demonstration of what it does.
Surely. Hello, I am Hero, the educational robot. I have a brain, just like you do. But my brain is a computer. My owner programs my computer for me, and I always do as I'm programmed. I can talk like this. I can turn my head. I can move my arm.
George, how much weight can that arm hold?
It can hold about 8 ounces extended and about a pound when it's fully retracted.
And what kind of functional use could this arm perform?
Oh, that arm could do things like pick up items from one assembly line and move them over to another. I can use my grip. I can move my wrist.
Does Hero have the same normal axes of movement that an industrial robot might have?
Yes, Hero has 6 axes of motion like a Class 3 industrial robot. and I can move about. I think I made an excellent pet. I'm even now strain.
Is he finished?
Hello, I am here already.
Stop him now. George, before we take his clothes off and see what's inside him, tell me, I see there's a keyboard and an LED display here. What do you do with that?
Yes, this is used for data entry, Stu, and the LED display is to tell you where your information is stored within.
So you can program him through this keyboard.
Yes.
And I see you have a kind of breadboard here. What do you use that for?
Yes, that can be used by students studying interfacing circuits.
Okay, let's take his panels off and see if we can look inside Hero and see what makes him tick, if that's what he does. Okay. I'll help you with the back one if you want to get the front one there. Okay, let's take a look at the front here, George, and what do we have over here?
Okay, this is your main circuit board here with your microprocessor and all of the various ICs that interact with the other boards.
Okay, can I spin them around here while
Sure.
we talk?
Now, these various boards here are the sensor boards that operate with the various sensors again. This is the main drive control board. This one is the sonar transmitter and receiver board. And around here we have the sonar board and the main drive board. And around here we have the voice synthesis board and one of the other sensor boards here.
Okay, mainly you use Hero as a training robot, as an educational robot, right?
Yes, he's designed to be used by the student in the laboratory to study
Okay,
robotics.
well, George, thanks so much, and now we'll go back to Gary.
As Stewart joins us on the set, I'd like to introduce Dusty Rhodes and John Hill of Microbotics. Dusty, you have a device here that looks very interesting. Are you going to show us about that?
We sure will. This is our Teach Mover, which is a developmental robot used by industrial engineers to develop work cells in the factory, also for training engineers. Let me show you one of the little tricks and games it can play. This is the block stacking game. And it will find the large block and put it in the middle. The robot has a sensor that can sense how large the device is. And here it says, I have the large block, I'll put it in the middle. Now it knows to go back to the previous location for the smaller block and put it on top. I'll let it go on for just a moment and show what happens if it finds no block. Now oftentimes we go over and put the blocks in different places and try to fool it. But like a worker who's confused by instructions, if it looks for no block without work, it goes and sits down.
During the setup for this, you had blocks placed around in various positions, and it wasn't able to find them. I assume that's because the sensing mechanism isn't really doesn't have any vision and so forth. Is that going to be added to this kind of device?
That's true. John could talk about adding a vision to the work cell or to the robot.
Well, if a robot had a camera interface to it, such that the camera was looking down over the work area, the computer could process the image and locate the particular block and direct the robot to go there. I mean, that would be possible. And these instances, then the robot could just automatically grab it.
I know that David has worked with vision some. Do you have anything to add to that?
Yeah, I agree with John. You could improve this by adding not just vision, you can have range and touch sensing, not just a micro switch like this robot has, more an array of touch sensors. Also, you could add some smarts into it so it knows what it is doing, and if it makes an error, it'll blow the whistle.
David, where are we in adding smarts to robots?
Well, we are struggling. Sensors are being added to robots today, and they are applied gradually into in industry. There are other applications of robots that would have to have sensors. These are unstructured environments, such as in the military or agriculture, in medical institutions, etc., or home use too. This is an area that is very difficult because robots are too dumb today to do this job, which requires a lot of intelligence.
Do you see the field of personal robots growing as personal computers did, or robotics moving in the direction of computers?
I put my bets more on the more application-oriented robots, such as I mentioned. The hobby is okay, but that's not where the big money would be, other than on a toy level.
But you know, if you take a parallel with I guess with the microcomputer, popularity of microcomputers and personal computers, a lot of that was a grassroots effort. The invention of the Apple, for example, by Steve Wozniak was a technical hobbyist endeavor, and it's kind of exciting to me to see robotics now come through that grassroots evolution.
Yeah, I agree with you. I think it's wonderful. I think there's a good analogy between computers and robots. Just like computers started just for commercial and scientific applications, now it's all over our life, right? And I think the same thing is going to happen with robots. And I think it's a great idea that there are a lot of hobbyists that are getting into it, because there's a new generation now that would not be afraid of robots, that would be able to apply it in many areas of our life.
David, something like this is relatively simple. I mean, it's an arm, it can pick things up and so on. You talked before about not only replacing blue-collar work with robots, but even white-collar work. How do you do that?
Well, you saw what Dusty was doing. He was using this teaching box to tell the robot what to do. And if this information that he has in his head could be transferred into an automatic system, it could be done. Specifically, computer-aided design database includes all the information that is needed to perform a certain job. Now, we can eliminate the trainer that uses the teach pendant to move the robot and tell it what to do by using self-teaching and self-calibration, that all the information would be transferred to a computer, and with the sensors would tell the robot where to find things and calibrate itself and then do the job.
Okay, Gary, well, if you and I aren't replaced by robots, we'll be here again next week for another edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random access is made possible by a grant from Byte, the Small Systems Journal, publishers of a monthly magazine on microcomputer technology and innovative projects in the world of computing.
In the Random Access file this week, the TV news stories may all be about Cabbage Patch dolls, but the real hot Christmas gift this year is unquestionably the low-priced home computer. Analysts now say 2.5 million computers will be under the Christmas tree this weekend, replacing last year's winner, video games, as the most popular Christmas present. And if industry figures are right, that will mean over 1 million computers thrown into the closet in just a few weeks, saturating even more the growing supply of used computers. That's leading to a fast-growing new business, computer swap meets and used computer stores. Computer Swap America, based in Palo Alto, will be expanding to 5 other cities across the country next year, and the Interstate Computer Bank, which used to sell used computers through the mail, has now opened up a storefront operation in Mountain View. Atari and Activision are hoping to pump some new life into the slumping video game business. The two largest video game suppliers announced this week a joint venture to distribute new video games via broadcast technology. They'll test out the new system early next year, and they say they hope to expand their service to include non-game software. Well, if Christmas '83 belongs to computers, the new year of 1984 may be called the year of the mouse. Analysts are saying the mouse business may grow to more than $10 million next year, and the consensus of opinion seems to be that the optical mouse will replace the mechanical mouse. One of the leaders in the field is Mouse Systems Corporation of Santa Clara. They expect to more than quadruple their business next year. 1984 will certainly be the year of the semiconductor. Estimates are now that chip industry sales will grow by more than 30% next year. In fact, domestic orders in November hit an all-time high of $1 billion. Indeed, the stock market has turned the chip companies into their favorites this fall after dumping on many other high-tech stocks. As the year ends, let's take a look at the year's big winners and losers. The winners were Intel, selling around 41 after hitting a low of 17 this year. National Semi selling at nearly 16 after plunging to below 7 earlier in the year. Other strong finishers are Tandem and Genentech. On the losing side are Activision, selling near $4 after hitting nearly 13 earlier this year, and Eagle down below 9 after hitting nearly 25. Other losers were Apple, down considerably from its high, and Televideo, also near its yearly low. If you're into the stock market, don't throw away that computer. Value Line has announced a new monthly software service called Value Screen. For about $500 a year, Value Line will send you a new disk every month, measuring 32 factors for each of some 1,600 common stocks. You can program the disks to look for certain key criteria and have the computer recommend transactions. The Osborne Company is back, though in a very different form. Osborne's creditors have reportedly agreed to a reorganization under new president and CEO Ronald Brown. Osborne will get out of manufacturing, probably out of the domestic market, and will focus on its new IBM-compatible executive model. Rumors are flying over pending upgrades in the IBM PC Junior. Lukewarm press has reportedly sent IBM back to the drawing boards. High on the list is an upgraded keyboard after many complaints about the chiclet-style Junior keyboard. There's also talk of adapting the Junior to enable it to handle 2 disk drives. Apple finally made some progress this week in its battle to stop the trade in fake Apple computers. For a while, the problem of the fake apples was thought to be limited to Southeast Asia, but the phony apples have started showing up right here in California. This week, U.S. Customs officials seized about 400 fake apples from computer dealers in San Francisco, Santa Ana, and Cupertino. Criminal charges are pending. We all know and use BASIC at one time or another, but do you know who wrote BASIC? 2 Dartmouth professors, John Kemeny and Thomas Kurtz, and they hardly made a penny off one of the most widely used languages. Well, they're going to try again with a new language they call True BASIC, a supposedly universal BASIC that will run on almost all machines. It's due out late next year. And if you're into this kind of thing, you may get excited about knowing that the world's record was broken last week for factoring the largest number. A Cray 1 supercomputer in Albuquerque, New Mexico, factored a 67-digit number in just over 13 hours. The record had been a 50-digit number. There actually is a practical aspect of this, since many computer security systems are based on the supposed impossibility of factoring numbers of that size. Well, we often hear that one of the wonderful things about computers on the job is that they never call in sick. Well, one computer did this week in Sacramento after being shot at by 2 teenagers. The computer kept attendance records at a Sacramento high school. I guess the kids had cut too many classes. And a robot testified this week at a Casino Control Commission hearing in Atlantic City. A casino there wants to use the robot on the gambling floor to promote its entertainment shows. The robot said it was only 1 year old. The commission said the law prohibits minors from being on the gambling floor. Well, that's clearly enough from this week's Random Access File. We'll be off next week due to the holidays, but we'll see you again next year, immediately following the Computer Chronicles. I'm Stewart Cheifet.
Random Access is made possible by a grant from Byte, the Small Systems Journal, publishers of a monthly magazine on microcomputer technology and innovative projects in the world of computing.
creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Herb, I want to try to take your picture here, if I may. Did you hear what that camera said? I'm going to do it one more time, just so the audience can hear this. Too dark, use flash. I don't really want to take your picture, by the way, Herb. I just wanted to use this camera, this Minolta camera here, as an example of the increasing use of speech in solid-state devices. For example, another one, I'm sure a lot of kids are familiar with this TI Speak and Spell.
Hello. Spelling level A. Press go to begin. Press enter to check your answers.
It's amazing, isn't it? We're talking about speech synthesis and a couple other speech subjects today on Computer Chronicles. Herb, and what I want to ask you to begin with is, let's take this camera for an example. It was kind of cute that it talked to me and said, use a flash, etc. But it didn't have to do that. A little blinking red light works in most other cameras. Is the use of speech a gimmick, a kind of marketing toy, or are there really useful applications for speech in computers?
Well, I'm sure we'll hear a lot about that today from our guest, Stewart. But I would observe that I find myself not really paying much attention to the warning lights on the dash on my car anymore, and yet I sure pay attention when it talks to me. And of course there are many voice terminals out there that can reach many more places than computer terminals can today. So I think there is something in the use of speech.
And by voice terminals, just telephones.
Telephones,
right.
Yes, right.
Okay, we're going to be talking not only about speech synthesis, but digital speech coding and speech recognition. And there's quite a bit of research going on in all these areas.
Spoken language contains variables that can completely change the meaning of a word, depending on the context, the inflection, or the accent of the speaker. So for a computer to accurately analyze and reproduce speech, it needs to first break up the words into sound fragments and then reassemble them with natural speech emphasis. Synthesizing devices work either by digitally encoding entire messages or by phoneme synthesis, building words from a library of digitally stored fragments. Encoding speech into these fragments points out the primary importance of speech inflection and accentuation in determining how a phrase is pronounced.
Harry Potter. Computer.
The operator of this scanning electron microscope normally works in a totally darkened room because of the microscope's sensitivity to light. Faced with two different instruments, a microscope and a computer, the operator's hands and eyes are continually busy. But in this case, a microphone has replaced the computer's keyboard. The computer has been trained to respond to verbal commands encoded previously by the operator in his own voice.
Charge.
Machines that can understand and carry out verbal commands have been in development since the late 1960s. Today's applications are still limited. The breakthrough will come with the perfection of recent speech systems that feature context-sensitive rules and flexible models of human speech.
Language is more than just phonics.
Speech was our earliest form of civilized communication and is still our most common and for many purposes our most convenient. It would certainly be more convenient if we could verbally instruct a computer and then listen to its output. Well, the technology is rapidly being developed that will enable us to do these things. There are many examples of talking computers used by the telephone company for referral numbers, and many applications where the user calls a computer on the telephone and keys in certain passwords or other information, and is given bank or inventory balance information by computer voice response. The observation that many people are better talkers than listeners also applies to computers. As we discuss in a later segment, it is much easier to program a computer to generate passable speech than it is to understand our speech. The computer knows exactly what it wants to say and can generate an unambiguous, if somewhat stilted, series of words to say it. Understanding different word boundaries, dialects, indefinite references based on global knowledge, or nonverbal signals is very difficult for anyone, computers included. An example of word boundary problems occurs when I say Sam Spade. Do I mean a fictional detective or a man named Sam who received his paycheck? Thanks to cheap, high-performance hardware and computer techniques called artificial intelligence, which we will study later, computers can now understand a limited vocabulary, or a larger vocabulary spoken by a limited number of people. We'll see some of these systems in our next segment. So let's get back to our program.
Joining us now is Carl Burney. Carl is Vice President for Corporate Development at Speech Plus. Speech Plus is involved in quite a bit of the new things in speech technology. Herb?
Let's start out, Carl, if you would, please, and tell us how does the computer synthesize speech?
Well, our machine takes any ASCII text, that's the way text information is stored in a computer, and converts that to intelligible speech. It first looks at the words, decides which phonemes are in those words. Phonemes are the basic elements of speech. It puts the phonemes together for the words. It massages them to make sure that they flow the way natural speech does, and then that's converted to a set of parameters for a speech synthesizer, which then produces speech.
When you say a phoneme, tell me more about it. You say that's the basic building block of speech. What is a phoneme, literally?
A phoneme is a short sound in speech. It's the fundamental element such that if a phoneme changes, it changes the meaning of a word. Phonemes are, you can roughly think of them as being vowels or fricative sounds, sounds, and a number of other sounds. There are roughly 38 to 45 phonemes in English, depending on which linguist you speak, you're talking to. And in other languages, there are roughly the same number.
Does your product cover all of the English language?
Yes, our product takes unrestricted text and converts it to English.
What size of a computer do you need to do that?
It's based on a commercially available 16-bit microcomputer chip.
When you say converts it to English, now suppose I were to type in French words.
It would attempt to pronounce them, but they probably wouldn't come out right because our phoneme models are for English and the phonemes in French are different.
With an English accent.
So this particular device is language dependent. It's
That's
programmable
correct.
in one particular
That's
language
correct.
with its particular set of
Also,
phonemes.
the pronunciation rules, not only the phonemes, but the way the phonemes flow together are different in different languages. So in our device, we have not only models of the phonemes, but we have the pronunciation rules as well.
So that sort of helps the sentence come out in context
That's
the
right.
way it might be if it were spoken.
With reasonably natural inflection.
Yeah, that's what I was going to ask. You said not only it recognizes the phonemes and then it massages those to turn it into normal speech. What do you mean by massaging it?
Well, what happens when you speak, you don't normally articulate everything. For instance, if you were giving instructions to someone, directions to someone, you would say, make a left turn at the corner. You don't say, make a left turn at the corner. So things are strung together in normal speech. And in fact, some sounds are not spoken at all in certain words. And there's rules for how you adjust the phonemes depending on what sound came first and what sound came afterwards. And also, you need to know where the sound appears within a word, and in fact, where it appears within a sentence to make sure that you get the inflection properly.
Does manipulation of the phonemes also include volume and inflection, or is that done separately?
Yes, it includes the stress. It includes. A phoneme isn't a fixed element. It starts at one point and it flows to another point depending on which sound comes next.
Carl, earlier when Herb and I were talking, we used the phrase speech synthesis, and that's different, isn't it, from speech coding? What's the difference, and what does this do?
Okay, the way to think of it is we call this synthesis by rule, because there is no pre-recorded speech or no stored speech in this device. It takes text and it produces speech according to the pronunciation rules of English. Okay, the other kind of speech, what people think of as speech synthesis, is synthesis by analysis, where the information is recorded from a human voice and then compressed or processed in some other manner by a computer so that it can be stored, and then it is simply reconstructed. There's no knowledge of what the words were, what they mean, or how they flow together. It's a sophisticated tape recording process, if you will.
Okay, Carl, I feel like there's been food on the plate, and I'm waiting for permission to eat it. Now, let's hear what this thing does.
Okay, let's. We created a few sentences before. We'll try one of those. Okay.
Describe what you're doing.
Okay,
as you punch it.
what I've done here is with this little keyboard, I've stored some messages ahead of time by typing them in, and here's one. Oh.
Hi, Stewart. Hi, Herb. Thanks for the opportunity to appear on Computer Chronicles.
Okay, so now you had just typed that phrase in before on the keyboard.
That's right. I can type anything on this keyboard, and it will then speak it.
Okay, now, again, going back to Herb's phone situation, are we looking actually at the thing you call call text?
That's
right.
Now? That's right.
Okay, now suppose I had an electronic message left for me in my computer, and could I then call it up on a telephone and ask the computer to read that file to me over the phone?
Exactly. That's
okay.
The
Could
basic...
you demonstrate something like that for me?
Sure. We have another message in here like that.
Stewart, we have rescheduled the taping to 4:30 this afternoon. See you then, Ron.
Okay, so that's a message from Ron. Again, if you were at your terminal to receive an electronic mail message, you could access that at your terminal. But if you were on the road and you stopped at a gas station and you wanted to find out what messages were left for you, you can call up a call text system and it will read your electronic mail to you over the phone. You made the point earlier, Herb, that there are many voice terminals in the world called telephones, but they don't hook up to a digital machine. Well, now they do, and you can in fact access any text database over the telephone in voice.
How large is the market for accessing databases via the telephone? Is that a new area that's just opening up, or are a lot of people doing it?
Well, it's a new application. There are at this point in time there are no commercial online applications of that, though we are talking to most of the major electronic mail suppliers about the potential of this. Naturally it's a new feature. The capability heretofore has not been available, and in fact the call text product line was introduced just at the end of last year, at the end of 1983, that is.
Carl, you played back a couple of messages which you had typed in earlier. I'd like you to actually type something in for me now so I can see how quickly you can turn a sentence into spoken speech.
What would you like to say?
Oh, just say we have about a minute left to do this.
Okay. We have a minute left to do that. We have... wait a minute, I'm in the wrong mode here. Excuse me just a moment. Okay. Now I have less than a minute, but we'll do it anyway. We have less than a minute to do this.
We have less than a minute to do this.
And it spoke very quickly. I appreciate that.
In fact, we can adjust the speaking rate also.
One last question before we have to take a break. Now, what is the product we're talking about? Is it this big blue box, or can I do something with my PC to accomplish this?
This is the product that's actually speaking. Okay, this board goes in an IBM personal computer, and this board contains the text-to-speech conversion equipment that's here. This is the microprocessor that is doing most of the controlling. It also has a telephone interface, which is the front end of the board, and in fact it has what's called an RS-232 port, which is the kind of port that you have on the back of a terminal. So in fact, this port, looking at a computer, looks like a terminal, and the computer thinks it's talking to a terminal. This port, you've probably seen that, looks like a telephone. So in fact, looking in from the telephone network, we have a telephone here, a computer terminal here, and the mechanism to convert text to speech in between.
We have to heed the
Okay.
computer's advice at the moment.
All right.
And in just a few seconds, matter of fact, we're going to take a look at a demonstration of speech recognition with a device that plugs into your, or in this case, our IBM PC. And that's coming up in just a moment.
Sales.
Which product line? Standard or deluxe?
Deluxe.
Earlier, we discussed the computer's ability to talk and listen. The correct terminology for these functions is computer voice response, CVR, for talking, and automatic speech recognition, ASR, for listening. Computer voice response uses two different techniques called waveform simulation and synthesis. Waveform simulation requires that someone speak the vocabulary into a microphone. The computer uses an analog-digital converter to digitize and store the words. When the computer wishes to give a voice response output, it retrieves the correct digitized word from storage and sends it to the awaiting listener through a digital to analog converter. In the CVR synthesis process, the computer digitally stores parts of word sounds, called phonemes, sort of an expanded set of phonetic ABCs. A sufficiently large vocabulary for most applications results from using about 100 phonemes. The needed phonemes are recalled from computer storage when needed, combined into proper words, and sent to the listener through a digital to analog converter. There is a great deal more sophisticated processing which takes place to give the proper inflection to the words and make them sound as natural as possible. The end result today is a very good approximation of human speech. The computer recognizes speech by digitizing words and comparing those patterns with stored patterns. The patterns will not match exactly because we don't always say words the same way. Consequently, the computer program must try for the closest match. This process works well for discrete words, but as mentioned earlier, word boundaries, large vocabularies, or speaking continuously present a problem. We'll see some speech recognition in our next segment. So let's get back to our program.
Joining us now is Ron Stevens. Ron is president and CEO of Votan. And Ron, we have a new piece of equipment up here now. Tell us what this is.
This box is the Votan V5000. It provides speech recognition and voice compression and playback facilities. It's connected over an RS-232 line with this IBM personal computer, and this is the color monitor that we have substituted for purposes of this demonstration for the normal monitor associated with the IBM PC.
Okay, run through a demonstration now and show us what this Votan unit does.
All right, the software package that's resident in the IBM PC is controlling this monitor, and I am going to illustrate the substitution of a microphone and my voice for the keyboard. So I'm going to control this program through the V5000 into the IBM PC and up to the screen with the microphone. Executive? Executive? Sales?
Which product line? Standard or deluxe?
Deluxe?
What channel? OEM, distribution, or total?
Total.
Would you like to compare to last year?
Yes.
Would you like to forecast for next year?
Yes.
We'll use 2 digits to indicate percentage growth over this year. Say the first digit.
2.
Say the second digit.
5.
The boss will never believe that. Let's keep it under 20%. Say the first digit.
1.
Say the second digit.
9. Exit. Exit. Telephone.
Who should I call?
Stockbroker.
Dialing.
There's a
Good
comment.
afternoon, ABC Brokerage. This is our computer information lookup system. You will be able to access information about your account by voice. At the sound of the tone,
Please enter your 3-digit access code, 1 digit at a time.
3, 5, 7.
Did you say 3, 5, 7?
Yes.
1 moment, please. Changes in your stock portfolio at the close of trading today. Amalgamated Widget up 2. You hold 2,000 shares. XYZ Corporation up 1/2. You hold 3,000 shares. Total gains in today's trading, $5,500. Would you like to leave a message for your broker?
Yes.
Start your message at the tone.
Buy 1,000 shares of Votan.
Would you like to hear your message?
Yes.
Buy 1,000 shares of Votan. Is this message okay?
Yes.
Your message has been sent. Thank you. Goodbye. Who
Exit.
should I call?
Exit. Exit.
That's pretty impressive.
Yes, it is.
First question I have, that speech is so good, it's hard to believe it's being generated by a computer. Now what technology do you use to generate this speech?
Well, we use, the general class of technology that we use is the analysis and coding type of technology discussed earlier in the program. And the closest analogy to that is the digital speech that is often used in major telecommunications networks called pulse code modulation, which is 64,000 bits per second. Instead of using 64,000 bits per second of speech, however, we use something closer to 10,000 bits per second. So it is much more cost effective. In fact, it makes it feasible to use that type of speech in a computer system in the context of the costs of disk space and so on.
So you actually have someone speaking in a vocabulary, and you digitize that vocabulary at a sampling rate of around 10,000.
Yes, yes. And then store anywhere from 20 to 100, perhaps 200, or perhaps 1,000, depending on the application. 1,000 of those types of messages at locations or addresses within the computer that are accessible by the computer program.
And you're calling them out a message at a time, and that's why the message sounds like a message.
Yes. Now, you can call it out as a single message if the application calls for it, or you can string 2 or more messages together in sequence. For example, when this application confirmed my identification number as 357, that was really concatenated together, is the term used in the industry.
So we've really had examples of both of the technical approaches to speech synthesis.
Yes.
Can you say a little bit about where do we stand in the state of the art on the recognition side?
Well, there are several dimensions along which that technology can be analyzed. First of all, what I was demonstrating here was speaker-dependent recognition using discrete words. What we have available, and I could have demonstrated it here today if we had prepared for it, is speaker-independent recognition. Speaker-independent recognition is a notably more difficult technology, and one of the consequences of that is you normally have a comparatively more limited vocabulary. The other dimension along which the technology can be evaluated has to do with the distinction between discrete words and continuous words. We also have that available in the lab, and there are a few other vendors in the market supplying that. That allows you to say, instead of 1, 2, 3, 1, 2, 3, without pauses in between. The obvious question that jumps to most people's minds is, how soon will we have continuous speaker-independent recognition? And the answer is not soon. That's a few years out. The third dimension along which it's important to analyze the technology is the dimension of scale of vocabulary. Now, there is a fairly close parallel between the synthesis area in terms of a discrete or individual words pre-programmed, as we shown here, and what was demonstrated earlier by Carl in terms of, in essence, unlimited vocabulary. The technology for doing unlimited vocabulary speech recognition has been worked on for a number of years and is being worked on presently. Both ourselves as well as perhaps a dozen other people are working on that, and that is probably 2 to 4 years away.
Carl, I'd like to get you back in here. Tell us about the applications from your side, from the kind of, like call text, for example, as you showed us.
Well, the primary application of the call text is to access any text database invoice over the telephone. It not only is applicable to retrieving electronic mail messages, but for instance, a salesman in a customer's office can call in over the telephone into the database and retrieve that customer's order status, or perhaps the current inventory of a particular part, so that he knows that the customer can place that order in time.
Okay.
The important concept there is that it doesn't require the intervention of an operator. It saves the cost of an operator.
As your computer told us about 10 minutes ago, we're out of time. Gentlemen, thanks so much for being here, and we'll see you again next week on the Computer Chronicles.
What makes a good computer speech application, and what's the prognosis for the future? Based on the current state of the art in computer speech understanding, not all applications are ready for talking computers. There are 3 considerations: feasibility, cost-effectiveness, and user acceptance. If the system requires too great a range of automatic speech recognition vocabulary, or too many individuals' input, then it may not be within today's technology. From a cost-effectiveness point of view, we must ensure sufficient hardware and software to handle the processing. The proper interface with telephones, for instance, and the need for backup if the internal or external communication system's down are important considerations. The last consideration is how the users will react if the transaction becomes too complicated. The future is promising for computer speech. The need is there, and the technology is improving rapidly. Some of the problems in language understanding are being actively researched in a field called artificial intelligence that we'll study in a future lesson. In our next lesson, we'll cover computers in education. Be sure and read Chapter 20 in your text, and I'll see you then. I'm Herb Luckner.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. On our program today, we're going to be talking about networking. It's been a hot topic in the computer industry for years now. In general, networking means the ability to interconnect several computers so that they can share things like peripherals or software or even data. Our guests today are two leaders in this field, Michael Pleiner of Scitech and Charlie Bass of Ungerman Bass. Gary, our two guests are both involved in a specialized form of networking, I guess you'd call it, called local area networking, LAN. How do you define that? What is a local area network?
I guess ever since we've had computers around, we've been trying to hook them up to transmit data around back and forth. Local area network is generally used around an office environment. It's limited geographically to a smaller area. Usually it's owned and operated by a customer rather than being a commercial utility that's being used. Because it's limited geographically, the performance is normally a bit better than you'd find, quite a bit better than you'd find in some of the traditional network systems. We're going to see examples of how the local area networks are being used, and I think we've got a piece here that will show us an example of a local area network used in an office environment.
The kind of countertop computer terminal that is typical of modern offices has a built-in limitation. It talks only to a central computer, linking it and the other terminals to one body of data. An area network is a way to expand this system by linking several computers together to share information directly with each other. Still a relatively new field, networking allows an organization or community to connect its various branches into an integrated, decentralized resource. At Stanford University's Central Computer Facility, a library network gives researchers instant access to material stored all over the United States. Campus terminals can tap into the system through a single yellow cable that snakes through the campus like a silent subway line. Although a local network can operate cheaply along telephone wires called twisted pairs, the single cable systems, known as baseband and broadband, have more flexibility, a greater data rate, and even bring the tangle of wires and cables almost under control. There are a number of ways that information gets shared within a network, along the arms of a star, around a ring, or through a bus. Messages either get automatic priority or travel like tokens from one station to another. Of course, the real advantage of all this is to the user, whose direct access to multiple sources of information becomes easier and faster.
Our guests today are Michael Pleiner, president of Scitech, and Charlie Bass, vice president of Ungerman Bass. Both their companies are leaders in the field of network systems development. Gary?
Well, we've talked about local area networks as being a specialized kind of reduced geography network. Charlie, what are the things that characterize local area network?
Well, I think it's more than just the geography, Gary. That certainly allows us to understand the problem and understand the technology, but we're talking about total connectivity between devices, and we're talking about peer-to-peer relationships, meaning we want to get rid of that central computer and allow all these devices to talk freely among themselves.
Mm-hmm. What sort of applications are we finding in an office environment that lets these smaller computers talk to themselves?
Well, one of the fundamental motivations is to share resources and to share information, meaning that we'd like to have a single terminal be able to talk to more than one computer, and we'd like to be able to have a user share a resource that he might ordinarily not be able to afford, or have access to data which is common, and so that we're sure of the integrity of that data.
Mm-hmm. Mike, do you have anything to add to that?
Yes, I share the same opinions. We see local area networks being used in the office automation environment. We also see the networks being used in the manufacturing floors, collecting data as well as being able to transfer data back to the manufacturing operations. We also see local area networks being used a lot for just general data communications utilities. The network becomes, in a sense, a communications utility, like electricity is distributed within the home. Terminals interconnected to many different computing resources. We also see that local area networks provide mixed set of services. For instance, on broadband networks, you can provide video, voice, and data on the same cable system.
You mentioned broadband. What is this concept of broadband and baseband and so forth? What is that technology all about?
The really distinguishing feature of broadband and baseband is the modulation technique. In a baseband system, you are directly modulating the cable with electrical signals. In a broadband system, you are using the same technology which distributes video, CATV video to the home. You use RF as a modulation technique, and you can use what's called frequency division multiplexing. That is basically stacking different channels of data or information or video on the cable, and they can run simultaneously.
So this kind of technology, you can get the data rates up pretty high. What sort of data rates would you expect to find in a local area network?
Well, you will find data rates that can range anywhere from 9.2 kilobits per second up to Ethernet type networks, which are 10 megabits per second. Most technologies can even carry data even faster than that. Broadband has 400 megahertz available to it. Fiber optics can go up into gigahertz ranges.
So we're getting significantly faster data communications than we'd find in, say, some of the traditional techniques have been used.
That's correct.
Excuse me, how do you make a decision as to which of those technologies you use in a particular application?
Well, if I could answer. First of all, this concept or this argument between baseband and broadband has really dominated the media and the discussions on the technology for some time now. And I think for most people, they're now realizing that the two technologies are both have their strengths and have their applications and are probably going to coexist rather than one killing off the other or dominating to the exclusion of the other. But choosing between them is difficult. It's a matter of application. It's a matter of cost, and it's a matter of efficiency and exactly what we're going after. The principal issue in baseband is probably its simplicity, and that results in cost savings, and it results in savings of installation and ongoing maintenance. The principal issue in broadband is its multiple channels, allowing multiple applications, something that baseband simply can't do. And I would characterize broadband as being somewhat more complex and somewhat more costly. However, if you need that application, if you need that ability to transfer something other than a simple data stream, broadband is the only way to go.
What about some of the software issues that relate to supporting networking, local area networking? Are we looking at a lot of specialized software that's being developed to support, say, inter-office communication and mail, or are we developing operating systems and operating environments and tools that support a much easier programming environment?
Well, first of all, there is an entire set of specialized software related to local networks, which we typically refer to as the protocols of these networks. And in order to put these networks in place, it has meant that we've had to provide the software in the context of systems that were built without any knowledge of the network. So in many cases, we've added the software on to existing systems. Over time, I think you'll see that that software will begin to permeate those systems themselves. In other words, operating systems will begin to be built with the assumption that there's a network there, rather than the case today where we try to tack it on to the existing system. That has somewhat limited the application, meaning that we've had to compromise how we use it because it wasn't fully integrated. Over time, the systems will be built with that assumption, and we'll see a lot more application, a lot more power as a result of it.
Mm-hmm. Mike, are you seeing any integration of software function through local area networks, actually using the networks and the work that you've seen?
Oh, yes. And I agree with Charlie. I think the local area network vendor takes a lot of the software and moves that into the devices themselves. For instance, the device here, there is a microprocessor in that unit, and there's a significant amount of communication software. You will also see, as applications migrate to further distributed processing, sharing of files, sharing of electronic mail, that you will see specialized application software written to basically be resident in the host computers or the microcomputers that will connect onto the local area networks.
Is standards a problem in this area of local area networking? I mean, can you link up different vendors' hardware, different operating systems? Mike?
Well, excuse me.
Okay. Yes, you can. They do exist some standards today. For instance, the common standard that both Charlie and we actually adhere to is just an RS-232 connection. That allows us to interconnect many different vendors of equipment. That does give you some limits, though, in terms of performance, in terms of function. And there are standards activities going on right now within the IEEE 802 committee with the National Bureau of Standards, which will derive a set of standards for the future. And both of our companies are participating in that.
Are these standards that are actually used to, say, intercommunicate between different kinds of local area networks? I mean, are standards really important if you're, say, have a vendor product where it's all self-contained in one geographic area? Is it really necessary to have those standards? Or do we look at standards for gateways, for example? Where do you see those standards actually being important?
Well, there's a lot of standards activity because we're talking about the interconnection of different devices, and the more common their communications are, the simpler it's going to be. However, we're starting with the fact that these standards aren't in place, and a big part of our job is to find the lowest common denominator, which Mike has mentioned, RS-232. It's not necessarily ideal for connecting networks, but it exists, and it's a well-established standard. But there are network technology standards themselves at the, if you will, the cable level of what kind of cable we're going to install and how we're going to share that. And most of the network activity has been around that set of issues. Those happen to be very low-level primitive issues compared to the entire problem. And over time, we're seeing attention being given to these higher-level problems so that once we can install the same cable and begin to share it, that in fact we can truly begin to communicate across that cable. We aren't there yet. And when we started this, a good bit of the industry thought and hoped that a single standard would emerge. That's clearly not the case. We're probably going to end up with a few dominant themes, and then we're going to have to figure out what the connection between those themes will be in the gateway technology that you talked about.
Excuse me, I want to ask you guys to demonstrate one of these network systems for us in just a minute. So while you get ready, we'll take a break, and we'll be back in just a moment with a demonstration of a local area network. Joining us now is Phil Edholm of SciTech. And Phil, you're going to give us a networking demonstration.
Yes, what we're going to do here is demonstrate on a small prototype network we've set up making sessions. First, I'm going to actually call over this network using this terminal to a host computer. And then when the computer prompts me for a login, actually log on. And I've now made a session over the network. The computer takes a moment to log us on, and in the interim, what I'd like to talk about is what we have here. We have a terminal, an asynchronous ASCII type of terminal, connected to a microprocessor-based packet communication unit. This unit incorporates a microprocessor, memory, and software necessary for all the layers of the protocol to allow communication over the cable, addressing, error recovery, retransmissions, etc. When the computer comes back, you'll notice we now have a session to a host computer, and by typing in something such as a system command, we can get a listing of directories on the computer. By typing a break, we're now back talking actually to the network, and we can do a status display. And you see now that we have actually one session over the network. With a network, one of the unique abilities is to have multiple sessions. Rather than just having one wire running from the terminal in one room to a computer in another room, we can literally have many wires running from that terminal, virtual wires through the cable to many different computers, and can turn them on and off. A very versatile technology supporting thousands of terminals on one cable.
Okay, that was an example of centralized intelligence. Now we want to see a demonstration of distributed intelligence. And Phil, what are you going to show us?
What we're going to see this time is a personal computer connected again into the network through basically the same type of technology, downloading from the same computer a file into the personal computer, and then printing that file out. So this time, rather than being at a dumb terminal, we have the ability to download a file, print it out, or work with it and upload it afterwards. In order to do this, what we've done is loaded into the PC a program which allows us to communicate to the network, basically a terminal simulation. Again, we call over the network to the computer address and then begin the login procedure to log onto the computer as we saw before. This is done, of course, to keep intruders out of the computer by requiring a password login into the computer, and then the computer has to respond to us. And this generally takes a moment.
So you're waiting to hear back from the host you're
From the host
talking
computer,
to.
exactly. And here it comes with a message of the day, basically telling us some information about the computer itself. And in a moment, we'll get a prompt back from the computer. When we get that prompt back, what we're going to do is begin a procedure to get a file from the computer, which is a letter file, and download it into a file in the PC called letter.
So you're downloading now from the host.
Right, now the file is being downloaded, and there it's now complete. And now what we can do is get out of the download terminal simulation program and go back directly communicating to the PC by typing in a command, which you notice flips us back talking to the PC. And it's now possible to take that file that we downloaded and print it out on the printer. And we got to type it in again. And there we go. And now this is the file that actually was downloaded from the host computer and is just a letter of a response to a customer. The interesting thing, of course, about this technology is that on the same piece of cable, this entire network is running over this type of cable, which is a 75 ohm coaxial cable. We can also have video. This is represented here. We have a small Walkman type of television set, which actually has the picture that's being transmitted out from the studio modulated on the same piece of wire. So a piece of wire that could support literally thousands of terminals and numbers of PCs and host-to-host computer communications can also support video and other types of systems.
Phil, let me ask you a little bit about this operation right here. This is a file transfer operation, what I guess I'd call a file transfer operation, upload and download. Is this typical of the kind of software that we're talking about in terms of communications over LANs, or are we looking at really a distribution of the whole operating system over that environment? I mean, ideally, we wouldn't want to have to make these file transfers, but we just access the file and it happens to be over the network, then...
In this case, the network is in effect communicating with the PC as a terminal, and the PC then is initiating over the network a file download procedure. And that involves a special piece of software, very small, in the PC to actually do the file download. The network communication, in other words, guaranteeing that the data is received without any errors, is actually in the network node itself.
But ideally, I guess in the long term, we'd like to have that operation completely transparent too.
Exactly.
Charlie, what is your response to that?
Well, I think that's exactly it, Gary. Is we have a case here of adding communications to an existing environment, and we're making the most of that communications. However, as you say, we'd like all this to occur transparently so that the commands that the user sees are very natural and he has no idea exactly where the resource is, where the transfer is taking place. It happens because of the underlying mechanisms and not because he explicitly requests it.
And this comes back to the original comment, I guess, that we made about integration of the local area network into the software itself. Is that true?
Right, which over time will happen. I mean, the next generation of these devices will assume a network, and these things will happen much more naturally than we've seen.
We talked earlier about standards in general, and if I recall, Xerox and Intel and Digital Equipment Corporation had a standard they were proposing. It was called Ethernet. And what's happened to that? It's been around for a while.
Well, it's in some terms could be declared very successful in that a number of companies have endorsed it and people make equipment according to that standard. I think a couple of things, however, have to be said, and one is Ethernet is not an end-all in itself. It represents a basic technology that aids in this problem. And secondly, it's not the only technology that's going to be applicable. We're seeing an example here of broadband technology, which has its own attributes and is an alternative to Ethernet.
So if we take a look at local area networks in general, it seems to me that over the last few years that we've heard the talk about local area networks, that maybe one of the things that's caused difficulty in acceptance is a standardization of the interface. Is that true?
Sure. The fact that, again, we were looking for something that would solve all the problems and we aren't going to find it. It's like the universal computer. There isn't one, and we probably wouldn't be happy with it if it existed. It'd be a Turing machine, probably.
Right.
All right. I think standards come in time. To try to come up with a standard too soon would mean that maybe we would standardize on the wrong thing. We're seeing a lot of activity now with Ethernet, with broadband in the standards communities, as well as token passing for manufacturing and manufacturing automation requirements. And their whole question is, what will IBM do? And that itself will set a standard for the industry.
IBM.
Gentlemen, yes, we're out of time on that note. Thanks very much for joining us, our three guests, and all of you, and hope you'll be with us again for the next edition of the Computer Chronicles.
Random access is made possible by a grant from Byte, the Small Systems Journal, publishers of a monthly magazine on microcomputer technology and innovative projects in the world of computing.
In today's Random Access file, have you always wanted to get into the stock market but never wanted to deal with those stockbrokers? Well, if you have a personal computer, you can buy and sell like the big boys now and never have to talk to a broker. C.D. Anderson, a small discount broker in San Francisco, has announced the first home brokerage computer system. For an initial $300 fee, you can use the service to place an order for almost any kind of investment transaction. And Charles Schwab has also announced plans for starting a home computer brokerage service beginning early next year. The computer invasion of the public schools is continuing, but amid new controversy. Latest figures are that 86% of all high schools have at least one personal computer for student use, and 61% of all elementary schools now have at least one computer. But educators are starting to argue over what to do with the computers. Some experts are saying it's a waste of time to teach kids programming. Others are saying that most computers in schools are now being used simply as electronic flashcard systems. The job of getting enough computers into the schools is monumental. One research firm says it will cost $4.5 billion to adequately equip America's schools with computers. And the value of it all is still not clear. In one study, 69% of the students tested knew how to draw a 90-degree angle on a computer, but only 19% of them knew how to draw one on paper. A Stanford study just released shows that boys are much more interested in computers than girls. The vast majority of students enrolled in computer camps are boys, as is the case with computer ownership and the purchase of computer games. The Stanford study says that could create real problems for women in the workplace of the future. IBM and Hitachi have buried the hatchet, reaching a settlement agreement in their stolen trade secrets case. Hitachi reportedly will pay IBM several $1 million. Hitachi has also agreed not to use any of the information it obtained and to return all stolen documents to IBM. Hitachi also agreed to disclose the names of anyone who offered to sell IBM trade secrets to the Japanese computer company. Industry experts are hopeful this settlement formula will set a precedent for resolving future trade secret cases. Well, AT&T says it's getting into the information business, and it sure is. AT&T just announced the sale of a $70 million information system to the Japanese phone company Nippon Telegraph and Telephone. AT&T's computer software system will be used to monitor Nippon's communications traffic. Nippon also plans to buy a $12 million Cray computer to run the system. The whole deal depends, however, on approval of an export license. News from the executive suite, more top management changes in the Valley this past week. Two top Atari executives have quit. John Cavalier and Jeffrey Heimbeck have left their positions in Sunnyvale. Cavalier moves to Apple, and leaving Apple is John Couch, the man behind the Lisa project. Couch joins the board of Software Ventures, Inc. of Mountain View. Couch says he wants to push the technology of software 4 or 5 steps past Lisa. If you're confused by all the new computer books coming out on the market, there's good reason. The publishing industry says there are now 2,000 computer how-to books in print, and that computer books are outselling all other business-related books. In fact, Crown Books says the growth in computer books is matched only by the growth in romance novels. Last year, more than 7 million computer books were sold for a total $30 million in sales. And the story's the same with computer magazines. There are now 72 monthly computer magazines on the market, and this is a business which didn't even exist 6 years ago. Last week we took a look at the best-selling business software. This week we'll check the top sellers in computer game software. The top 5 in order are Zaxxon from Datasoft, Wizardry from Certec, Flight Simulator from Microsoft, Pinball Construction Set from Electronic Arts, and Zork 1 from Infocom. Finally, it had to happen when Sweet Lady signed on to CompuServe's CB channel. Little did she know what was in store. She met Mr. Mike, who helped her figure out how to retrieve electronic mail. Mr. Mike and Sweet Lady then moved to the private talk mode, and wouldn't you know it, last week Sweet Lady and Mr. Mike got married on the CB channel, of course. The whole ceremony took place on CompuServe with more than 70 invited guests logged in, and when the minister entered the words, "You may kiss the bride," Mr. Mike typed in KISS. Now that's networking. And that's this week's edition of Random Access, a capsule look at what's going on in the world of computing. Watch for Random Access each week immediately following the Computer Chronicles.
Random Access is made possible by a grant from Byte, the Small Systems Journal, publishers of a monthly magazine on microcomputer technology and innovative projects in the world of computing.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and sitting in for Gary Kildall this week is Herb Lechner. On today's program, we're going to be delving into the mysterious computer chip itself, that tiny piece of silicon that seems to be able to hold so many circuits. Herb, we have moved along from 8-bit to 16-bit, even 32-bit processors, from 16K chips. We even hear talk now of 256K, 4-megabit memory chips. How far can we go in jamming stuff into these computer chips?
Well, I'm embarrassed to admit, Stewart, that about 10 years ago when I was asked that question, I responded that I thought we were approaching the limit, because I assumed that the components of computing would continue to be a few inches or a foot apart, and light only travels a foot in 1 nanosecond. But obviously, micron distances have proved me wrong today.
So who knows how far we can go.
Who knows how far we can go.
Before we get into chip architecture itself, let's take a look at silicon, the natural material which is the basis for all this semiconductor technology.
Integrated circuits, computers on a chip, micro-miniaturization. The semiconductor that makes these revolutionary devices possible is derived from one of the most common materials in the Earth's crust, silicate. The purified extract, silicon, is heated until it becomes molten, and a seed crystal is dipped into the melt and slowly drawn out. As the seed crystal is withdrawn, the molten silicon crystallizes, forming a single crystal or ingot. The ingot is sliced into thin wafers. Once polished and microscopically cleaned, these brilliant discs are the foundation for integrated circuits. The process of transformation begins with computer-aided design, a method that calls up circuit design modules from the computer's memory. A new design can be created and edited with the stroke of a light pen and a video screen. But the printout of computer-edited copy is routinely checked against the hand-drawn design, still, at present, the final document. If they match, the data is converted to a photographic mask, and through photolithography, the design is transposed onto the wafer. A chemical wash develops the pattern by dissolving away or etching sections exposed through the mask. As each layer of circuitry is applied, it is checked for alignment with the others. This step becomes critical as large-scale integration is replaced with very large and soon super large-scale integration, a jump from 10,000 to 100,000 transistors on a single chip.
Our guest on today's Computer Chronicles is Phil Downing. He's Vice President for Corporate Technology at Advanced Micro Devices, sometimes known as AMD. Herb?
Phil, there's been so much development, and we've come such a long ways from vacuum tubes to today's integrated circuits. Can you start out by giving us just sort of a quick view of where are we today?
Well, as you know, Herb, today we're able to put thousands of transistors onto a single chip and virtually take an entire computer and put it on. And we do this with photolithography type of processing that enables us to pattern images down at the 1 micron size. This not only allows us to build microcomputer chips, but also memories having densities of thousands of bits, 64,000 bits, 256,000 bit memories.
Well, have we exhausted the technology? Have we come as far as we can, or is there more to go?
No, we see the trends over the last decade in which the feature sizes that we use to make these chips going down at about 10% per year, continuing over the next decade. We'll still be able to reduce the feature sizes below 1 micron.
What technology does it take to allow you to make things that small? How are you able to make them down to the size of a micron?
It used to be simple contact printing. The photographic images were put onto a plate which is brought into contact with the material being processed, and simple contact printing image transfer. What's happened in the last 10 years is that we've moved to a projection imaging capability that allows us to not only get very, very fine feature sizes, but because we don't bring the mask into contact with the wafer, we don't damage the material during processing. That gives us very few defects in the manufacturing process, and with very few defects we can now make these very complex circuits economically.
Do you run into quality control problems as you get greater and greater scales of integration? I mean, do you end up with fewer acceptable chips?
Well, as the feature sizes go down, the number of defects that you can capture during the process increase. And so we have to maintain more and more clean conditions in our manufacturing process. This does translate into more difficulty in the process, but we evolve our quality control measures as we develop the technology so that we can do it economically. Also, there are means of building extra circuitry into some of these chips so that you can program out during testing faulty portions of the chip and end up with reconstructed good chips. This is called redundancy. And this also helps maintaining the quality and also the economics of building these chips.
How hard is it to design a chip? I know that you run tens of millions of chips once they are designed, but I also know that there are a number of chips on the market. How do you go about designing a chip or modifying one?
The design is probably one of the most complex tasks it faces today. We talk about the evolution of the microelectronics technology, but many people in our industry have stated that the technology is moving faster than our ability to design these complex chips. And so what we've had to do is to change the way we design the chips. It used to be that with a collection of 100 or several hundred components on the chip, you could define a small system, a set of AND gates, OR gates, a multiplexer, or something like that, and you could draw this up on a piece of paper, on a precision graph, and then this could be translated into a set of photographic plates for processing. These days, when you're talking about having 100,000 transistors on a chip, the task can no longer be handled by drawing individual components on a piece of paper. So we have to use computers to maintain these huge files of various geometries that ultimately get translated into the chip process, and that's called computer-aided design. And that's an area that requires a great deal of development in the next decade for us to capitalize on what the technology is going to be capable of doing.
What are the trade-offs as you go to faster and faster movement of electrons through the chip in terms of heat generation? Do you reach a point where you start to create a problem?
Absolutely, and in fact, one of the latest technologies that people talk about today, complementary MOS technology, many people call it CMOS technology, addresses that very problem. And that is that each element or each logical element on the chip consumes a certain amount of power, and different circuit and device technologies consume different amounts of power for each element. In bipolar technologies is a large amount of power consumed for each element to gain very high performance. In NMOS technologies, there is still a moderate amount of power consumed, and for levels of complexities that we deal with today, the power consumption is handleable. But as we build the complexity to hundreds of thousands of components on a chip, the power consumption by each element is unacceptable, even in NMOS technology. And so you have to use a technology like complementary MOS, which doesn't burn any power during its static operation. Only when it switches does it consume power. And this is very key for us in building more complex chips.
Can these technologies be both used in the same computer?
Oh, absolutely. In fact, many companies like ourselves have offer multiple technologies in the products that they deliver. And we put together kits of products that are made to work together that use bipolar technology, NMOS technology, and as CMOS technology comes into its own in this decade, all three of those technologies will be used together.
Phil, you mentioned that the chip technology maybe is ahead of your ability to design for that technology. I've also heard that your chip technology is kind of ahead of our ability to actually apply it and use the amount of integration you can get on a chip. Is that true?
Well, now you're getting into the systems area, and that's not my area of expertise, but being a user of computers and computer-aided design, we certainly see an broad application of hardware to solve the software problem. We substitute a great deal of computational capability for clever software design. And we find that higher and higher levels of integration and software capability are crucial to us in our design task. Engineering workstations that give the power of 1 million instruction per second computer at the hands of each individual engineer is something that we very definitely can use.
We've heard about the possibility of 4 megabyte chips. I mean, is that a conceivable project?
Well, I think people would feel very happy if we could conceive of a 4 megabit chip.
Megabit,
okay. If you look at today's state-of-the-art, IBM has recently announced a prototype version of a 512-bit dynamic memory. And there is a project that's being proposed for the Semiconductor Research Corporation to actually develop a 4 megabit dynamic memory. And we certainly think that it's feasible to accomplish that in the next 4 or 5 years.
Let me ask you about the material itself. We're talking about silicon primarily in chips. Is that the material of the future forever for chips, or is there another element that might solve some of your problems?
It's a very application-sensitive topic, and that is for microwave types of circuits and for light-emitting diodes or optical-type chips where you're looking for optical interfaces. Other materials in silicon are suitable for that. Indium phosphide, gallium arsenide probably being the most popular of them. However, if you're talking about VLSI, very large-scale integrated circuits, we really see silicon as being the material that's going to dominate in the foreseeable future.
Okay, in just a minute we're going to take you on a guided tour of a computer chip. That's coming up next. Okay, Phil, you're holding 2 chips, I guess, in that case. Tell me what it is you have there.
Well, I have a chip that was designed in 1975. This is the 2901 chip, which is a 4-bit slice microprocessor. And next to it, you see a much larger chip, which is a 16-bit microprocessor, which is called the AM29116. This chip, being a 16-bit microprocessor, is roughly 5 times the component complexity of this one here. And I have a photomicrograph of this smaller chip. This is about 1/8 of an inch on a side here, and so you can see that this is quite a large blow-up.
Okay, now this, in fact, is the 4th generation of this particular chip, isn't it?
That's right. The 2901C, we go 2901, and then the 2901A was introduced, B and C, so this makes it the 4th one.
Okay, and what kind of chip is this?
This is a 4-bit bit slice microprocessor.
Okay, and could you take us through a tour of all the components that are crowded inside that tiny thing?
Well, 4-bit slice microprocessor is basically an ALU with a register file and a set of instruction decoders and, of course, an input-output section. Now, what you see in the center here is a register file. This is a 2-port RAM so that it can both read and write different bits of the memory at the same time. It takes the data, the 4 bits of data, out of this register file and pumps it through this section here, which is the ALU, which is controlled by the instruction decode, which you see up in this section here, and some of it in this section over here. So the random logic that you see that's very irregular is what makes up the instruction decoding. ALU is quite a regular structure, as is the register file here. You can see the outputs along the section here, and a set of inputs along the side of the chip here for control and data input.
Okay, and ALU for people who don't understand?
Arithmetic logic unit.
Okay.
This is the part that does the work.
Right. Now, explain to me, you said it's been improved now 3 different times to get to a 4th generation. What does it mean to improve this chip each time you redesign it?
There have actually been 3 things done with this chip to improve it. One of them is simply capitalizing on changes in our photolithographic processing. The lines get narrower because the manufacturing capability improves, and we want to capitalize on that to make it smaller. Making it smaller does 2 things all by itself. It makes it more economical to build, and it also improves the performance of the chip because as the individual devices get smaller, their performance improves. 2 other things have been done. One, we have changed the bipolar technology with which the chip is made to improve its performance characteristics. That has had an obvious benefit. And also we've changed the circuit technology. This chip was originally designed in a TTL circuit technology, and we changed to what is called an ECL, or emitter coupled logic technology. It's a different bipolar circuit design approach, and this has in fact changed the operational speed of the circuit by about a factor of 2. All in all, we have accumulated about a 4x improvement in performance by redesigning the chip 4 times.
Phil, it's been said by some that the Japanese are pulling ahead of us in the design and manufacture of advanced microchips. Do you agree with this? And if so, what is our response to that?
The Japanese have certainly come a long way in the last decade. 10 years ago, they were not a significant factor in the integrated circuit business, and today we could consider them a very worthy competitor, especially in the memory area. The Japanese, I think it's well known that they have excellent manufacturing capability, and they also have excellent capital formation, which gives them a significant competitive edge over our industry in the United States. The response, at least from advanced micro devices, and I believe it's characteristic of the industry, is to be very innovative in the products that we build, so that we expect that the new products that we introduce will allow us to maintain profitability in our industry.
What about the 5th generation project we hear about in Japan? How dependent is a 5th generation computer on increased levels of integration?
Well, again, you're getting outside my area of expertise, but certainly the chip technology is considered to be very key because of the enormous computational requirements of that type of a system. It's, I think, pretty widely held that you need very sophisticated distributed processing in order to implement this kind of a system, the 5th generation computer, and inexpensive arrays of microprocessors is going to be key in making that happen.
I believe the Japanese have talked about having as many as 100,000 switches on a given chip. Is that a proper recollection?
Well, that's true. That's, in fact, below the state-of-the-art of the industry today.
Oh, it is?
Yes. Western Electric and IBM and even ourselves have built chips with several 100,000 components on a chip. If you look at this other chip here, we have a 256K EEPROM here, which has one transistor for each bit of memory, obviously. And so that means that it has more than 250,000 components on one chip. And there are microprocessors that have been built in the industry today that have 500,000 components on a chip.
Is standards a problem in your end of this business? It seems to be a problem in every aspect of this computer business. AMD, you have your chips, and Intel has its, and Zilog, and so on. Does that complicate this field in any way, or in terms of looking at, say, networking and Ethernet type standards and so on? Is standards an issue in your industry?
Most definitely. We participate strongly in the definition of network standards, especially at the lower levels of network protocol, the physical layer and the link layer in protocol, in the protocol structure is something that if we don't have a good standard definition, it's very hard for us to get a good part defined. And since we invest years of design activity in many of these complex parts, we can't afford to be wrong. So standards are a very important element of our business.
How do you handle the standards problem as we get more and more into the manufacture of specialized or custom chips?
Actually, in two ways. One is that we have to be very capable in terms of defining complex products, obviously, and although there are many who would believe that it's not possible to continue to do that with increasing levels of complexity, that statement's been made for the last 20 years. And we do believe that there is a large market for standard components, large, high-volume type of parts,
and
similar to this, and that will continue.
Mm-hmm.
However, we also see that there will be a growing market for semi-custom and custom type parts. And that'll come about mainly because the design problem that we face today in building standard components forces us to automate the design process just for our own purposes. It costs us millions of dollars today to design a microprocessor. We have to solve that problem for ourselves, and in solving it for ourselves, we'll develop tools that enable us to design semi-custom and custom chips efficiently.
Mm-hmm.
And in fact, today, many systems manufacturers do design their own chips with some of the sophisticated tools that are available today. IBM builds many of their systems with gate array components, which are semi-custom integrated circuit products. So we will see an increasing share of the market taken by custom and semi-custom type chips.
Phil, we have just about a minute left. Let's look 5 years down the line. What are we looking at as the next major advance or next major improvement in chip technology?
Well, as I said, the technology that you will see emerging in the next few years as a dominant technology is CMOS, because of the fact that it can build chips of very high complexity without a power consumption problem. And then beyond that, I think that you're going to see a continuation and evolution of the memory technology that will take us to the 4 megabit memory level and beyond that. So I think that we will see technology continue to decrease the cost per function. Today we're looking at somewhere homing in on 1 millicent per bit memory prices. And we're going to see a half a millicent and a quarter of a millicent per bit in the future.
Okay, we're all out of time. Phil Downing of AMD, thanks very much for joining us, and we'll see you again next week on Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Herb Lechner sitting in this week for Gary Kildall. Herb, what I'm working on right now is a business applications program called Lotus 123. It's one of the more popular business application packages right now. The 123 stands for the three basic functions which are more or less integrated in here: database management, spreadsheet analysis, and graphics. What I have right now is the spreadsheet analysis part of the program. I just transferred a file out of my database manager, put it into the spreadsheet analysis, just sorted it out to list these hypothetical offices of our hypothetical business here. And what I can do now, if I want to see a graphic representation of these particular figures, which are quarterly sales figures by office, I can just, with one or two keystrokes, turn that into a pretty impressive demonstration. Our subject today is business applications, Herb, and the first thing I wanted to ask to get going is lots of businesses are making that transition into the use of computers to solve business problems. In some cases, it seems to work out very well. Frankly, in other cases, people aren't so happy with this process. What makes the difference between succeeding and failing in using a computer in your business?
Well, Stewart, in 1983, Time elected a Computer Man of the Year, and yet I haven't seen any boards of directors putting computers in as presidents of companies. And I really think that the difference between success and failure in the use of computers, as in any business tool, lies in the hands and the skill of the person using it, their ability to select, use, apply this tool to accomplish their business needs.
Okay, we're going to be meeting an executive from Computerland. We'll meet a computer expert from Stanford University, and we'll hear firsthand what IBM is doing to help solve the business problems that companies have. First, let's go out inside and see how computers are being used now in business.
Integrating computers into the workplace evolved from the basic need and curse of almost every office: producing, manipulating, and storing written information. Like the original number-crunching computers used in science and mathematics, business automation systems are paper crunchers and time crunchers, squeezing ledgers and files onto disks and opening flexible communication lines of enormous capacity. There is no shortage of predictions about what the impact of automation will be on traditional workplaces, but one trend is certain: offices are being redesigned to accommodate a new level of information gathering and distribution. In glossy magazines that promise paper-free offices, personal computer terminals are ubiquitous. Just as business software becomes more integrated, hardware is becoming a more integral part of desks, counters, and even briefcases, absorbing more and more of the traditional desktop tools. In some of the latest designs, communication and data manipulation are combined into one small module, bringing together telephone, word processors, spreadsheets, files, and electronic mail. Digital voice storage is incorporated in an effort to make the system more executive and clerical friendly.
Kevin, I'll be sending you the one-pager advertising the system.
Computers are suited for more than just front office use, but the computerized desk is an example of automation applied to streamline the most time-consuming tasks. Paperwork and phone calls are estimated to make up as much as 75% of office activity.
Computerland is the biggest computer retail chain in the country with about 600 stores now, and we have the Vice President for Products, Chuck Kinch, from Computerland with us. And next to Chuck is Stewart Regis, Assistant Chairman of the Computer Science Division at Stanford, and Stewart is an expert in office automation systems. Herb?
Chuck, why don't you start us off today by telling us what are the popular business applications?
Well, the tendency is more towards horizontal type packages more than vertical, with the emphasis being at the moment on integrated packages like SuperCalc 3 or Lotus 123 that involve some portion of a number of types of packages like word processing, decision support, and database.
Is it the integration that seems to be the popular thing, or the packages themselves?
The integration seems to be the popular thing. That's supported by the fact that there's more than one very popular package.
And tell us exactly what you mean when you talk about horizontal emphasis.
Okay. A horizontal package is a package that could be used by a wide variety of business people. For example, word processing is what we would consider to be a horizontal application. It could be used by a doctor, a lawyer, a business person, a bakery owner could use word processing, whereas architectural design assistance is a very vertical package. It could only be sold to and used by architects.
Right. The people that you're dealing mostly with, are they large computer users or small computer users? Who do you see when they come for packages?
Our two biggest customers are the Fortune 1000 corporations and small business.
I see.
Stewart, is it fair to say that any business is a subject for computerization, or are there certain kinds of businesses, certain kinds of companies that are really better off doing business the old-fashioned way and not going into computers?
Well, I think people have gotten a little bit too much into the computer bandwagon. I mean, nowadays, if something's wrong, it seems to be buy computers. That's the solution. I think that in the next 5 to 10 years, though, virtually every business will want to incorporate computers in some way into their business. I think we're seeing the computer as the communications tool of the future. It would be like having a business without phones. I think that it's going to be integral to every business.
Well, it is pervasive, and many people are delighted with the computer applications, but some are not. What makes the difference between a happy customer and one who isn't?
Chuck, maybe that's your area.
Is that one for me?
That's a tough one.
Okay. One thing that we found is true is that if the customer is poorly organized to begin with and the systems just generally aren't working at all, the computer isn't going to help. So we ask our customers to sort of do some preparation and get their systems in order before they automate. The computer is not necessarily the answer, but part of it.
What happens when a customer, let's try to go through a scenario, a customer walks into, say, a Computerland store, and he's running a small business, and he's got all these problems. How do you mesh the variety of solutions which are on the shelf and the problems this particular guy has?
Well, a lot of what some people would call the sales cycle really constitutes information gathering on the part of the salesperson, and then a certain amount of analysis, and then a lot of education back to the customer. And ultimately, we try to let the customer make the final decision after they've been educated to some degree with a little guidance by the salesperson.
What kind of an educational program would you map out for a customer, either of you, I think?
Well, I see it even as a user of computers rather than someone who sells them. I have an administrative post in the university. I'm in charge of the training program, for example, for our secretaries. It's very interesting to see that we have to screen people from the very beginning. When they first come in for an interview, we have to talk to them about computers because there are a lot of people out there who are very afraid of them. I think that's also one of the major challenges of office automation is getting people who feel comfortable even starting with the machines. There are a lot of people who have genuine fears of it. Mm-hmm. Even managers, I might say especially managers, often have that kind of fear.
Do you see that also in your stores, Chuck?
Oh, absolutely. That's why our current slogan is Make Friends with the Future. We like to portray our stores as being friendly places. A good place to start, we'd like to think, is a Computerland store, where somebody might give you some recommended reading, or just have a general discussion and talk about the principles behind microcomputers.
Chuck, could we get specific and maybe list the various kinds of business applications we're really talking about? What's the variety of areas in which you can use computer software now?
Well, of course, we've discussed a little bit about the integrated packages, which make up a number of types of packages together. To split that out, the more popular ones are word processing, decision support or spreadsheet, it's sometimes called, database applications. We're seeing some increased popularity in word processing and in graphics programs also.
Particularly graphics programs that will display information that you have in your database, for example.
Yes.
One of the things that we find in our department, well, and also at the university as a whole, one of the worst things that happens is duplication of effort. You have somebody who's working on a Wang word processor who writes a letter. This memo goes over to somebody else, and that person's secretary types it into an IBM PC. Some discussion goes back the other way. Some figures are generated. It's given to the person who's the graphics wizard who can make pie charts, etc. It's much easier if you do have an integrated package where these things are easy.
You know, I'm frankly surprised, though, because in the small business environment, in the large business environment, I see where people would want the decision support type tools, of a fairly horizontal and general nature. But do all the small businesses now have their chart of accounts and general ledger stream programs and payroll and tax programs? Is that why you're not seeing still a high level of interest in vertical applications of that type?
The general business type package is probably the next most popular line right behind the horizontal packages
financially oriented business.
Yes, we sort of look at it as a very narrow horizontal package. Most people can use general accounting. However, it is rather vertical in its expertise, and it requires some accounting expertise also.
I see.
Go ahead.
An interesting application that you didn't mention was electronic mail. And I can see that for a small business that wouldn't be as interesting. I was just curious how sales go in terms of any kind of electronic mail packages.
We see a significant increase in communications. I listed communications as one of the up-and-coming horizontal packages. It's not specifically electronic mail, but it certainly is part of communications packages. Packages like PC Talk and Crosstalk are starting to hit the bestseller charts for us.
Okay, there's not much doubt about who is the leader in business applications right now. That's IBM. And in just a moment, we're going to have a rare opportunity to talk with an IBM representative and one of their customers to see how they go about solving business applications with computers. And that's coming up in just a moment. Joining us now is Bill Blackmer. Bill is the manager for productivity systems at Levi Strauss here in San Francisco. And next to Bill is Dan Carroll. Dan is a regional marketing representative with IBM and a specialist in office systems. Now, Bill, I want to start with you. Levi is a large corporation. How do you go through the process of recognizing that you have a problem and then figuring out how you're going to use a computer to solve that problem?
We had a problem where we recognized that office systems, or the office environment, the headquarters type environment at Levi Strauss, was probably the last area where we have thrown computers, where we have thrown data processing, where we have thrown technology in there in an effort to make people more productive. We've obviously done it in our warehouse environment, time and motion studies, and also in our distribution center environment. That combined with the fact that our corporation and even the marketing environment that we work in requires us to make more efficient use of our time and to get information to our senior executives more quickly, that we had to look at office systems as something that needed some serious study. So that's how we basically got involved in office systems in the early days.
Are there some basic criteria you established up front as to what the system had to do?
Yeah, we kind of looked at it as a three-tiered approach. There was one thing that Levi's has a little saying that says that Levi's is people. Office systems, office automation is a scary term to a lot of people, so it became very important to put these people at ease and to make them own the process. So office automation, we involved the people that were involved in office automation in the early stages, which were largely word processing, secretaries in the decision-making process. We wanted them to feel comfortable with what they were getting, we wanted them to know why, and we kind of wanted them to own the decision because they are the basis and the backbone of our decision. So people was important to us. The second thing was integration. We needed an environment where our secretaries and our middle managers in Dallas could talk to New York, could talk to London, whatever our cases, or whatever the case might be that you'd want to get into. So we needed an integrated system that could work off our communications network and off our mainframe. The third area that was important was something we call planning. Office automation and systems tends to start off with the idea that the secretary is the resource. Well, it does not take a person very long to realize that you have to deal with middle managers, that you have to even deal with senior executives to get information flow out of your corporate databases to those environments to make decisions. So we call it people, we call it integration, and we call it planning. But people is important.
Dan, how does IBM go about supporting a customer who, like Levi's, recognizes they have a problem and want to do something about it?
Well, once we have the chance to sit down with a customer like Bill, we try to pursue two directions at the same time. First, we try to take advantage of the host databases and networks that may be installed at that customer. And then secondly, because each customer at the end user level in the office tends to be different, we try to understand the proportions of 6 types of workers that are typically found in a white-collar workforce in our customers. Those types are the manager or the business professional, the data processing professional, the engineering or scientific professional, an office or text worker, a commercial worker, somebody who might be involved with a cash register or other information gathering equipment, and finally the production worker, the folks that we all know and love in the factory, who may be operating machines which can collect information for the database.
Okay, Bill, we have up on the computer here something called Profs, which you've just installed at Levi from IBM. Tell us what it is and give us a demonstration.
PROF stands for Professional Office System. What it is a beginning of an office systems plan, and this is basically a small part of it, which allows you to schedule appointments, set up the beginnings of electronic mail, just a little personal communications between your people where you don't spend a lot of time in telephone tag or writing messages and things, to take the power of the computer and make it do a little bit more.
Okay, show us, for example, how using Profs you would schedule a meeting between yourself and somebody else at your company.
Okay, real quickly, obviously what we have up here on the screen is on the left side is an identification for a specific key called PF1 through 5 here and what it does. This is a menu specifically customized to Levi's. We know our environment best, and that was the nice thing about the package is we could get as specific for our environment as we want to. So we want to schedule an appointment here. So we hit PF1, which says I want you to go out there and pull in that part of the system that calls for scheduling appointments. Here it comes back. I happen to be the one logged on, so it's looking for me. It's telling me today. And like I said, and this gives us a series of options that deal with scheduling. So you want to schedule a meeting. So let's hit what it calls there, which is the PF7 key. And once again, now it's going out here and loading this thing in. Just as an example, let's schedule a meeting for Monday, sometime on Monday, for, what would you like, 2 hours?
2 hours? Let's do a 2-hour block.
Let's get me involved in this meeting this time.
So we'll try to set up a meeting between you and somebody else at Levi.
Right. A lady that needs no introduction at Levi's.
And what's happening now?
All right, what it's now doing is it's going out there and looking in my schedule and Bonnie's schedule for Monday and finding out if there's an open 2-hour period. So, you know, if we have 800 schedules out there, it's looking for our 2 specific ones and coming back with a note.
And what does it tell you?
Well, this note is telling us that it could not find a meeting time to match these requirements on this day for Bonnie and I.
Okay, so you didn't have a 2-hour block, or she didn't have a 2-hour block free.
That's correct. In this case, we know that I don't have a 2-hour block free.
Okay, now let's try to schedule, say, a shorter meeting, see if it could find a shorter period of time for you two to get together.
Sure. Go back once again. It always throws you back to the menu so that you do your best not to get lost. So we'll schedule a meeting again, the PF7 key.
And the time is, you're in fact plugged into a mainframe here, aren't you?
Yeah, this particular test that we're running right now is tied to an information network that's running in Florida, but it is customized to our specific environment. It's an example. It's exactly what we're going to bring in-house. So let's go out here and let's schedule, what would you like, 15 minutes?
15-minute meeting.
All right, so we'll hit 15 minutes, and I always wonder when I do this if I'm going to spell my name wrong, and I just did. Okay, and let's get Bonnie in here. A-N.
I suppose if you did enter the wrong name, it would tell you so.
Well, it would either tell you so if it could match 5 or 6 characters up, it would go out and find the name anyway, without any, whoops. Well, let's hit transmit so that we get some action done here. Once again, it's going out there now and comparing our 2 schedules.
Okay, now looking for 2 15-minute blocks which are open on both your schedules now.
That's correct.
And what's it saying?
And it's coming back and saying that we have a 15-minute schedule here on Monday, and at between 8 and 8:15, and we have a whole hour open Monday afternoon. What we do at this stage, if we decided to pick the 8 o'clock meeting, is simply enter an X here, saying I've decided I want that time with her. It throws me into a note that says, where do you want the meeting? What's the purpose of the meeting? But it's a note that's going to be sent to her electronically, so when she's on her terminal, she'll know that that meeting is there and set up. And this is where I would enter that information.
Okay, Dan, is this typical of the kind of problem solving you might take in any other corporate client?
Oh, very much so. We, in fact, use a system like this internally within IBM. I got the note to come here today on a terminal just like that. And it's very much an iterative process of postulating a requirement for productivity, trying a solution, seeing if it works, and if so, expanding and replicating it throughout an organization.
First question that comes to mind when you see it, I mean, it's very impressive what it does. It's got to cost a lot of money to put a system like this in. Is it really worth saving the trouble of making the phone call to Bonnie and saying, when are you free on Monday?
Bill, maybe you could speak to that better than I.
I always get the hard ones. I think when you get into the office environment, you're not really talking automation in the traditional sense, where you get out there and you say, if I could only do that 5% faster or type 10 more pages. Automation's a bad term for the office, because if increased productivity equals the fact that what you do is type 10 more letters, spend 15 more minutes in a telephone call or something like that, you wake up with the view that I know a 4-year-old who was in a truly automated office and asked, what do you do? What does your father do? He said, well, he types and he looks in files and he does some things on the terminal. Well, sure, I do those things, but that's not really my job. So productivity means making your job easier to do business work, not office work.
Gentlemen, we're out of time. Thanks very much for being here, and thank you for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
In the Random Access file this week, Macintosh. What else can one say? If people weren't talking about the Mac itself, they were talking about the Mac commercial. In any event, the long-awaited Macintosh is now on the market amidst an incredible amount of hoopla. Early reports from dealers indicate what is described as tremendous consumer response. Early readings from dealers also indicate some concern over Apple's plan to sell Macs to universities at nearly 60% off. The dealers fear an active cut-price secondary market, with students buying Macs for $1,000 and selling them at a profit and still undercutting dealers by about half. Apple Chairman Steve Jobs talked about the new Mac during its unveiling earlier this week.
And what's so exciting about Macintosh is, while Lisa pioneered this amazing technology, this amazing software technology that makes this possible, with Macintosh we've been able to take that software technology and pull it down into a price range that's going to be affordable not just to the corporation, as Lisa is, but to the individual.
The Mac is basically a mini Lisa with a 32-bit microprocessor, one built-in 3.5-inch microfloppy, a mouse, and a 9-inch black and white monitor. The retail price is $2,500, and most analysts are saying that the success of the Macintosh is critical to Apple's future. Most reviewers have given the Mac excellent marks. However, some say that the lack of color on the Mac may limit its appeal. Meanwhile, the Macintosh got a nice early boost when the accounting firm of Pete Marwick announced that it will buy 2,500 Macs to be carried around by its auditors for use in on-site audits. The move makes Pete Marwick the first major accounting firm to send its auditors out into the field with computers. The importance of Macintosh to Apple's future was emphasized this week as first quarter earnings reports started surfacing. Apple's net profit fell 75%. The reasons cited were slow Lisa sales, price cuts on the IIe, and heavy R&D costs related to the Macintosh. Digital Equipment reversed its drop and showed a 40% increase in earnings, by the way. and IBM reported earnings up nearly 25% during the last quarter. And a market research report released this week shows that IBM and IBM clones now have about 60% of the Office PC market. The report projected that IBM machines would have more than 70% of the market by 1989. Well, this was the week of the Macintosh. IBM reported the start of volume shipments of the PC Junior this week. However, there were questions as to what volume really meant, as IBM warned that supplies would be limited. There were rumors that IBM was having problems due to parts shortages, but IBM said absolutely not. Last week, IBM announced the availability of a Unix system for the IBM PC. Now, AT&T and Digital Research have announced a deal to jointly develop and distribute software based on AT&T's Unix operating system. Digital's president and CEO, by the way, is Gary Kildall, host of the Computer Chronicles. While Apple this week was singing the virtues of its new 32-bit Macintosh, giant Hewlett-Packard announced that it was dropping plans to market a 32-bit computer. HP said instead it will concentrate on a new breakthrough product for release in 1985. Gene Amdahl's Trilogy computer ran into problems this week as Trilogy announced a delay in shipments of its new supercomputer. There were reportedly problems with the first prototype chips. Trilogy is developing 2.5-inch square wafer chips that will replace as many as 100 conventional chips. Apparently, the prototype chip had problems with its metal coating, leading to shorting and overheating. Fairchild of Mountain View got slapped on the wrist this week as the Pentagon took Fairchild off its list of approved suppliers. The Defense Department said Fairchild had failed to comply with government-specified quality control standards. In the world of software, MicroPro of San Rafael announced this week that it will go public with an offering of 2.5 million shares in March. MicroPro is best known for WordStar. And a new report by a software publishers group says that software piracy in the United States is now costing the software industry $20 billion a year. Some estimates say that nearly 80% of the software in use is pirated. Finally, there was almost more interest this week in Apple's Macintosh commercial than there was in the computer itself. The $500,000 TV spot ran during last weekend's Super Bowl and caused quite a sensation. Some thinking it was absurd, some thinking it was fantastic. The popular analysis of the spot was that Apple was picturing IBM as Big Brother with Macintosh as the hero of the people. Well, we'll see. That's it for this week's Random Access. I'm Stewart Cheifet.
Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. On today's program, we're going to be talking about mass storage devices, disk drives, floppy disks, Winchesters, and some of the newest technologies for improving the mass storage of computer data. And we'll meet Alan Shugart, one of the pioneers in disk drive technology. Gary, we call a disk drive a peripheral, but really it seems to me of all the peripherals, a disk drive is really a key part of a computer system. There really aren't too many serious applications you can run on a computer without a disk drive.
Oh, yeah, that's absolutely true. The traditional model of a computer includes a backup storage device, a central processing unit, and main memory or central memory. And it was really the scaling down of those three components that really led to the microcomputer revolution in the first place. In the early 1970s, we already had semiconductor memory that was replacing core storage, and the companies had started to produce these microprocessor chips. And it really wasn't until a floppy disk came around that we had a complete computer system that could be used to do useful things, as you mentioned. It's interesting that the disk drive is really the only part of that, or the only component of that system where it's still mechanical. And it'll be interesting to talk to our experts today and see where they think it's going to go. Are we going to stick with mechanical storage, or is it going to become more semiconductor also?
Okay, before we meet our guests, we're going to take a brief look at the history of mass storage technology.
Progress in the field of mass memory storage for computers has been directed by three basic needs: volume and density of information, and speed of access to that information. In the 1950s, computer data storage borrowed the recording technology being used by sound engineers, magnetic tape. Like its earliest predecessor, the wire recorder, oxide tape stored data sequentially. To reach information stored at the end of a reel meant running through everything stored on the tape up to that point. Short of faster tape drives, the only way to make data more accessible was to change the format of the recording medium. Disk storage, which allowed random access to information, was already under development in the mid-50s, but the popularity and potential of this technique became clear only in the last decade. The original 24-inch platters shrank to only 5 1/4 inches in diameter, while bit density increased 3,900 times, from a few thousand bits to almost 8 million bits per square inch. The improvements that led to that advance have today given way to new approaches that promise yet another dramatic increase in storage density. Thin film heads are smaller, more sensitive read-write heads made possible by technology developed in chip manufacturing. Because of their tinier components, they can read bits recorded much closer together on narrower tracks, about 12 million per square inch. Another development called perpendicular recording magnetizes the disk surface with vertically recorded pulses, data bits recorded on end instead of arranged horizontally. Once again, the effect is dramatic. This small change in the alignment of data means a 2- to 3-fold increase in storage capacity.
Joining us now is Alan Shugart. He's one of the pioneers in the disk drive industry. Alan used to work with IBM, then he started his own company, Shugart Corporation, and then he started another company, Seagate. Alan, welcome to the Computer Chronicles.
Thank you.
Gary.
Alan, I don't know if you know this, but I got my very first disk drive from your previous company, Shugart Associates, and they gave it to me for free at the time. I probably don't do that anymore, do you?
No, I remember that. I remember that. I objected to giving away anything.
I think it was 10,000 hours on a test drive. It was. They gave me a new set of bearings to go with it, too. Do you think that the floppy disk drive was really instrumental in setting off the whole microcomputer revolution?
Oh, there's no doubt in my mind. The introduction of the 8-inch floppy really proved the technology, but the introduction of the 5 1/4-inch floppy really expanded the market and provided for the big explosion. No question at all.
We have these devices now that are called Winchester disks or hard disk drives, and they seem to be coming out of Seagate, of course, as a premier company in that area. How are the hard disk systems going to affect personal computing?
Well, I think what the hard disk system does is it's really complementary to the floppy, and what it's going to do is expand the capability of small desktop computers to do some very large jobs that require lots of storage. You don't see any small desktop computers with hard disk systems that also don't have a mini floppy in it also.
Mm-hmm. There's a way of getting data from one computer system to the other.
Yeah, absolutely. It's input, output, and backup.
One of the criticisms for using hard disks in small computers, when you move them around, people worry about reliability. What's your feeling on that? Is there a problem with transporting Winchester disks around?
Well, certainly a Winchester disk is much more susceptible to damage from shock and vibration than a floppy, and that's because the media and the magnetic heads have to stay there all the time, and the heads are in contact with the media. If you bounce it around too much, you could have some problems, where in the floppy you can take out the floppy diskette itself when you're transporting it. So the Winchester is much more delicate.
Is it something that's going to be that problem going to be taken care of in the future?
Well, I think that they're getting better and better. I think that the newer versions are becoming much more shock resistant with stiffer air bearings and so forth. No, I think they're getting better.
Well, one of the things we have here is a 5 1/4-inch floppy disk drive, and this is fairly common, appears in the personal computers, and it has a lot of mechanical devices in it. There are little bales and heads that appear down here, and there's a board for decoding all the circuitry or the information that's coming through from the heads. And it seems to be a lot of mechanics in there, kind of the Model T of computing to some extent. Over here we have a bubble memory board this happens to be produced by Intel Corporation, and this is the bubble memory module itself. That's a 1 megabit chip. Now, some people would say that this type of device is going to be replaced eventually by a semiconductor memory device. What are your feelings about that, Al?
Well, I don't think it'll happen now. the floppy disk drive theoretically has an unlimited storage capacity because you can keep removing the diskette and putting a new diskette in. So it really has unlimited offline storage capacity, which the bubble memory doesn't have. So on a cost per bit basis, I don't think you're ever going to beat magnetic disk storage with semiconductor-like devices or bubble memories.
Al, you said the 5 1/4 inch disc was really the size that got the personal computer thing moving. That we see here a computer that uses a 3 1/2 inch, and here's a 3 1/2 inch micro floppy. Do you see this size as replacing the 5 1/4 inch format?
No, I don't. I think there's a marketplace for the smaller size, and I don't know if it will be the 3 1/2 or the 3 1/4 or the 3 or the 3 3/4. There seems to be lots of different formats vying for becoming the standard. There may be more than one standard, but I don't see that they'll ever replace the 5 1/4 inch mini floppy because the world's programs are written on mini floppies, and you're never going to be able to, in your wildest imagination, transcribe all those programs onto smaller disks. It just isn't going to be done.
You know, it might be worthwhile just spending a minute talking about another technology that seems to be coming up these days, and that's one of video discs. Well, I happen to have one here on the table.
You're like a magician with you.
Yeah. And complete Beatles.
Really a video disc.
And it says here that if you pull these little things out, you get we just taught everybody how to get a video disc out. Now, this happens to be an RCA video disc, and it's a linear video disc. It's not built to be a random access device. At least it's the way it's recorded. And I think they say they can hold something like 10 gigabytes. Is that right? Gigabyte. One gigabyte.
Very
sorry.
big number, anyway.
And that's equivalent of the Encyclopedia Britannica. Now, is there any application for this sort of thing in, say, personal computing and as a storage device?
I don't think so yet, except possibly for some archival storage. The problem with that kind of technology is one of error rate. Entertainment-type recording for either audio or video, you can have a lot of errors, and your eyes and your ears can't hear it. And the error rates associated with that kind of technology are several orders of magnitude less reliable than business computing requires. The disk drives. The data reliability of disk drives are several orders of magnitude better than you can get on that type of technology.
Now that's a non-optical video disc.
This
right?
happens to be called CED. That's RCA's version of a video disc.
Yeah. What about an optical device, a laser type disc? Is that more reliable?
Yeah, well, I think optical memory that you see advertised in the paper all the time now it's really for archival storage. You write it, and then it stays the same forever. And I think that there's a place in computer systems for optical memory for archival storage. But my judgment, optical memory that has updating capability, like you can do with magnetic disk storage, is still in the laboratory curiosity stage.
How about, I've heard about perpendicular magnetic recording as a way of organizing the data on a disk so that you can get more volume, more density. Tell me what that is and where that's at.
Well, when you're storing data on a magnetic surface of a disk, what you're doing is you're flipping the little magnets that you can't really see, but there are little magnets in the disk that are lying on their sides, and you record something, you flip that magnet over, and then you can detect later on that you flipped that magnet. And there are only so many little magnets lying flat that you can get on the particular surface of a disk, and that's the recording density capability. If you could somehow get those little magnets standing on end, it's like a cord of wood. You could get more wood standing on end than you can lying flat. And if you could get them standing on end and then flip them and detect the flip, you can get more data storage in a given area than you can with them all lying down. And I think vertical recording is definitely in the cards.
With regard to the 5 1/4 inch mini floppy, again, one way you can get more on there is to use both sides of the disk. And there's some controversy about whether or not that's a good idea and whether a double-sided disk is as reliable. What's your view on that?
Well, I'm not sure if with what's available now, if it's more reliable or if it's less reliable or not. But there's no fundamental reason, I don't believe, why a double-sided shouldn't be just as reliable as a single-sided. I think perhaps some vendors in the industry stretched the technology farther than they should have and didn't do some other things. And as a result, double-sided, double-track density floppies got a bad name. And in some of those cases, they're probably not as reliable as a good old 48 track per inch single-sided, but there's no fundamental technical reason why they shouldn't be just as reliable.
From a user's point of view, is there a big difference in the quality of a mini floppy disk that you buy?
Gee, I don't know. I don't buy very many.
But I mean, in the technology of manufacturing the medium itself, I mean, there are different price ranges and so on. And from a user's point of view, are they all the same or they're not all the same?
I really couldn't tell you. I'm sure Gary's more familiar with that than I am, but I don't use very many floppies, and so I really couldn't tell you.
Gary, could you tell?
Well, I haven't had any particular trouble with any media that I've run across over the years. I've found an inherent reliability in just about all these. I think, as Al mentioned, is mainly based on the kind of electronics that people are putting into these machines.
Okay, gentlemen, and we're going to take a short break. In just a moment, we're going to be joined by a man from Memorex, and you'll be able to decide for yourself whether he's here live or on tape. Okay, joining us now is Frank Sordello of Memorex. Frank is the Corporate Vice President for Technology there. Like Alan Shugart, Frank was with IBM way back when, I believe. And also, Frank is the holder of 38 patents in magnetic recording and disk technology. Gary, you want to start?
Well, with a background like that, I'm sure you can give us a pretty good idea of what's going on. Frank, you've got a number of different kinds of platters here. Can you tell us a little bit about what you've got?
Certainly. The platter with the thick substrate that we see right here is our latest product platter of a 14-inch diameter. For the Memorex Corporation, it's the 3680 1.2 gigabyte per spindle disk file platter.
Could you pick it up, perhaps, Frank? We get a picture of what you're talking about.
Certainly. The key items with the latest high-performance disk file technology consist of the adjectives thick and thin. Thick substrate, that is the thickness of the aluminum substrate, and thin film heads that go with it. With that, we are able to store that capacity that I mentioned, which is equivalent to all of the words and letters in 4 complete sets of encyclopedia: Britannica, Americana, Book of Knowledge, and perhaps even the Funk and Wagnalls.
On that one platter?
No, on 9 platters and 1 spindle in the device.
And then what else do we have here?
Well, this is a thinner substrate, 75 milli-inch aluminum substrate, 8-inch disc platter that's used in some of the smaller products of the day. And these are the 5 1/4-inch disc platters that are used in the so-called Winchester
This is what
mini
we're talking
drives.
about here.
Yes, that's a particulate oxide, just as these platters are. These are thin film platters, which is the next generation of platters.
Now, you mentioned, Frank, thick medium here and thin film head technology. Tell us what that is exactly.
All right, the heads are essentially a bent nail with wires wrapped around them. The technology consists in the size of the bent nail. In order to lay down 15,000 bits per inch along the circumference of the platter, the size of the nail, the equivalent quote around the nail, has to be very, very small. Currently, ferrite head products, and currently in the past 8 years, have been made by lapping and grinding and machining of the geometric dimensions of the so-called quote nail, unquote. The semiconductor industry has taught us how to put a computer on a chip using photolithography and deposition techniques, thin film deposition techniques. Therefore, the thin film head technology consists of manufacturing the equivalent of the bent nail, utilizing photolithography to get dimensions that are in the millionths of an inch, and repeatability and bulk mass production.
Is that that's a thin film head over there? Maybe you could show us what that looks like.
Yes. This is the 3680's thin film magnetic recording head arm assembly. There's 4 heads on the end. The top 2 service the bottom surface of the top disc. The bottom 2 service the top surface of the bottom disc. These heads consist of an air-bearing slider, which has a pair of wings or skis, and on the rear, very difficult to see, but can be seen in microphotographs, are thin film elements that have been deposited. These devices are able to record 12.5 million bits for every square inch of disk surface.
Frank, do you feel like you're going to reach any kind of mechanical limitations here at some point, or are you going to be able to just keep getting this dense, more dense, more dense?
Well, we have projected in our strategic plans what the limitations are. There are 3 key measurements in any disk file product. They consist of the number of tracks per inch along the radius of the disk. The second one is the number of bits per inch around the circumference of the disk. And the third key parameter is the product of the two, the tracks per inch times the bits per inch. On the present products that are mass-produced with thin film heads and advanced particulate media, we have 800 tracks per inch, 15,200 bits per inch, and the product comes out 12.5 million bits per square inch. Through additional thin film heads and thin film media that will be making its debut shortly, that areal density will change by a factor of 16 times. We have the principles by which we can increase the areal density by 16 times to in the order of 200 million bits per square inch.
What's the cost factor involved in this thin head technology?
Well, if we look at the recording head, it consists of 2 parts. The air-bearing slider, which is the larger part that you see, and then the magnetic transducer, what I called the bent nail earlier, part that's on the rear. If we compare it to the Winchester ferrite heads of today's mass production in older technologies, we find that the air-bearing slider cost is about the same. The transducer will eventually have a lower cost, just as vacuum tubes cost less than solid-state devices. The factor for product cost 5-6 years from now will be in the order of 3 to 5% less, but not significantly less. However, if you tried to manufacture a ferrite head to perform at the capability of the thin film head, then the cost picture would be overturned.
When we're talking about thin film head technology, that only relates to Winchester's hard disks, or does that have application to floppies?
It has application to all magnetic recording. The thin film materials, which lend themselves so well for magnetic recording, are relatively soft, and therefore they have a wear problem. The rigid disk have the air-bearing sliders, which allow the heads to fly at 13 to 15 millionths of an inch above the surface. Hence, there is no wear. Hence, thin film heads make their debut there first. When the wear problem is resolved, thin film heads will find its way through floppies, tape drives, all magnetic recording.
To try to appreciate that distance, I think you have an analogy about an airplane, don't you, to help us understand
yes,
that?
It's a classic one. The products of 8 years ago, the flying height was 20 millionths of an inch, would be the equivalent of a 747 flying at 590 miles an hour, 1/8 of an inch above the Earth's surface. The products that are exhibited here, flying at 13 microinch, that dimension is closer to 1/16 of an inch above the Earth's surface.
Alan, from your perspective and your end of the business, is this a major factor in what you're doing?
Currently, right now, it's not, because the recording densities that we have that we're required in our products don't need that kind of technology. At some point in the future, we would expect thin film heads to be used in our small, very cost-sensitive products also.
It's interesting to note that this is a 1.2 gigabytes per spindle, which is, if we get back to our original discussion about video discs, this is just about the same size as that video disc, roughly. And there's been a lot of discussion in the industry about how you do some simulation of video discs, and maybe this is part of the answer is in your 1.2 gigabytes per spindle.
Real quickly, we just have very little time left. This is something I thought worth looking at. This is a laser card, which we just got to look at, which apparently has 2 megabytes of information on this. Frank, do you see optical storage devices as replacing in any way magnetic storage devices?
Yes, when one thing occurs. When the erasable, real-time erasable, just as magnetic recording is real-time erasable, optical media makes its debut, then I believe we will see the exponential decay in time of magnetic recording. Optical recording gives us the promise of over 2 billion bits per square inch. The first non-erasable optical devices are in the range of 1/4 billion, that is 250 million to 500 million bits per square inch already.
Frank, I have to interrupt because we're out of time. Frank Sardello of Memorex and Alan Shugart of Seagate, thanks very much for being with us, and I hope you'll join us next week on another edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and sitting in for Gary Kildall this week is Herb Lechner. We're talking about printers on today's program, and I guess most computer users have found that a computer alone really doesn't do you very much good unless you have an output device on which you can save data, graphics, program listings on a good old-fashioned piece of paper. Now, Herb, it seems, though, that printer technology has lagged behind computer technology in general. The printer is still the slowest component in the system. The price really hasn't come down that much, and it's often the first part of the system to break down. Why is that?
I think, Stewart, the answer to that is the fact that there have not been the breakthroughs in the mechanical components of printers that there have in the electronic areas. And I believe that both users and manufacturers alike are well aware of that and are trying to become less dependent upon the purely mechanical functioning of printers and trying to develop electronic controlled components. Examples of which we will have on our show today, the inkjet printer and the laser printer, instead of mechanical impact technologies.
Okay, before we take a look at the latest in printer technology, let's briefly review the history of printer technology.
When Charles Hollerith introduced his census-taking machine in 1890, it had one important task: to collect and tabulate large numbers more efficiently than the humans it replaced. Like other early computers, its electromechanical memory was limited, and printout of stored information was restricted to the final computation. As computers became less mechanical and more electronic, information retrieval became more flexible. Once magnetically encoded onto a reel of tape, data could be changed or erased instantly, and the recording medium used over again. Printed information, or hard copy, was unnecessary as long as data was used only within the functions of the machine. Information gathering became even more perishable when video display terminals became standard, reproducing text, graphics, and even mimicking the physical surroundings of a workplace. But today, while computers may have reduced the need to stockpile written information, a quick look at the typical office reveals that one of the most common peripherals is, ironically, the printer. Popular impact printers like this daisy wheel still operate much like a typewriter, but with fewer moving parts and much greater speed. Although advances in printer technology have not matched the progress made on the electronic side, the trend away from mechanical complexity has brought paper and ink printing to a new level of sophistication. The focus of new research is on non-impact printers, using heat, electricity, phototypesetting, or even lasers that burn characters into the paper.
Later on, we're going to be taking a look at the cutting edge of printer technology, laser printers being developed now by Xerox. First of all, we want to talk, though, about the kinds of printers that are available for most computer users. And with us to do that are two gentlemen from the Diablo printer division of Xerox. We have Steve Ray, who's a systems engineer with Diablo, and Paul Shapiro, who is the manager of product planning. Herb?
Gentlemen, maybe you could get us started by taking the various numbers and different kinds of printers that are available today and sort of categorizing them for us so we know what we're talking about.
Okay, well, most generally there are, you could classify printers as either non-impact or impact technologies, and within each of those you could, I guess, semi-classify them as what kinds of technologies they employ to put marks on paper. For example, there's matrix within impact and inkjet within non-impact. Within that, there's various cost performance ranges, and then, of course, you'd always have to consider the quality of the print, which is spot density.
How does a user try to figure out which printer is right for him? And we've got 3 printers sitting here, and that doesn't even begin to represent the variety out there. How do you make a determination as to what printer a particular user should buy?
Steve?
Well, I think what you'd like to do is, with the explosion of the PCs, the personal computers in the marketplace today, categorize it as if you want to have an impact type printing, very hard copy that's good for letters and mailers or that sort of thing. And then, of course, for a very high speed output, you might want to go into a thermal type technology, which is thermal transfer to plain paper. And then, of course, if you really wanted to go for with all the color output that people have now, you go for a color inkjet, and here we have a Type 3 color inkjet today.
How about, say, the first tier? Say I'm choosing between a dot matrix impact printer and a daisy wheel impact printer. How do I make my determination, say, just choosing between those two?
Well, it depends on the quality of output that you're looking for in a particular product, as well as the kind of speed of output. If I were, for example, looking for fully formed characters, a letter quality output, I would gravitate towards a daisy wheel printer, which tends to give you the best quality possible. If you're looking for a very high-speed type of output with less than letter quality, called correspondence quality or draft quality, a dot matrix printer might be the way to go.
Where does the thermal printer fit into this?
I'd say for very high-speed output, our thermal printer here that we have today runs at 6 pages per minute, typically, which is quite fast compared to, say, a daisy wheel, which would be slower, maybe a page, 2 pages per minute. And then for inkjet, we run even slower, but of course we're working with color in this case.
Maybe we could demonstrate at least the first 2 you have at the top there, Steve, because it'd be interesting to sense the speed comparison you're talking about. Maybe
Sure.
you could fire up your daisy wheel and let's see, number 1, how much noise it makes, and number 2, how fast it goes.
Okay.
And maybe you can talk us through it as you do it.
What we're showing here today is a daisy wheel that's been out in the marketplace for many years. In the early 70s, it was firstly introduced by Diablo Systems, as a matter of fact. What we have is a character print wheel here with 192 fully formed characters on it, so that you can do scientific notation, and we also have other application print wheels for a legal market, or actually even moving into, say, a multi-purpose market where you want to do sort of European-type applications. With one print wheel, we can print 33 Western European languages with never changing that print element, and that is in fully formed character.
We see 2 trends in the daisy wheel printing technology. The first one is to larger numbers of characters per print wheel, and here we have 192. We also see the growth of accessorization. You're actually seeing a electronic double bin feeder. This is a very throughput-oriented kind of trend for the market, to increase the amount of throughput per any amount of time.
Maybe we can look at your thermal now. I think everybody's aware how much noise the daisy wheel makes, which is a factor, I suppose, if you're trying to place it in an office environment.
Sure.
What speed, by the way, did that daisy wheel operate at?
About 40 characters per second is what we can specify for what we call a AAA type text. The thermal printer is much quieter, 55 dBA. As far as cost-wise, it would be more expensive, of course, because you are getting that extra speed out of it.
In the area of cost performance, the thermal transfer machine, the machine that you see printing right here, is it runs at about 6 pages per minute as opposed to 2, and yet the price is only about twice the price of a daisy wheel printer. In terms of spots per inch, the thermal transfer machine is about a little less dense than a daisy wheel, which runs at about 450 spots per inch as opposed to the 200 spots per inch that you see here.
I guess that sort of leads us then into the new technology, the color and the graphics technology. How is the market moving for that kind of a device now?
Now, as graphics become and color becomes a more important part of the PC user, the market tends to be gravitating a great deal towards graphics and color, especially with those processors like the Apple Lisa and that are able to do bitmap graphics, that is, control each and every bit on a tube, each and every bit on a page. The thermal transfer machine, which has a great ability to do graphics as well as the inkjet, as a color graphics, is a natural migration.
Mm-hmm. How do we interface these printers with a computer? Say we have a computer and we want to go about knowing that we can get some of these capabilities, but wanting to be sure that we buy something that where the plug fits.
What we've done at Diablo is we've tried to answer that in what we call all-purpose interfaces, something that you can just take a personal computer, because typically your end user will just want to have something which we call plug and play. You take your personal computer, you take your data cable, and you plug it in. What we've done is we think we've been rather innovative in the way of being able to run parallel or serial machines off of a host processor, so it becomes very, very user-friendly in that case.
We have just a little bit of time left. Sure. Maybe you could fire up your inkjet printer and also tell us how that works.
Sure. What we specify for this, well, what we're saying is a Series C color inkjet is a Type 3 inkjet, which is a drop on demand. That differs from a continuous flow in the fact that we're able to actually, as Paul mentioned, specify where on the paper you want to put the dot, and through an ink reservoir, through a piezoelectric type electronic means, squirt a drop per nozzle onto the paper.
How fast are the squirts?
It goes about 20 characters per second for text. We do have the ability in having 4 colors on here to generate, through doing mixing, to generate 7 colors, and actually 8 if you include white as a color. Very quiet. It's very nice for having it next to a single workstation.
What is the cost factor of the inkjet compared to the others?
The inkjet is slightly less expensive than a fully formed character printer here, and I guess compared to the thermal transfer, which quite frankly has 5 times the throughput or 6 times the throughput of an inkjet, it's about 1/5 the cost. 1/5.
One last question. On the thermal, don't you have some built-in limitations there? You need special paper, you can't do multiple copies, you can't use fan fold and so on?
Actually, that's only partially correct. The thermal is able to use a bond paper here. Depending on the rag content, of course, gives you the greater quality and output. Fan folded is not necessary. You can use, as you can see, we're using cut sheet feeding here, cut sheet paper, and so the nice thing about the thermal transfer, as opposed to the direct thermal, which you're probably familiar with, is that it's able to use plain bond paper, which is a very nice characteristic of this new technology.
Okay, that's a real brief introduction, Steve Ray and Paul Shapiro, and I thank you very much for introducing us to these 3 basic types of printers. And in just a moment, we're going to take a look at the latest in printing technology, laser printing, and that's coming up next.
We have been told that one of the characterizations or categorizations of printers are their speed. To talk about a very fast printer technology, we have with us Dr. John Urbach from Xerox Palo Alto Research Center to talk about laser printers. John, can you tell us in general terms how a laser printer operates?
Well, a laser printer operates in a manner that is somewhat analogous to the way a television system operates. Only in this case, a finely focused beam of light from a laser is scanned across a line. It is turned on and off at a very high rate by what we call a modulator, and this paints out regions of illumination or lack of illumination along the scan line. The scan line can then be repeated over and over again, and some kind of a light-sensitive recording medium is moved along underneath the scan line, thus generating a raster image, a two-dimensional raster image, quite analogous to the kind that we had seen there from the inkjet printer. The difference, however, is that it goes very much faster and at very much higher resolution than this type of inkjet printer.
Typically, how fast in terms of lines or pages is a laser printer?
Yes, we're more comfortable talking about pages than lines because the great flexibility in character size that you have with these printers makes it hard to describe accurately in terms of lines. So in terms of pages, they vary from a high of perhaps 3 pages per second down to on the order of 10 pages per minute. They cover a fairly large range of speed.
Yes. You mentioned flexibility. What do you mean by flexibility in a laser printer?
Well, since you can paint out every possible resolution element on the page, exactly as you can in a television system, you have the ability to create a completely arbitrary map of any type of image information that your computer can generate. Most computers can't generate information in a manner flexible enough to take advantage of the capability of a laser printer. But if the computer can generate the image, then within some very broad limits, the laser printer can generate.
Anything you can compute, you can print, so to speak.
Right.
Well, you are prepared to give us a demonstration of a laser printer today. Would you like to describe what we will be seeing, please?
Yes. Remember the basic principle, which we can see on this figure, is that the light from the laser goes through a modulator which switches it on and off very rapidly, and then through a scanning system of which, in our case, a rotating polygon of this type is the heart. The rotating polygon has a large number of facets, mirrored facets on it, and that is what actually deflects the light to generate the scan line. That scan line is then focused by a fixed optical system onto the photoreceptor. In our case, the photoreceptor is from a conventional xerographic copying machine, and instead of making a copy of some original, that photoreceptor now records the image that has been generated by the computer. Now, in the particular demonstration that we'll see, we have an experimental color laser printer. These are relatively rare, but they are an illustration of the power.
This is not a standard product.
No, there are such products available, but they're not widely used yet.
Okay, now let's go to see the demonstration. Stewart?
This is Doug Curry, systems engineer with Xerox. And Doug, you have a file in memory now of a graphic of a baboon, which we're going to use for demonstration purposes here. I want you to show me what control you have here at the computer terminal over the parameters that we're going to use in printing this out.
Yes, Stewart. When we print a color file, we do so by superimposing 3 separate images of magenta, yellow, and cyan. Now what I've done here is I've brought the magenta layer up onto the display so that we can modify some of the color intensity distributions. Now, for instance, I can take the mouse and point to various places on the baboon and find out what the pixel intensity is at that location. I can then go down to the tone reproduction curve and modify it with the use of the mouse. For instance, if I want a more contrast in my output, I can make a slightly nonlinear function for my drawing. And I can modify it by clicking the mouse button, and then I can show the modified version. And I can flash back and forth to find out whether or not that is what I really want. And what I'm going to do now is to actually print out the 3 separate layers, and then after that I'll print out the final full color image.
This is Tibor Fischli, manager of printer technology at Xerox. And Tibor, explain to me now that we're printing, what's going on inside the printer?
Now the information is coming from the computer, and that video is used to modulate the scanning beam, which in turn lays down the image on the photoreceptor drum, one by one, color by color, and actually the xerographic process does not really know or care where the light is coming for the exposure and initiating the whole process.
And what do we have then coming out of the machine?
Now we have a full color picture of the baboon.
Tibor, that graphic is pretty impressive coming out of this printer. Can you show me now a demonstration of what the device is inside the printer that's doing it?
Yes. This laser printer is identical to the one which was used for the demonstration. I would like to now tell you the major component and describe the optical path. The beam from this helium neon laser is folded and focused into this acousto-optical modulator. The diverging beam from the modulator is folded along the optical path into the polygon, and after reflection from the polygon is coming back through the same element as it folded and focused on the surface of the photoreceptor, which is now here represented by this white screen.
Could you actually show us the laser beam inside here?
Yes, I will spray some Freon. It would make the light path visible. You can see how it's coming out from the laser, going through the modulator, into the folding optics, and into the polygon.
That was a very interesting demonstration, John. Now can you sort of talk to us about the future of laser printing technology? Are there going to be more laser printers? Are they going to come down in price? Will they displace other printer technologies that we've talked about today?
I think, Herb, the answer is yes to all of those questions. There will be more laser printers and they will come down in price. The early laser printers were very fast but also very expensive machines costing hundreds of thousands of dollars. The price is now rapidly coming down, helped in some of the future products and some recently introduced ones by the use of the junction diode laser, this little gadget I have here, which will replace the large helium neon laser and the modulator, reducing both size and cost of future printers. And with this and other refinements, we'll see the price coming down quite rapidly over the next few years.
So naturally you're enthusiastic about the future of this technology and its ability to do the text processing and the graphics processing that we talked about earlier.
Yes, I am, and I also believe that by increasing the resolution, as in this experimental machine, we can also move toward high-resolution graphics and pictorials.
I'm afraid we're out of time for this session of Computer Chronicles. Thank you very much, and we will see you on our session next week.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Well, Gary, it may not look like it, but I'm shopping right now at a place called CompuStore, which I've accessed through the source here, and I'm looking for a video cassette recorder. And what the computer is showing me right now is various machines which are in the CompuStore inventory, and if I want to see details, say, on one particular machine, I can ask it to give me a little more description about that one machine listed as number 1. If I wanted to buy the machine, I could just type in some commands, buy the machine, it would automatically charge my credit card, and so on. What we're talking about today is hard to define, frankly. It's sort of online databases or telecomputing or information utilities. It's hard to describe. One phrase we hear is time sharing. Is this really traditionally what we mean by time sharing?
Well, time sharing is kind of an old term. It's been around for several years, and it's a situation where many people share the use of a large computer system. But personal computers sort of stole away a lot of the customers from time-sharing services because they're less costly and a lot more convenient to use. But personal computers really don't compete very well with large computer systems when it comes to accessing large information bases. So this is where time-sharing systems may make a comeback in the form of information services as accessing through a personal computer or a terminal to a large information base, if it can be cheap enough and convenient enough to use.
Okay, we're going to be looking at some of the major online databases, such as the Source, Dialog, and CompuServe. But in addition to those, there are nearly 2,000 specialized online databases serving a variety of specialized interests.
For many specialized users of databases, the key to a useful and usable system is information selection, the ability to search through massive amounts of data, locate multiple sources and references, and relate them in a number of different ways. In scientific and technical fields, business and medicine, a database search can squeeze an hour or a month's worth of research into a few minutes. In the field of biotechnology called crop genetics, plant genes are manipulated to produce new varieties in which desirable traits from several plants are combined. Because of the extreme complexity and often experimental nature of this research, a worldwide bank of information is a very valuable tool. In this example, a search is initiated through a vast chemical database to find any documents referring to a particular chemical as it affects the reproductive abilities of wheat. The chemical's reference number is listed in a separate database of over 5 million chemicals. When the number is plugged into the document database, it locates studies going back in 5-year increments and displays a summary of each. To characterize a database as an electronic filing cabinet is to underestimate its power. By indexing and cross-referencing the ideas and research of 1,000 minds, the database offers its creative user an organized way to connect and relate ideas. Used to its full potential, it can find solid support for a vague theory and bring even distantly related ideas together.
Joining Gary and me now are our two guests for this first portion of the program, Jay Fitzgerald, who's West Coast Regional Manager for The Source, and Paul Schindler, West Coast Editor for Information Systems News. Gary.
Now, Jay, it looks like all you really need to get at all these data services are a personal computer or a terminal and a modem of some sort. And what does that give you access to out there in the world?
Well, among other things, it will give you access into the Source Telecomputing Corporation's computers. The Source is a very general, broad-based type communications and information retrieval type service. It's a little bit different than Dialog, which we'll see later, in that it doesn't go into such great depth. It applies itself more to current events. We have on the screen right now what we call our main source menu, outlining some of the broader categories which we can go into. The menu is designed as a routing or a navigational system down through to the services that we wanted. We're going to go into item number 6, which is mail and communications, and it's going to take us down one more level of menu. And from here we have options of electronic mail, which is item number 1, chat, which is an interactive use of the system. We can talk to another user who is online presently. Our post system is a bulletin board type system where users can post messages about different topics to other users and get replies back and help with their problems. Participate is a conferencing system, and we have mailgram messages and ecom messages, which are sending messages out to non-source users through either the mailgram system or the U.S. Mail's ecom system.
Okay, Jay, could you go in there now and see if there's mail waiting for you, for example, on this?
If we choose option number 1, we're given another menu, and we can ask number 5 to read our mail.
And it's now going to...
It's checking the mailbox or the account number for any incoming unread mail.
For you.
For me, right.
And theoretically, when it finds something, it'll bring it up on the screen, and you'll be able to read the message waiting for you on the screen.
Right.
We're very reminiscent to the time-sharing days. Let's wait for the response.
Right. So the first thing that it gives us is what we call our scan lines, and it shows us who the document is from, and you'll notice there's a friendly name there matched with it. So you don't even want to know what that is.
No? Okay.
No. This is what we have is user STC053 is on the source right now and wants to know whether he would, if I would like to talk to him.
Tell him no.
Here comes the message.
Now, this isn't what I'd really consider a database service in this particular case. Which of these things, you talk about participate and chat and mail, are any of those things considered, do you consider a database service?
No, our database services are in the form of the UPI Newswire, management content service, which is abstracts through business journals. We also provide Media General service, which is historical information on corporate stocks.
And yet I feel electronic mail, if I may say, is an important adjunct to online database systems because, or information utilities, take that broader term that's starting to come into vogue, because information, useful information to you, is not necessarily limited to information generated by someone you don't know. To take my own personal case, my newspaper has a correspondent in Tokyo. Information from her is very useful to us. In fact, we pay her for it. That's why she's our correspondent. But it's sometimes more useful to me than information that I can get from UPI via the source or the Dow Jones wire via Dow Jones. So I think it's part and parcel. You have to adjust your thinking a little to view it in those terms. But if you have a modem on a computer and belong to a database service, electronic mail, I think, is an important adjunct to it.
Well, in fact, that's one of the things that can't be done really with a personal computer that's isolated. So it really is a service that can't be done locally.
Exactly.
Jay, you have so many services available on something like the source. What do most users use, in fact?
The heaviest usage is in the communications type services. The electronic mail and the post system are the most used out of that group. Following that, people get quite heavily involved in UPI wire, travel information, airline schedules, that type of thing, making reservations.
Post is your bulletin board system?
Post is a bulletin board system, right. There's about 100 categories where I, as a user, say an IBM personal computer user, I can post a message on the system where other IBM users can find it and respond to questions I might have about the system, hardware that I might have for sale, any information I want to offer up about the IBM computer.
Paul, if you take interrupt for just a second, you're talking about the airline services. Can I actually get a ticket written out and sent to me through the...
Well, not directly through the airlines. However, you can tie into our own online travel agency and order your tickets and your hotel reservations and your car reservations.
And you get those verified out at the time that you're dialing?
Right. Depending upon the time constraints that you're under, they will either send you the tickets in the mail or you can pick them up at the airport. So you can take your travel plans from beginning to end through the system.
Paul, you are a user of the source in addition to being a correspondent in this field. There are, frankly, lots of complaints that users of things like the source and CompuServe have about response time and complicated different commands depending on what part of it you're in. What are your perceptions as a user?
Well, you certainly hit the nail right on the head. The most fertile area for development in all online database services is to make the interface easier. Personal computers help a great deal in this. You were asking me earlier about my source ID. Now, it turns out that to make life easier for me, I have programmed my ID and password into my personal computer. I push one button, and it does all that. And it takes me right into Mail, which is the service I use most of the time. That's it. I also use 2 or 3 other services, CompuServe and Dow Jones. And the Dow Jones ID is 12 digits. I do happen to have it memorized, but why should I bother? That's an advantage that personal computers have, which make online services easier to use than if you had a dumb terminal. Still, when I want to know about the computer industry, every Monday morning I call in, check the headlines on Dow Jones to make sure I should know what I'm working on that week for my newspaper. It's period I/EDP01. Friendly, that isn't. And a lot of work is being done in these areas. There is a great deal of work left to do. Plus the response time problem. Unlike poverty, response time is a problem that does respond to throwing money at it, however. And it becomes then a cost-benefit question. The companies like Dialog and The Source have worked very hard, I think, perceptibly hard, and CompuServe, have worked very hard to increase the amount of equipment on their end of the process so that the response time is reasonable on our end as users. But there comes a point, peak load of every day, where you just can't meet it. And you probably pretty well know when the peak load times are. In fact, it would probably be useful to people to know. You were telling me earlier what the bad times of day are to try to call into the system. Of course, it varies by time zone.
Yeah, the heaviest usage tends to be in what we call our non-prime time, which begins on the East Coast it begins straight across the country at 6 p.m.
Eastern.
But Eastern time, right. In California, in this particular area, your toughest times on the Source, or your slowest times, are going to be between 6 and 9 p.m. Okay, it's 6 o'clock here. We have 9 o'clock on the East Coast. So we have people at the end of the non-prime time there and the beginning of the non-prime time here. So we have virtually the entire country working in their nighttime, their home hour, their leisure hour on the system. So it will slow down just a little bit.
Okay, Jay, we've been talking now about general information utilities, the Source, CompuServe, Dow Jones, and things like that. In fact, the oldest and one of the largest online databases is Dialog, and we'll take a look at Dialog. That's coming up in just a moment. Joining us now is Dr. Roger Summit. Roger is president of Dialog Information Services of Palo Alto. Roger, before we get into a demo of Dialog, just briefly tell me what kind of service it is.
Well, we're an interactive computer-based online information retrieval service, and our objective is to store on the computer basically all of the information that's been published in the last 10 years or so. We've principally been an institutional service serving librarians and information specialists in major companies around the world. The advent of the personal computer has brought more end-user use, as we call it, into using the service directly for personal interests and personal problems.
Give us a demonstration of how you would use Dialog.
Sure. A controversial issue recently has been Laetril and the fact that it contains cyanide and possible damage from that. I will go into the National Library of Medicine database called Medline, which indexes some 3,000 journals and contains 4 million abstracts, to see what it has on Laetril and cyanide. I've already logged into the database, so now I can just tell the computer to search out the words that I'm interested in. So I'll say select. Laetril and cyanide. It'll go through these 4 million items and pull out those that are concerned with these two topics together. And I see I wind up with 16 items. So let's type out the first one. And just say type 1, and it'll pull up the first of these 16 items. It says acute cyanide poisoning from Laetril ingestion. Well, that would be an interesting article to me if I had this concern. I can press another button here and order a copy of the source document itself if I wish to. I can pull up the second item, and again, it contains cyanide intoxication from Laetrile, and I can order items like this, or I can print the entire 16 offline on the computer in Palo Alto and have them mailed to me.
Roger, what are some of the different databases that are available?
Well, we have databases in virtually every area of business, of medicine, of engineering, of science, of technology, and directories. We have things like Who's Who, Chemical Abstracts, Engineering Index.
And how up to date are these? Is someone really watching each database consistently to make sure they're up to date?
Yes, well, the professional societies collect literature that they send to us on tape. We update the databases daily, weekly, and in some cases monthly, but it's always quite up to date.
One of the things that we talked about earlier was the cost and convenience of personal computers, and just whether these large information services can be as cost effective or as convenient. And one of the things you worked with here is what we'd, I guess, call a query language, the interface to the user. How free is that, free form is that query language that you have?
Well, it's fairly free form. We're basically describing our interest using and/or and not logic with keywords that we put into the computer. In terms of the personal computer, one thing to think of is that dialogue is a peripheral of some 140 gigabytes to your personal computer at the end of a telephone line.
Okay, and we talked about cost here. What do you think the cost would be, say, for this particular query that we just made?
Well, I can just do an end here, and it'll tell me that this would be $4.21. Now, we haven't been searching very tight. We've been sitting here and talking, so if I were to actually do this, it would probably be substantially cheaper than that.
So if we were doing something with, let's say, a homework exercise, maybe it might cost $10 to...
Well, it might cost $2. It might cost $4 or $5. We have an after-hours service called Knowledge Index that takes our principal databases and offers those at 40 cents a minute. So it's even cheaper than the daytime service.
Where is the future of these kinds of online databases going? I mean, will we ever get to the point where we could, for instance, have graphics come up on this terminal?
I think the first direction this is going is towards source documents, toward the full text of the articles themselves. We have a major project underway to put on all of the source documents behind Magazine Index, which is a popular literature database that we have. We have the full text of the Harvard Business Review online. We have the UPI Newswire coming in online. So there's a movement toward full text so that you don't have to order these by mail.
It seems like there might be an area of competition, say, for again, for small computers, and that would be, say, in databases that don't really change very much, and using, say, video disks where you have maybe a gigabyte of storage, up to a gigabyte of storage on a single disk. And do you see any competition or any future directions of the use of video disks to supplant some of this?
I think perhaps in specialized areas where there's intense interest. The coverage here is so comprehensive and the use density is so low that even with video disks on a personal computer, it's more cost effective to store centrally and access as you need.
Jay, talking about the source again, do you have problems, or maybe, Roger, you have the same problem, in not being able to keep up with the demand? I know one of the complaints about some of these services are slow reaction time and slow to get on. Is there a technical limitation to your ability to handle the demand?
Well, certainly there's a technical limitation to any computers that any outfit uses to provide this type of service. We have gotten ourselves ramped up to such a speed now where we can anticipate the demand, we can see what's happening down the road, and we can keep ahead of the demand for the system.
Gary mentioned also video disc. What about cable? We hear an awful lot of talk about video, text, and cable is the real technology that will bring these kinds of services into the average home. Is there sort of competition between cable-delivered services and telephone-delivered services like yours?
Well, at this point we don't see that much, although I'm sure it's going to begin to play a more and more important role as time goes on, as more and more cable systems are installed throughout the country. It seems at this point, however, the telephone systems that we're using are satisfying the needs of the customers.
But that's true probably for the area in which you have a network interface or an interface that you can call locally. But I know that, say, in the Monterey area where I live, that the cost of the long-distance charges is very high when you're accessing services like this.
Well, the primary networks that I know the source uses, and I believe Dialog uses, are expanding out weekly with new nodes in more and more remote locations. Of course, as computers spread, these nodes will be used and expanded on.
We have about a minute left, Roger. One other question. Would it be possible to have, say, a merger of things like database management software and something like dialogue, a form of perhaps artificial intelligence where the program itself could say, I need this piece of information which I don't have in my file, and I'm going to call up dialogue or the source and get it?
That's a very good point. And I think a second direction that these systems are moving is in the direction of artificial intelligence. We're looking at particular specialized areas, for instance, a person's dossier, a dossier on a person, a dossier on a product, or a dossier on a company. Very common kinds of things can be done without any explicit input of commands.
Okay, gentlemen, we're out of time. Thanks very much for showing us both the source and dialogue. It's been very fascinating. And thank you for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and sitting in this week for Gary Kildall is Herb Lechner of SRI. Herb, what we have up on our Apple computer here today is the Koala Micro Illustrator and my handy Koala pad here. And we see a menu of some artists' choices, and if I can, I'm going to try to communicate to you here in some computer graphics. And so far, it's working. If I get your name right. There we go. And I can even make it a little more sexy than that. We'll give you a little brighter background color so it's a kind of more upbeat message. Herb, computer graphics is the subject of our show today, and computer graphics, in fact, involves more than just this little thing we're playing with or even video games, which some people associate with computer graphics. There are some pretty serious applications, aren't there?
Very much so, Stewart. Computer fine art hangs in galleries right alongside of traditional art. And, of course, in the commercial area, computers aid animators and play a very important role in TV advertising today. And, of course, the basic building blocks of computer art, that is, the graphics subsystems, play a role not only in art, but in related activities such as computer-aided design and other graphic applications.
Okay, on today's program, we'll be looking at one of the newest computer graphic systems called Iris. We'll look at a computer art system called the Paint Box, and we'll meet two computer artists, real people, that is. First, let's take a look at the kind of computer art being done now on mainframe computers.
Since the first light pen and graphics displays of the 1950s, computer-assisted artwork has been associated with beautiful, if mathematical, images of symmetry and abstraction. But the applications today extend far beyond repetitive patterns. With enough computing power, computer graphics can extend an artist's reach to cover the height and length of a wall, or compress the time it takes to animate something from a month to an hour. Using a digitizing tablet, MIT artist Ron McNeil chooses from a palette of colors and pre-programmed images to create a collage that exists only in the computer's memory. Before ever seeing a canvas, it undergoes some dramatic transformations. Starting with materials from different sources like photographs or three-dimensional objects, the composite can be manipulated to change in color, size, or geometric aspect. The screen-sized image shown here is only an intermediate step toward the final hard copy, a painting that is 14 feet high and 48 feet long. Like a colossal paintbrush with a memory, the giant XY plotter magnifies the completed artwork into a wall-sized mural, strip by strip and color by color. As an ingenious collaboration between digital imagery and robotics, the giant plotter is unique. But the special talents of computer graphics are increasingly used in another area of the visual arts, animation. To an art form that was once the near-exclusive province of film, computers offer a much faster method of animating images. Again, through a digitizing tablet, an artist can create a figure by drawing in just enough points to determine its size and rough shape. For a symmetrical object, all the computer needs is the outline of one side, which is then shaped into a fluid form, regenerated, and filled in with color and three-dimensional detail. The software calculates and reproduces the characteristics of light and shadow that the object would possess in 3D. Finally, to animate the drawing, the artist specifies some key camera positions from which the object is viewed in space. The program then fills in the missing frames that simulate movement between those points. Making a drawing come to life is the most tedious part of an animator's job. Fortunately, it is also readily adaptable to digital processing. The systems used to produce these images are not designed to replace artists, but to assist them. And with enough human talent, they can mimic reality in detail or expand it to the fringes of our imagination.
Our guests around the table now are Michael Arendt. Michael's a computer artist and design director with Aaron Marcus & Associates in Berkeley. And next to Michael is Don McKinney, vice president with Silicon Graphics here in Mountain View in the Silicon Valley. Herb?
Michael, in your consultant role, you use all kinds of computers graphics equipment. You have a setup here today for us. Do you want to tell us a little bit about this equipment and what you're going to do?
Well, this is an 8-bit microcomputer, which is very similar to the type of computers that most of the viewers would use in their home, for instance, to play games. And we use these type of systems, for instance, to create imagery for digital directories and education software and such like that.
And what exactly do you show us how you use this system here?
Okay, well, the traditional artist tool is a brush. This is an electronic artist tool, and it's using a graphics tablet, which you see here, and an electronic pen. And with this, I can paint images and put graphics, combine graphics, photographic images, and text on the screen. I can very quickly load in an image here, for instance, to show you a raw photographic image that was input using a video digitizer, which is simply a video camera. And once I get the image into the computer...
That's an unfortunate example, by the way, Michael, but we'll go with it.
Once I get the image into the computer, then I can use this graphics tablet to take away parts of the image that I don't want. As you can see here, it's loading in this microcomputer.
What do you mean by parts of the images you don't want, Michael?
Well, for instance, maybe I want to take out a background and put in another background, or I want to take out areas where I would like to put in other types of things like text and things like that, which I'll demonstrate here. I'll show you, for instance, I'm showing you the build of an image.
Don, while Michael is working here a second, there are great memory demands, aren't there, in doing graphics? How do you accomplish that with just a small microcomputer?
Well, and really it depends on the exact amount of memory. The memory requirements really are the requirements of the amount of color that you have, and also what we call the resolution of the screen. So the higher and smoother the image appears, the more memory is required. In the case of what you'll see later today, we have approximately 3 million bytes of memory just used to store an image in real time.
Okay, Michael, I'm sorry, you're ready.
Okay, now I've taken away the background, and now I've put in a cartoon bubble here. And then I can load in another image here to show you other things that I've...
So you're loading images you've pre-prepared?
Yes, I pre-prepared these images.
How did you go about getting the old background out? Did you trace around it or something?
Yes, you can block it out with a function on the tablet using a black background blockout. And then so, as you can see, the image is slowly building here, and then I'll show you the final image that I've created. And then I can show you how you can manipulate that image other ways also.
What is the tablet you're using? Tell me how that works.
Well, it works by addressing various areas in the computer memory, and essentially it's giving it a command either to put color onto the screen or putting geometric figures on the screen like circles or grids. And you can also put text on the screen, as you see here. Here's the final image I've built, which has a combination of a photographic image. It has graphics in the background, and it has text also combined with those graphics. And I've been able to do that with this tablet. I can also, for instance, do things like turn the image upside down, or I can also flip-flop the image this way here, and then I could bring it back up. I can also invert the colors, for instance, so I can make it negative or make them in new colors. And then there are other functions on the tablet, too, that you can do. For instance, you can create textures with what's called electronic brushes and things like that.
Okay, well, we're moving our way up from the simple koala pad to something more sophisticated, and Don, that gets us into your area. And I think you have your iris system set up over in the other part of the studio here, so let's take a walk over and see what iris does. Don, how does your iris system here differ from what we've seen up until now?
Up until now, we've really been looking at microcomputers, really personal computers, and this is really a different class of machine. The biggest difference, though, that separates us out is the idea of us using custom chips developed by Silicon Graphics for our own use to do these three-dimensional calculations. This example here is a Rubik's Cube, and what's going on here is we're calculating the location of all the endpoints of all the faces so that we can rotate those in 3D and do all the hidden surface removals all in a very real-time mode. Why don't we go on to the next demonstration here to give an idea of how our machine can be used.
What kind of machine, what's the hardware we're using here, Don?
This is a terminal configuration that has a little floppy disk on top, but the basic computer that we're using here is a Motorola 68000, often used in some of the other reasonably high-performance microcomputers. The other chips that we actually have are called what we call our geometry engine, and it's a high-speed three-dimensional floating point calculation unit that runs at 6.5 million floating point operations per second. This speed we are planning to enhance to over 10 million floating point operations just in a few minutes.
What's the demo here?
This one is a series of pictures of a series of buildings where we're doing a calculation in real time. So I'm going to angle up away from the buildings, and I'm going to zoom back away. And as I'm zooming away, you can see this building going further and further back. You can see that the light sourcing is done so that the certain surfaces that are closer to the rays of sun are visible. Now what I'll do is I'll add buildings in 3D. So you can see as I move around the space, I can actually get the full panoramic effect of this block, or I can even zoom in. So I can go through areas. Let's skip on to the next. The next is...
before we get to that, Don, what would the application be, say, of something like this architectural thing you just showed me?
We have several customers that are in the AE&C market, the architectural engineering and construction business, and we have several local companies that are doing piping diagrams and piping calculations for intersections of pipes in, say, nuclear plants. Another case might be for an architectural firm that would add software to our product and sell it to the end-user architectural people for doing building design, for doing construction of faces, landscape architectural design, even an interior decorating, use it to place desks and furniture within a given room.
Okay, tell me about this demo now.
Okay, this one is, again, it's a three-dimensional object. It's a rendering of a robot. So the first thing I'm going to do here is get it a little bit larger. And then what I'll do is I'll tip it over so you can actually look at this robot arm from the top. And I'll spin the arm around. And now as I'm closer, let me tilt it back up so you can see it from the front view. And in this case, what I'm doing is I have a one button. By touching it, I can cause the shoulder to move the entire arm up and down, or I can cause another button can cause the forearm to move up and down, and then the last series I can cause the pinchers to actually open and close, or to even grip something. An application for this might be an auto assembly plant where you're grabbing a metal part to be welded into another area.
Okay, we have time maybe for one more, and I'll load your disk for you.
Okay, this is another sophisticated 3D application where we're actually computing the location of an aircraft in flight. So the first thing that will happen is we'll be looking out the front of the airplane at a building or a hangar, and then we're going to taxi up the runway, make a right turn, taxi down the runway, make another right turn, and take off.
Okay, and you talked about the speed of about 6.5 million. What was the units?
Floating point computations per second. Most computers are measured in MIPS, and some are measured in what's called flops. And the difference being that it's either an integer mathematics or it's a floating point mathematics.
Okay, let's see what this is.
Okay, so what I'm doing now is I'm sitting at the runway. I'm going to accelerate the plane as it goes toward the building. I'm turning the rudder now using the mouse and locking in on a direction. And then I'm going to sweep around and get back onto the main runway. And now, as I'll accelerate the plane still further, raise the flaps, just like in a normal takeoff, I can switch between the viewing angle of the pilot looking out the front of the window to the viewing angle of the from the tower, and now I'm off the ground.
Done. That's very impressive. Okay, if you watch television, you are familiar with computer graphics. Some of the effects you see on the Computer Chronicles are, in fact, generated by computer. Well, we'll see a very sophisticated video computer graphics system in just a minute. Joining us now is Ann Chase, who is a freelance computer artist, and Kevin Prince. Kevin is engineering manager at MCI Quantel. Now, Ann, you played around with a picture of me at the break just before we got to the segment. That was animation, I take it. And how do you do that with this system?
Well, basically, I can find that animation stack in the library and show you how I set it up. Just by tapping. It's cell by cell is how it's set up. And here you can see that I just drew the tie and rolled it up on your neck.
So you captured the real picture and then drew on top of the real picture and then just did the cell animation.
Right, just cycled the animation in.
Does this machine do all that with just commands that you give it?
Yeah, basically just your artistic ability and what you can do using the capabilities of the machine.
Kevin, what are the capabilities of the machine? What kind of hardware, software is supporting this system?
Well, hardware-wise, we're based around the 68,000 processor, as the previous people were talking about. But we've got a lot of dedicated hardware to do all the fast wipes, the actual painting and drawing in the system, and changing all the brush sizes, etc. It's taken us some time to develop that, but associated with that is, probably more importantly, is the actual software interaction with the user. Everything you see is obviously a very large operating system that we've had to divide for the system.
And could you show us, you mentioned drawing and brush strokes, some of the freehand capability of the system?
Basically what I'll do here is just wipe the canvas, and you can see that I'm in a paint mode. And this shows me my brush size, and I'll take a white here, and you can see that I can just paint right on the screen. I can choose a different color just by tapping and say a larger brush size and paint over the top of that. Then I can go back and choose that mixed color right off the image and store it to use later.
Now, this is obviously much finer drawing, greater resolution than some of the earlier things we saw at the beginning of the program. That's a function of what, Kevin?
That's basically the way we do our store manipulation, the way we actually store the picture. We have various methods of mapping the image that we're actually trying to work with into the store. Very different to individual pixel operations, which the other machines will be working with.
And Paintbox is, in fact, in use right now in television graphics. How is it being used?
Well, most of the networks have actually got several of these systems, and they very often use the machine for their news production and practically every night you will see some form of over-the-shoulder shot that's probably been generated on the paint box. But hopefully it's so good you would never notice.
Now, this system gives you the capability of mixing that which is artistically drawn with that which is real-life photograph sort of a thing. How is that done?
Well, actually, I can just go to the live source, and you can see that right now we're taking in a live video source of what we're doing, and at any time I won't even look at myself. Let's just tap something down and see what we have here. There we have me. And I can go ahead and manipulate this right now.
You have just captured a still frame from this live coverage of what you're doing right now, and now you can paint with it.
Right, or I could, let's say I'd like to create a stencil. And just very quickly, I can go in here with a stencil medium and just outline something and fill it.
And why are you filling that now?
What I'm going to do is a cut and paste technique. This is a stencil medium that's laid over the image. What I'll do is...
This is the word processing of art. Cut and paste.
That's it, yes. And then I'll just paste it up.
At this point we're taking a portion of that image and we've now got, as you can see, two images.
There we are.
Twins.
I think that's a vast improvement.
That's right. That's rather incredible. And you seem to have a lot of fun doing this. Is there is there resistance to an artist, or shall we say a pure artist who's used to dealing in brushes and paints, getting comfortable with using this technology?
Maybe at first it's a little difficult to use the menu, to learn to think and actually read at the same time while you're drawing. But once you've worked with the system for a short period of time, it's just like second nature. Very simple to use, set up in artist terms.
It's clear how valuable this would be to a television media. What about the area of fine art? And is computer art catching on there too, or growing?
Definitely, definitely. It's the wave of the future. That's what's going to be happening in art in a couple of years. In fact, it already is.
Should brush manufacturers worry?
No, no.
They're not in trouble yet.
Not yet.
Kevin, we have about a minute left. How far can you go with this technology? Will we get to the point where you could have, where we could be replaced by animated people and sync it up with words?
I sincerely hope not. The way I see it at the moment is that we're providing the means by which an artist can extend their capabilities. We can turn a reasonable artist into a good one, and an extremely good one into a superb artist. All we're doing is allowing them to create their artwork in a much shorter space of time, and in the medium in which it's required.
Well, that's fascinating. And you don't exist anymore on that picture, Kevin, but we know you're here. We're all out of time. Thanks so much for being with us. Thank you for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Gary, what we have up on the computer right now, it's actually a game called Epidemic by Strategic Simulations, but more importantly, it's an example of how you use a computer to choose among alternatives, make a decision, establish a complex strategy for solving a problem. The problem in this case is a worldwide epidemic caused by viruses coming in from outer space. What we see here on the first screen is a view of the world, our first bit of information. It shows us the different regions of the world. For instance, region 7, which is in Western Europe, it shows us we have a 2.5 level epidemic there. The arrows show us whether it's getting worse, better, staying the same. We have a projection in days. In 7 days, it'll get really serious in that country. Whether or not any remedies are being applied there, what the success or failure rate of those remedies are, and how many people have died in that particular country. We see, say, 16 million people, it shows us have already died in Western Europe. I can go to a next screen now, and this is a satellite view of the world, as you can see, and we'll be tracking right now these meteorites that are coming in from space carrying the virus.
There's a meteorite here coming in over Africa.
Exactly. Mm-hmm. And we now have to decide whether or not to use missile launchers to try to intercept these things, or whether we should just go ahead and try to solve the epidemics on the ground. And I'm going to have to wait for a second till it tracks this very slow-moving meteorite right there. Now we can go to a third screen, and as you can see, get even more information. This is another status report on the world, and those countries in which there are these dotted liney patterns means there's a problem. We can see Western Europe, in fact, has a problem. So we can go inside Western Europe and get even more information about what's going on, and for the first time start to look at the choices we have, the decisions we have to make in terms of trying to attack this problem. We see we have a total of 12 different remedies we could apply to this situation to try to solve the problem. And the more information I can get is to actually apply one of these remedies. Say in this case Alpha 2, which is using a vaccine in that particular case.
I noticed also that it was showing you the percentage probability that a certain remedy would actually help. So this is where the computer system is
right,
actually
and also it's
out.
showing me a projection as to the percentage of reduction I would get from using that particular remedy. Now we can go back to our worldview again and see what happened when we tried that vaccination in Western Europe, whether it worked, whether it didn't work, and that helps us make the next decision. Now, this is just a game, Gary, but as I say, it's a good example of how the computer helps me make decisions, choose from alternatives. What we're talking about more or less is something called computer-aided decision-making, I suppose, or decision support systems, and like some of these other things we've talked about, the first trouble is trying to define what it is we are talking about. How would you define a decision support system?
Well, I think a decision support system is a catch-all phrase for a lot of different concepts. But as we've seen here, this is an example of the computer system that's helping say a manager or a decision maker with strategies, long-term strategies, and giving information about that will help, sort of an able assistant in many cases. Now, the underlying technology might be, say, expert systems, relational databases, and even spreadsheets as a part of the tools that would be used in decision support. But it's a new area, and I think that it's going to be very interesting to see what our experts tell us about this.
Okay, we're actually going to be using a decision support system to make some real business decisions later on in the program. First, let's go out and see how computer-aided decision-making is being used right now.
Decision support systems encompass a broad range of analytical tools, from forecasting programs that calculate trends and predict outcomes to expert systems that can draw conclusions and make their own decisions. Whether or not decision aids require some degree of artificial intelligence, they are presently in routine use, having proven their efficiency and accuracy in a number of applications. At a major American railroad, decision support systems were designed in-house to assist in long-term financial and operations planning. Based on forecasts of future demand, the system reviews records of train capacities, labor costs, taxes, fuel costs, and revenues to predict the financial impact of alternative strategies. The potential risks and benefits of various models can be demonstrated graphically. An early system called Prospector analyzes the mineral content of geological formations and recommends drilling sites. Containing many of the features associated with artificial intelligence, Prospector asks for information on rock types, ground appearance, and rock chemistry. The user responds with a number from +5 to -5 on a scale of probability. Prospector draws conclusions based on these probabilities and makes its own recommendations. The system can also carry on a dialogue with its user, who can question the program's interim choices as it progresses. Unlike Prospector, the most common types of decision support systems require known facts rather than probabilities, and they cannot respond to queries about how decisions are reached. But future research is likely to narrow the gap between programs that lay the groundwork for decisions and programs that can make the decisions.
Joining us now is Mike Thoma. Mike is Vice President of Management Decision Systems of Boston, Massachusetts. And next to Mike is Steve Weil. Steve is Vice President with Intelligence of Menlo Park here in California. Gary?
Steve, I guess the concept of a decision support system is a relatively new idea, at least a commercial application. Can you give us some idea of how decision support systems are actually used?
Yeah. Well, we actually specialize in decision support systems that are sometimes called knowledge-based or expert systems that try to bring the actual judgment of an expert to the desktop of a manager or a business professional in the course of making a particular kind of decision. For example, we're working right now on a system that will help commercial lending officers at banks make decisions about small companies and their creditworthiness. So we'll actually try to capture the type of industry knowledge that a lender who had been lending for a long time to the restaurant business or some other business would bring in analyzing the financial statements and management experience of a restaurateur in deciding whether or not they're worthy for a loan that they're applying for.
Mike, does a decision support system have to be the expert system like Steve was describing?
No. Decision support systems don't need to be an expert system like Steve is deciding. I've related a lot of times when people have asked me that question, a story that happened with my father, who was 78, a consultant. I said, Dad, I'd like you to sell you a decision support system. He said, I don't need a decision support system. I make the decisions. You give me an alternative evaluation system, I'm interested, but otherwise, forget it. So I think that the requirement of adding on an expert system is like hiring a consultant, and a decision support system can be used as a very well-trained assistant who's going to carry out the analysis that I direct.
And it provides you with a lot of high-level information as a result of that.
It'll provide me with a lot of high-level information and analyses and maybe, hopefully, even more questions.
Is interactivity a key element of a decision support system? I mean, does the system have to respond uniquely to the questioner?
My own feeling is that the decision support systems really do have to be interactive. And the reason is that you're in a decision-making process, and it's very close to an innovation process, which is you have an idea, you'd like some feedback. And to operate in a non-interactive mode would be to say, gee, I've had an idea, what do you think about it? Send it through the mail. 13 weeks later, you get an answer, no. I forgot what I said, I forgot what the information was, and I haven't been able to do it. So it's interactivity and responsiveness to an idea that generates another one.
So this is typically going to be then connected to a larger computer system where there's some sort of a database that gives you the facts and figures that you're going to try to put together then.
You certainly want to be operating in an interactive environment, and I think and you certainly want to be connected to a computer, whether it's big or not. I think it really depends on the problem.
Right. Steve, do your systems depend on a mainframe, in fact?
Yes, the systems we're initially developing will depend on a mainframe, though given the direction that personal computers are going these days, I expect that within a few years, at most, our systems will in fact run on future personal computers. On this element, by the way, of interactivity, we are so concerned about that that we have spent a lot of time ensuring that our systems provide full explanation of how they came to the conclusions they came to. We think that managers and professionals do not have the ability to point at the computer and say, the computer told me to make that loan, now it's too bad that the company went bust or whatever. We think that really our products have to work as a staff assistant in the same way that a good staff assistant would explain how they came to a conclusion. They need to give full explanation of their reasoning.
Mike, you have your company's system up here, and the hypothetical we're creating here is suppose the Computer Chronicles show would like to buy a software company, okay, and we want to use your system to help us make that decision. And we initially, I think, identified, 62 software companies that were out there. Now, how would you use this system to give me the information we needed to make that decision?
Okay, what we have here is a database of Standard & Poor's CompuStat data in a product that we market called Express Easy Scan. And as you suggested, we've zeroed in on the software marketplace. We'll pick it up here and let's see what publicly held companies are going to show up that are in our 62 consideration set.
So what again are you asking for now, Mike?
Are we interested in seeing those companies
yes,
now? Let's
yes.
just take a brief look at those 62 companies, which will just roll right through here. They're in any random order. They happen to be by the ticker symbol, so it would be like scanning through the San Francisco Chronicle or whatever through the pages at the back and saying, gee, these are the companies that happen to be in the software business. And my job right now is to zero in on those that I think are more interesting. And my first cut, now that I see that there's 62 and my decision isn't simple, I'd like some help in going a little farther. So one of the things that I'm interested in is to be able to say, I like a really high growth company. So I'd like to screen on a company a little bit farther, and so rather than just taking those 62 that are right there, I'd like to use some data that's in the database to help me with that. And so EasyScan is asking me which screening criteria do I want. I'm into growth, and I'd like growth greater than, let's say, 30% sales growth. Let's say it's over the, ending up in 1982, since some of them may have different time periods that are sitting in there.
So you're asking for a subset of those 62 which have a growth rate of 30% or more over the past 5-year period up to 1982.
Compound growth rate. So we've seen that the EasyScan has given us 12 companies are now in consideration. I'm curious as to who they are. That might give me a hint. But before looking at them, I might want to rank them a different way, and that might give me some more information rather than just the raw data. So I'll ask ask EasyScan to jump over and move into a ranking mode. Yeah, I think I will rank them. I can operate in one finger mode and just hit 1. And the sorting criteria will be on, well, in addition to growth, I'm interested in profitability, so like my president, I'll ask for margins higher, preferably. And the system is smart enough to rank numeric data from high to low, and the ranking is complete. So what I'd like to do now is just take a quick look at those. Why don't I show those, and
so we would now see the 12 companies which the computer has picked in the ranking you've asked it to do.
Right, which is on from high to low and in terms of after-tax.
And here they are.
Right. So these first two look pretty good. I can specify those 2 ticker symbols, or I can keep it, if I didn't want to see all of those, I could do it by attribute again, which is to just rank them and keep the...
Okay, could we get to see a graphic comparison of the top 2 ranking companies?
You'd like the number to keep is 2? You ask, we respond. No problem. All right. 2 companies are in consideration. So what I'd like to do now, I'm done with my ranking. I'd like to graph. For some of the people in the audience are interested in bars and venture capitalists. That's where they're found a lot. And how about the last 5 years?
Okay, last 5 years.
No problem. So.
And it's putting together the graph right now?
Right. So it's back there thinking away. And preparing a graph on those 2 companies, which I've promptly forgotten. Selecting out the last 5 years. It asked me if I want to save this for later on. I said, no, let's move right ahead. And this is operating over a fairly low-speed line. If you were plugged into your own computer, it would be a little bit faster.
Okay, you are plugged into your company's mainframe somewhere else.
Right, it's going through a public network at 1200 baud. I happen to operate at 4000 in my office, or the one I'm plugged into, the little local machine that we have, it's 96.
And there we are.
So the decision is yours.
Okay. Now, assuming we want to go ahead and negotiate with one of these 2 companies to acquire them, we'd want to develop a kind of negotiating strategy. Well, that gets to our next decision support system we'll be looking at in just a moment. Joining us now is Jim Chapman. Jim is Vice President with Human Edge Software of Palo Alto, California. Jim, you have another example of a decision support system here, a product you have called Sales Edge. Tell us what that is.
Yes, Stewart. Somewhat different than the other packages that have been shown earlier. This package works on the IBM PC, and it's for your personal computer. It's to give you a step-by-step strategy report in such areas as sales, negotiation, and management. The particular product that I brought here is the Sales Edge, and I've loaded in 81 questions about the salesman himself, something about his characteristics, his attitudes towards sales, and generally we get a snapshot view as we complete these items of who the salesman is and how they're likely to think.
Let's assume Gary's the salesman here and
Okay.
complete your profile.
I was rejected as an encyclopedia salesman right out of high school. So.
The item that's up here now, Gary, you have the opportunity to either agree or disagree. It describes you. Okay. Sometimes a sales call makes me nervous.
Always makes me nervous.
Agreed. I like the freedom to travel a sales job gives me.
Mm-hmm.
I enjoy swapping stories with customers.
That's a lot of fun, sure.
I am sensitive to criticism from
Don't like
customers.
criticism. Yeah.
There you go. I enjoy putting one over on a customer.
Well, I'll agree with that one.
There goes your public interest. I like talking at company meetings.
Okay.
Okay, we've completed that section, and again, we are going to go ahead and store that information simply by putting it out on the diskette.
Okay, again, that was just a small sample of the normal dialogue that would take place.
Exactly. We're at the main menu now, and we won't look at the instructions. We've already completed the assessing yourself. Let's go ahead and take a look at a customer I've already loaded in here. And we'll bring up the customer profile by simply putting in the name of the file name. File name is Monroe. That's logged in. And what we can take a look at here is a series of adjectives that we've already logged in ahead of time that either we agree or disagree describe that particular customer. For example, talkative, we disagreed. Apprehensive, we agreed to. Now what we can do is go ahead and move on to see the actual report itself. And we'll bring the report up on the screen here in a second.
So we're now going to ask for the software's version of what strategy to take in selling this customer who's
exactly
been profiled.
What's real interesting about this is, of course, you can use it every time you're going to work for the second time with a particular customer. You get a feel for what he's like, and you're able to put that information in to the computer so that you can get this strategy. And it will tell you where your strengths are, where your weaknesses are, and where you're able to work more effectively with them.
Jim, how successful has this been in actually a sales situation?
It's actually,
that out?
Yeah, it's actually very successful. I've used it myself, and so has a number of customers across the country in beta testing, and we modified it so that it would work more appropriately. And what we're getting back from customers, over 1,000 of them across the country now, is that it is very useful. And just planning a strategy before you do anything.
Jim, while we're waiting for it to get its information together, is it superficial in a way? I mean, can you really come up with a meaningful, you're going to make a business decision based on 86 kind of quick yes and no questions?
I think you can, and I'll tell you the reason why. It's actually a cross-fertilization of two areas of research, and we're looking at the research when we're taking and putting together the strategy itself. The research is on personality and also in the application that we're talking about here in sales. For example, as we roll through here, we saw the what to expect section. We'll see at the very end the closing strategies. We're going to select the most appropriate closing strategy for a particular customer based on how they're likely to think and how they're likely to close a sale.
I noticed that in the report that this goes back to Steve's comment earlier that the program does make doesn't analyze the situation, tells you why it's making certain recommendations, and I think that this is probably the important part. You can take that for what it's worth.
Yes.
It would be very hard for me to trust, say, a program that was on a diskette to make a decision about the way my business would go.
Yeah, it's important to note that there are multiple diskettes As for example, this particular report is asking for another diskette to
Why don't you
complete
put
the
that in
report.
now? Maybe we'll have time to just see what those closing strategies were. While we're waiting for that, Steve, maybe I can get you back in here. How far can we go with this kind of decision support system stuff? Are we going to get into making legal decisions, governmental decisions beyond loan decisions?
Well, I think that many legal and governmental decisions could be approached with these types of systems, but I do think that the state of the art of the technology is such that that's still 3 or 5 years off. If you look at the kind of events that influence the sovereign heads of governments, or the kind of changes that happen in the law, these are quite a bit more difficult to model than lending decisions.
Is there a danger that, say, at some point in the evolution of decision-making programs like this, that people would tend to rely on them?
That certainly is always a danger, and that is a general thing with computer systems. We believe that these systems will improve decision-making, but they can't be followed slavishly. They really are only giving recommendations.
Jim, we have about 1 minute. Maybe you can rip us through the conclusions here.
Okay, well, we're about midway through the report, and it's telling us how to present information to this customer, Monroe, and we're getting information about this particular fellow, and he's detailed-oriented to present the details. That's important to close this customer.
And it says, like, find out what his business needs are. I mean, that sounds like the kind of stuff you might just read out of a sales text, but you're saying it's tailored to these people.
Exactly. If it's an impulsive character, you wouldn't want to find out anything about his business needs. You go right to the close. It's immediate close. This fellow is not one of those individuals.
Speaking of immediate closes, Jim, we've got to do one of those right now. Thanks for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
I'm Susan Bimba, sitting in for Stewart Cheifet. In the Random Access files this week, the government is investigating 12 semiconductor makers across the country. All are suspected of selling faulty, counterfeit, or inadequately tested chips. Officials of National Semiconductor say it's likely the company will be indicted soon as the result of a grand jury inquiry. National Semi has been under investigation for about 2 years, suspected of inadequately testing chips it sold to government contractors. The chips have been used in everything from military jet bombers to satellites to radios and walkie-talkies. In 1982, National Semiconductor admitted its chips hadn't gotten the required hours of heat stress testing and was barred from selling to government contractors for about 3 months. The company and its officials could face criminal charges, be fined, or be sued by the government for the money paid for the chips. New legislation has been introduced that should make computer hackers here in California feel a little less secure. The state legislature will be reviewing a proposal that would make it a misdemeanor to break into any computer system, even if there's no malicious intent. The hacker could be charged with a felony if malicious intent is proven. The current law addresses the problem of malicious hacking, but supporters of the proposal say the old law is too narrow in its focus. They say the new proposal might keep some potential hackers from invading computer systems for the thrill of it. Commodore has released the figures for its second fiscal quarter. In the quarter ending December 31st, Commodore's profit margin was $50.1 million. That's more than double the profit margin of the previous year's second fiscal quarter. Commodore is also experiencing a major shift among its executives. 4 have resigned in the last 2 weeks. They include the acting president of Commodore's U.S. unit, marketing vice president, the systems engineering director, and a director of materials. The resignations occurred just 2 weeks after Jack Tramiel left the company. The home computer maker says the resignations are not related. The company is delaying plans to debut its new computer. The 264 was due to be released in April. Commodore's general manager says decisions on the kind of programs to include and what price to charge have pushed back the 264's introduction date. Apple has been reorganized since the introduction of the Macintosh and New Lisa computers. Company President John Sculley has changed it from a 6-division operation to a 3-division operation. The Apple II division will be in charge of Apple II and III. The Apple 32 division will handle the Lisas and Macintosh and all 32-bit system products. The Accessory Products division will be responsible for the equipment such as printers, keyboards, and communications products. Apple also plans to open a plant in Mexico. It's being called Apple de Mexico. The government of Mexico requires that companies wanting to sell computers in that country operate their plants there, and the plants must be majority owned by a Mexican entity. It's estimated that Apple computers make up about 40% of Mexico's personal computer market. Some owners of Hewlett-Packard computers will be able to hook up to a nationwide network soon, and they won't need a telephone. HP and the Vitalink Communications will market a high-speed data communications network with the help of a satellite. That's good for HP and Vitalink, but may cut into some of IBM and AT&T's business. 400 workers of the Storage Technology Corporation got the news that they were being laid off. They were called into the cafeteria of the Santa Clara plant Friday afternoon and told they had to be out of the building in about 2 hours. Storage Tech was working on a large IBM-compatible mainframe computer. During 1981 and 82, business was brisk for the company, but when 1983 began, so did a steady decline in Storage Tech sales. So the Colorado-based company decided to close the Santa Clara operation and get what it called a substantial write-off. Approximately 100 employees will be held over so the company can make use of the chip technology it's developed in the Silicon Valley. Well, if you've joined the chorus that's saying video games are a thing of the past, you may have to change your tune soon. And the praises you're singing might be about computer games. As people are becoming more computer-oriented, they are more willing to relax with them. And what better way to break up the monotony of working at a computer than by plugging in your favorite entertainment software and playing a while? Several Silicon Valley companies have switched from video games to computer games and say business is booming. But both video and computer game enthusiasts say they can coexist and make a profit at the same time. That's it for this week's Random Access File. Stewart Cheifet will be back next week. I'm Susan Bimba.
Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and sitting in this week for Gary Kildall is Herb Lechner of SRI. Herb, our subject today is ergonomics, or human factors engineering, looking at how computers and people can work better together. And most people may not recognize this monster here. This is an Apple I computer from back in 1977. You supply the lumber by yourself, by the way. It's not very user-friendly. You've done a study at SRI on ergonomics. What were the findings of that study?
We didn't have anything quite this crude to work with, Stuart, but we did find that there are areas in which we can improve the man-machine interface. They range from hardware-specific items, like the design of the keyboards and the height of the characters, to the furniture, to the general workspace, the room for work layout, the heat, the noise level, the lighting, and all the way to personnel issues such as making sure that the people who are going to use the equipment are part of the selection and decision-making process.
Okay, on today's program, we'll be looking at the newest chapter from Apple, looking at the Macintosh and how it approaches ergonomic problems. First of all, let's take a look at some human engineering problems in which the consequences are more serious than just eye strain or inconvenience.
The sophisticated aircraft instruments developed in the 1940s and 50s created human interface problems that were entirely new to industrial designers. Mechanical devices gave way to electromechanical and electronically controlled mechanisms, generating more information more rapidly and putting greater burdens on the operator. In its earliest days, ergonomics was concerned with the safety of people who used these devices in applications where an error could cause injury or loss of life. As the use of ergonomic design became more common, it quickly spread to other working environments, with the goal of increasing productivity and reducing fatigue and stress. Among computer users, some major concerns surfaced in the 1970s. Muscular pain, stress, and in particular eye fatigue were the most common health complaints. Sitting in front of a video display was a radical change for most workers and led to studies on how the eye responds to CRT stimuli. In this experiment, an infrared beam follows the eye's movement across the screen, measuring pupillary responses and focusing ability when faced with characters of different polarity, sharpness, or contrast. The irritation resulting from screen glare, another major source of complaints, is measured by this test, in which different patterns at varying contrast levels are projected onto a CRT screen. As each pattern changes, the subject looks for its reflection in the screen. The difference between an anti-glare and a reflective screen is easy to demonstrate. Ergonomics developed as designers became aware of an obvious relationship. The efficiency of a machine depends on how efficiently it can be handled. In a field where the problems are sometimes physical and sometimes psychological, the objective is the same: to adapt machine design to human thought and movement.
Our guests in the studio now are Wanda Smith, Manager of Human Factors Engineering at Hewlett-Packard, and Karen Kessel, an ergonomics consultant and editor of the Office Systems Ergonomic Report. Herb?
Karen, not everyone may be familiar with our use of the term ergonomics. Some people think it has something to do with the interaction between people and computers, but there are software interactions and there are physical interactions. How do you define ergonomics in this sense?
Well, basically in that way, that you must consider the entire workstation design, and that of course includes the terminal and the systems operation, which is both software and the task. What we try to do is look at the user and ask, what are the user's needs? How is the user constrained in this task? How are they constrained in that? What are their memory capabilities, for example, and try to tailor the environment so that it best suits them.
Wanda, when you look at a computer terminal or keyboard, more or less it reminds you of a typewriter. Is one of the problems people are kind of caught in that typewriter mode and not really thinking that this is a really different machine to be using?
Yes, I think there are some what we call transfer of training problems, particularly with people who have never used a terminal before. In other words, a keyboard hooked up to a computer, and sometimes that's evident when people continually hit the return or a button on the right that might erase all the data. As normally they think of that return button as returning the type element back to the left side of the paper, and what happens with a terminal is that you actually return the cursor to the left-hand side of the terminal. So there is a problem with transfer of training, but it seems to be overcome very quickly.
Not too long ago, there was quite a bit of concern expressed by VDT users about their safety and about the physical comfort of using a VDT terminal. I've noticed some changes since then, detachable keyboards and all. What actually transpired there?
Well, actually, several years ago, the concern of the users was brought to the attention of the manufacturers, and there was some legislation started in Europe, and as a result of the concern mainly, but also of the legislation, there's been a number of product design changes that really better accommodates the user and makes the whole system more adaptable and more flexible for the user.
Karen, looking at the hardware side a second, what are the ergonomics issues you face here? We think of things like screens and keyboards and what else?
Okay, yeah, lighting, character quality, other aspects of the physical workstation that include things like if you're using your terminal a good deal of the time and also having to get information from a telephone, you don't want to put the telephone across the room, you want it close to you. So it's considering the entire workstation. In particular, concerning the VDT, we're concerned about screen quality. What should the keyboard be like? These kinds of issues.
What about on the software side? It seems that's a more subtle problem, isn't it?
Yeah, it's also a more difficult issue because then you're asking questions about the cognitive capabilities of the user. You're sometimes asking, given a certain goal, what stages is the user going to go through to get there? Basically, what are they going to be thinking of? You're trying to anticipate them, and you're trying to design a system that better accommodates them. And that's very difficult.
And I suppose we have to be a little flexible. All users are not the same. There are tall people and short people. And
exactly. Various users come to the VDT situation with different kinds of knowledge.
We have adjustable chairs, but I wonder if we have adjustable software.
Wanda, speaking of cognitive problems, you have a demonstration here with the HP Orion computer. Tell us what's on there.
This is a demonstration of a time planning algorithm that's typical. It's in the field known as a PERT chart, and this is a demo of how this kind of information can be changed to multicolor in order to pick out the information on the screen that differentiates it from other parts of activities that will be going on during this person's planning of time.
Okay, so what we saw first was a black and white chart, which wasn't too easy to decipher.
Well, it was easy to see the information, but it wasn't easy to differentiate the information. One of the advantages of this display is that it has 4,029 colors, and we can vary the colors on parts of this display to show areas that need to be differentiated and that actually help the user to discriminate parts of the information on the screen from other sections. You can see that I've color-coded the critical path in this area red, I've color-coded the slack time in green, and now what I'll do is I'll color the events with a yellow to discriminate those particular parts of the screen or the events from others. You can see it's kind of a yellowish, goldish color.
Okay, that certainly makes it easier to read. You have another demonstration on text processing, which I think is worth
yes,
looking at.
Many people don't realize that you can use multicolor displays for applications like text processing. Most of the time they think of multicolor displays for CAD/CAM. And what I'm actually going to do now is to bring up a menu showing you something that I've designed to show how to discriminate sections of information in a letter by using a multicolor dimension. Most people, when they write a letter to a customer, let's say I've got a shipping account, what I want to do is to find out what parts of the letter are critical information and what parts of the letter are typical information that we might want to change on a daily basis, excuse me, or maybe not change at all. Now this takes a few seconds to bring up the program, but it's an application that's new, it's different than CAD/CAM, and we're starting to use multicolored displays to study the visual and cognitive responses of people, which, as Karen said before, is a much more difficult problem than just the hardware design.
This application would be if, for example, we wanted to edit a standard letter?
Yes. Yes, it could be used for editing. You can use multicolored coding for defining technical terms in a report that you may want to put into a glossary. This is an example where the standard text is color-coded in blue. The information that you normally change when you do a new letter, maybe to a new customer, is color-coded in yellow, and the information that's critical is color-coded in kind of a maroon color. And particularly if you notice the last line says, continued non-receipt of this payment will jeopardize future orders. And that will alert the data input operator to the fact that this person either hasn't made his payment or there's some problem, alerting him to the fact that maybe we don't want to send that person orders in the future, or at least tell the payments received.
Wanda, one last thing. In doing your demo, I see you have a kind of thumb wheel, speaking of ergonomics, on the keyboard. That's kind of a mouse of a sort, isn't it?
Well, it is a mouse. What it does, actually, it moves the cursor around the display so that you can put various types of information at different spots on the screen. Now, one of the advantages of a thumb wheel designed into a keyboard is that it doesn't require a lot of space on the tabletop as would a mouse or maybe some other kind of interface device. One of the things that we're interested in as human factors engineer is what kind of device should be used for a typical user in a specific application, and that's the kind of analysis we go through to design a product for specific users.
Okay, in just a moment, we'll take a look at one of the newest chapters in Apple Computer's approach to ergonomic design, the Macintosh, and that's coming up next. Joining us now is Susan Kerr. Susan is an icon designer with the Macintosh Software Group, and Jerry Manick, who's product design manager for Macintosh. We're talking, Jerry, about ergonomics on this show. How did the Mac address some of the ergonomics problems we've been discussing?
There are certain basic design criteria that we use for keyboards, the angle of keyboards, the angle of the front screen of the Macintosh. Taken out of the literature, we wanted Macintosh to be able to be used by the 99th percentile, male, female. Also we knew that children would be using the Macintosh. That pretty much decided the arrangement of the tube above the disk drive slot. We wanted the keyboard to be very light, to be able to be moved around easily. Macintosh itself, we wanted the case to be as small as possible because it's a portable unit. We wanted a very strong statement of transportability, thus the handle on the top. We wanted the keyboard to be able to be easily connected and disconnected. The 4-wire coil cord plugs into the front of Macintosh to make it easy to assemble it. The disk drive is pretty unique, we think. We've gone away from the soft floppy disks that can be easily damaged with heat or bringing something magnetic close to it. This hard plastic shell on the disk drive, on the diskette, completely protects the media inside and can be used, carried in your pocket without worry about getting dirty or damaged. It also makes the disk drive very reliable in practically any climate. You can be assured that you won't lose data by using that.
Tell us about the mouse. That's obviously been a key part of Lisa and now Mac technology.
The mouse is a very efficient cursor pointing device. There have been a lot of studies about how the most efficient way to point the cursor is. Actually, the mouse is designed to be used all the way from a child to an adult with a very light touch on your hand. The early mice, even from Apple, had 3 buttons or 2 buttons on top. We worked very hard to get just the button to be a single button without having to have the person remember right or left, just click. And as Susan will show you later, the function is done.
Susan, you're an icon designer, among other things, and have you learned something from the experience on Lisa as to the effectiveness of icons, how to use them, and how they fit in?
Well, certainly, I think one of the best experiences is seeing a person who's never used a Lisa before or a Mac before, and even never used a computer before. It is possible, easily possible, to teach most people to use one of these computers in about 20 minutes. And a lot of that is because you can explain what an icon means, and a person can remember it easily. So we certainly used Lisa as a jumping off point and making just some refinements and additions for some new features.
Okay, your area, the icons, are another one of the key ergonomic aspects, I suppose, of using a Mac. Maybe you can run through a demonstration here, Susan, and show us how we use the icons to get from place to place. Tell us where we are right at this moment with Mac.
Well, what you see now is the image, the icon that you get when you just plug Mac in and turn it on. It prompts you with a picture of the diskette. So you've
and a question mark saying, where's my diskette?
Saying, I need something.
Okay,
so that all you do is, it only fits in one way, so there's no way you can break it or make a mistake.
Just pop it in. You get an image of a content Mac, so you know that everything is okay and you're welcomed. It's just so that the person using Mac gets information all the time visually, so nothing has to be translated. A little wristwatch to tell you, just wait 1 second.
Things are happening. You've replaced the salt timer?
Yeah, we're moving into the 80s.
So what do we have now?
So what we have now is an image on the screen of the diskette that we put in the slot. And it can be with the mouse, it can be moved.
Okay. And it's already showing you the name of that disk.
Right. And it's highlighted in the sense that it's inverted so that Mac knows that you want to do something to this diskette. And your choices of what you might want to do are listed in hidden menus that operate a little bit like window shades. When you move your cursor.
So let's pull down the File menu. See, that would tell us now what?
Right, that our choices, we could find out something about this diskette, or we can just open it, or we could eject it. But if we open it, just say open, and immediately you get what we call a window that displays graphically and in words what is contained on the diskette in the machine. So you can see there's a picture of a hand painting, which symbolizes a paint program, and a handwriting for the word processor, and a couple of memos that were already written, some folders. If, say, you want to store a document or two in a folder, it's analogous to life. You just put the piece of paper in the folder.
Now you've got something called the control panel here. Show me what that is.
Always available to you are a number of desk accessories. So you move the cursor to control panel, let go of the mouse button.
And what do we have?
So this, which looks a little bit like a dashboard, lets you fine-tune the system in a number of ways to your comfort level or just your personal preferences. The computer will work no matter what settings. So that,
such as, what controls do you have?
Say, here's a little volume control. You can see the speaker. So every now and then you hear a beep with Mac when you turn it on, or sometimes during applications. If you're at home by yourself and you're listening to the stereo, you might want to know that you'll always hear those beeps. If you're a student working in the library, you can move it so that just the bar will flash, so there's no noise at all. Say some of the other features let you adjust keyboard repeat rate, or a menu flash, or the amount of time between double clicks, which might vary with the age of the person using
I'm going to rush you because I want to see as much of this as we can in the time we have. Show me Notepad and how that works.
We can pop the control panel away by just clicking on it. And Notepad lets you, while you're working in any application, as well as just this, what we call the Finder, which is like a directory, be able to grab the keyboard and write a note to yourself. Remember to read page 12. And you could say, put this away, or you could move it over.
Show me how you flip the pages of the Notepad. That's kind of impressive.
We can go to page 2, where it says another note, one left for oneself. Flip to page 3. Up to 8 pages of notes that could help you in your work or just remind you of social events.
One of the items was Scrapbook?
Right. Scrapbook lets you keep literally, you're only up to 256. You're only limited by how much memory you have free. Pictures or messages or documents always available for the terms we use are cutting and pasting.
Maybe you can go to Mac Write, and then we could build up to how you'd use that.
Right. So say to open a word processor application, you could click on Mac Write and say open. If you want to get right to a document, which automatically launches the application. Same procedure, which is why it's easy to use.
And now you're loading the word processing.
We're loading the word processor and to the specific document that
I think one of the advantages, too, of Macintosh is that things happen so quickly. It certainly fits into the ergonomic pattern of the user interacting quickly with the device.
It's just very direct, no complicated sequence of commands to remember. We can, here's an old little bit of sample text. This is how the word processor appears to you. A ruler lets you set formats, which is certainly a familiar object. Say you want to go from single to double space, just click on the wider image if you want.
And you can justify or center. We're not going to have time actually, but you could have pulled up pictures from Mac Paint from the scrapbook and then insert them into the document.
Paste them in just by saying paste from the menu. If you want to change a word to be bold, just say bold. Change the font to something like Old English.
Okay, I know you're having fun, Susan, but I'm going to have to stop you.
It's hard when it's your baby not to be enthusiastic.
I get the feeling. Well, thanks so much for showing off Mac to us, and thanks for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine. In the Random Access file, the computer will soon be more than just a teaching tool in colleges. It is becoming the college itself. A company named Telelearning Systems has announced the creation of the first nationwide computer college offering credit and degrees for taking courses on a computer. Telelearning Systems will be working with 7 major colleges and universities around the country to offer the computer courses. The schools are located in Ohio, Nebraska, California, Wisconsin, New Jersey, and New York. It's being called the Electronic University. 4 Japanese computer companies have announced a major breakthrough in chip technology, the world's first 1 megabit ROM chip. The chip is 15 thousandths of an inch thick, yet it can hold 1 million bits of information, the equivalent of about 70 pages of printed material. The chip, which is smaller than the head of a thumbtack, has nearly half a mile of conductive wiring in it. The chip was developed by Hitachi, NEC, Toshiba, and the NTT Electrical Laboratory of Tokyo. Scientists at the Lawrence Livermore Laboratory in California say they have just unveiled the world's fastest computer, a new Cray XMP supercomputer, which can do 200 million calculations per second. Scientists at the Livermore Lab will be using the Cray supercomputer to do research on the so-called Star Wars defense system. Texas Instruments has announced a new voice interface for its professional line of computers. The device will allow users to communicate with the computer by speaking up to 50 different commands. The voice interface costs $2,600 and will be available in April. And Kpro has announced that it will soon market a new IBM-compatible notebook-size portable computer. Kpro says it will be priced at the high end, more expensive than current Kpro models. Giant IBM, meanwhile, seems to be moving ahead to secure its dominant share in the personal computer market. There are rumors that IBM will soon take aim on the clones. The introduction of the IBM Portable, one step in that direction. Other rumored moves include greatly increased product production, a drop in prices, wider distribution, and the possibility of a new computer that would be harder to imitate. To appreciate the size of IBM's dominance, the increase in IBM computer sales last year, just the increase was $6 billion. And IBM scored a big victory last week. The Harvard Business School has settled on IBM as the required computer for all students. The business school announced that as of next fall semester, all students will be expected to own an IBM Portable for use in homework assignments. Harvard College, however, decided to go with Apple and is making Macintosh the official student computer. Apple, meanwhile, got sued last week by shareholders complaining about alleged misrepresentations on the Lisa computer. The class action suit also charges that Apple officials sold more than 2 million shares of stock prior to the company's announcement of lower profits. Well, if you like chess and Dungeons and Dragons, you might like Archon, a new software game. That's the subject of this week's software review. Here's Paul Schindler.
Games. Some people don't take them very seriously today, although we know, for example, that chess was taken quite seriously in India, where it was invented 13 centuries ago. We also know that kids who drop billions on arcade games play for keeps. Well, so does a company in San Mateo, California called Electronic Arts. It's said that games on home computers, for technical reasons, can't hope to match the experience of games in an arcade. Well, someone forgot to tell the people at Electronic Arts. Today, we'll look at their game called Archon. Now, since I was playing with a chess set when we started, you might think Archon is a chess game. It isn't. There are plenty of chess games, but there are few games with men and women of magic, the forces of light and dark. The Whole Earth software catalog calls Archon an addictive cross between Dungeons and Dragons and chess. Well, with the goblins, the unicorns, and the colorful graphics, it may be hard to see the resemblance until you play it a little. Electronic Arts credits the authors of Archon, so we will too. They're Ann Westfall, John Freeman, and Paul Reich III. Archon costs $40 from Electronic Arts. For Random Access, I'm Paul Schindler.
And next week, Paul looks at Offix, a new low-cost word processing and filing program. Well, do you remember that video movie store in the neighborhood that used to sell mainly records? Well, you may soon be talking about the software store that used to sell books. Software is expanding outside the computer store and into bookshops. 2 major book chains are already carrying software. And just last week, a major book publisher, Addison Wesley, got into the business of distributing Infocom's software to retail bookstores. Finally, if you're into self-evaluation, trying to find out who the real you is, there's a new software program to help you. It's called Unbecoming a Hero. The program takes you through an extended series of questions to help you figure out what are the values most important to you. The program also lets you create a role model and then helps you understand why you admire that kind of person. It costs $30 and it runs on an Apple. And that's it for this week's Random Access File. I'm Stewart Cheifet. Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Monsieur Kildall, est-ce que je peux avoir $1?
You got me on that one.
What I was asking you was, would you lend me $1? Only I was using the French language to communicate to your brain, your computer, and I guess you're programmed in the English language, so you didn't perform the program the way I hoped you would, and you didn't give me the $1. The point of this little story is that our subject today is computer programming languages, Gary, and of course there are many languages you can program in, just like there are many languages we can speak in. Before we talk about these different individual programming languages, I thought you might explain the different levels of computer language.
Well, there are 3 major levels of computer programming languages that sort of depend upon your level of sophistication, what you're going to use the language for. The lowest level is what's called machine language, and that's the language the machine understands, the ones and the zeros. The next level up from that is what they call systems languages, and the languages like the programming language C would be in that category. And those languages are used to program applications such as word processors or spreadsheets. And then the third level, the highest level, is what's called an application language or an end-user language. And there's languages like Fortran, COBOL, Logo, so forth fit into that category. And so we'll get a chance today to talk about some of those languages and see how they're used.
Okay, indeed. We'll see a demonstration of COBOL, Forth, Logo. We'll talk about Pascal. First, though, let's try to understand a bit better this problem created by having so many different programming languages.
Type 西、吧、
This multilingual keyboard can perform the tasks of interpreter, grammatical advisor, and artist in translating English sounds into Japanese text. The program does for human languages what most computers are incapable of doing with their own languages. Because machine codes vary from one microprocessor to another, the same programming language cannot be shared by two different computers. For example, Apple BASIC is not IBM BASIC. A language customized for one machine will not run on another. Like their human counterparts, computer programming languages differ in structure, syntax, code, and even symbols. But the lack of standard transferable code puts the programmer at a time-consuming disadvantage. After learning to write a program for one computer, he must rewrite it for another. Because of a computer's wide range of applications, languages are specialized. Fortran for science and math, COBOL for business, Logo for education. The more friendly a high-level language, the more translation it requires before it can be executed at the machine level, and correspondingly, the slower it runs. In some cases, lack of speed at the machine level is a trade-off for quick interaction with the user. Adding a third layer of complexity to computer programming is the assembly language, required to translate high-level languages into machine code. Programs written in assembly language are faster in execution, but more difficult to write than those in a high-level language. Software firms are developing more powerful, portable languages for use in micros, but as long as computer manufacturers design exclusivity into their products and languages, users are faced with the same dilemma. Machines that will communicate with everyone except each other.
Ruski jazyk.
Our guests today are Paul O'Grady. Paul is Executive Vice President for Strategic Development at Microfocus, and Paul works with COBOL. And next to Paul, Dave Eisenberg, a Senior Engineer and Software Developer with Apple Computers, and Dave works with Pascal. Gary.
You know, Stewart, there's been a lot of languages around for several years that are sort of considered traditional languages, like PL1, Fortran, COBOL is a good example of that. And one of the difficulties in the small computer industry is trying to bring those down into really usable languages. Nowadays, people expect a lot more interaction in the way they deal with computer systems, and I know that Microfocus has been working on COBOL, trying to make that more of a personal orientation. So what have you done?
Well, we see ourselves, Gary, as in the business of exploding myths about COBOL. The mainframe people have myths about it, that it can't run on this kind of equipment, and the microcomputer people have myths about it in the sense that they just don't like the language at all, a lot of people. What we try to do is we try to differentiate between the environment and the language itself. And the environment in the past for COBOL has been the mainframe environment. We believe that that is what has led to much dissatisfaction in that environment. What we've done here, though, with personal COBOL, which is one of our latest products, is show what we believe is the kind of thing that can be done and which is very appealing on this kind of equipment. I've already put us into personal COBOL. Personal COBOL is a combination of an editor, a forms generator, a checker, syntax checker, and the ability to run programs. In this case, I'm going to go straight into the forms part, and I've already created a form for us.
Oh, this is a form that you created by drawing the lines in and so forth.
Yes. Everything that you see on this screen here was created by directly keying in the lines, the text, the X's, the square brackets, the whole thing. And I did it in approximately 5 minutes or so before the program started. What I'm going to do now is to start to generate the COBOL for this, because another of the businesses that Microfocus sees itself as being in is trying to redefine the term programming. And programming for us is simply generating code in whatever way possible, the most effective way possible. In this case, we're going to generate all of the code for this screen automatically. That I'll do now. We also wrote this program so that people who have finger trouble like me never really crashed the program. I hope to prove that. I'm going to create a complete program, an index program. I position the cursor as it tells me to, and we're now generating COBOL in the lower part of the screen.
Now this, traditionally, again, if you talk about traditional COBOL programming, you'd start with a program that would, you'd work out all the details of it that would produce this screen. Is that
Yes.
correct? Now in this case, what you've done is you've manually made the screen up by moving the cursor around, and it's doing the inverse. It's actually producing the program instead.
That is
right?
correct, yes, and we've already produced it. We've produced the COBOL for that. What I can now do is I can decide whether or not I want to save that. In this case, I'll exit without saving. I've already created the text elsewhere. As I said, some people have finger trouble, and I always have finger trouble at points like this.
Paul, you mentioned that some programmers have not liked COBOL in the past. Why is that? What is it about it that created a problem?
There is a lot of detail to the syntax. The period at the end of each COBOL statement often caused problems, but there is also the need to define records at the beginning of a program prior to getting into the guts of it, making the program do the work. However, that comes from the type of application that COBOL was designed to bear upon. Those are typically data handling applications, file manipulating applications, and for that kind of application it is necessary to create the records to start with.
And in what you worked with here, though, is again a program generation concept. Now, if you talk about forms, you put up forms ahead of time and then you generate a COBOL program. Can you also do that for data structures for accessing files, or is this something that would come up in the future?
In terms of the data structures, they're already built into the index sequential file mechanism of the COBOL, and we adhere to the COBOL standard. But yes, in the future one can conceive of the ability to input the data structure directly into the program prior to generating it.
Dave, you work primarily with Pascal, and tell us about Pascal and why you like it. What are its special features?
One of the nicer things about Pascal is its power of expression in terms of, for a small amount of text on the screen, which is, given the right programmer, awfully readable, you can get a lot of power out of it. It allows you to express an algorithm, a method for doing a computation or some process, the way you think about it instead of having to force it into some other mold. And that's one of the advantages of COBOL for business applications. It's built for that, such that you can think in terms of a business or record problem and do it that way. Pascal is similar, but pretty much for more general purpose applications.
Pascal had several years ago a lot of interest in terms of using it as a systems language, and it was sort of touted as the all-purpose language for doing everything. What happened? Why did that not really take place?
Pascal was first designed as a language for teaching about computing and computer science, and even its inventor admitted, Nicholas Wirth, admitted that that was what it was for. And he's been at work lately on something called Modula, which is designed to take over from Pascal in terms of the systems area, which lets you get closer to the machine level, but still, again, have the power of expression that Pascal has.
Paul, in coming up with something like personal COBOL we think of as you say, mainframe, big corporation environment type language. What kind of use, what kind of application do you see with something like personal COBOL?
Well, we see not just the classic business data processing applications. We see personal applications such as diary application, personal filing applications, and we also see office automation applications, all being applicable to COBOL. They all require data handling and file maintenance, which COBOL was originally designed for.
I think it's also important to think of COBOL as being a system implementer's language. That is, it's not the kind of a language that
that you really promote as, say, an end-user language. Is that correct?
I would agree with that, certainly.
More to the kind of an individual who is going to go out and write some extensive programs and then go off and sell those programs. And so there's a whole layer of programming languages that fit in that category that maybe an end user might not even want to consider, at least until they've had some experience with programming languages.
Yes, I agree. I think none of the standard, the normally accepted programming languages are applicable for end users at this point, personally. Not even BASIC.
Okay, well, our third guest is going to talk to us about Forth, and that's coming up in just a moment. Joining us now is Elizabeth Rather. Elizabeth is president of Forth Incorporated of Hermosa Beach, California. Elizabeth, tell us about Forth. What makes that a unique programming language?
It's unique in two respects. First, it is the only language that I'm aware of that was designed from first principles to run in a small computer, doing interactive software development for real-time applications. The second area that it's unique relates to Gary's remark early in the program when he mentioned the three levels of programming, and Forth incorporates all of them. You can work right down at the machine code level when you need to. You can do system programming in Forth. In fact, the operating system that we're running on here was all written in Forth. And you can do very high-level kinds of things, very high-level application-oriented programming. For example, we have here a graphics program that is loaded, and I have a list of a large number of demo programs that I could run here. I'm going to try one of them called Logos, which draws, it's not related to the language logo, it draws our company's logo, which is a little bit chauvinistic, but the principal thing that this is illustrating, this is a rather complex figure here, and we're doing area fill, which is a fairly sophisticated graphics technique, and it's doing it very fast and very well. It's now got everything all white except for what was concealed in the little spots there, and eventually we'll be able to make even the little spots go away. But there are high-level words that put together this entire process, and I can show you some of them. I can say,
was that entirely done in Forth? As far as was it any assembly language involved in that area fill, or was that entirely done in Forth?
No, there is some assembly language.
So it's a mixture of those two.
Yes,
Forth.
and you put in as much assembly language as you need, either to control hardware directly or to make things run fast. And you notice this is a very fast program. But you have the high-level version. I can say locate logos, locate fill, for example. This is the area fill routine, which is written in code, because area fill is something that needs to run very, very fast. So you have assembly language code here, and then we have some other words called dark and light that are what we call high level.
Part of this is assembly language you're showing us. Part of this is Forth in a Forth statement. Is that true?
Yes, that's right. The word dark, for example, that I'm highlighting here, makes the screen go dark, like that. And it simply picks up the color and blackens the screen and then resets what the previous color was, so that when you draw something again, you'll draw it in whatever color it was. And
so what we're seeing right here, the
high-level things.
The highlighted line itself is Forth in this case.
Yes, that's right.
Gary, you have your company, Digital Research, has Logo out now.
I just happen to have a disc with me.
And maybe you could load up Logo for a minute and show us how Logo
give me some help over there with
compares to these other languages. Dave, while we're waiting for Logo to boot up there, let me ask you, are there always going to be all these different languages, or are they going to merge into a smaller number?
Well, it would be nice to have an ideal language, but I don't think it'll ever really happen. Mostly because, well, for example, COBOL, which we saw earlier, is designed and used primarily for business applications. Forth is designed for real-time applications. Logo is designed for education, teaching people to program. And, well, when you discuss languages, it almost becomes a religious argument. But really, a language is just a tool, and it's like arguing, well, which is better, a hammer or a screwdriver? And you tell me what you want to do with it, and then I'll tell you which one's better.
I think that's probably the most important point about languages, is that if you use the right one for the right application, then it's the most effective thing you can do. Logo is like
a lot of different interpreted languages. It gives you an immediate feedback to the work that you're doing. And what I'll do here, I'm just going to make this screen into a split screen. And I'll show you what I mean by the immediate interaction. For example, if I type forward 30, then you see the pointer, or the turtle as it's called, moved in a direction. Now that's immediate feedback to what you typed in. Now a lot of programming languages like Fortran or let's say many Pascal versions are what they call compiled languages, and you don't get immediate feedback. You have to go through an edit step and a compile step and maybe even linkage editing. And that requires a lot of abstraction, a lot of thinking about what you're doing. Where languages that are interactive, like Logo and Forth and other interpreters, give you immediate feedback. Now this next thing I'm going to load in here is called Blackjack. And it happens to be a demo program. You're familiar with that one? Okay. Now the reason I'm loading this one, this happens to be an example of how you use turtle graphics or graphics to draw pictures. And this particular program was written by a 13-year-old in about 3 or 4 days. Now, it was a rather precocious 13-year-old.
Yeah, your son. That's
well,
not
no, actually,
he's genetically superior, Gary.
It was actually his friend.
Okay.
but the point of it is that you can do things like this, like a little game of blackjack, without a great deal of effort in a language that's interactive and graphical in nature.
One of the nice things about these languages where you define your own words is that you can make it read fairly close to English. You can actually pick up a program and read it.
Gary, while you're playing blackjack there, most new computer users get exposed to BASIC as their kind of language, and we haven't really talked about that yet. You're showing how easy it is to do a game like this in Logo. How is it better than BASIC? What are the problems in BASIC as a programming language?
Well, BASIC is historically came from Fortran. It has a lot of the original problems of Fortran. Fortran is one of the, in fact, may have been the very first, I guess, high-level programming language, recognized high-level programming language. And so BASIC sort of followed that genealogy and has a scientific orientation to it, step-by-step breakdown of the problem into simple steps that sometimes not really the best way to think about the breaking a problem apart. Now, Logo came from the MIT Learning Project, where they thought about the problem of problem solving itself, and then the language that would be an underlying language that would be good for that. So I think BASIC it's an easy language to learn, but it has its limitations as soon as you start to do anything complicated.
BASIC was designed to be learned quickly by college undergraduates doing very simple things. It wasn't designed to do either sophisticated programs, nor was it designed to grow. And I think both Forth and Logo have the capacity to grow in the sense that you can teach them new things, and there is a learning process going on in the computer, or between the programmer and the computer, which is very similar to the learning process of teaching a small child to do new things.
Well, I think that's interesting with Logo also is that it's sort of a bait and switch tactic in the sense that you sort of get children interested in the language because of the graphics, because they think of it as a big track that they program and runs around the floor, in this case a turtle. But behind it is a language, Lisp, which has been used for years in artificial intelligence, and all the Lisp processing and that's a part of Lisp is also part of Logo. And so there's the Forth and Lisp share some foundations that are somewhat similar.
Dave, are there any new languages on the horizon, or do we have a finite number now?
The last roster of programming languages that I saw had about 700 or 800 names in it, and I don't see an end in sight. A lot of languages are designed for one specific thing. I guess you'd call them almost a toy language, except to the person who invents it. So most of them, I think, are offshoots of the main languages like Fortran, COBOL, ALGOL, or Lisp. And yeah, as long as people have ideas for things they want to do, they'll invent a new language.
So it's a kind of evolutionary process, I think all of you said, where one language kind of builds on.
Well, I think also it's a matter of getting started as far as learning a language. Once you've learned one language, it's not very difficult to start picking up other languages, but it seems to be a threshold to get over the very first time. So I think that's an interesting thing about learning languages, that you get started at least.
Okay, well, we started and we're finished. Thank you very much for being with us, and thank you for joining us in this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall, whom I'm trying to beat in a game of Pong.
Pay attention.
Pong is the granddaddy of all computer games, and that's the subject of our program today, computer games. And Gary, computer games, in fact, were important, weren't they, in getting the whole personal computer thing going?
Well, they certainly were a part of it. One of the unique aspects of a personal computer is that it often has bitmap color graphics, like the Apple II, for example. And that way you can do very dynamic things, games that you couldn't do, say, with a teletype style or scrolling display you would find in a larger computer system. This particular game, obviously, is a pretty old vintage, and they've gotten a lot more sophisticated since then, and we're going to see some of that today.
Indeed, we've got a very exciting show. We'll be meeting some of the superstars of computer game programming from Electronic Arts, from Atari, and from Activision. And while the idea of computers in games may be new, the idea of people playing games with machines is not really new.
Now that was the first one.
That was legitimate.
Before the first program was written to simulate a starry background or a speeding racer, penny arcades offered simpler, more mechanical amusements, but with the same goals in mind: to challenge and entertain. If the locale was less exotic and the competition less ferocious, at least some of the game's interactions were similar. A player needed manual dexterity in competing for points or a reward, more tangible in some cases than in others. As a device for escaping daily routine, computer-generated graphics brought a level of fantasy that no mechanical game could ever approach. Instead of escaping from a schoolroom or an office, a player could leave the Earth or move to a different universe. Modern arcade computer games offer different kinds of challenges, from fast action games that demand even faster reactions, to maze-type games where the player threads his way around obstacles, and war games where the object is to destroy or be destroyed. In one of the latest adventure games, animated images are stored on Laserdisc to be recalled sequentially, following the story's plot and according to the player's responses. If the player moves the control stick in the right direction, he is rewarded with a successful escape. But if the player makes a mistake, the program picks an alternative sequence of images, and the results can be extremely uncomfortable. Whether used to create unknown worlds or to enhance the reality of familiar worlds, computer games succeed in an unlikely domain, transforming pinpoints of light on a little screen into a believable realm, larger than life, and usually more exciting.
The studio are Steve Kitchen, designer of an incredible new game, Space Shuttle, from Activision, and Chris Crawford, one of the top game designers with Atari. Gary?
Steve and Chris, you both build computer-based games. Do you call yourselves designers or programmers?
I call myself a designer because most of the sweat and blood I expend occurs in the design phase, not in the programming phase. I spend a great deal of time worrying about what my audience will experience in the game, and only towards the end of the project do I actually get down to writing any code.
When you think about the design of the game, what are the elements of the game that make it interesting?
Well, that has to do a great deal with what I'm trying to accomplish. I set a goal. I want a game to achieve a certain effect. I want to somehow communicate a message to my audience. That message then dictates the topic and the style of the game, the nature of the graphics, the feel. That's what the texture of the game that I'm trying to build into it. That's what I spend most of my time worrying about.
Chris, you're talking more like a writer rather than a computer programmer. Steve, is that how you see what you do?
That's basically what we are. We're writers. We're writing a book, a novel, creating a vicarious universe in this computer program. We have to model everything we want, put every small detail in. Very often, in my game, for instance, I had to do extensive research for 1.5 years to understand my subject before I could distill the important aspects out and then put them into this cartridge.
Like a writer would.
Exactly like a writer would. When a writer writes a book, the book is a vicarious universe. You read it and become part of it. It's the same thing. When you play these games, these programs, you vicariously become part of the universe that the programmer puts into it.
Okay, you've got Space Shuttle up here, and give us a demonstration of how this works.
Well, this is an automatic demo flight we're going to fly. This is a complete Space Shuttle mission from launch to landing. This is actually themed after the STS-2 flight back in November of 1981. We're starting off now at Cape Kennedy in the morning. The clouds are rolling by, the sun is coming up, and we're doing our countdown now. Now at T-4 seconds, we're going to turn our main engines on. You're going to see the thrust indicators at the top of the screen there moving along. There we go. At T+3 seconds, the solid rocket boosters are going to turn on, and we're going to go through the clouds and off the pad. And there we go. Now, the aspect of the game here is to fly the space shuttle successfully into a 210 nautical mile orbit, doing all the control functions that an astronaut would really do, setting your yaw and your pitch, keeping on a trajectory line. At 26.2 nautical miles, the solid rocket boosters will jettison off. Now, this is a very important point of accuracy, is there's a yellow flash. There we go. This is something that wasn't noted until STS-1 when the first astronauts went up, that this actually happened. I had to find all of these details out about what you would experience if you were inside of the space shuttle and you were doing the flying, so that when you play this game, you feel like you've actually flown.
Steve, it seems to me the incredible thing is this game is running on an Atari 2600, not a computer. How do you squeeze all of this into that unit?
Well, it takes a lot of time programming, coding. You have to model the universe as you feel it should really be, and then you have to find how you can fit it all in piece by piece. You start off with the basic mission, and then you add features and you add the functions all along the way. When I finished the game, I was not happy with it, and I had an additional list of 146 separate items I wanted to put in that I still felt were important. I spent an additional 3 months finishing those off and getting them all in. I wanted this to be absolutely accurate and absolutely complete. And it
you
is.
Put this all inside of how big a ROM?
It's an 8K cartridge.
8K cartridge. That's an incredible amount of...
It took 13 months of programming, and a lot of that time was spent putting it all together. Now, we've just achieved orbit. There's the Earth stream rolling underneath. The external tank will jettison. There it goes. And we've docked with an orbiting satellite, which actually was themed after the Skylab. In fact, Dr. Ed Gibson did a review on the game, and he noted that it looked like you were trying to fly into his old nemesis in space. And then we do our deorbit, and we come in for a landing at Edwards Air Force Base.
Now, one thing unique you did in adapting this game to the 2600 is using the switches in the 2600 as functional switches. How did you do that?
And what we had to do was I had to throw out all the old ideas of what this machine would do. This was originally a video game console, so I said, look, all these switches are controlled by the computer. I'm going to redefine them to be computer switches. I'm going to control the main engines, the backup engines, the cargo bay doors, the landing gear, the sequence of information on the screen. It became so different that we had to develop an overlay to fit over the screen. We had to develop what's called a cheat sheet, which is just what the astronauts use. This gives you all the instructions that are necessary to fly your shuttle. And the instruction book is 30 pages long. And it gives you a lot of detail into exactly how to fly the space shuttle. And basically, it's a small flight manual. We provide a glossary. We provide drawings of the space shuttle, engine indicators. Here's a side view of the space shuttle that we provide. So really, you understand all about the space shuttle in order to fly this game accurately.
You get a little pilot's license when you get through this?
If you fly successfully, you receive a patch, and if you fly just as an astronaut would, you might get your wings. We're entering the Earth's atmosphere now, and you see we're getting the ionization cone that appears around the space shuttle. If you saw the movie The Right Stuff, you would see in the sequence with John Glenn, this is what the astronauts see in the window. This is hot ionized gas being superheated by the friction of the shuttle on the way in. We've even lost our signals. We've lost our altitude and speed information, and we've lost our computer screens.
Steve, it seems piloting the space shuttle is very difficult to do, one would think. Can a kid or a normal person actually pull this off?
Well, what I did when I designed this was I understood that problem. Having the average individual fly the space shuttle would take years of work. But I looked at how NASA trains its astronauts, and they start off, first of all, by giving them a lot of book exercises. They give them film strips of what it's like to fly the space shuttle. This is flight number 1. You're seeing essentially a film strip. You can pick up the joystick and take control at any time you want to, but you don't have to. There's a second flight called a training flight, and that basically is like flying in a simulator. You can make mistakes, you can make errors, and the computer will compensate, and it will let you know. And then flight 3 is the actual real thing. So you work your way up to flying the actual mission. You can get into it very easily, and then work your way up and finally try to achieve your wings.
The interesting thing about this game, I think, is that it's an educational learning experience as well as
vicariously educational.
Right.
You're not sitting there playing flashcards. You're learning about one of the most technologically advanced items today. There are the dual sonic booms that occur. The first one was the space shuttle. The second one was the chase planes. And we're coming in now at Edwards Air Force Base. When you get done mastering this game, you've effectively learned all about what an astronaut does when he's in orbit. So the next time you see a launch go off, you're going to know what he has to do, when he has to do it, and what he goes through.
That's incredible. We need another minute or so before we land here. While we're waiting, Chris, let's talk about, your new game is called Excalibur. What is that about?
Excalibur is a game of leadership. The concept, I wanted to express to people the ideas behind von Clausewitz's statement, war is the extension of policy to other means. That is, I was a little tired of war games that glorify war. So I wanted to show that war is something that sometimes cannot be avoided, but must never be entered into in a cavalier manner. And so really I was trying to teach concepts of leadership. And so in the game Excalibur, I make you as King Arthur. I give you the task of unifying Britain. Now, unification is entirely different from conquest. That is, you have to convince people of your authority. You have to convince them to follow you, and that involves more than merely brute force.
Chris, we have a little bit of time left. Can you get Excalibur up on the screen and show us just a piece of that?
This is the title scene to Excalibur, and it's does nothing more than give the title and set a tone and show off who did it.
Mm-hmm. And this was designed to run on the Atari 800, or?
Yes, I've cut it off. This was designed for the 800 with 48K and a disk drive. It's a huge game. It actually won't fit on the 800. It requires disk swapping. And so you bring in whole chunks of game at a time. It's actually 66K of object code. Very, very large game, all written in assembly language.
Okay, well, if you've played Raster Blaster or messed around with Pinball Construction Set, you've been manipulated by the mind of Bill Budge, one of the premier game designers. We'll meet Bill and the president of Electronic Arts in just a moment. Joining us now is game designer Bill Budge, who works with Electronic Arts, and the president of Electronic Arts, Trip Hawkins.
Bill, there's quite an array of games out here on the table. And what is it that makes a game successful, or what kind of factors go into the design of a game?
It's really hard to, you can't ask people what they want to see on the computer and what kind of programs they want. I really think that a person writing a program has to have an inner conviction of something and write a program that they want to write and a program that they want to use. When I started writing this program, it was something I really wanted to do. I wanted to see it work. And
where'd you get the idea for
I always liked building things, and it was a funny indirect kind of process. I got tired of writing video games. I was really sick of playing them by this time. And I thought, well, it's fun to make video games. I still kind of like to write them, and I bet other people would really like to write them.
You're talking about the pinball construction set.
Right.
And this is kind of a nice game because it actually involves you in the construction of the game itself. It's kind of like a metagame. Is the success of that been pretty good in the sense that, is there a special segment that you're selling to as far as the construction set?
Well, when you start out, yeah, you're looking to the really avant-garde computer users. It takes a while for the message to get out there when everyone is still discovering Pac-Man and a program comes along that's telling them they can build video games. Well, it doesn't register at first, but it's got a slow growth that builds up, and finally now we're getting very good results. So the game kind of craze dies out. This stuff's taken off.
Trip, on the business side, what do you look for a successful software game?
Well, I think Pinball Construction Set has a lot of the things that you look for, and that's why it's now one of the top 10 sellers in the country, according to Billboard magazine. We have a philosophy of having products that are simple, hot, and deep. Simple so that you don't have to read a lot of instructions. Of course, most people don't want to have to learn how to operate the computer. They want to just do things with it right away. And Pinball Construction Set, you can immediately play one of the pinball games that are included, or you can quickly make up one of your own, and it's very simple to do that, as I think Bill will illustrate. We also like to have products that are hot in that they should fully use the sound and graphics and other capabilities of the machine. And we also look for programs that are deep. In the case of Pinball Construction Set, you can make your own pinball games, so it has a lot of creative possibilities and allows people to control what they're going to make and interact with it and change it. And that's one of the things that extends the life of the product and causes people to come back to it again and again.
Bill, it's kind of fun to take a look at this.
I'm dying. I'm dying to say. Go ahead, Bill.
Okay, well, this is a very simple sort of real-world idea. It's a construction set. You have something that you're building on this side of the screen and a set of parts over here. And I have a hand here that I control with the joystick, and I use that to move things around, say, on the board, the game I'm building. I can modify this game. And I can get parts out of the box, and I can just add them over.
So they're kind of bumpers you're putting into your game?
I'm just putting bumpers, yeah. This is a favorite of really young kids. They like to just grab a whole bunch of bumpers, fill the board up with them, and put a ball on there. A pinball aficionado would gasp, but little kids don't really build pinball machines. They just sort of build things with this. And I can get a ball and put that over here. Then if I want to try out the game, I can just push this menu selection right here, and the game starts to play. Now, you can see I've got two balls, one up there. I can launch this one, and I can go out and play the game a little bit, and the balls drop down at the bottom eventually. But before I let that happen, I'll just go back to the parts box and start editing again, get rid of some of these.
Bill, this was kind of a new level, I suppose, of computer game where you really can design the game yourself. What, if you can tell us, what are you working on now? What would be the next step in computer games?
I want to extend the idea of a construction set. I think this one was hard to do when I started, and because there are lots of combinations and things you can't really predict when you're making a kit to make a meta game, as you said. I'd like to extend the idea even further, and the problem there is then designing the parts box. In pinball, it's a small set of parts. You don't really have to worry about thinking up abstractions. In a general construction set, it's not clear what the parts should be. It's almost like you're inventing a new language for representing specifications for programs. It gets very difficult computer science problems.
Trip, at the arcade level, we hear that maybe games sort of peaked and people aren't quite as interested. Are computer games here to stay, or is it a fad?
I think computer games are fundamentally different from video games, mainly because computer technology in the home can be extended and become a much broader base of technology. Just as an example, all of these programs that we're talking about here, they come on floppy disks, and each one of these holds much more memory than can be held in the memory of a coin-operated arcade game. And it really is, it becomes a question of the program size when you finally want to know how good a program can I have and how much can I do with it and how long will it take before I'm bored with it or I've exhausted the educational value. And I can get, something like 3 or 4 times more program on here than I can fit into the memory of a coin-operated game.
Okay, you've got one-on-one there. Maybe we can get it loaded. Well, I think, Gary, you had a question.
Well, the only thing I was going to mention is it seems like the games have gone from relatively unsophisticated games to something that requires a lot of sophistication in terms of programming, and the memory size is really an important thing, important aspect of that.
Yeah,
it's hard to really put that back into 8K.
Has that been the difference, really, in the early computer games? Pretty limited now. The incredible graphics and speed. Has it really been a function of the available memory?
Part of it is just programmers getting better, I think. Not many people wrote video games 5 years ago. There was a small selection. Now there are thousands of people who are capable of writing a good video game. And a few people have upped the ante, so it's not enough maybe to write a video game. You have to write a video game plus a game editor. I think the more popular games really have these extra features built in.
Can we get one-on-one in there? That's a kind of exciting demonstration of what you can do. And I think, Trip, you're going to take on either Dr. J or Larry Bird here. Is that right? Tell us about one-on-one.
Well, the basic idea of one-on-one was to get these two guys, Julie serving Larry Bird, who are probably the two best-known basketball players and probably the two best forwards that have ever played the game, and to capture their personalities in the game. And so we decided to hire them to help us design the game, and we had photo sessions where we took pictures of them in action. In fact, we had a camera mounted at mid-court just exactly from this angle while we photographed them. And then we worked with them on prototypes of the product where we'd sit down and talk to them about the moves that they would use and some of the strategies and the shooting percentages that they would have in different places on the court. And that was a fascinating learning experience.
But you say programmed in the personality. I mean, these characters play like Larry Bird.
Very much so. In fact, why don't I go ahead and get started? Yeah. Right now they're playing against one another in a demonstration game, but if I press the button on my joystick, it'll take me to a menu, and I can quickly make a selection. I want to play against the computer. I'm going to allow the computer to play Larry Bird. And I'm going to play at the varsity level. There are different levels depending on how good a player I am. And now I go ahead and start the game. And that's Larry Bird taking an outside shot, and he hit it. Now, Bird is particularly effective at outside shots. But watch Julius now. I'm going to be able to drive around him, I hope. Whoops, he stole the ball from me.
Now, you're Larry Bird now.
No, I'm Dr. J.
You're
and
Dr.
Unfortunately,
J,
I let Bird steal the ball.
Larry, okay.
He's trying to work his way into the basket. So he's got a quick 4-0 lead over me. Oh, now I have to have the indignation of seeing on an instant replay.
That's great. Where do you think, Trip, the software games are going to next? I mean, what's the next generation of this kind of stuff? I hate to interrupt you, trying to get back on
screen. Well, I had to have a slam dunk there. Sorry.
Yeah, what's happening next? I mean, what's the next tier, the next level of computer
Well,
games?
at a really simplistic level,
it's very easy
to it's very easy to extend the realism and the graphics that are in the current products, and I think it's also you're going to increasingly see more creative possibilities for the player, which is I think where a lot of the educational value comes from. Being able to create your own pinball game is one example. We've extended that with Music Construction Set to a product that is about music, and of course there are a lot of people that are really interested in music and interested in having their children learn about music, and it uses a lot of the ideas that Bill pioneered with the pinball construction set. And I think that the area where the greatest challenges will come is in looking for original ideas and new creative ways to break the mold. I mean, a lot of people look at what other people have done and try to do something that's a spin-off from that, but the really creative geniuses in the industry are capable of coming up with something completely new.
Do they just come to you, they say, we've got an idea and here's a program I've written, and then you turn around and sell it?
It happens all different ways. We have one of our better products, it's called Hard Hat Mac, and 2 high school boys came into our office one day and they had 3 sheets of high school notebook paper they'd drawn up in their physics class, and we signed a contract based on that.
Gentlemen, we're out of time. Bill, Trip, thanks so much. Thank you for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random access is made possible by a grant from Popular Computing, a McGraw-Hill magazine. In the random access file, Hewlett-Packard has made another major move into the personal computer field with a new portable printer designed for the PC market. It is a non-impact inkjet printer with low noise operation, battery-powered, 150 characters per second, and an 11 by 12 character matrix. The price is under $500, and it will be available next month. IBM in the news again this week. First of all, IBM announced a licensing agreement with Intel to allow IBM to produce its own 8088 chips, the microprocessor used in the PC. Tremendous demand on Intel's output of the 8088 has kept IBM from producing enough PCs to meet its demand. Perhaps more important, though, is the fact that Intel apparently also gave IBM the right to make its own 8286 chips, a much more advanced microprocessor, which analysts believe IBM will use in its new personal computer, codenamed Popcorn. With the ability to turn out the chips, it is thought that IBM may now be able to introduce the Popcorn this summer. The use of the advanced microprocessor will enable Popcorn to do sophisticated graphics and other complex integrated functions. Sounds like Popcorn may take on the Macintosh Lisa crowd. Victor Technologies, the high-flying hardware computer company which took a nosedive this year, may be bought out by the British firm Applied Computer Technologies. The would-be buyer indicated it might close down the Silicon Valley factory and move operations to Scotland. Also on the ailing list, Tandon Corporation, the nation's largest maker of disk drives, says it will lay off about 1,000 employees and transfer most of its manufacturing overseas to cut production costs. In fact, countries all over the world are dropping in on the Silicon Valley trying to get a piece of the high-tech action. In the last year, 20 different countries have sent delegations to the Silicon Valley in an effort to lure their business abroad. The countries offer incentives such as government subsidies and attractive tax packages. The most successful recruiter by far has been Ireland. One foreign country very much on the mind of high-tech executives is Japan, with particular attention focused now on the debate in the Japanese parliament on a new proposed software bill which would limit software copyright protection for U.S. products to 15 years and force American companies to allow Japanese firms to sell U.S.-made software. The net result would be little protection for American manufacturers, with Japanese companies able to sell the same software at a lower price by avoiding the high research and development cost. And speaking of software, you say you have a modem but can't use all the bells and whistles because you don't have the right communication software? Listen to Paul Schindler.
Okay, it's all set. 3 men in a monkey suit. Listen, I'm going to have to get back to you later. Bye-bye. Communications. Did you know that using one of these devices, called modems, computers can talk on the phone, just like us, only faster? But if you already have PC communications, you might be surprised to hear that you're in a minority. Fewer than 1/4 of PCs communicate. So many of you are waiting to make the plunge. Perhaps the hundreds of communications packages on the market have daunted you. Well, the Whole Earth Software Catalog and Review has sorted communications out for beginners. Now, if your computer runs the CP/M operating system, we suggest you consider MITE, or Modem 7. For users of the IBM PC, the best packages are SmartCom 2 and Crosstalk 16. PC Talk 3 is more limited, but then at $35, it's also the cheapest communications package. Apple computer users may want TSC Terminal if they use 40-column screens, or Data Capture 2 for 80 columns. Commodore and Radio Shack users will find CompuServe's VidTex a best buy. Now, there simply isn't time to get into all the wonderful things you can do once you have communications, but believe me, a PC on the phone opens up new worlds. Just ask someone who already has a modem. Call them, or call their computer. For Random Access, I'm Paul Schindler.
Next week, Paul takes a look at Ken Houston's professional blackjack program. Well, the hot software this month, tax preparation programs. 2 of the more than 20 tax packages have hit the software top 10 this week. The 2 bestsellers are Tax Advantage from Continental Software. It sells for about $70. And Tax Prepare from Howard Soft. It's a bit more complex and sells for $250. And as if you hadn't noticed, there are still more computer magazines coming out on the market. The latest count shows more than 300 computer periodicals. The fastest growing ones are Compute, Personal Computing, Popular Computing, and InfoWorld. Finally, the last place you want to see a computer, let alone a robot, is in your neighborhood bar. Yet it seems the sweep of technology has no limits. In San Francisco this week, the world's first robot bartender was unveiled. The robot can talk, can take spoken orders, and can mix 200 different drinks. But on the first test run, when the waitress yelled out, "Give me a Bloody Mary and a beer," the robot knocked a glass off the bar and onto the floor and poured beer all over the counter. The robot's designer said there were still some bugs to be worked out. Kind of makes a human feel good. That's it for this week's Random Access File. I'm Stewart Cheifet. Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Gary, we've done a lot of shows about computer hardware and software, but of course it takes people to design and build these things, and that's the subject of our program today, the people in the computer business, and I guess the Silicon Valley is in fact as famous for its young entrepreneurs as it is for its products. And speaking of young entrepreneurs, you're one of them, having founded Digital Research about 9 or 10 years ago. Gary, how has the people side of this business changed during that period?
Well, I know I've traded in my cowboy boots and blue jeans for a three-piece suit here, so some changes have gone on. I think the biggest change I've seen has been in, say, the impact of just having no products that are competitive at all to a market now where everybody's in there, including IBM, that have multi-million-dollar budgets, and you've got to figure out how to work around big giants like that. It's become much more professional, and the stakes are higher, and it's been a lot more fun, I think.
Okay, we're going to meet some of the superstars of the computer field. We'll meet a man who's called the father of the Silicon Valley. We'll meet a man who revolutionized the computer business by coming out with the first low-cost portable. And we'll meet a woman who didn't know a computer from a commuter, but she's now the CEO of a major computer company. First, let's take a look at some of the other people who played a key role in the evolution of the computer business.
Those of us involved with micros back in 1974, 75, we had not already designed all of the interface cards and the peripherals and the software that goes into the mini computers of the day, or the larger systems. And to us, it was so exciting because it was like we thought we were doing the things for the first time they'd ever been done. And it was the first time they'd ever been done that cheap, using a lot of the LSI technology. And so there was a lot of just the excitement everywhere we went. It was like putting out a little table and showing off a little card that would play music on a computer or make color was the most exciting thing in the world, and we thought we were way ahead of the rest of the world. What I was doing around that time was not even thinking about what are the right steps to take to have a very large successful company or a large successful product. It was just, I had been working my whole life to build a certain type of computer for myself, and I just built the best one that was doable in that day with the particular components available, etc. And in that sense, it wasn't like an intelligence that can lead you towards the right path. It was just being very free. I had the freedom because I was only doing it for myself. It was not a company project where a manager defined what had to be done. So I was lucky to be able to do what I did. Everywhere I go now, I go to business meetings and presentations, and they're all sitting there in three-piece suits. It's a large business. There's a lot of dollars involved. The people who have come out of school trained to run and manage business is the key element today, and that's where most of the creativity is going. There's very few technically creative products in the microcomputer world.
Is a garage operation still feasible in the small computer industry today, or is that stage over?
Well, that stage is pretty much becoming over for hardware. It used to be people could quickly manufacture some simple little PC boards on a small budget, get an ad in a little hobbyist magazine and start selling a bunch of them. And so very small entrepreneurships, thousands of them sprung up, many of them centered around Apple. That was probably the biggest direction to go. Now it's pretty much that's possible for software groups to come up with a good software project, and there are avenues to find companies that will market it for you or turn it into a product if you got something good going. Perhaps once a decade, a very large market comes from zero up to billions of dollars within a few years. It's very rare that there's such a dramatic explosion out of nowhere of a new market. It may happen again in microelectronics and computers before too long. Maybe every 10 years, a new group of people come out, and they haven't been along with the Apple and the thousands of peripherals and the thousands of softwares, and they think every time they're doing it for the first time ever. They're going to get a couple of their own hobby computer magazines that are in their group. They don't come to our group. They're going to start talking and having little trade shows and showing each other projects, and they'll start new businesses of their own. And I think that's probably about to happen. It's like you go to a trade show and they pull up in their mobile home, and it's a little garage shop, you know, they pull it out the back and they show it off, and you want to buy a couple, and you know, these may be very large companies in a few years. But right now we all shun them on them. We just say, oh, you know, there's just a couple guys who drove out of their home with it. That's what they said about us. Yes. You can understand it. When you're looking down at someone else, you can understand how you were perceived back in those days, and then you also realize they were right. It's just a quirk of fate that they were wrong.
Though the computer industry is quite young and heavily dependent upon technology, it is the people who make it grow. Throughout this series, one can find some of the most influential individuals in the entire industry. Our very own Gary Kildall created the first standard operating system, CPM, or control program for microprocessors, in 1974. In 1975, he started Digital Research, one of the top software development companies in the world. Al Shugart, a pioneer in magnetic storage devices, founded Shugart Incorporated, which he later sold before founding Seagate Technologies, also a disk drive manufacturer. Ed Feigenbaum is a professor at Stanford University and a noted author on the fifth generation, artificial intelligence, and expert systems. J. David Eisenberg is senior engineer of software development for Apple Computer. Dr. Kazuhiro Fushi is director of Japan's fifth generation project. Bill Budge is a game developer for Electronic Arts. Wanda Smith is Hewlett-Packard's Human Factors Engineering Manager. David Nitzen is an expert in robotics. Professor Patrick Supis of Stanford University is a pioneer in the field of computer-aided instruction. Dr. Roger Summit founded Dialog, one of the original online databases. John Couch made a big contribution to the popularization of integrated software as head of Apple's Lisa project. Michael Arendt is a commercial artist who uses a computer as a design tool. Stanford University professor John McCarthy developed Lisp as a fundamental language for artificial intelligence work. And of course there are many more. It should be noted that the computer industry is made up of many different kinds of people, performing many different functions. In our next segment, we'll meet some more fascinating people. So let's go back to our program.
Joining us now is Adam Osborne, formerly of Osborne Computers and now CEO of Paperback Software, Inc., and Laurie Harp, CEO of Vector Graphic. Gary?
You know, Adam, you and Laurie have been in this business for a long time, as long as I have. In fact, I remember you when we were at Intel, we were working on some documentation together, and that must have been in '73.
That's right. Yes.
And I know that a lot of viewers probably have some questions about, you know, is it possible really to get into this industry now, or has it been completely dominated by companies like IBM and Tandy and so forth? Is there a place for a young inventor to really make his mark?
Well, I think that all depends really in what area. If you want to build a microcomputer, it's probably not a good idea at this point because it's going to be the clash of the titans now. There's nothing high-tech about microcomputers anymore. It's very simply, you know, it's like building a washing machine or a refrigerator, quite honestly. It's the economics of volume and reliability, and that's it. That's the end of it. If, on the other hand, you want to go into some other area, good grief, you know, there's probably more opportunities today than there's ever been. It's just that you're better off building razor blades rather than razors.
If the opportunities are not in computers, where are these areas in which there are opportunities?
Peripherals, add-ons, software. You can make a lot of money with extra cards that'll fit into a popular computer, attachments, peripherals, particularly the software industry. Now, it's very much in its infancy right now. The organization and methodology is going to undergo massive change, but on the other hand, there will be probably 10 to 100 times as much software sold every year, 5 or 6 years from now, as there is now. Obviously, that's hypergrowth. Obviously, that's where there are the opportunities.
Adam, you talked about the titans, by the way. Who do you see as the titans right now?
Well, IBM's obviously there. I'm quite certain that AT&T are going to come in to challenge them in a big way, and there will be one or more Japanese companies that come in as well, and they're going to dominate the market.
Laura, you are in the business of making computers now. Do you agree with Adam's perspective?
Yes, I would say, what he said is pretty accurate. And to just go back to your first question, is it possible for companies to get started today? I think the costs involved are going to be prohibitive. When we started our company, you could do it with $5,000, a lot of sleepless nights, and you would be rolling. Today, that's an impossibility. I mean, capitalization has to be several $1 million, and you still, I don't think, have enough money to really get enough critical mass in short enough of a period of time to, to be one of the contenders. But the peripheral market, and I think especially in the area of communications, is going to be extremely significant to make add-on devices that link the kind of systems that have been installed to, together.
When you talk about communications, you mean like communications with the source or CompuServe and hooking small computers up with...
yes, that's part of it, right.
I think another important point is that large companies, the Titans, really only get into an area of software or hardware when it's been proven to be successful. IBM is a good example of that.
Oh, absolutely.
And the small garage shop operations have opportunities where the large company is just not willing to put the effort. Yeah. And so those are the spin-off areas that I think that will be...
There's also price consideration as well. When people are talking about investing thousands of dollars, they tend to be very careful about where they're buying because it's an investment. When they're buying a $50 product, or even up to maybe sometimes a couple of $100, they say, what the heck? If it doesn't work, I've learned something. That's why a lot of these very inexpensive computers sold as well as they did later just to collect dust. There never will be an IBM in software, for example, because you're now eventually you'll be dealing with $50 products. And there's the vicariousness of human nature. Everyone's going to want to buy that little something different. And it's only a $50 investment.
That's where a lot of the real inventors are going to show up, would be in the software area. Right. There's a comment you just made about the number of small computers that are gathering dust. Do you have any just ideas of what you think the number of, or the percentage, say, of personal computers that, let's say, below the $1,000 mark, that are actually being used productively, in, say, a home room?
I would say probably 50% are catching dust. I have no way to totally substantiate that because I don't think a lot of research has been done on non-utilization of computers. But I personally know several people who had gone out in the early days, bought a Radio Shack, bought the early available computers, and are going out now. They bring them home, and they really suddenly realize they don't have quite the need they thought they had for a system. I would say probably 50%. I don't know if you agree with that, Adam, but...
Well, we've done a little bit of research in this area. It does tend to vary quite a lot by brand. The ZX80 and ZX81, probably more than any, are now collecting dust, simply because they were bought initially by people who just wanted to find out what a computer was all about, and they spent $100 doing it. So that it served its purpose, so the fact it's collecting dust is no longer an indictment of the product. The Commodore 64, we find, more than any is collecting dust, and that's a lot of it to do with reliability problems where people just say, they're just not going to get it fixed when it stops working. It only costs $200 in the first place.
It seems like a lot of the inventiveness that's going to go into software is really going to be around products that really make personal computers are useful in the home, and take them out of the closet. Well, if they haven't been purchased yet, but actually make when they come into a home that they're actually used in a way that's productive.
Is that a concern of the industry, Adam? You suggested, well, it doesn't matter, something like the Sinclair. Well, it served its purpose. Or are people in this industry concerned about making sure that, I assume you want people to use these products, because then they'll go out and buy the peripherals and buy the software and so on?
Well, it depends really on each company and what direction the company is going into. We, for example, have no intention of going into the home computer market where, you go into this under $500 rat race. I mean, the economies of scales in manufacturing companies such as ours can never accomplish that. So, from my vantage point, it's not an area I'm interested in. I mean, anything under $3,000 is, an absolute no. For our company.
We hear about the falling out that is starting to take place and will take place in the computer field, and Adam Peoplesite, your company, is one of those examples. Is that, in fact, something that has to happen and is going to happen?
Well, Osborne Computer's failure was nothing to do with falling out. It was nothing to do with industry competition or collapse. The company, plain and simple, committed suicide. All I will say about it right now is that everything you have read in the paper you can hit the reset button on because it's not right. This is not yet the right time for me to say what really happened, so I'm not going to.
So you don't, Adam.
That's right. No, but very specifically, your answer is partially yes and partially no. If IBM were not consuming 70% of the market, which they are right now, today. You know, the numbers that you read about are actually inaccurate. IBM dominates the market far more than any of the statistics you read. What I like to say, you know, I've said before, is that IBM is one, there is no second. You know, after IBM, it picks up again at somewhere like 5th or 6th. You know, if they weren't there, clearly a lot of other people would be able to do a lot better. But on the other hand, if you take 30% of the market, it is so huge that it will support an awful lot of people who are selling 3, 4, 5, 10,000 computers a month. Sure, there'll be a shakeout, but then, you know, there's been a shakeout in the hardware industry. Gary, you remember a lot of the early companies. Where's InSight? You know, where's MIPS? Yes, I mean, it's been going on for years. It's nothing new.
Okay, you mentioned IBM, and of course IBM is a key player. We're going to soon meet a gentleman who played a key role at IBM and in the IBM competitors. That's coming up in just a moment.
We are unfortunately limited to brief comments about a very few computer entrepreneurs who typify the vast contributions of their colleagues. But we can't leave this subject without one more example, that of the original Silicon Valley garage-based startup, Hewlett-Packard. William Hewlett and David Packard both graduated from Stanford University in 1934. The two engineering classmates became close friends and formed their partnership in 1939. Their first plant was a small garage in Palo Alto, and their initial capital investment around $500. Their first product was a resistance capacity audio oscillator based on a design developed by Hewlett while attending graduate school. Hewlett-Packard has grown to be a major designer and manufacturer of computers and computer peripherals, test and measurement instruments, handheld calculators, electronic components, medical electronic equipment, and instrumentation for chemical analysis. The company employs about 70,000 people worldwide, with annual sales between $4 and $5 billion. Packard and Hewlett have been extremely influential in the industry, and both remain active in the company as chairman of the board and vice chairman respectively. We'll meet Gene Amdahl in our next segment, so let's get back to our program.
Joining us now is Gene Amdahl, formerly of IBM, formerly of Amdahl Corporation, and now of Trilogy Systems, Inc. Welcome, Gene.
Gene, I think it's very interesting to have your perspective on IBM and the IBM PC lookalikes that have come out here, because you've been, if there's anybody that's been working with following IBM and trying to get at that customer base, it's been Amdahl. And so what is your feeling about the IBM PC clones or the lookalikes? Can they be successful?
Well, I'm not as familiar with the PC area as I am with the large computer area, but I am quite familiar with IBM, and their pattern really hasn't changed over all of the years that I've known them. And that is, they move into a field when the field is just proven well enough in terms of it becoming of a size sufficiently large to be of interest, and secondly, that somebody has learned what it takes to satisfy that market. Once this is learned, IBM is then ready to move in for their share of the action. And if they have the same degree of success in this area as they had in the high-performance area, their architecture will become a de facto standard not because they will have the best architecture, but because so many people will be expecting them to be successful. And the cost of developing your applications on even your personal computer are going to be sufficiently great so that even as a person, an individual, you really won't like to change architectures in order to progress through the advancements.
Now, how do you track a change that IBM might make in the future? If there's one company that I've seen that's probably more secure than even Mattel or the U.S. government has been IBM. And when you stock up your large inventory, how do you take care of that transition IBM might make, say, in a moment's notice?
Well, you can't do it perfectly, but if you are in a portion of the field where the technology or certain functional limitations have formed the boundary of where you could go, as those possibilities get moved forward, then, or as you expect them to be moved forward, you can expect that the offerings by IBM are most likely going to move in that direction.
Okay,
and
so you have sort of indicators of what's going on, right? Laurie, I know that you've been involved very closely with the whole industry as it's switched toward IBM hardware. What are your feelings about the PC clones?
In my opinion, they're not going to have a future. I think right now they're enjoying a tremendous wave because of the inability of IBM to deliver in sufficient quantities. And I think most of the clone companies, if you look at them carefully, are not creating any value. They are putting hardware together, they're buying software that is available to everyone, and they're not really creating anything that makes them proprietary. And I believe that if IBM takes a different turn, a lot of the software generators will follow suit, and many of the clone companies have to protect some of their installed base, and I don't think they can turn as quickly as IBM will, because IBM will have planned this move, a year or more in advance. So quite frankly, I don't think that they're going to be a long-term solution.
Adam, you described earlier the computer business now is like the dishwasher business, basically, and Gene said that IBM's power is really not that it has a better technology. Is the computer business now not really as technology-driven, but marketing and advertising and packaging?
Well, I think that the major difference between the PC market as it is today and the industry that Gene was talking about is the fact that it's really got nothing to do with high-tech anymore. For that reason, I would both agree and disagree with what Laurie said. I think the bulk of the clone companies existing today won't make it. The reason is that they look upon themselves as computer manufacturers. However, I believe that there is a vast market for clone companies. The reason is that a rough kind of estimate that we've made is that there's something like 15% of the market where hell will freeze over before they'll buy IBM. There's another 15% of the market that don't care, and 70% of the market who prefer IBM. Now, 15% of the market is huge. Furthermore, there's another consideration. If you're talking about people who are looking at it as though it's a dishwasher or a refrigerator, you're now talking about people who can come in to a huge installed base. IBM is shipping 10,000 PCs a day right now. It doesn't really matter very much if they do go on to something else. The base they leave behind is so big that there are a lot of people can run out their inventories. And furthermore, because they're building entirely on a low-cost, high-quality basis, you get somebody who comes in who knows how to manufacture, and they can start eating into the IBM PC market more than they ever could a mainframe market, because it's the same. For the very fact that it's the same, people eventually say, well, what have I got to lose? If a piece goes wrong, it's almost interchangeable.
So the companies that would be successful are the ones that think of themselves as manufacturing companies rather than computer companies.
That's right, absolutely.
Gene, you've been in this for a long time, starting Amdahl some time ago, starting Trilogy recently. Let's talk about the venture capital situation. How is it different now in trying to get a computer company going than it was a decade ago?
Well, a decade ago, there was a great recession. There was also a situation in which the capital gains taxes were much higher than they are today, some 50%. With the capital gains taxes like that, and with the recession, the stock market for new issues was abysmal, to say the least. It was essentially non-functional entirely.
And how about today?
Today, there's a rather buoyant market, extremely buoyant compared to 10 years ago.
Lori, what's your perspective on venture capital today? You just went through that, didn't you?
Well, I went through it twice, once in '79 when the venture capital pool was just growing, and I went through it again today. It depends on at what point in time you actually go out to look for money. In the history of Vector, having gone through the difficulties we have gone through, we did not have too much leverage to determine determine price because we needed the cash so badly. But in many startup situations where you have something that has a very good angle, you are the ones who can really, you're the one who can essentially determine price, because there are not that many good deals around, but there's a tremendous amount of venture capital available.
I'm sorry we're out of time. Thanks so much, all of you, for being here with us. Thank you for joining us on this edition of the Computer Chronicles.
This program has focused on some of the more successful industry entrepreneurs, those who had vision and an insight into the new technology and the perseverance to see their ideas through. For the most part, these individuals had strong technical backgrounds as engineers, programmers, scientists, and the like. And this was enough to get the business off the ground in its very early phase. Later, there came a second phase in the enterprise when a different kind of entrepreneurialism was needed to take the enterprise from a strong technical startup into the successful mature business. Once the ideas are formulated, the investment capital is secured, and the assembly lines are rolling, the product must be sold and serviced, and continuing return realized on the investment. That's when people with strong marketing and financial backgrounds are needed to make the company profitable. Good marketing people are trained not necessarily in high-tech or electronic fields, but in business and product marketing. As the computer industry matures, it becomes more and more like any other business, with all the various departments: design, manufacturing, marketing, sales, public relations, advertising, and the like. The only difference is the speed at which the computer technology changes, which continues to promote competition and entrepreneurialism by all participants in this dynamic field. Our next lesson covers computer security. Be sure and read Chapter 23 of your text, and I'll see you then. I'm Herb Lechner.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Our subject today is the fifth generation, the computers of the future. These are sometimes known as expert systems or computers dealing with artificial intelligence. They're sometimes called KIPS, K-I-P-S, Knowledge Information Processing Systems, or sometimes for short just knowledge-based systems. And our guest today will be Edward Feigenbaum. He's one of the founding fathers of the field of artificial intelligence, and today one of the world's leading experts in that field. Gary, Feigenbaum calls it the fifth generation. Is this just one more technological advance, or does the fifth generation really represent a kind of quantum leap into a different kind of computing?
Well, it certainly does represent a quantum leap. The major evolutionary changes in hardware over the last 40 years in computers they've been referred to as generations. But the fifth generation is really a Japanese slogan that underlies their effort at a 10-year national program to produce what's been called the Knowledge Information Processing Systems, or KIPS. At the heart of these KIPS systems are knowledge-based systems, knowledge-based software, and that's a technology that's really grown up in our own country's field of artificial intelligence. Today we're going to be looking at the knowledge-based systems or expert systems, and also take a look at what threat the fifth generation poses to the U.S. Computer industry. We have a short segment here that shows the use of computers in today's society. This is an example of actually robotics, and we'll see how more advanced applications as our session goes further today.
This computer tape librarian is a robot. It responds to commands from departments all over Stanford University, loading and unloading tape reels, storing them in precise slots on a shelf. It performs what would be a dreary and repetitive task for a human being. It is computer controlled and it follows instructions, but it does not make decisions. The robot can't advise the operator, for example, on the best way to store his tapes, or what to do if one is misplaced or damaged. It performs a simple task the same way every time. But suppose the machine could give advice, that instead of just processing data or answering a command, it had enough knowledge stored to manipulate facts and make a decision. This new kind of computer, one that can intelligently use the information stored inside it, is now being developed. Often referred to as the fifth generation, it is the next step in making the machine approach and perhaps even duplicate the way a human being thinks. A hint of what we may soon have exists today in what is called an expert system. It requires two kinds of knowledge. First, documented facts, and second, heuristic knowledge, or the same kind of ability that a human expert needs to make a good judgment based on experience and practice. Building this almost intangible talent into a computer's memory is called knowledge engineering, and the country that first masters that technique will be in a unique global position. The race to achieve that position has already begun.
Our guest today is Edward Feigenbaum, professor of computer science at Stanford University and author of the book, The Fifth Generation. Also joining us is Herb Lechner from SRI International. Herb appears frequently on this program to lend his expertise to the subject. Gary?
Well, I think it's a real honor to have Ed here today to talk about expert systems. If there's ever an expert in expert systems, he's got to be sitting here today. It's, I think, a very exciting topic for me, especially since it's probably one of the most promising new software areas that we're seeing coming up over the horizon. Artificial intelligence seems to be one of those areas that's kind of a moving target. Things that 10 years ago were topics of discussion in AI tend to become practical applications. And I think knowledge-based systems tend to be in that category right now. Could you give us an idea of basically what knowledge-based systems, expert systems are all about?
The computers, as you know, are general symbol processing devices capable of manipulating any kinds of symbols, of which numbers constitute one important class, but computers are much more general than that. We've known about the generality of computation since at least the time of Turing in the 1930s, and actually I've tracked it back to intuitions that Babbage had that were reported by Ada Lovelace, after whom the Ada programming language is named. In 1842, Ada Lovelace wrote that the analytical engine of Babbage's constituted the link between the mechanical world and the world of the most abstract concepts. That currently, in the modern terminology, is called the physical symbol system hypothesis and is the basis for artificial intelligence work. In artificial intelligence as a science, we talk about the use of computers to process symbolic knowledge using logical inference methods, symbolic inference methods. In other words, we're talking about inference and not calculation in the traditional sense. We're talking about knowledge and not numbers in the traditional sense. When we talk about knowledge, we mean not only the factual knowledge of a field which is available in the open literature, it's published in textbooks, it's commonly agreed upon by experts in the field, it's delivered in lectures, but we're also talking about a much more subtle kind of knowledge which we call the heuristic knowledge of a field, the experiential knowledge, the non-rigorous knowledge. George Polya, the great Stanford mathematician, in popularizing this in the 50s, called heuristic reasoning the art of good guessing. And we'd like to invest computers with the art of good guessing. And the people who do that for practical applications are called knowledge engineers. They build and test and revise programs, and these programs are called expert systems or knowledge systems. Usually the goal of the expert system designer is to design a program whose behavior will match the behavior or exceed the quality of behavior of human professionals, experts in a field. Those are the programs which we normally call expert systems. The expert systems work has been going on since about 1965, the beginning of the second decade of artificial intelligence research in this country. At the time that the expert systems work developed, the artificial intelligence field was focusing on the concept of generality as signifying intelligence. Not performance, but generality, the ability of a program to shift its attention from one area to the other easily and solve problems. The expert systems people, initially at Stanford and then later at other places, took the other approach, that if you wanted to create programs which were very intelligent, which performed at the level of human experts, you had to encode a great deal of knowledge about a field. The key result of 17 or 18 years of work in this area now is simply that. Knowledge is power. The primary source of power in expert systems is the knowledge that they contain, and of only secondary importance is the inference procedure that they use for drawing out the lines of reasoning. This turns out to be true of all areas of artificial intelligence, not just expert systems, and in fact, you can see it in the work that goes on in understanding natural language, where a great deal of world knowledge needs to be present for the programs to disambiguate natural language utterances. We see it also in the AI vision programs, image understanding. It's very difficult to understand a picture unless you know something about the world represented in that picture. What a river looks like, what a railroad looks like, what a city looks like, what a cloud looks like. All of this focus on knowledge has really led to what is called the shift to a knowledge-based paradigm in AI. And that's probably the single biggest event that's happened in the second and third decades of AI work.
So the context around the problem is really important, or is a very important part of that.
It's very
solution.
difficult to understand problems, to achieve goals, to understand utterances and signals, unless you have a great deal of knowledge.
If we take expert systems in particular, is it fair to say that this is something now that's moving from the university environment into industry, that it's becoming industrially acceptable now to use expert systems? And do you have any comments on that?
Well, that's what all the excitement is about. We see a kind of frenetic pace going on, newspaper articles and TV shows and all that on the subject of artificial intelligence. It's caused by that transition. We're beginning to see the industrialization of AI. We're beginning to see the kind of transition that took place in the late 40s and early 50s from laboratory to industry and computing in general.
Ed, what are some of the applications that have seen the light of day utilizing these knowledge base and artificial intelligence techniques?
By now there are hundreds of them, so I can just skim the surface. The granddaddy of all these applications was started in 1965 at Stanford by Professor Lederberg in the medical school and Professor Gerasi in chemistry and myself. That was an application to chemical analysis, where data from physical instruments were analyzed in terms of chemical structures that may have given rise to that data, a program called the Dendrol program. So there have been several follow-up applications in the area of programs to interpret instrument data intelligently. Subsequent to that, there were numerous applications to diagnostic processes and therapeutic advising in medicine. For example, at Stanford, the MySIN program for consulting about infectious disease diagnosis and therapy. A more recent effort to advise clinicians, oncologists, about the prescription of cancer chemotherapy in the Stanford Cancer Outpatient Clinic. Programs at the University of Pittsburgh for differential diagnosis in internal medicine. In fact, that's a spectacular program that knows a couple 100,000 things about internal medicine, knows about 500 different diseases, 3,500 different signs and symptoms of disease, and does an extremely good job at differential diagnosis. In addition to that, industries have used expert systems for engineering purposes. The configuration of computers from customer orders or business equipment systems. The use of expert systems for assisting in the design of integrated circuits. The use of expert systems for diagnosing equipment failures, for example, computer equipment failures.
On that subject, Ed, let me interrupt a second. I think you have a program you worked on called Drilling Advisor, which helps analyze, for a geologist, a situation like that. We're going to take a break for just a second, but when we come back, Ed is going to walk us through this particular expert system called Drilling Advisor. That's coming up next. Ed, we want to try to demonstrate how one of these expert systems would work, and I know one of your products is something I think you call Drilling Advisor. Maybe you could give us a brief introduction to this program.
Stewart, expert systems are characterized by having extremely high value added. In the case of the Drilling Advisor, the value added is in terms of capturing, replicating, and distributing of expertise. The Elf Aquitaine Oil Company, the French national oil company, has a problem with regard to drilling of oil wells. Drilling problems can be very expensive. Elf Aquitaine has too few experts in the world in order to capture and diagnose all the problems encountered by the drilling teams. These drilling problems can occur on the other side of the world, from France, for example, and they're after an expert system that can capture the expertise and sit it down there at the drill rig. The Elf Aquitaine Drilling Advisor was done in a collaboration with a Silicon Valley venture startup firm named Technology that does knowledge engineering custom systems of the type that you'll see.
Okay, maybe we can roll. We have a brief demonstration now for about a minute and a half of actually how this program works. We can take a look at that right now.
One knowledge system currently under development at Technology provides advice on problems encountered while drilling oil wells. The field version of this system will aid oil well drilling crews to avoid or correct accidents that occur during the drilling process. Since an offshore oil rig may cost more than $100,000 per day to operate, time and equipment lost due to accidents can account for as much as 2% of the total cost of drilling a well. Because few individuals possess the knowledge, experience, and judgment to properly handle drilling incidents, the availability of an advisor in the form of a knowledge-based expert system is expected to reduce lost time and equipment, help train drilling crews to handle problems, and significantly reduce the cost of drilling an oil well. The Technology Drilling Advisor prototype is an expert in the diagnosis of sticking problems. Sticking occurs when the surface crew is unable to move the current drill string up or down. The upper left of the screen is devoted to a typed dialogue between the user and the knowledge system. The entire right half of the screen serves in the prototype to display the internal operation of the knowledge system. This is mostly used for debugging. At the lower left of the screen, the current drilling environment is diagrammed. This includes representations of 6 major causes of sticking. Initiating a session with a drilling advisor, the user types the name of the well. The system then retrieves from its disk storage any information that had previously been entered about this well, including any problems encountered. After determining that this is a vertical well, the drilling advisor requests information about relevant strata and formations in the well. Using a similar format, the user informs the system that a sticking problem has occurred during an attempt to repair the drill string at 4,000 meters. The drilling advisor now focuses its attention on the immediate problem, designated Episode 1 on the screen. First, the system requests information about the drilling fluid and learns that the drill has ceased to rotate.
Okay, Ed, from that portion we saw now, how is that knowledge represented in the program, and how does the program use that knowledge?
The drilling advisor is what's called a rule-based system, and the knowledge is represented in the form of rules which contain 2 sides, an if side and a then side. The if side contains a number of conditions which I like to think of as the relevancy conditions of this piece of knowledge. If those conditions are satisfied, then that rule will be evoked from the knowledge base and built into the line of reasoning. The then side contains the conclusion that can be drawn on the basis of the evidence that's in the if side. Now, the way it's used is in a scheme called goal-directed backward chaining, in which the program works backwards through the rules from a goal to be achieved to some known facts, such as were being accumulated from the user at the console.
Okay, we have a little bit more of the dialogue. Let's take a look at it and see how it works.
Returning to the dialogue, the drilling advisor is asking the user for the free point, the point below which the drill string is not stuck. In this case, the information is unknown. The user indicates that the sandstone strata is permeable and that the specific gravity of the drilling fluid is 1.24. But when the system requests the fluid-specific gravity of the sandstone strata, the user becomes confused. While the previous questions indicated a sensible line of reasoning, the user does not understand the relevance of this question to the overall problem. Rather than answering the question, the user types why. The drilling advisor then presents an explanation of the specific reason that the question is being asked, to help determine the sticking force. This is followed by a more detailed description of the current state of the system's reasoning, including the various factors that must be used to calculate the total sticking force.
Okay, Ed, this part where the user can ask the computer why, how does that work? That seems pretty significant part of an expert system.
We regard these expert systems as assistants to human professionals, and we believe that they will not be used unless they can explain to the human user how they are reasoning. So we have these explanation programs as pieces of knowledge engineering in the system that allow the system to be a transparent box. We shun black boxes. We like the user to be able to peer right through the box and understand how the system is working. Now, in this particular case, the program looks back over the chain of rules that have been accumulating due to the backward chaining procedure, and then spins out the rules that have led the program down to a certain point in the consultation.
You know, as we still have some time here, I think it's worthwhile discussing for a few minutes this threat that you see in the 5th generation Japanese computer systems. Can you give us some idea of what's going on there?
The Japanese government, working through the Japanese Technology Planning Agency, MITI, the Ministry of International Trade and Industry, has established a major national project which they're funding at the level of $450 million worth of government funding and an equivalent amount of industry funding over a 10-year period, aimed at producing hardware and software and applications in what they call the knowledge industry. Applications similar to the one that we've been seeing here, packaged expertise, knowledge-based systems of all kinds. The Japanese overall strategy is a very interesting one. They lack market share in the world computer market. They'd like to have more. It's very difficult to gain market share from the world's leader, IBM. What you have to do is to gain a position in an area in which IBM has not been active, and that's artificial intelligence. So the Japanese want to get there first and fast so that they can gain a good chunk of the market before IBM wakes up.
Are we ahead of the Japanese right now in expert systems?
Real quickly, Ed, we have just a few seconds.
Well, I think we are. We've been ahead for some time. I think with a dedicated effort on the part of the Japanese, we'd better move pretty fast if we want to stay ahead.
And we are out of time, I'm sorry to say. Thank you very much for being with us, Ed Feigenbaum and Herb Lechner, and I hope you'll join us again for another edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random access is made possible by a grant from Byte, the Small Systems Journal, publishers of a monthly magazine on microcomputer technology and innovative projects in the world of computing.
In today's Random Access file, there appears to be a major effort underway by American computer chip manufacturers to regain their lead over the Japanese. The federal government is working with a new trade organization called the Semiconductor Research Corporation, or SRC. Reportedly, more than 20 major electronics corporations are involved in SRC with the goal of producing the world's first 4-megabyte chip by the year 1988. U.S. firms used to control the 16K chip market with about 2/3 of world sales, but Japanese manufacturers have dominated in the 64K chip market with 70%. Chip experts are saying the 4-megabyte chip will require electronic connections of 1 micron or less. If you don't know, a micron is about 1/1100th the width of a human hair. The Semiconductor Industry Association says boom times are back for chip makers. Estimates are that U.S. companies should sell nearly $11 billion worth of semiconductors this year, an increase of some 16% over last year. Meanwhile, National Semiconductor in Santa Clara reports an excellent first quarter with net income of 41 cents a share. That's up from less than 1 cent a share a year ago. And Intel and Advanced Micro Devices showed very strong fourth quarters. Just a few weeks ago, Fortune Computers was bragging that it wouldn't follow in the footsteps of Osborne. But this week, Fortune has been reeling a bit. Its founder and CEO, Gary Friedman, resigned at the request of the board of directors. Fortune suffered a $3 million loss during the last quarter. Its stock, which had sold at $22 a share earlier this year, is now down to about $8.50. What's new? Well, you've probably seen those new TV ads for MCI Electronic Mail. MCI, which has been challenging Ma Bell for the long-distance phone business, is now challenging the post office with its new MCI mail service for personal computer owners. MCI says its system will interface with the post office and courier services so that you can even send electronic mail to people who don't have personal computers. Coleco finally showed off a production version of its Atom computer to the Boston Computer Society. Reports are that the much-touted word processor is not too sophisticated. Coleco hinted at a utility pack due to come out next year, which will improve its word processing. Latest word is that shipment of atoms are finally due to be made at the end of this month. If you bought one of those portable computers that you can take on an airplane, you might want to check with the airlines. Many computer users are being told no when they drag out the old keyboard and put it on their laps. Some airlines are worried about radio interference with the plane's navigation system. According to the LA Times, TWA and Republic say okay to using the portables, but United, PSA, Eastern, Continental, and Western have banned the use of portable computers while flying. Nolan Bushnell is back. If you've forgotten, he's the guy who invented video games and founded Atari, then sold it to for a fortune, to Warner Communications. Well, Bushnell's 7-year non-compete agreement expired this month, and word is that he's soon coming out with twin Laserdisc video games. He's also into robots, and rumors are he's working on robots to serve pizza at his Pizza Time Theater restaurants. If you missed it, by the way, a major court decision on copywriting software came out of the U.S. Court of Appeals in Philadelphia a few weeks ago. Apple had sued Franklin Computers for copying its operating system program. The court ruled that the program, even as etched on a silicon chip, was copyrightable and so could not be copied without compensation to its creator. What's the best-selling business program these days? Lotus 1-2-3 has jumped to the top of the software charts. In the first 6 months of this year, Lotus sold more than $12 million worth of 1-2-3, and success breeds competition. About 30 software companies have announced plans for what they say will be improved versions of 1-2-3. Finally, with computers and software multiplying like rabbits, the inevitable has happened. Some ad agencies are thinking about placing advertisements on software disks or on computer networks. The Dow Jones Information Service says it will start doing something like this. The best guess is that early ads will be text only and will promote software, computer magazines, and financial services. That's it for this week's Random Access, a capsule look at what's happening in the world of computing. Be sure to watch for Random Access following each edition of the Computer Chronicles.
Random Access is made possible by a grant from Byte, the Small Systems Journal, publishers of a monthly magazine on microcomputer technology and innovative projects in the world of computing.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Gary, I've been working with this abacus here, and the abacus is, of course, one of the oldest computing machines, about 5,000 years old, and if you're really fast, maybe you can do 2 or 3 operations per second on this thing. Well, today, of course, we're talking about computers which can do hundreds of millions of operations per second. The question is, why do you need that incredible kind of speed in a computer?
Well, incredible speed helps sell computers, for one thing. But realistically, there are many problems that do require high-performance computers to get an effective solution. Real-time graphics is one example where the foreground and background images change at a fixed rate of, say, 30 frames per second. It takes a higher performance processor to keep up with a higher density graphics to match that frame rate. Now, there are many examples like that. Say, weather modeling is one. Another is the information analysis required by an expert system.
Okay, these incredibly fast computers are called supercomputers, and that's the subject of our program today. We'll see the fastest computers in the world in operation, both here in the United States and in Japan. Let's begin our look at supercomputers by seeing what's going on in this country.
Over 1 million times faster than the serial processing machines of the 1950s, modern supercomputers owe most of their high-speed capabilities to massive parallel architectures. Multiple functional units and comprehensive pipelining have led to processing speeds in excess of 100 million operations per second. Supercomputer applications are as distinctly varied as they are specialized, from satellite imagery to superreal graphics, from space exploration to doomsday weapons research. At Lawrence Livermore Laboratory, the world's largest user of supercomputers, magnetic fusion experiments require massive computing power available through the lab's Octopus network, a multi-access system that shares a total of 7 supercomputers. Processing time on these machines is rented to over 150 American and foreign users who gain access through satellite transmission. But the fastest machine at the lab, and one of the fastest commercially available, is the Cray XMP. This dual processor supercomputer is reserved for the most secretive and the most costly activity at Lawrence, nuclear weapons design and analysis. With the Japanese now challenging what was once an American-dominated market, supercomputer research is taking on a new approach. The Japanese machines are not only faster, but they offer simpler, more portable software that uses standard programs aimed at a much wider market. Like the extremely successful bullet train, Japan's supercomputers herald a new generation of speed and technical sophistication. At issue is whether American companies will play a role in this new era of super-fast computers.
Joining us now is George Michael. George is head of the Computing Research Group at Lawrence Livermore National Laboratory, and John Repp, Marketing Program Manager for Control Data Corporation. Gary?
George, it was about 10 years ago that I sold one of the first CPM systems in Lawrence Livermore Labs, and it was used as a little peripheral on the Octopus network, a network of supercomputers with microfiche storage and so forth. What was going on out there? What goes on at Livermore Labs with supercomputers?
Well, the business of the laboratory is solving partial differential equations when it comes right down to it. Okay? They're doing advanced technological stuff in where it's based on nuclear energy or weapon technology, anything like that. These things require enormous computations. Okay? You'd like to be sure that you're right. So we use computers to do that. In other words, a computer is not an end in itself, it's the thing that's used to support the work that the laboratory is chartered to do.
Do you find that what you do is you buy more and more computers as your need grows, or you try to use different techniques to use those computers more effectively?
Oh,
What's the process?
We do both. Mm-hmm. In fact, the secret to supercomputers or to any other computer at any time in any context is that it's more than just a computer. There has to be a language to express ideas. There has to be algorithm development that shows how to be sure you've done the right thing. Okay? Given that, it's well, there's a lot of research that has to go on that prevents you from just saying, I can buy that computer and just get another factor of 20 or whatever it is that you need in speed. You have to build the thing, and as you well know.
Now, you work a lot with Control Data Corporation, is that correct? And with John. And what is it in the technology now? What are the limitations? Do we really have our supercomputers growing in an order of magnitude every few years, or what's going on?
Well, I don't know. I don't know how John feels about it, but I will say that if you plot the performance characteristic of machines since 1950, what you can see is that there's been a 2 orders of magnitude, that's a factor of 100, improvement in the decade from 50 to 60 and from 60 to 70, and then it turned over and we didn't get a factor of 10. Why? Well, some of the stuff was that the components are tired or they just can't go any faster. Some of the things is that we're trying to do things incorrectly. Okay, we got to rethink about how they're done, and some of it was that the machines require very strange perturbations in algorithms before they'll really perform. So we have to change all that and bring it all together, and then we'll start picking up speed again.
Now, the CDC Star was I guess a supercomputer, 10 years ago, and it was a different architecture, and it was basically an array processing machine. And one of the difficulties that came about with the Star was that it really required different kinds of compilers and software techniques. Has that been a problem over the last 10 years? Has it been solved?
Well, when Star was first introduced, I think part of it with the help of the laboratories and coming up with a new philosophy, a new logic to produce the high power, it had to restructure your whole problem, restructure your thinking and how you were going to solve a problem. And over the years, it's taken quite some time to get to the point where vectors are recognized. I deal primarily in the commercial world, and as George and I were talking beforehand, the evolution was in the government. The government had the R&D funds. The government was able to produce and use the kind of architecture that came up. And we're seeing in the commercial world, it's almost a revolution right now. We were talking about it's kind of like jumping on the bandwagon now of I got to have one. I ought to get to a point where I can use it. And they're also reaching a point where they can't solve the problems in the same old way they were doing it. They went into the three-dimensional world where you have a lot more data points that you have to analyze and through whatever algorithms, and they're reaching a point where they could keep adding a lot of computers, or they could go to what we quote-unquote call a supercomputer today and move into tomorrow. So we're seeing quite a bit of change going on right now.
John, what are the commercial applications? We've heard about Lawrence Livermore and those kind of research and government things. What are the commercial applications now of a supercomputer?
Well, I can let me categorize it a touch into 3 or 4 different areas. Petroleum. Petroleum companies or oil companies have gone into supercomputing in a big way, not still totally knowing what they're doing with it, but the search for oil. Again, domestically, they've had to take a look at the seismic processing and also the reservoir simulation. So that's been a very big move, and probably the biggest, as far as I know, in usage of supercomputers. But again, restructuring the way they do things. It's a three-dimensional world, again, that they're looking at. In the automobile industry, we're starting to see that the major companies in the U.S. are going to supercomputing. They want to be able to crash a car by a computer versus taking a number of cars and smashing them up the way they have. They look at productivity of number of cars they have to produce to make a profit. And several of the companies now, by using larger computers and going into supercomputing, have been able to cut the number of cars that they produce to become profitable. And again, that's computer-aided design and all the things they're doing.
One of the things that Captain Grace Hopper used to hand out at her lecture is the Grace Hopper nanosecond, which is about this long, and the distance that light travels in a nanosecond. She claimed that this was a fundamental limitation of the speed of computing. And what's your feeling on that? Has that been solved by various techniques? But
I don't think it's a limit. In fact, I've not seen any physical quantity an effective limit. You tell me about the limit or tell the research world about it, and they'll figure a way around it. Parallelism is a simple-minded way of getting around the limit of how much signal can travel in a given unit of time. Parallelism is a radically new idea, and yet it's very, very old. But in order to successfully cope with it, as John says, there's a great deal of rethinking that has to be done. And perhaps it's the most difficult part that we face right now. Okay, we have to do it in such a way that the ultimate user isn't besotted with all this stuff that, in minutia that ruins him, and he can concentrate on his problem. But we have to take care that when his program is running on a machine, that it will run correctly, and it will complete its job and things like that. That's something that people are just beginning to study now. Well, I shouldn't say just beginning to study. Maybe the last 10 years people have been looking at that. The intensity of that kind of study is increasing right now.
George, you've mentioned you kind of hit a wall this decade and not continuing to increase the speed. What are the technological problems? What are the barriers? I mean, what are the areas in which research is being focused to continue to increase speed?
Okay. Let's take the star as the first example. When the star is going to perform at its, quote, blazingly high speed, okay, the vector unit, which is part of the machine, must be running, okay? As far as the scientific computations are concerned, it turns out that a great deal of the computation cannot be kept in the vector mode, okay? It drops out of it. We call that entering a scalar mode. And then if the scalar is slow, well, you just go slower, okay? Now, it was a traumatic experience to learn how to vectorize big physics codes, things that are concerned with the flow of fluid or concerned with the migration of neutrons all over a reactor or something like that. Okay? It was tough to do that. So we had to invent vectorizing compilers, and then we learned that it's easy to get 60% of the overall program to vectorize, but then the other 40% will be the dominant thing in terms of how you perceive its speed. So
you feel like the real problem right now is mainly trying to rethink how the algorithms are stated and presented to the computer system rather than trying to change the underlying technology itself.
Well, there's some importance, excuse me, John, there is some importance in getting better technology, but in fact, that's just what you've said is the major problem. We have to learn how to, in a sense, remap algorithms onto architectures, and I feel that it's time to challenge the the manufacturers in some sense and say, instead of us having to warp our algorithms to fit your computers, why don't you learn how to warp your computer to fit my algorithm? And so we're getting a little dialogue going, and we're introducing the universities to that dialogue too. And I think that's going to lead, before the end of this decade, to some really successful stuff.
John, what's your response?
Well, I was going to say I don't disagree. It's just if you take a look at the commercial world, and instead of rewriting their codes, they've done conversions. And they've taken a real cut at making conversions, and obviously they're not using the supercomputer the way it can be done. It's in a lot of cases, very time-consuming and expensive. And they have a lot of code that they've written over the years, and it's all been built on and changed and added to. And to go rewrite, to do vector coding, to go on and do pure, solid vector coding, it takes a lot of time to rethink the problem.
It's a redevelopment of all those programs again.
As a matter of fact, in one case that I've seen this done, they've gotten spectacular results. But it took time and a lot of R&D on their part to do it.
Okay, in just a moment, we're going to go to Japan to look at the Japanese version of a supercomputer. That's coming up next.
At the University of Tokyo, the Computer Science Department has a new Hitachi model S81020, one of the fastest supercomputers in the world, capable of 800 million floating-point operations per second. Hitachi Corporation is one of the 10 participants in the National Super Speed Computer Project, a long-term collaboration between the Japanese public and private sectors, aimed at producing a supercomputer 10 times faster than the fastest known today, one that is capable of 10 billion flops per second.
私が作ろうとしているスーパーコンピューターというのは
The computer we are planning to build will be 10 times faster because of its chip design.
一桁速いもの。で、
The architecture will have to be 100 times faster to achieve a tenfold increase in speed.
で、したがってデバイスではジョセフソンジャンクションとハイエレ
The
クトロンモビリテ
technology
ィト
we
ラ
are
ンジスタ
exploring to reach this speed includes Josephson junctions, high electron mobility transistors, and gallium arsenide.
それからそのアーキテクチャの方で
In
は、ね、
terms of architecture, we will have to develop a much higher degree of parallel processing.
処理する方法というのを追求しようと。
We are also working on new software suitable for this kind of architecture.
というのも同時に行おうとしています。
The testing of superconductive materials and new chip designs is underway at the government's electrotechnical laboratory, part of a massive scientific and academic complex in Tsukuba, also known as Science City, about 60 miles north of Tokyo. Because of the extreme heat created by high-speed circuitry, chips must be cooled to extreme temperatures. In this test, an experimental chip is immersed in liquid nitrogen. Its functional operating temperature is minus 270 degrees centigrade. In tests like this one on Josephson's junction switches, the laboratory has achieved higher speeds than with gallium arsenide. Higher computational speed will also depend on new ways of handling data through parallel processing and pipeline architecture.
一方、一つはね、ベルトコンベヤーをお考えいただければいい
The
と思います。
best way to explain parallel processing and multi-pipeline architecture is by comparing it to an auto assembly line conveyor belt.
完成したものがそのベルトコンベヤーから出てくると。
The belt begins with one part and picks up components along the way until the product is complete. It's an efficient way to make one product using one line.
で、その時に
Now, if you increase the number of conveyor belts, you can produce more cars. But if you increase the number of belts by 100, for example, don't expect to increase the output by 100 times, because to allocate work to 100 conveyor belts efficiently is very difficult.
したがってその、プロセッサーの数を
You need a
100
good
にすれば
manager to allocate parts
単純に100倍になると
effectively.
いうことにはなりま
On
せん
the other
けれ
hand,
ども
while we can't expect 100 times the output with 100 times as many processors, we can still expect a substantial increase in processing
増えて
capacity.
くるということはお分かりいただけると思います。
The comprehensive Japanese approach to high-speed computation has led to some impressive accomplishments and some lingering uncertainties.
Joseph Junction should be used
in a very low temperature. So if we move it from the low temperature to the room temperature, it will be break down. It seems to be very difficult to extend them to large-scale computer logic with high reliability for practical use.
One of our problems is that when we develop a new machine, we need a new language. Since most research centers at present have a great number of Fortran programs, our success with the machine depends in part on whether users are willing to change to a new language. Some new languages have been developed, but very few are in widespread use today. It could become a very big problem.
The supercomputer project's merger of private and public sectors results in some unusual arrangements between the companies and the government labs.
Patent or copyright which are developed during the joint project period, those patents should belong to the nation, in other words, Japan government. However, the participant has the right to use such a patent. And second problem is after finishing the project, each makers, in other words, participant, develops the own products. At that time, in other words, we are completely free competition.
Directors of the multi-million-dollar supercomputer project don't see it as a threat to monopolize the world market, but as an efficient way to make major leaps in a field where small breakthroughs can lead to revolutionary changes.
Good technology is always born out of a competitive environment. So if America were the only country developing this kind of computer, we wouldn't expect the kind of breakthroughs that come from competition. Or if Japan monopolized the research, I don't think the progress we're seeing now would continue. We hope that we can always be a good competitor of the United States.
Okay, George and John, there is the perception of a kind of competition between the Japanese computer companies and the American computer companies, Cray and CDC, in the supercomputer field. How do you see is there a difference in approach between the Japanese and the Americans?
I think that you'd have to say there is a difference of approach. I'm not sure that's the place to look for the success that they seem to be enjoying. They have, well, just take the case of Fujitsu. By our discussions with them, they managed to analyze about 5,000 programs, Fortran programs, and then they wrote a vectorizing compiler. And what they learned was partly encapsulated in the compiler and partly introduced in their hardware. So the compiler knows it's got strange kinds of pieces of hardware and it can use them. The effect of that is that we think it's about the best looking compiler we've run into. Now, it doesn't say it's the only good one, but it certainly is good. And as a first approximation, I'm really impressed. I really would worry more about the next generation of computers that comes along from them rather than the current ones. Okay.
John, what's the CDC's reaction to what NEC, Hitachi, Fujitsu are doing?
Well, I think we're looking at, first of all, it's not proven. I think they're still in a research environment. They haven't delivered. But let's say they even deliver what they've committed to. I think by 1986, you're going to see the U.S. companies coming out with powers of 10 over what they're producing right now. So where does that take you after 86, 87? I think we're looking at magnitudes of 100 by 1990. So I think we've met the competition pretty well. They've certainly been tough competitors, and they've come up with some excellent technology. But we look at ours being tenfold of that by 1986, 87.
Are there bigger consequences? We hear of, the leadership and defense aspects, George, and who will have the leadership role in either the next generation or supercomputers. Is it really a big issue, this competition?
I think so. I think that we're not faced with a life and death situation. I believe that if people in this country don't get busy, that the Japanese machines will become dominant in terms of the speed that they can produce and the price that they can sell it at. We have, to contrast Fujitsu and Hitachi and NEC, we have Cray, CDC, and then it gets hard to find somebody else here. Denelcor is trying mightily, and a few others that are not named that well yet. I mean, they aren't really visible. That's nothing to meet the structured challenge that the Japanese have, if you want to call it a challenge.
Okay, gentlemen, that's all the time we have. Thanks so much for joining us. Thank you for being with us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution. Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet. Sitting in for Gary Kildall this week is Herb Lechner of SRI. Herb, we think of chess as the ultimate game of skill, a game that requires mental agility, intelligence, if you will. Yet here I am playing a game of chess with a computer, which is analyzing board positions and applying a certain kind of intelligence to figure out what its next move should be. That's the subject of our program today, artificial intelligence. And in some people's minds, AI suggests attempting to duplicate the way a human brain works. Is that what AI is, in fact?
Not in most modern AI research, Stewart. Early research in AI looked at duplicating human thought processes, but current AI research is more concerned with duplicating the end result of intelligence. And computers that act as experts in expert systems, and computers that can communicate with us in our language, understanding some of the context of that language, are two areas that are receiving a lot of attention in artificial intelligence research today.
Okay, we're going to meet two of the world's foremost experts on artificial intelligence, and we'll take a look at two fascinating examples of expert systems. One of the leading experts on expert systems is Dr. Edward Feigenbaum of Stanford University. We asked Professor Feigenbaum about the evolution of artificial intelligence.
The computers, as you know, are general symbol processing devices capable of manipulating any kinds of symbols, of which numbers constitute one important class, but computers are much more general than that. We've known about the generality of computation since at least the time of Turing in the 1930s, and actually I've tracked it back to intuitions that Babbage had that were reported by Ada Lovelace, after whom the Ada programming language is named. In 1842, Ada Lovelace wrote that the analytical engine of Babbage's constituted the link between the mechanical world and the world of the most abstract concepts. That currently in the modern terminology is called the physical symbol system hypothesis and is the basis for artificial intelligence work. In artificial intelligence as a science, we talk about the use of computers to process symbolic knowledge using logical inference methods, symbolic inference methods. In other words, we're talking about inference and not calculation in the traditional sense. We're talking about knowledge and not numbers in the traditional sense.
A current application of inferential knowledge engineering is in the field of expert systems, programs like this oil exploration advisor. Developed to assist drilling rigs in remote areas, the program behaves much like a qualified specialist. It asks questions of its user and then gives advice on how to avoid or correct accidents so common in drilling operations. If at some point in the line of questioning the user becomes confused by the query, he can ask the program to explain itself, simply by entering why. The advisor responds with a specific source behind the question and explains its reasoning up to that point. The symbolic processing behind the human-like talents of this program have found applications in a broad range of fields, from medicine to robotics. Perhaps the most difficult area for AI to master has been natural language, a talent that results in very friendly computers, but that requires enormous processing capacity. The ambiguities of syntax and context have restricted present systems to very limited applications. A simple geographic question, depending on the phrasing, can lead to multiple interpretations. The program will determine the question's most likely meaning only after an exhaustive deconstruction of the sentence, and might even reject an unusual phrasing of the same query. In a parallel development, investing AI programs with linguistic ability has led to an interactive study of graphic communication. In this experiment, the visual dynamics of communication form the foundation for a linguistic expert advisor capable not only of discerning visual patterns, but also acting as a kind of tutor. One interactive application has given persons without normal speech the ability to adapt or construct alternative symbolic languages, a remarkable instance of using a computer program's intelligence to help interpret human intelligence.
Joining us now is Jeffrey Perrone. Jeffrey's a management consultant involved in expert systems for micros, and Niels Nielsen, director of the Artificial Intelligence Center at SRI International. Herb.
Niels, could you kind of help us scope the field of artificial intelligence as it exists today?
Well, I'll try, Herb. It's a broad field. If you ask many of different people what constitutes artificial intelligence, I think you'd get a lot of different answers. For me, I think it concerns mainly the putting of knowledge into computer programs, so that the programs then can solve certain problems which humans find somewhat easy, or perhaps intellectual challenges sometimes. And the knowledge that one puts in is knowledge that's represented in a particular sort of way.
So the idea is that it's just not smarter programs that do artificial intelligence programming. It is some difference in techniques that they use relative to what ordinary programmers.
Well, there's a part of computer science that artificial intelligence is concerned with that does, in fact, involve a certain body of techniques that are a little different, perhaps, than what goes on in the rest of computer science.
Jeffrey, Niels is involved in the research end of AI, and you're involved in some of the applications. Are we at the point today where we can apply AI?
Absolutely, Stewart.
In what ways?
Well, I feel that artificial intelligence, and specifically expert systems or knowledge-based systems, now are applicable any place that specialized knowledge is used routinely to reach decisions, troubleshooting strategies, diagnoses, those areas. So I kind of think of it as something where we've reached a watershed where it is no longer very expensive or very difficult for individuals with no technical background to build systems and apply them usefully.
And you distribute a system which is an expert system and also helps one build expert systems. Is that correct?
Right. Well, actually, it's a tool for generating particular expert systems applications in virtually any area where there is that routine use of special knowledge.
And it runs on microcomputers.
Right. It runs on the IBM personal computer and a number of other compatible microcomputers.
Do you use the same techniques in this system that Nils was referring to are used in systems that might run on larger equipment?
It uses some of the same ideas, and it has its own unique approach as well. One of the specific areas where this is a different sort of program is that instead of requiring explicit statement of rules to build a system, it only requires examples of previous decisions, previous tasks, previous diagnoses to build the systems. And that's going to break through, I believe, the knowledge engineering bottleneck mentioned by people like Edward Feigenbaum in building these systems.
Jeffrey, you have Expert Ease, your system, up here, and show us the demonstration.
Sure. Okay. Well, this is a particular application generated with this system, and it was generated by an anesthesiologist, Hilary Don, and myself. And what it does is it makes diagnoses for breathing or airway problems. The first question here that it asks the naive user is, when was the onset of the problem? And I'll answer days. It then will ask, what's the quality of the stridor, which is a rasping sound made when one's breathing, kind of a sort of sound. And let's say that the quality is moderate.
Who would use this system, a doctor?
Okay.
Or
this might be used by a physician's assistant to screen patients for perhaps further fine-tuning by someone with more expertise. Is the patient drowsy? Let's say no. Are there any predisposing factors to developing stridor, prior events that might lead to this condition? Let's say yes. And it comes up with, consider the diagnosis of intrathoracic tracheal stenosis. Now, I'm not a physician, so I don't know exactly what that means, but that gives you an idea of how it might lead to a particular diagnosis. Now, what I'd like to do is I'd like to show you a trivial example called Sunday, which actually comes with the manual for the program as a tutorial, essentially. Now, Sunday is a model of deciding what to do on a Sunday afternoon. How are you going to spend your time? And it consists of a couple of questions, multiple choice questions like you've just seen, and those would be answered. So now what I'm going to do is run the query system. And it asks, do you have your family with you? Let's say yes. What is the weather like? Is it raining or sunny? Let's say sunny. So it says, why don't you take the family to the beach? Now, the way that you would build one of these models is by starting on something called the attribute screen. The attribute screen is where you sketch out the dimensions of the particular problem or situation. Now here the attributes are weather and family, and there's the advice column, which would be the result of a particular decision.
What size matrix can you do on that?
Okay, you can actually do, in any particular problem, 31 attributes and up to 255 values per attribute. And those can then be chained together, so you can do very large models, just limited by the size of your disk storage, essentially. The values, such as raining and sunny, could be thought of as answers to the question represented by the attribute. Once you've done a preliminary sketch of this sort, you then go to something called the example screen. And on the example screen, you enter in examples of previous decisions. Now, this was developed by Dr. Donald Mickey in Edinburgh, based on the idea that information is communicated by experts or masters to their apprentices in the form of examples or cases. So here you see, horizontally running across the screen, answers to those questions. Raining, yes, we're with the family. The advice would be go to the museum. And the next case would be if it's sunny and I was with the family, then I would go to the beach. And the third case there consists of an I don't care what the weather is like. If there's no family with me, then I'm going to go fishing.
Jeffrey, you described this obviously as a trivial example, this Sunday one, but in general, do you have the capacity within a PC to seriously approach this kind of problem solving?
Yes, you can do quite significant things. As a matter of fact, I've recently been speaking with the Whole Earth Software Review people about doing some systems to recommend software, such as word processing programs or communications hardware, modems, that sort of thing.
Niels, I want to ask you what I hope doesn't sound like a dumb question, but kind of what's the point? Why do we develop something like this kind of system? Is it to replace the doctor, say, in the diagnosis situation? What is the end result of this?
Well, I think there'd be a lot of uses of systems like this. I think the present ones actually do have a lot of brittle features that perhaps might limit their utility at the present time. But in the long run, that is 10 years, 20 years, something like that, These kinds of systems, I think, will be quite generally useful in a wide range of settings. First of all, the knowledge that these systems contain, at least we hope to put in the knowledge of world-class experts, people who know so much about the field that there might only be 5 or 6 of them in the whole world who know that much. Now, there can be some pretty good practicing people who nevertheless aren't quite as good as the world experts in a particular subject. So it helps us spread the knowledge of an expert around a good deal in a way which can be copied quite easily.
Okay, in just a moment we're going to meet the man who invented the term artificial intelligence, and we'll see a demonstration of knowledge engineering. That's coming up next. Joining us now is Tom Kaler. Tom is Director of Applied Artificial Intelligence at IntelliGenetics. Tom, you've got a complex system here. First of all, tell me how this would be different from the system we saw in the first part of the program.
Well, one way is that it's different is that we can develop a graphics environment which connects to the underlying knowledge bases so that the user really is just fooling around with meters and valves and objects that they're used to. Here, for example, if we look at this levelometer, we can just point to it.
Before you get to that, what's the environment we're looking at here?
Oh, this is the key system, the knowledge engineering environment, and we have knowledge bases hooked up to a control panel right here at the moment, and it's just a little example to show you how we can hear
a control panel of what?
This could be a control panel, say, to a nuclear reactor, or to an instrument, or any other kind of operational device that you would want to work with. And here, for example, we're just changing the value of a meter, and notice that it's generating a strip chart showing the time course behavior. Another thing we can do with these kinds of panels is we can go in and look at valves, and we can affect the valve whether it's open or shut. Now, what's important about this is affecting an underlying knowledge base, which will then apply heuristics and decision-making procedures to the system.
Can you show us that, how you can go to the part? There you go. We
Sure.
solve a problem.
Well, what we see underneath here now is a knowledge base for a nuclear reactor. And we can have a representation of the components of the nuclear reactor, as well as a representation of the decision-making behavior that would be carried out by the expert. And what you will see here is that it's both possible to use rule-based reasoning as well as representation of the underlying knowledge. One of the first things we'll do here is just take a look at how we could test the hypotheses of a particular accident situation. And we just point to test hypotheses and activate it here. And what we see the system doing is going through a decision-making process where it's accessing the underlying knowledge base, looking at the various states of the components. And by the way, the states of these particular components can be accessed directly into the instrument or into the nuclear reactor.
Now, you can actually interrogate the system and ask it what course of logic is it following. Is that correct?
That's right. Right now it's come up and asked the operator a question. Is it true that the steam generator level is decreasing? So we can say, why is this being asked? And it will explain to us that it's doing it in order to prove that the steam generator inventory is inadequate. We will then give it an answer, and it goes on to reach a conclusion.
Okay, Tom, this system runs in Lisp. Why is Lisp the right language for an AI application?
Well, one of the reasons that Lisp is so important is that you need to have very powerful symbol manipulating capabilities. Decision-making is primarily a symbolic activity. Knowledge representation is primarily symbolic, and you need that kind of capability.
Okay, thank you. Herb.
John McCarthy has joined us. John is a professor of computer science at Stanford University and one of the pioneers in the field of artificial intelligence. Among his other accomplishments, he invented Lisp, the language that Stewart just referred to. John, why did you invent Lisp?
Well, for artificial intelligence work, the kind of thing that they are doing here.
What are its characteristics that make it different than some other language as applied to artificial intelligence?
Besides the ones that Tom mentioned, one of its important characteristics is that its programs and are in the same format as its data, so that it is easy to make programs that produce programs and look at programs.
So it allows us to deal with facts and logic more than numbers.
That's correct.
I guess it's
on everyone's mind when we talk about smart machines. How smart can machines become? What are the limits of artificial intelligence?
Well, I see no limit short of human intelligence, and then with faster machines one could do the equivalent that a human could do in a short time in a very long time.
Niels, what's your thought on that? How far can we go with this?
Well, I'd separate some of the problems that we're facing in order to make machines more intelligent into about three different varieties. We've heard a lot about how important knowledge is. And one of the important things about knowledge is what knowledge should be represented in a program. And some of the difficulties that we're having in making programs smarter is that we're not sure exactly what it is we want to tell those programs about certain subjects. Another category is, once we figure that out, how do we represent the knowledge in the computer itself? And certain kinds of knowledge is proving a little difficult for us to represent it. The third category has to do with how that knowledge is used, and certainly there's various activities there that have been rather successful, but other things that really have to be done yet.
Is there a frustration level in this field in that there's a lot of hope of what you can do with something like AI, but yet, as you've pointed out, Niels, it seems harder perhaps than one thought to really put this into a practical application? John?
Well, there is a certain level of technology in artificial intelligence today, and many people are making applications based on this technology. On the other hand, something that Niels said earlier rouses a thought in me. He said that we can put in the knowledge of a world-class expert, and that's indeed true. We can put in the knowledge of a world-class expert, provided it fits into the format that the present programs allow, namely of the kind, if this is true, then do that. But more general kinds of knowledge that are used in a sort of vaguer way are sometimes harder to put in.
Say, in the medical diagnosis area, at the beginning of the program, we had a simple example of medical diagnosis. There were several systems developed, and yet there were problems, in fact, in using that. What were those problems?
Well, I'm not sure what were the problems of those specific systems. However, to take a medical example, one can make a definition that a container is sterile if all the bacteria in it are dead. However, this piece of knowledge is not used in a special way to determine whether a container is sterile by examining each of the bacteria. It's used as part of more general facts, like if you heat the container enough, then the bacteria will be all killed, and the fact that if the container is not sterile and you empty it out onto a culture medium, then you'll get colonies of bacteria. And the still further fact is important, that if you leave the bacteria in food, then they will spoil it.
Niels, where do you see the future practically going in AI? What's the biggest potential market, if you will, for these kinds of applications?
Well, it seems to me that expert systems, as they have been going along, probably represents a rather large market, and we'll continue to develop systems that are less brittle over the next 5, 10, 15 years. Another very important application is computer programs that are able to converse with humans in English, everyday, ordinary language. And that's going to make computers accessible to a much wider variety of people.
We have just about a minute. I like your phrase, brittle. Explain more what you mean by a brittle system.
Well, it has to do with being able to reason about the context, I think, in which a particular discussion or conversation with the expert system is taking place. If the information that's needed to reach a certain conclusion is there and is there explicitly, then the system is usually able to come up with some reasonable answer. If it has to have what you might call common sense knowledge, knowledge that all of us learn by the time we're 10 or 15, then it has a good deal more difficulty and, as a matter of fact, fails in many of those cases.
So, ironically, common sense is the most difficult thing.
There's very few people who are willing to pay for putting common sense knowledge into a computer, whereas it is interesting and commercially important to put knowledge about a nuclear reactor into a computer.
Okay, gentlemen, we're out of time. Thanks very much for being here. Thank you for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
I'm Susan Bimba, sitting in for Stewart Cheifet. In the random access file this week, the Commerce Department has made a move to stop the export of technology to countries allied with the Soviet Union, hitting the Digital Equipment Corporation with tough new restrictions on its exporting practices. Now DEC has to get individual export licenses for each sophisticated computer it ships to West Germany, Austria, or Norway. Government officials say in these countries, computers can be easily diverted to the Eastern Bloc countries. Several months ago, one of DEC's computers was intercepted en route to the Soviet Union, but the company was found to be blameless in the incident. Despite a strong lobby by the high-tech industry, President Reagan has given the Pentagon power to advise the Commerce Department on computer and high-tech exports to all foreign countries. The Pentagon already had the right to advise about applications for exports to communist countries. The Pentagon feels its input would help cut down on the number of computers that get diverted from non-communist countries to communist ones. The National Semiconductor Corporation could be banned from making chips for government projects. Early this month, the company admitted that over a 3-year period, it inadequately tested chips that were used on many military projects. Now the Defense Logistic Agency is investigating National Semi, trying to find out exactly who's responsible for lying to the government about the testing. Despite these problems, National Semiconductor is reporting a profit of $15.4 million for the quarter ending March 4th. IBM is reporting big demand for its little computers. The company says this year its shipments of the PC will be triple what it was last year. It's estimated that IBM will ship more than 2 million of its PCs, PC Juniors, and other desktop IBM computers combined. And now that IBM is making its own portable computer, it looks as if Compaq, a maker of IBM-compatible portables, will be lowering its prices. So far, no date has been given for the price cut, but industry insiders say it will probably be around the beginning of April. Right now, the Compaq portable sells for $2,995. That's $200 more than the IBM portable. With a projected $500 cut, the Compaq will sell for $300 less than the IBM portable. Atari Incorporated is making cuts, but it will be employee cuts. The video game maker says it plans to lay off about 300 workers. At the same time, an Atari spokesman says there are plans to expand the sales and engineering staffs by about 100. Last year, the company lost over $500 million, laid off more than 2,000 of its Bay Area workers, and moved part of its operation to Taiwan and Hong Kong. Well, last week we told you the Japanese Trade Ministry may introduce a bill that would reduce protection of U.S. software in Japan. This week, the U.S. government is warning that if Japan's parliament ratifies the bill, the U.S. will retaliate in kind. If approved, the bill would limit copyright protection to U.S.-made software, making it necessary for U.S. software owners to license their programs to Japanese makers. Well, a little closer to home, our software reviewer, Paul Schindler, has some information for blackjack buffs who don't have money to burn.
If you gamble in Nevada or Atlantic City, that's a familiar sight, the shuffling of blackjack cards, usually accompanied by the sight of your money being swept in by the dealer at the end of the round. Well, if you're tired of losing, there's a computer program for you. It's Ken Houston's Professional Blackjack. Now, it's pretty rare when the writer gets top billing when they name a computer program, but Houston deserves it. He's a former official of the Pacific Stock Exchange, and now he's a full-time gambler. Of course, some people would say that isn't much of a switch, but anyway, on a recent trip to Las Vegas, Houston was kicked out of 5 casinos after winning more than $3,000. Now, most computer blackjack games will just play blackjack with you. But the Whole Earth Software Catalog and Review says Houston's Professional Blackjack will teach you how to play the game and win using various point-counting methods. The graphics are crisp. The table is green. The cards realistic looking. And the sound is good too. You can hear the cards hitting the table. Another use of sound, the program advises you on betting and card play, and it beeps at you when you goof. Ken Houston's Professional Blackjack is $70 from Screenplay in Chapel Hill, North Carolina. For Random Access, I'm Paul Schindler.
Next week, Paul reviews Volksreiter Deluxe, and that's it for this week's Random Access. I'm Susan Bimba.
Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, sitting in for Gary Kildall this week as Herb Lechner of SRI. Herb, we think of chess as the ultimate game of skill, a game that requires mental agility, intelligence, if you will. Yet here I am playing a game of chess with a computer, which is analyzing board positions and applying a certain kind of intelligence to figure out what its next move should be. That's the subject of our program today, artificial intelligence. And in some people's minds, AI suggests attempting to duplicate the way a human brain works. Is that what AI is, in fact?
Not in most modern AI research, Stewart. Early research in AI looked at duplicating human thought processes, but current AI research is more concerned with duplicating the end result of intelligence. And computers that act as experts in expert systems, and computers that can communicate with us in our language, understanding some of the context of that language, are two areas that are receiving a lot of attention in artificial intelligence research today.
Okay, we're going to meet two of the world's foremost experts on artificial intelligence, and we'll take a look at two fascinating examples of expert systems. One of the leading experts on expert systems is Dr. Edward Feigenbaum of Stanford University. We asked Professor Feigenbaum about the evolution of artificial intelligence.
The computers, as you know, are general symbol processing devices capable of manipulating any kinds of symbols, of which numbers constitute one important class, but computers are much more general than that. We've known about the generality of computation since at least the time of Turing in the 1930s, and actually I've tracked it back to intuitions that Babbage had that were reported by Ada Lovelace, after whom the Ada programming language is named. In 1842, Ada Lovelace wrote that the analytical engine of Babbage's constituted the link between the mechanical world and the world of the most abstract concepts. That currently, in the modern terminology, is called the physical symbol system hypothesis and is the basis for artificial intelligence work. In artificial intelligence as a science, we talk about the use of computers to process symbolic knowledge using logical inference methods, symbolic inference methods. In other words, we're talking about inference and not calculation in the traditional sense. We're talking about knowledge and not numbers in the traditional sense.
A current application of inferential knowledge engineering is in the field of expert systems, programs like this Oil Exploration Advisor. Developed to assist drilling rigs in remote areas, the program behaves much like a qualified specialist. It asks questions of its user and then gives advice on how to avoid or correct accidents so common in drilling operations. If at some point in the line of questioning the user becomes confused by the query, he can ask the program to explain itself, simply by entering why. The advisor responds with a specific source behind the question and explains its reasoning up to that point. The symbolic processing behind the human-like talents of this program have found applications in a broad range of fields, from medicine to robotics. Perhaps the most difficult area for AI to master has been natural language, a talent that results in very friendly computers, but that requires enormous processing capacity. The ambiguities of syntax and context have restricted present systems to very limited applications. A simple geographic question, depending on the phrasing, can lead to multiple interpretations. The program will determine the question's most likely meaning only after an exhaustive deconstruction of the sentence, and might even reject an unusual phrasing of the same query. In a parallel development, investing AI programs with linguistic ability has led to an interactive study of graphic communication. In this experiment, the visual dynamics of communication form the foundation for a linguistic expert advisor capable not only of discerning visual patterns, but also acting as a kind of tutor. One interactive application has given persons without normal speech the ability to adapt or construct alternative symbolic languages, a remarkable instance of using a computer program's intelligence to help interpret human intelligence.
Joining us now is Jeffrey Perrone. Jeffrey's a management consultant involved in expert systems for micros, and Niels Nielsen, director of the Artificial Intelligence Center at SRI International. Herb.
Niels, could you kind of help us scope the field of artificial intelligence as it exists today?
Well, I'll try, Herb. It's a broad field. If you ask many of different people what constitutes artificial intelligence, I think you'd get a lot of different answers. For me, I think it concerns mainly the putting of knowledge into computer programs, so that the programs then can solve certain problems which humans find somewhat easy, or perhaps intellectual challenges sometimes. And the knowledge that one puts in is knowledge that's represented in a particular sort of way.
So the idea is that it's just not smarter programs that do artificial intelligence programming. It is some difference in techniques that they use relative to what ordinary programmers do.
Well, there's a part of computer science that artificial intelligence is concerned with that does, in fact, involve a certain body of techniques that are a little different, perhaps, than what goes on in the rest of computer science.
Jeffrey, Niels is involved in the research end of AI, and you're involved in some of the applications. Are we at the point today where we can apply AI?
Absolutely, Stewart.
In what ways?
Well, I feel that artificial intelligence, and specifically expert systems or knowledge-based systems, now are applicable any place that specialized knowledge is used routinely to reach decisions, troubleshooting strategies, diagnoses, those areas. So I kind of think of it as something where we've reached a watershed where it is no longer very expensive or very difficult for individuals with no technical background to build systems and apply them usefully.
And you distribute a system which is an expert system and also helps one build expert systems. Is that correct?
Right. Well, actually, it's a tool for generating particular expert systems applications in virtually any area where there is that routine use of special knowledge.
And it runs on microcomputers.
Right. It runs on the IBM personal computer and a number of other compatible microcomputers.
Do you use the same techniques in this system that Niels was referring to are used in systems that might run on larger equipment?
It uses some of the same ideas, and it has its own unique approach as well. One of the specific areas where this is a different sort of program is that instead of requiring explicit statement of rules to build a system, it only requires examples of previous decisions, previous tasks, previous diagnoses to build the systems. And that's going to break through, I believe, the knowledge engineering bottleneck mentioned by people like Edward Feigenbaum in building these systems.
Jeffrey, you have Expert Ease, your system, up here, and show us the demonstration.
Sure. Okay. Well, this is a particular application generated with this system, and it was generated by an anesthesiologist, Hilary Don, and myself. And what it does is it makes diagnoses for breathing or airway problems. The first question here that it asks the naive user is, when was the onset of the problem? And I'll answer days. It then will ask, what's the quality of the stridor, which is a rasping sound made when one's breathing, kind of a sort of sound. And let's say that the quality is moderate.
Who would use this system, a doctor?
Okay.
Or
this might be used by a physician's assistant to screen patients for perhaps further fine-tuning by someone with more expertise. Is the patient drowsy? Let's say no. Are there any predisposing factors to developing stridor, prior events that might lead to this condition? Let's say yes. And it comes up with, consider the diagnosis of intrathoracic tracheal stenosis. Now, I'm not a physician, so I don't know exactly what that means, but that gives you an idea of how it might lead to a particular diagnosis. Now, what I'd like to do is I'd like to show you a trivial example called Sunday, which actually comes with the manual for the program as a tutorial, essentially. Now, Sunday is a model of deciding what to do on a Sunday afternoon. How are you going to spend your time? And consists of a couple of questions, multiple choice questions like you've just seen, and those would be answered. So now what I'm going to do is run the query system. And it asks, do you have your family with you? Let's say yes. What is the weather like? Is it raining or sunny? Let's say sunny. So it says, why don't you take the family to the beach? Now, the way that you would build one of these models is by starting on something called the attribute screen. The attribute screen is where you sketch out the dimensions of the particular problem or situation. Now here the attributes are weather and family, and there's the advice column, which would be the result of a particular decision.
What size matrix can you do on that?
Okay, you can actually do, in any particular problem, 31 attributes and up to 255 values per attribute. And those can then be chained together, so you can do very large models, just limited by the size of your disk storage, essentially. The values, such as raining and sunny, could be thought of as answers to the question represented by the attribute. Once you've done a preliminary sketch of this sort, you then go to something called the example screen. And on the example screen, you enter in examples of previous decisions. Now, this was developed by Dr. Donald Mickey in Edinburgh, based on the idea that information is communicated by experts or masters to their apprentices in the form of examples or cases. So here you see, horizontally running across the screen, answers to those questions. Raining, yes, we're with the family. The advice would be go to the museum. And the next case would be if it's sunny and I was with the family, then I would go to the beach. And the third case there consists of that I don't care what the weather is like. If there's no family with me, then I'm going to go fishing.
Jeffrey, you described this obviously as a trivial example, this Sunday one, but in general, do you have the capacity within a PC to seriously approach this kind of problem solving?
Yes, you can do quite significant things. As a matter of fact, I've recently been speaking with the Whole Earth Software Review people about doing some systems to recommend software, such as word processing programs or communications hardware, modems, that sort of thing.
Niels, I want to ask you what I hope doesn't sound like a dumb question, but kind of what's the point? Why do we develop something like this kind of system? Is it to replace the doctor, say, in the diagnosis situation? What is the end result of this?
Well, I think there'd be a lot of uses of systems like this. I think the present ones actually do have a lot of brittle features that perhaps might limit their utility at the present time. But in the long run, that is 10 years, 20 years, something like that, these kinds of systems, I think, will be quite generally useful in a wide range of settings. First of all, the knowledge that these systems contain, at least we hope to put in the knowledge of world-class experts, people who know so much about the field that there might only be 5 or 6 of them in the whole world who know that much. Now, there can be some pretty good practicing people who nevertheless aren't quite as good as the world experts in a particular subject. So it helps us spread the knowledge of an expert around a good deal in a way which can be copied quite easily.
Okay, in just a moment, we're going to meet the man who invented the term artificial intelligence, and we'll see a demonstration of knowledge engineering. That's coming up next. Joining us now is Tom Kaler. Tom is Director of Applied Artificial Intelligence at IntelliGenetics. Tom, you've got a complex system here. First of all, tell me how this would be different from the system we saw in the first part of the program.
Well, one way is that it's different is that we can develop a graphics environment which connects to the underlying knowledge bases so that the user really is just fooling around with meters and valves and objects that they're used to. Here, for example, if we look at this levelometer, we can just point to it.
Before you get to that, what's the environment we're looking at here?
Oh, this is the key system, the knowledge engineering environment, and we have knowledge bases hooked up to a control panel right here at the moment, and it's just a little example to show you how we can hear...
A control panel of what?
This could be a control panel, say, to a nuclear reactor,
okay,
or to an instrument, or any other kind of operational device that you would want to work with. And here, for example, we're just changing the value of a meter, and notice that it's generating a strip chart showing the time course behavior. Another thing we can do with these kinds of panels is we can go in and look at valves, and we can affect the valve whether it's open or shut. Now, what's important about this is affecting an underlying knowledge base, which will then apply heuristics and decision-making procedures to the system.
Can you show us that, how you can go to the part? There you go. We
Sure.
solve a problem.
Well, what we see underneath here now is a knowledge base for a nuclear reactor. And we can have a representation of the components of the nuclear reactor, as well as a representation of the decision-making behavior that would be carried out by the expert. And what you will see here is that it's both possible to use rule-based reasoning as well as representation of the underlying knowledge. One of the first things we'll do here is just take a look at how we could test the hypotheses of a particular accident situation. And we just point to test hypotheses and activate it here. And what we see the system doing is going through a decision-making process where it's accessing the underlying knowledge base, looking at the various states of the components. And by the way, the states of these particular components can be accessed directly into the instrument or into the nuclear reactor.
Now, you can actually interrogate the system and ask it what course of logic is it following. Is that correct?
That's right. Right now it's come up and asked the operator a question. Is it true that the steam generator level is decreasing? So we can say, why is this being asked? And it will explain to us that it's doing it in order to prove that the steam generator inventory is inadequate. We will then give it an answer, and it goes on to reach a conclusion.
Okay, Tom, this system runs in Lisp. Why is Lisp the right language for an AI application?
Well, one of the reasons that Lisp is so important is that you need to have very powerful symbol manipulating capabilities. Decision making is primarily a symbolic activity. Knowledge representation is primarily symbolic, and you need that kind of capability.
Okay, thank you. Herb.
John McCarthy has joined us. John is a professor of computer science at Stanford University and one of the pioneers in the field of artificial intelligence. Among his other accomplishments, he invented Lisp, the language that Stewart just referred to. John, why did you invent Lisp?
Well, for artificial intelligence work, the kind of thing that they are doing here.
What are its characteristics that make it different than some other language as applied to artificial intelligence?
Besides the ones that Tom mentioned, one of its important characteristics is that its programs and are in the same format as its data, so that it is easy to make programs that produce programs and look at programs.
So it allows us to deal with facts and logic more than numbers.
That's correct.
I guess it's on everyone's mind when we talk about smart machines. How smart can machines become? What are the limits of artificial intelligence?
Well, I see no limit short of human intelligence, and then with faster machines one could do the equivalent that a human could do in a short time in a very long time.
Niels, what's your thought on that? How far can we go with this?
Well, I'd separate some of the problems that we're facing in order to make machines more intelligent into about three different varieties. We've heard a lot about how important knowledge is. And one of the important things about knowledge is what knowledge should be represented in a program. And some of the difficulties that we're having in making programs smarter is that we're not sure exactly what it is we want to tell those programs about certain subjects. Another category is, once we figure that out, how do we represent the knowledge in the computer itself? And certain kinds of knowledge is proving a little difficult for us to represent it. The third category has to do with how that knowledge is used. And certainly there's various activities there that have been rather successful, but other things that really have to be done yet.
Is there a frustration level in this field in that there's a lot of hope of what you can do with something like AI, but yet, as you've pointed out, Niels, it seems harder perhaps than one thought to really put this into a practical application? John?
Well, there is a certain level of technology in artificial intelligence today, and many people are making applications based on this technology. On the other hand, something that Niels said earlier rouses a thought in me. He said that we can put in the knowledge of a world-class expert, and that's indeed true. We can put in the knowledge of a world-class expert, provided it fits into the format that the present programs allow, namely of the kind, if this is true, then do that. But more general kinds of knowledge that are used in a sort of vaguer way are sometimes harder to put in.
Say, in the medical diagnosis area, at the beginning of the program, we had a simple example of medical diagnosis. There were several systems developed, and yet there were problems, in fact, in using that. What were those problems?
Well, I'm not sure what were the problems of those specific systems. However, to take a medical example, one can make a definition that a container is sterile if all the bacteria in it are dead. However, this piece of knowledge is not used in a special way to determine whether a container is sterile by examining each of the bacteria. It's used as part of more general facts, like if you heat the container enough, then the bacteria will be all killed, and the fact that if the container is not sterile and you empty it out onto a culture medium, then you'll get colonies of bacteria. And the still further fact is important, that if you leave the bacteria in food, then they will spoil it.
Niels, where do you see the future practically going in AI? What's the biggest potential market, if you will, for these kinds of applications?
Well, it seems to me that expert systems, as they have been going along, probably represents a rather large market, and we'll continue to develop systems that are less brittle over the next 5, 10, 15 years. Another very important application is computer programs that are able to converse with humans in English, everyday, ordinary language. And that's going to make computers accessible to a much wider variety of people.
We have just about a minute. I like your phrase, brittle. Explain more what you mean by a brittle system.
Well, it has to do with being able to reason about the context, I think, in which a particular discussion or conversation with the expert system is taking place. If the information that's needed to reach a certain conclusion is there and is there explicitly, then the system is usually able to come up with some reasonable answer. If it has to have what you might call common sense knowledge that all of us learn by the time we're 10 or 15, then it has a good deal more difficulty and, as a matter of fact, fails in many of those cases.
So, ironically, common sense is the most difficult thing.
There's very few people who are willing to pay for putting common sense knowledge into a computer, whereas it is interesting and commercially important to put knowledge about a nuclear reactor into a computer.
Okay, gentlemen, we're out of time. Thanks very much for being here. Thank you for joining us on this edition of the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Random access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
I'm Susan Bimba, sitting in for Stewart Cheifet. In the random access file this week, the Commerce Department has made a move to stop the export of technology to countries allied with the Soviet Union, hitting the Digital Equipment Corporation with tough new restrictions on its exporting practices. Now DEC has to get individual export licenses for each sophisticated computer it ships to West Germany, Austria, or Norway. Government officials say in these countries, computers can be easily diverted to the Eastern Bloc countries. Several months ago, one of DEC's computers was intercepted en route to the Soviet Union, but the company was found to be blameless in the incident. Despite a strong lobby by the high-tech industry, President Reagan has given the Pentagon power to advise the Commerce Department on computer and high-tech exports to all foreign countries. The Pentagon already had the right to advise about applications for exports to communist countries. The Pentagon feels its input would help cut down on the number of computers that get diverted from non-communist countries to communist ones. The National Semiconductor Corporation could be banned from making chips for government projects. Early this month, the company admitted that over a 3-year period, it inadequately tested chips that were used on many military projects. Now the Defense Logistic Agency is investigating National Semi, trying to find out exactly who's responsible for lying to the government about the testing. Despite these problems, National Semiconductor is reporting a profit of $15.4 million for the quarter ending March 4th. IBM is reporting big demand for its little computers. The company says this year its shipments of the PC will be triple what it was last year. It's estimated that IBM will ship more than 2 million of its PCs, PC Juniors, and other desktop IBM computers combined. And now that IBM is making its own portable computer, it looks as if Compaq, a maker of IBM-compatible portables, will be lowering its prices. So far, no date has been given for the price cut, but industry insiders say it will probably be around the beginning of April. Right now, the Compaq portable sells for $2,995. That's $200 more than the IBM portable. With a projected $500 cut, the Compaq will sell for $300 less than the IBM portable. Atari Incorporated is making cuts, but it will be employee cuts. The video game maker says it plans to lay off about 300 workers. At the same time, an Atari spokesman says there are plans to expand the sales and engineering staffs by about 100. Last year, the company lost over $500 million, laid off more than 2,000 of its Bay Area workers, and moved part of its operation to Taiwan and Hong Kong. Well, last week we told you the Japanese Trade Ministry may introduce a bill that would reduce protection of U.S. software in Japan. This week, the U.S. government is warning that if Japan's parliament ratifies the bill, the U.S. will retaliate in kind. If approved, the bill would limit copyright protection to U.S.-made software, making it necessary for U.S. software owners to license their programs to Japanese makers. Well, a little closer to home, our software reviewer, Paul Schindler, has some information for blackjack buffs who don't have money to burn.
If you gamble in Nevada or Atlantic City, that's a familiar sight, the shuffling of blackjack cards, usually accompanied by the sight of your money being swept in by the dealer at the end of the round. Well, if you're tired of losing, there's a computer program for you. It's Ken Houston's Professional Blackjack. Now, it's pretty rare when the writer gets top billing when they name a computer program, but Houston deserves it. He's a former official of the Pacific Stock Exchange, and now he's a full-time gambler. Of course, some people would say that isn't much of a switch, but anyway, on a recent trip to Las Vegas, Houston was kicked out of 5 casinos after winning more than $3,000. Now, most computer blackjack games will just play blackjack with you. But the Whole Earth Software Catalog and Review says Houston's Professional Blackjack will teach you how to play the game and win using various point-counting methods. The graphics are crisp, the table is green, the cards realistic-looking, and the sound is good too. You can hear the cards hitting the table. Another use of sound, the program advises you on betting and card play, and it beeps at you when you goof. Ken Houston's Professional Blackjack is $70 from Screenplay in Chapel Hill, North Carolina. For Random Access, I'm Paul Schindler.
Next week, Paul reviews Volkswagen Deluxe, and that's it for this week's Random Access. I'm Susan Bimba.
Random Access is made possible by a grant from Popular Computing, a McGraw-Hill magazine.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Herb Lechner sitting in for Gary Kildall this week. Herb, what I have up on the computer here it's a game, I guess, but it's really a teaching tool that teaches the student working with this algebraic expressions and the graphic representations of these algebraic expressions. What just happened is these little guys here are called algebroids, and the test for me is to write an equation down here using all these available trigonometric and algebraic functions to try to plot a graph which will intersect as many of these algebroids as possible. Now let's just for the heck of it, try something very simple here, and we'll just say y equals x and see if we can hit a couple of these guys with the graph that gets drawn. And you can see the graph coming. I may have got one guy by the leg and one guy by the ear, and after it draws the graph, it'll then show me whether I've hit these guys or not. Come on.
Got him. 2 down.
And the object here, obviously, is to learn equations, these expressions, learn their graphic representation. And we'll just go one more round. Just to show you how it really does motivate someone, there's a character in here called the graph gobbler. And you're not allowed to have your graph run through him. So I'll see if we can draw something simpler. You think y minus x will make it?
Looks like it.
Herb, let's try that. And just demonstrate.
There you go.
And he eats your graph up. And he punishes you by sending you to the committee, which then penalizes you. Anyhow, we're talking about computers in education today, Herb. And first question that comes to mind as we talk about the use of computers in education is some people, shut up, algebroid. Some people are afraid, I think, of this technology, and there's a fear that computers are going to replace teachers, they're going to perhaps dehumanize education. Is that what you see in the future?
I think the expectations for the use of computers in school were very high, and along with those expectations, there was concern about the dehumanizing effect. I don't think that we've seen the use of computers nearly as extensively as we expected, and therefore I don't think the impacts, pro or con, have been terribly significant. But I do look forward to talking to our guests about that.
Okay, before we meet our studio guests and see some demonstrations of other educational software, let's go visit some schools where computers are being used.
With over 1/2 of American schools equipped with computers, students from elementary grades through college are likely to have some computer instruction at almost every level of their education. But there are still doubts over the best way to integrate computers into a traditional curriculum. Replacing the teacher with a terminal changes the focus of learning away from the instructor and to the computer. While traditional contact between teacher and student is diminished, the terminal becomes a kind of private tutor, adjusting to the different learning rates and abilities of each student. It is also interactive, demanding answers within a specific length of time, making corrections, and helping the student to understand the reasons behind a mistake. Programming languages for children rely on colorful graphics and game-like approaches, especially to teach analytical skills and problem-solving logic. For younger children, time spent at the terminal can seem more like a game than a lesson.
Let me do it. Okay. Y, E, are you sure? Oh, yeah. Yeah. I forgot this. We have 29 points. Oh, great.
Much of computer instruction today is for rote learning and practice drills, but there is another level of application that demands much more creative interaction. Programming languages like Logo are designed to teach children to make up their own programs, create their own commands, and in general put students in the active role of controlling the machine, instead of just responding to an electronic inquisitor. Proponents of this approach claim that students trained to think logically will become better at problem solving in general. But at least one study questions whether there is any difference between a Logo-trained and a traditionally trained child.
Joining us now is Professor Patrick Suppies of Stanford University and Nancy Palmer, who's coordinator of computer education at the Palo Alto School District here in the Silicon Valley. Herb?
In the opening, I mentioned that it didn't seem to me that the application of computers in education was moving along as rapidly as we had hoped. How do you all feel about that?
Well, I agree with that for most of the period, which is now about 20 years, that I've been involved in the application of computers in education. Certainly for the first 15 years, I kept thinking it ought to go faster. There ought to be more to do. There's a lot to be done here. Why aren't we getting more done? In the last 3 or 4 years, the pace has really changed. A lot of people are interested. There's a lot of hardware and an increasing amount of software in the schools. I think Nancy would agree with that.
Yes, I certainly would. That's the case in our district anyway. The teachers, there's a lot more interest from teachers now, and they're starting to use computers within their classroom in a lot of different ways. Students in Palo Alto are now starting to use word processing and some other types of programs, data management kinds of programs to help them, so that the computer is becoming more of a tool for them. Still learning to use computer programming languages like BASIC and Logo and Pascal, but there's a wider application now of computers.
Of course, it's also important to emphasize that we've only really begun. You know, your question is right in the sense where we are now will be very different from where we are 20 years from now.
What's triggered the movement in these past few years? What's different now than what we had 10 years ago?
I would say primarily the enormous reduction in the cost of hardware.
And the change in the technology itself. You know, just in the last 8 years, when we first had computers, as far as microcomputers, for the last 8 years, and that's made computers a lot more reasonable for schools to buy, and also easier to use. So as the technology improves, as far as the ease of using it, you're going to see a lot more.
You know that favorite joke that about computers in schools. If computers followed that, if Rolls-Royces followed the same trail as computers, a Rolls-Royce would now cost $2.50 and be an inch and a half long. And that enormous reduction is in cost is really revolutionized. Of course, not only schools, but other places, but we see it in schools.
Pat, you're using computers at Stanford now to teach your course in logic. How do you actually use the computers to teach that course?
I don't give any lectures. The students don't go to lectures in this course. They come to computer terminals. There is no textbook separate from what they learn at the computer terminal. And from the student standpoint, what's very good is they come and go on their own. 7 days a week, 24 hours a day, we're open for business. I have a TA, for example, a teaching assistant on duty Saturday nights, 8 to 11 p.m. And that coming and going is very important advantage from the student standpoint.
How about from an instructional point of view, though? Is it better education? Is it you pay a price for that convenience?
Well, I think you don't really pay a price. I think that there are gives and takes in any particular way of approaching instruction. I think in addition to the freedom to come and go, I would mention the individualization. Some students just learn that kind of topic, that kind of subject matter, very much more easily and quicker than other students. And that individualization is taken account of because the pace of one student doesn't affect the pace of another student, as opposed to a classroom setting. Secondly, the students get excellent opportunities to practice and be corrected in their practice of doing logical derivations and giving proofs, giving logical counterexamples. And that practice, that dealing with material in that elegant way you can do it on at a computer terminal with a good sophisticated program to back it up in terms of checking any kind of proofs the students give. That's a great advantage.
Okay, Pat, on the terminal we have here, you're hooked up by modem to the computer at Stanford. And give us a demonstration of what a student would do to take a class in your logic course.
This is towards the very beginning of the course. The course is a large course. The students spend on average about 75 hours to complete the course at a terminal like this. And we're just at the beginning of learning the classical rule in Latin, modus ponendo ponens. We call it in English affirming the antecedents. You're given an argument, if A then B. Secondly, given A, infer B. And they're going to practice, learn the strategies and begin to practice derivations, logical derivations, using this rule.
Okay, so the first thing is kind of the text material that teaches the principle.
Principle and the strategy of how to attack a proof. For example, here it's saying, well, we'll use the simple working backward strategy. Look for what we're going to derive. What is the conclusion we want to infer? And then the next step is look for a conditional statement and some premises that we can begin to work with.
Okay, can the student go ahead then and actually try to practice what he's just learned?
Yes, and that practice is, of course, the critical thing. Just putting out the exposition wouldn't be very interesting. What is interesting and powerful in the course is the great flexibility of responses the student can give in terms of constructing proofs that interest him. So we'll consider a very simple example of this. There isn't time to do something complicated. Here, we want to derive the premise W. We use letters here to make the argument simple. And the premises are using the arrow for if-then. The first premise is if S, then Q. The second premise is if Q, then W. And the third is S. Now, we can combine 1 and 3, affirming the antecedent of the conditional in 1 to get the conclusion Q. So we type in 1, comma 3, and AA for the affirm the antecedent rule. See, the language is mainly a control language the students give. We don't like the students to have to type a lot. Now we have Q, and we look at 2, if Q, then W, combining 2 and 4. Suppose I made a mistake. Let's see what happens. So I combine 1 and 4. But, of course, 4 is not the antecedent of 1. And the program types back, you need a conditional and its antecedent. I don't have the antecedent. So now let's do it right. 2, 4, lines 2 and 4, affirm the antecedent, and we'll get immediately the desired conclusion W.
Mm-hmm. Nancy, at the high school level, how are computers being used there? Just to teach computers themselves, or used in this way to teach other courses?
They're used in both ways. They're used as, for programming itself, and they're also used for word processing, in business classes, in accounting. We have foreign language. We have programs on the computer that students can practice foreign languages and actually learn a foreign language by computer. And there's some programs that are being used in the science department now, and we have a couple of social studies teachers that are using simulations.
I guess the real key is, what difference has it made? What's the bottom line? Are the achievement scores going up for those classes using computers?
Well, that's kind of a hard one to answer. As far as any real strong data on achievement scores by using computers, I don't think we're at that stage that we've come up with anything like that. We feel that there has been a difference in students with their interest in school, for instance, a lot of different things that have kept motivated. But as far as any real data, no, we don't have any.
Okay, we're going to stop for a moment and come back soon and take a look at Logo, a teaching language, which is an interesting language to look at. We'll have a demonstration of that. Also, we're going to meet the author of a book called Brave New Schools, about the use of computers in the schools in the future. That's coming up in just a moment. With us now is Glenn Kleiman, founder of the Teaching Tools Microcomputer Service and author of the book, as we mentioned, Brave New Schools. Glenn, we want to talk to you about Logo in particular. And we hear an awful lot more than we have about Logo now as a teaching language, as something to be used for students. What is the significance of Logo as a language?
Well, Logo is a newer programming language than, say, BASIC. It's one that's been widely touted as the language to use to introduce kids to computers. There have been a lot of claims about Logo, that it's an ideal way to teach problem-solving skills, that it would revolutionize education. I don't really believe a lot of those claims, but I think it has a number of nice advantages for introducing kids to computers, introducing kids to programming, and also that it does have some implications for more general problem-solving types of skills.
Could we do a little demonstration here? Maybe people would understand more what we're talking about, and then we can follow up. You
Okay.
have Logo loaded, and show us what it is.
I have Logo up and loaded. There are a couple of components to Logo, and maybe I should fill in a minute or so of background before going to the demo. Sure. There are two main components. One that's very well known is called Turtle Graphics, which has to do with displaying things on the computer screen. That's what I'll be showing, and that's what's widely used with kids. There's a whole second component called list processing commands, which enables you to use this programming language to work with words, sentences, numbers, and other types of things. But it's the turtle graphics commands that have really been widely used in education. What we have in turtle graphics are some very simple commands that kids can learn easily. You can tell the turtle to do things like move forward a certain number of turtle steps, turn right or left a certain number of degrees. The turtle has a pen. It can lift the pen up or down. If the pen is down, it can draw things as it goes. Okay? The idea of Logo is that these simple commands can be combined into what we call procedures, and very complex programs can gradually be built up among a number of procedures. What I have already loaded in the computer is one example procedure, which is a simple one, but one that can do a number of interesting things. The procedure has been given the name magic, and magic requires that we tell the turtle we want to use magic, and we give it 4 numbers so that it knows what to do. And as a sample, we can start out with the numbers 20, 90, 10, and 8. If we do that, the turtle will draw us a little picture. What the numbers are telling the turtle to do, the first number is the length of the first line. The second number, 90 here, is the angle for the turtle to change, to turn. So we'll see we have right angles here. We can also see that the length of each line the turtle has drawn increases as we go on. The third number is the increment. Okay, so the first line was 20, we increase it by 10, the next one's 30, the next one's 40. The final number, 8 here, is the number of turns for the turtle to make before stopping. Okay, so it's a simple procedure built up of forward and right and repetition. Okay. The interesting thing about this particular procedure is we can get very different kinds of pictures just by changing the numbers. So here I'm changing the starting line, the increment, and the number of turns, but I'm leaving the angle at 90 degrees. Okay, we get a little more intricate, interesting picture. Now what happens if we just change that angle? So let's use the same starting number, increase the angle to 135, same increment, same number of turns. Okay. Now we have a star-shaped picture, a very different type of image just from changing the angle. So one kind of thing that Logo is designed for is to lead kids to explore the computer, explore what will happen with these kinds of forms, and children can just get a feel for what angles are, how you can build up different pictures by typing in different numbers and seeing what will happen. Okay. There are some more I can show if we have a few
go ahead.
more minutes.
Yes, you show us another.
Okay, let's just make another change in the angle.
Still doing magic, though? Yeah.
Still doing magic, if I typed it correctly. And changing the angle and changing the number of turns that the turtle makes. Yeah. Here we have a much steeper angle and another very different picture. Now let me show you what the procedure itself is. We can have the computer list the procedure. This is the entire program that we're working with. The first line simply says to the turtle, we're going to tell you how to do the magic procedure. We're going to teach you a new word, in a sense. The magic procedure uses these 4 numbers, which we're calling start, angle, increment, and end for number of turns. The first thing the turtle does is go forward, the number of steps it's told to by start, turns right, the angle. We then say, if n equals 0, stop. What we're doing here is we're setting n to a number. The turtle will count down till n reaches 0, and it will stop there. The last line of the program is really the powerful line. It says, do magic again, but do it with the line changed by the increment and with n being 1 less. Okay? That's what's called a recursive command. The magic procedure is repeating itself, changing as it goes along. That's the entire program that created that variety of pictures.
Okay, Glenn, it's kind of interesting and it's fun to see all those pictures, but it seems a bit whimsical in a way. I mean, what's the big deal?
It is perhaps whimsical in a way. Kids enjoy whimsy. I think the big deal is that it's a very different approach than the kinds of things Professor Suppies was showing. Professor Suppies was showing computers really used to do the kinds of things we've always done in education, to do tutorials, to do drills. And certainly that's a valid use of computers. Logo is widely cited as an example of doing something new with computers, introducing an environment, a tool that kids can explore, where the child has more control than the computer. Here it's not that problems and questions are coming out of the computer's waiting for the child to respond. Here the child has complete control of the situation.
Pat, what's your observation on this use of a computer as opposed to what you're doing?
Oh, I think that the use of Logo could be valuable and fascinating for for young students. I think that in teaching students about computers, the nice thing about Logo is they get a quick and easy sense of how a computer language works. That doesn't mean, for example, that I think that's the only use, obviously. But I think it's quite an acceptable and valid use.
Are there social or perhaps antisocial consequences to coupling kids with machines rather than kids with traditional flesh and blood teachers?
Well, I think we want to differentiate cases. In the elementary school, it's very important to have a relationship to a teacher. One of the paradoxes of American education is that the data are overwhelming, that's the way it should be, and yet class size on average is larger in elementary schools than in secondary schools. As we get to older and older students, let's say out to adults, then we're in a different kind of world. Many adults, for example, in the future may want to get a good deal of their education at home over a terminal because it's inconvenient to go to a campus site.
You do see, as you mentioned in your own course, the possibility that an entire course or maybe curriculum would be taken by a mature student via computer.
Sure. And my own courses at Stanford are meant to be an example of that. And that could well be a course in programming. I mean, as far as it's very similar to teaching logic that way. But the socially important thing is you can teach courses that way. So you can have a decentralization, and it's really a social decision and an administrative and psychological decision, not a technical decision.
Okay, real quickly, Glenn.
I think I have a somewhat different view. I view the computer as a tool for the teacher to use. I certainly don't think computers are capable of replacing teachers. I, in fact, was a student in Dr. Suppi's course the first year it was taught by computer, and I found that the computer is a good means for practicing logic, but I think there's an elegance to logic. There's intuitions about logic. There's information about how formal logic relates to general problem solving that one could get from a professor like Dr. Suppi's better than any computer program.
Gentlemen, I'm afraid on that note we'll have to leave it because we're out of time right now. Thanks so much for being with us. We'll see you again next week on the Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.